Chapter 1. Cement, Portland cement, natural cement, slag cement, size and weight of barrels of cement, specifications and testing. Sand, properties of good sand, cost of sand, washing with hose, washing with sand ejectors, washing with tank washers. Aggregates, broken stone, gravel, slag and cinders, balanced aggregate, size of aggregate, cost of aggregate, screened and crusher run stone for concrete, quarrying and crushing stone, screening and washing gravel. Chapter 2. Voids, voids in sand, effect of mixture, effect of size of grains, voids in broken stone and gravel. Effect of method of loading, test determinations, specific gravity, effect of hauling, theory of the quantity of cement in mortar. Tables of quantities in mortar, tables of quantities in concrete. Percentage of water in concrete, methods of measuring and weighing, automatic measuring devices. Chapter 3. Loading into stockpiles, loading from stockpiles, transporting materials to mixing boards, mixing, loading and hauling mixed concrete, dumping, spreading and ramming, cost of superintendents, summary of costs. Chapter 4. Introduction, conveying and hoisting devices, unloading with grab buckets, inclines, trestle and car plants, cableways, belt conveyors, chutes, methods of charging mixers, charging by gravity from overhead bins, charging with wheelbarrows, charging with cars, charging by shoveling, charging with derricks, types of mixers, batch mixers. Chicago improved cube tilting mixer, Ransom non-tilting mixer, Smith tilting mixer, continuous mixers, Eureka automatic feed mixer, gravity mixers, Gilbreth trough mixer, Haynes gravity mixer, output of mixers, mixer efficiency. Chapter 5. Introduction, depositing in closed buckets, O'Rourke bucket, Cyclopean bucket, Stubner bucket, depositing in bags, depositing through a tremie, Charlestown Bridge, Arch Bridge Piers, France, Nussdorf Lock, Vienna, grouting submerged stone, tests of H.F. White. Hermitage breakwater. Chapter 6. Introduction, rubble concrete, Chattahoochee River Dam, Barossa Dam, South Australia, other rubble concrete dams, Boonton Dam, Spear Falls Dam, Hemet Dam, Small Reservoir Dam, Boyd's Corner Dam, abutment for railway bridge, English data, Tharsis and Calamas Rye, bridge piers, Nova Scotia, asphalt concrete, slope paving for earth dam, base for mill floor. Chapter 7. Introduction, lowering the freezing point of the mixing water, common salt, sodium chloride, freezing temperature chart, heating concrete materials, portable heaters, heating in stationary bins, other examples of heating methods, power plant, Billings, Mont, Wachusett Dam, Huron Power Co., Dam, Arch Bridge, Piano Ill, Chicago, Burlington, and Quincy work, heating in water tank, covering and housing the work, method of housing in dam, Chaudière Falls, Quebec, method of housing in building work. Chapter 8. Imperfectly made forms, imperfect mixing and placing, efflorescence, spaded and troweled finishes, plaster and stucco finish, mortar and cement facing, special facing mixtures for minimizing form marks, washes, finishing by scrubbing and washing, finishing by etching with acid, tooling concrete surfaces, gravel or pebble surface finish, colored facing. Chapter 9. Introduction, effect of design on form work, kind of lumber, finish and dimensions of lumber, computation of forms, design and construction, unit construction of forms, lubrication of forms, falsework and bracing, time for and method of removing forms, estimating and cost of form work. Chapter 10. Introduction, molding piles in place, method of constructing Raymond piles, method of constructing simplex piles, method of constructing piles with enlarged footings, method of constructing piles by the compressor system, method of constructing piers in caissons, molding piles for driving, driving molded piles, method and cost of molding and jetting piles for an ocean pier, method of molding and jetting square piles for a building foundation, method of molding and jetting corrugated piles for a building foundation, method of molding and driving round piles, molding and driving square piles for a building foundation, method of molding and driving octagonal piles, method and cost of making reinforced piles by rolling. Chapter 11. Introduction Fortification Work. Gun Emplacement Staten Island, NY. Mortar Battery Platform Tampa Bay, FLA. Emplacement for Battery Tampa Bay, FLA. U.S. Fortification Work. Lock Walls, Cascades Canal, Locks, Coosa River, Alabama, Lock Walls, Illinois and Mississippi Canal, Hand Mixing and Placing Canal Lock Foundations, Breakwater at Marquette, Mich. Breakwater, Buffalo, NY. Breakwater, Port Colborne, Ontario, Concrete Block Pier, Superior Entry, Wisconsin, Dam, Richmond, Ind. Dam at McCall Ferry, PA. Dam at Chaudière Falls, Quebec. Chapter 12. Introduction. Rectangular pier for a railway bridge, backing for bridge piers and abutments, pneumatic caissons, Williamsburg Bridge, filling pier cylinders, piers, Calf Killer River Bridge, constructing 21 bridge piers, permanent way structures, Kansas City Outer Belt and Electric Rye. Plate girder bridge abutments and piers, Lonesome Valley Viaduct, hand mixing and wheelbarrow work for bridge piers. Chapter 13. Introduction, Comparative Economy of Plain and Reinforced Concrete Walls, Form Construction, Mixing and Placing Concrete Walls in Trench, Chicago Drainage Canal, Grand Central Terminal, New York, NY. Wall for railway yard, footing for rubble stone retaining walls, track elevation, Allegheny, PA. Chapter 14. Introduction, Mixtures employed, distribution of stock piles, hints on hand mixing, methods of machine mixing, foundation for stone block pavement, New York, NY. Foundation for pavement, New Orleans, LA. Foundation for pavement, Toronto, Canada. Miscellaneous examples of pavement foundation work. Foundation for brick pavement, Champaign, Ill. Foundation construction using continuous mixes. Foundation construction for street railway track using continuous mixes. Foundation construction using batch mixes and wagon haulage. Foundation construction using a traction mixer. Foundation construction using a continuous mixer. Foundation construction using a portable batch mixer. Chapter 15. Introduction, Cement sidewalks, general method of construction, bonding of wearing surface and base, protection of work from sun and frost, cause and prevention of cracks, cost of cement walks, Toronto, Ont. Quincy, Mass., San Francisco, Cal., cost in Iowa. Concrete pavement, Windsor, Ontario, Richmond, Ind. Concrete curb and gutter, form construction, concrete mixtures and concreting, cost of curb and gutter, Ottawa, Canada, Champaign, Ill. Chapter 16. Introduction, Capitol Hill Tunnel, Pennsylvania, Washington, D.C. Constructing side walls in relining Mullen Tunnel, lining a short tunnel, Peekskill, N.Y. Cascade Tunnel, Great Northern Rye. Relining Hodges Pass Tunnel, Oregon Short Line Rye. Lining a 4,000 FT. Tunnel, method of mixing and placing concrete for a tunnel lining, Gunnison Tunnel. New York Rapid Transit Subway. Traveling forms for lining New York Rapid Transit Railway tunnels. Subway lining, Long Island, Brooklyn, N.Y. Chapter 17. Introduction, Centers, Mixing and Transporting Concrete, Cableway Plants, Car Plant for Force-Span Arch Bridge, Hoist and Car Plant for 21-Span Arch Viaduct, Traveling derrick plant for Fospan Arch Bridge, Concrete Highway Bridges, Greene County, Iowa, Highway Girder Bridges, Molding Slabs for Girder Bridges, Connecticut, Ave. Bridge, Washington, D.C., Arch Bridges, Elcott, Ind. Arch Bridge, Plainwell, Mich. 5-span Arch Bridge, Grand Rapids, Mich. Chapter 18. Introduction, Box Culvert Construction, C, B, and Q, Arch Culvert Costs, NC and St. L. Rye. 18 ft. Arch Culvert, 6 Arch Culvert, 6 to 16 ft. Span, 14 3/4 ft. Arch Culvert, Culverts for New Construction, Wabash, Rye. Small Arch Culvert Costs, Pennsylvania, 26 ft. Span Arch Culvert, 12 ft. Culvert, Kalamazoo, Mich. Method and Cost of Molding Culvert Pipe. Chapter 19. Introduction, Construction, Erection and Removal of Forms. Column forms, rectangular columns, polygonal columns, circular columns, ornamental columns, slab and girder forms, slab and I-beam floors, concrete slab and girder floors, wall forms, erecting forms, removing forms, fabrication and placing reinforcement. Fabrication, placing, mixing, transporting and placing concrete. Mixing, transporting, bucket hoists, platform hoists. Derricks, placing and ramming. Constructing wall columns for a brick building. Floor and column construction for a 6-story building. Wall and roof construction for 1-story car barn. Constructing wall columns for a 1-story machine shop. Constructing 1-story walls with movable forms and gallows frames. Floor and roof construction for 4-story garage. Chapter 20. Introduction, Column, Girder and Slab Construction, Warehouses, Brooklyn, N.Y., Factory, Reading, Pa, Kiln House, New Village, N.J. Hollow Block Wall Construction, Factory Buildings, Grand Rapids, Mich. Residence, Quogue, N.Y., 2-story building, Albuquerque, N.Mex. General Cost Data. Chapter 21. Introduction, Forms and Centers, Concreting, Reinforced Conduit, Salt River Irrigation Works, Arizona, Conduit, Torresdale Filters, Philadelphia, Pa. Conduit, Jersey City Water Supply, Twin Tube Water Conduit at Newark, N.J. 66 in. Circular Sewer, South Bend, Ind. Sewer Invert, Haverhill, Mass. 29 ft. Sewer, St. Louis, Mo. Sewer, Middlesboro, Chi. Intercepting Sewer, Cleveland, Ohio. Reinforced Concrete Sewer, Wilmington, Del. Sewer with monolithic invert and block arch, cost of block manholes, cement pipe constructed in place, pipe sewer, St. Joseph, Mo. Cost of molding small cement pipe, molded pipe water main, Swansea, England. Chapter 22. Introduction, Small Covered Reservoir, 500,000 gallon covered reservoir, Ft. Mead, So, DAC. Circular Reservoir, Bloomington, Ill. Standpipe at Attleboro, Mass. Gas holder tank, Des Moines, Iowa. Gas holder tank, New York City, lining a reservoir, Quincy, Mass. Relining a reservoir, Chelsea, Mass. Lining Jerome Park Reservoir, reservoir floor, Canton, Ill. Reservoir floor, Pittsburgh, Pa. Constructing a silo, grained arch reservoir roof, grain elevator bins. Chapter 23. Introduction, Separately molded ornaments, wooden molds, iron molds, sand molding, plaster molds, ornaments molded in place. Big Muddy Bridge, Forest Park Bridge, miscellaneous structures. Chapter 24. Introduction, Drilling and Blasting Concrete, Bench Monuments, Chicago, Roman 3. Pole base, mile post, bonding new concrete to old, dimensions and capacities of mixers, data for estimating weight of steel in reinforced concrete, computing weight from percentage of volume, weights and dimensions of plain and special reinforcing metals, recipes for coloring mortars. Chapter 25. Impervious concrete mixtures, Star Stettin cement, Medusa waterproofing compound, Novoid waterproofing compound, impermeable coatings and washes, bituminous coatings, Cherelmi stone liquid wash, Sylvester wash, Sylvester mortars, hydrolytic coating, cement mortar coatings, oil and paraffine washes, impermeable diaphragms, Long Island subway, New York Rapid Transit Subway. Concrete construction methods and cost. Chapter 26. Concrete is an artificial stone produced by mixing cement mortar with broken stone, gravel, broken slag, cinders, or other similar fragmentary materials. The component parts are therefore hydraulic cement, sand, and the broken stone or other coarse material commonly designated as the aggregate. Cement. At least a score of varieties of hydraulic cement are listed in the classifications of cement technologists. The constructing engineer and contractor recognize only 3 varieties: Portland cement, natural cement, and slag or pozzolan cement. All concrete used in engineering work is made of either Portland, natural, or slag cement, and the great bulk of all concrete is made of Portland cement. Only these 3 varieties of cement are, therefore, considered here, and they only in their aspects having relation to the economics of construction work. For a full discussion of the chemical and physical properties of hydraulic cements, and for the methods of determining these properties by tests, the reader is referred to Practical Cement Testing by W. Purves Taylor. Portland cement. Portland cement is the best of the hydraulic cements. Being made from a rigidly controlled artificial mixture of lime, silica, and alumina, the product of the best mills is a remarkably strong, uniform, and stable material. It is suitable for all classes of concrete work, and is the only variety of hydraulic cement allowable for reinforced concrete, or for plain concrete having to endure hard wear or to be used where strength, density, and durability of high degree are demanded. Natural cement. Natural cement differs from Portland cement in degree only. It is made by calcining and grinding a limestone rock containing naturally enough clayey matter, silica and alumina, to make a cement that will harden under water. Owing to the imperfection and irregularity of the natural rock mixture, natural cement is weaker and less uniform than Portland cement. Natural cement concrete is suitable for work in which great unit strength or uniformity of quality is not essential. It is never used for reinforced work. Slag cement. Slag cement has a strength approaching very closely that of Portland cement, but as it will not stand exposure to the air, slag cement concrete is suitable for use only under water. Slag cement is made by grinding together slaked lime and granulated blast furnace slag. Size and weight of barrels of cement. The commercial unit of measurement of cement is the barrel. The unit of shipment is the bag. A barrel of Portland cement contains 380 pounds of cement, and the barrel itself weighs 20 pounds. There are 4 bags, cloth or paper sacks of cement to the barrel, and the regulation cloth sack weighs 1.5 pounds. The size of cement barrels varies due to the differences in weight of cement and to differences in compacting the cement into the barrel. A light burned Portland cement weighs 100 pounds per struck bushel. A heavy burned Portland cement weighs 118 to 125 pounds per struck bushel. The number of cubic feet of packed Portland cement in a barrel ranges from 3 to 3.5. Natural cements are lighter than Portland cement. A barrel of Louisville, Akron, Utica, or other Western natural cement contains 265 pounds of cement and weighs 15 pounds. Itself, A barrel of Rosendale or other Easton cement contains 300 pounds. Of cement, and the barrel itself weighs 20 pounds. There are 3¾ cu. ft. in a barrel of Louisville cement. Usually there are 3 bags to a barrel of natural cement. As stated above, the usual shipping unit for cement is the bag, but cement is often bought in barrels or, for large works, in bulk. When bought in cloth bags, a charge is made of 10 CTS, each for the bags, but on return of the bags, a credit of 8 to 10 CTS. Each is allowed. Cement bought in barrels costs 10 CTS. More per barrel than in bulk, and cement ordered in paper bags costs 5 CTS, more per barrel than in bulk. Cement is usually bought in cloth sacks which are returned, but to get the advantage of this method of purchase, the user must have an accurate system for preserving, checking up, and shipping the bags. Where any considerable amount of cement is to be used, the contractor will find that it will pay to erect a small bag house or to close off a room at the mixing plant. Provide the enclosure with a locked door and with a small window into which the bags are required to be thrown as fast as emptied. One trustworthy man is given the key and the task of counting up the empty bags each day to see that they check with the bags of cement used. The following rule for packing and shipping is given by Gilbreth. A. Field System, Frank B. Gilbreth, Myron C. Clark Publishing Co., New York and Chicago. Pack cement bags laid flat, one on top of the other in piles of 50. They can then be counted easily. Freight must be prepaid when cement bags are returned, and bills of lading must be obtained in duplicate or credit, cannot be obtained on shipment. The volumes given above are for cement compacted in the barrel. When the cement is emptied and shoveled into boxes, it measures from 20 to 30% more than when packed in the barrel. The following table compiled from tests made for the Boston Transit Commission, Mr. Howard Carson, chief engineer, in 1896, shows the variation in volume of cement measured loose and packed in barrels. Brand vol, barrel cu, ft vol packed cu, ft vol loose cu, ft % increase in bulk Portland. Giant 3, 5.3, 35.4, 1725 Atlas 3, 45.3, 21.3, 75.18 Sailors 3, 25.3, 15.4, 05.30 Alson 3, 22.3, 16.4, 1933 Dickerhoff 3, 12.3, 034, 0033. Mr. Clarence M. Foster is authority for the statement that Utica cement barrels measure 16¼ ins. Across at the heads, 19½ ins. Across the bilge, and 25¾ ins. In length under heads, and contain 377 cu ft. When 265 pounds of Utica natural hydraulic cement are packed in a barrel, it fills it within 2½ ins of the top and occupies 345 cu ft. And this is therefore the volume of a barrel of Utica hydraulic cement packed tight. In comparative tests made of the weights and volumes of various brands of cements at Chicago in 1903, the following figures were secured. Vol per BBL, cu, ft, weight per BBL, pounds, weight per cu, ft, brand, loose, gross, net, loose pounds, Dickerhoff 4, 47 395 369. 583 Atlas 4, 45 401 381.85. 5 Alpha 4, 37 400. 5 381.86. 5 Puzzleland 4, 84 375 353. 573. 5 Steel 4, 96 345 322. 567. 5 Hilton 4, 64, 393, 370. 579. 5 Specifications and testing. The great bulk of cement used in construction work is bought on specification. The various government bureaus, state and city works departments, railway companies, and most public service corporations have their own specifications. Standard specifications are also put forward by several of the national engineering societies, and one of these, or the personal specification of the engineer, is used for individual works. Buying cement to specification necessitates testing to determine that the material purchased meets the specified requirements. For a complete discussion of the methods of conducting such tests, the reader is referred to Practical Cement Testing by W. Purves Taylor. According to this authority, a field testing laboratory will cost for equipment $250 to $350. Such a laboratory can be operated by 2 or 3 men at a salary charge of from $100 to $200 per month. 2 men will test on an average 4 samples per day, and each additional man will test 4 more samples. The cost of testing will range from $3 to $5 per sample, which is roughly equivalent to 3 CTS per barrel of cement, or from 3 to 5 CTS per cubic yard of concrete. These figures are for field laboratory work reasonably well conducted under ordinarily favorable conditions. In large laboratories, the cost per sample will run somewhat lower. Sand. Sand constitutes from 1/3 to 1/2 of the volume of concrete. When a large amount of concrete is to be made, a contractor cannot, therefore, afford to guess at his source of sand supply. A long haul over poor roads can easily make the sand cost more than the stone per cubic yard of concrete. Properties of good sand. Engineers commonly specify that sand for concrete shall be clean and sharp, and silicious in character. Neither sharpness nor excessive cleanliness is worth seeking after if it involves much expense. Tests show conclusively that sand with rounded grains makes quite as strong a mortar, other things being equal, as does sand with angular grains. The admixture with sand of a considerable percentage of loam or clay is also not the unmixed evil it has been supposed to be. Myron S. Folk records a number of elaborate experiments on this point. These experiments demonstrate conclusively that loam and clay in sand, to the amount of 10 to 15%, result in no material reduction in the strength of mortars made with this sand, as compared with mortars made with the same sand after washing. There can be no doubt but that for much concrete work, the expense entailed in washing sand is an unnecessary one. B. Cements, Mortars, and Concretes by Myron S. Folk, Myron C. Clark Publishing Co., Chicago, Ill. The only substitute for natural sand for concrete that need be considered practically is pulverized stone, either the dust and fine screenings produced in crushing rock or an artificial sand made by reducing suitable rocks to powder. As a conclusion from the records of numerous tests, M.S. Folk says, it may be concluded that rock screenings may be substituted for sand, either in mortar or concrete, without any loss of strength resulting. This is important commercially, for it precludes the necessity of screening the dust from crushed rock and avoids, at the same time, the cost of procuring a natural sand to take its place. The principal danger in using stone dust is failure to secure the proper balance of different size grains. This is also an important matter in the choice of natural sands. Sand composed of a mixture of grains ranging from fine to coarse gives uniformly stronger mortars than does sand with grains of nearly one size. and as between a coarse and a fine sand of one size of grains, the coarse sand gives the stronger mortar. Further data on the effect of size of grains on the utility of sand for concrete are given in Chapter 2, in the section on voids in sand, and for those who wish to study in detail the test data on this and the other matters referred to here, the authors recommend cements, mortars, and concretes, their physical properties, by Myron S. Falk, Cost of Sand. A very common price for sand in cities is $1 per cu, YD, delivered at the work. It may be noted here that as sand is often sold by the load instead of the cubic yard, it is wise to have a written agreement defining the size of a load. Where the contractor gets his sand from the pit, its cost will be the cost of excavating and loading at the pit, the cost of hauling in wagons, the cost of freight and rehandling it if necessary, and the cost of washing added together. An energetic man working under a good foreman will load 20 cu, ids, of sand into wagons per 10-hour day. With a poor foreman or when laborers are scarce, it is not safe to count on more than 15 cu, ids, per day. With wages at $1.50 per day, this will make the cost of loading 10 CTS per cubic yard. The cost of hauling will include the cost of lost team time and dumping, which will average about 5 CTS per cubic yard with 1 cu, YD. Loads, wages of team 35 CTS per hour and speed of travel 2.5 miles per hour. The cost of hauling proper is a half CT per 100 FT or 27 CTS per mile. Assuming a mile haul, the cost of sand delivered based on the above figures will be 10 CTS, plus 5 CTS, plus a half CT, per 100 FT, equals 15 plus 27 CTS, equals 42 CTS, per cu, YD. Freight rates can always be secured, and it is usually safe to estimate the weight on a basis of 2,700 pounds per cubic yard. For a full discussion of the cost of excavating sand and other earths, the reader is referred to Earth Excavation and Embankments, Methods and Cost, by Halbert P. Gillette and Daniel J. Howe. Methods and cost of washing sand. When the available sand carries considerable percentages of loam or clay, and the specifications require that clean sand shall be used, washing is necessary. The best and cheapest method of performing this task will depend upon the local conditions and the amount of sand to be washed. Washing with hose. When the quantity of sand to be washed does not exceed 15 to 30 cu, ids, per day, the simplest method perhaps is to use a hose. Build a wooden tank or box 8 FT, wide and 15 FT, long, the bottom having a slope of 8 ins. In the 15 FT, the sides should be about 8 ins, high at the lower end and rise gradually to 3 FT, in height at the upper end. Close the lower end of the tank with a board gate about 6 ins, in height and sliding in grooves so that it can be removed. Dump about 3 cu, ids, of sand into the upper end of the tank and play a 3/4 in. Hose stream of water on it, the hose man standing at the lower end of the tank. The water and sand flow down the inclined bottom of the tank where the sand remains and the dirt flows over the gate and off with the water. It takes about an hour to wash a 3 cu, YD, batch, and by building a pair of tanks so that the hose man can shift from one to the other, washing can proceed continuously, and one man will wash 30 cu, ids, per 10-hour day at a cost, with wages at $1.50 of 5 CTS per cubic yard. The sand, of course, has to be shoveled from the tank, and this will cost about 10 CTS per cubic yard, making 15 CTS per cubic yard for washing and shoveling, and to this must be added any extra hauling, and if the water is pumped, the cost of pumping, which may amount to 10 CTS. Per cubic yard for coal and wages, altogether a cost of from 15 to 30 CTS. Per cubic yard may be figured for washing sand with a hose. Fig. 1. Plan and elevation of 2-hopper ejector sand washing plant. Fig. 2. Plan and elevation of 4-hopper ejector sand washing plant, washing with sand ejectors. When large quantities of sand are to be washed, use may be made of the sand ejector system, commonly employed in washing filter sand at large water filtration plants. Water under pressure is required. In this system, the dirty sand is delivered into a conical or pyramidal hopper, from the bottom of which it is drawn by an ejector and delivered mixed with water into a second similar hopper. Here the water and dirt overflow the top of the hopper, while the sand settles and is again ejected into a third hopper or to the stock pile or bins. The system may consist of anywhere from 2 to 6 hoppers. Figure 1 shows a 2-hopper layout and Fig. 2 shows a 4-hopper layout. In the first plant, the washed sand is delivered into bins so arranged, as will be seen, that the bins are virtually a third washing hopper. The clean sand is chuted from these bins directly into cars or wagons. In the second plant, the clean sand is ejected into a trough which leads it into buckets handled by a derrick. The details of one of the washing hoppers for the plant shown by Fig. 1 are illustrated by Fig. 3. Fig. 3. Details of washing hopper and ejector for plants shown by Fig. 1. At filter plants, the dirty sand is delivered mixed with water to the first hopper by means of ejectors stationed in the filters and discharging through pipes to the washers. When, as would usually be the case in contract work, the sand is delivered comparatively dry to the first hopper, this hopper must be provided with a sprinkler pipe to wet the sand. In studying the ejector washing plants illustrated, it should be borne in mind that for concrete work they would not need to be of such permanent construction as for filter plants. The washers would be mounted on timber frames, underground piping would be done away with, etc. At best, however, such plants are expensive and will be warranted only when the amount of sand to be washed is large. The usual assumption of waterworks engineers is that the volume of water required for washing filter sand is 15 times the volume of the sand washed. At the Albany, NY, filters the sand passes through 5 ejectors at the rate of 3 to 5 ids per hour and takes 4,000 gallons of water per cubic yard. 1 man shovels sand into the washer and 2 take it away. Based on an output of 32 ids, in 10 hours, Mr. Allen Hazen estimates the cost of washing as follows: 3 men at $2 per day, $6. 110,000 gallons of water at $0. 055, 50, total 32 ids at 36 CTS. $11. 50 washing with tank washers. Figure 4 shows a sand washer used in constructing a concrete lock at Springdale, PA, in the United States government improvement work on the Allegheny River. The device consisted of a circular tank 9 ft in diameter and 7 ft high, provided with a sloping false bottom perforated with 1 in, holes through which water was forced as indicated. A 7x5x6 in pump with a 3 in discharge pipe was used to force water into the tank, and the rotating paddles were operated by a 7 HP engine. This apparatus washed a batch of 14 ids in from 1 to 2 hours at a cost of 7 CTS per cubic yard. The sand contained much fine coal and silt. The above data are given by Mr. W. H. Roper, Fig. 4. Details of tank washer used at Springdale, Pa, Fig. 5. Details of tank washer used at Yonkers, NY, Fig. 6. Details of rotating tank sand washer used at Hudson, NY. Another form of tank washer designed by Mr. Allen Hazen for washing bank sand at Yonkers, NY, is shown by Fig. 5. This apparatus consisted of a 10 x 2 x 2½ ft wooden box with a 6-in pipe entering one end at the bottom and there branching into 3 3-in pipes extending along the bottom and capped at the ends. The undersides of the 3-in pipes were pierced with a 1/2-in, holes 6 ins, apart, through which water under pressure was discharged into the box. Sand was shoveled into the box at one end, and the upward currents of water raised the fine and dirty particles until they escaped through the waste troughs. When the box became filled with sand, a sliding door at one end was opened, and the batch discharged. The operation was continuous as long as sand was shoveled into the box. By manipulating the door, the sand could be made to run out with a very small percentage of water. Sand containing 7% of dirt was thus washed so that it contained only 0.6% dirt. The washer handled 200 cu/ids of sand in 10 hours. The above data are given by F. H. Stephenson, a somewhat more elaborate form of tank washer than either of those described is shown by Fig. 6. This apparatus was used by Mr. Geo. A. Soper for washing filter sand at Hudson, NY. The dirty sand was shoveled into a sort of hopper from which it was fed by a hose stream into an inclined cylinder, along which it traveled and was discharged into a wooden trough provided with a screw conveyor and closed at both ends. The water overflowing the sides of the trough carried away the dirt, and the clean sand was delivered by the screw to the bucket elevator, which hoisted it to a platform from which it was taken by barrows to the stockpile. A 4 HP engine with a 5 HP boiler operated the cylinder, screw, elevator, and pump. 4 men operated the washer and handled 32 cu/ids of sand per day, with wages at $1.50. The cost of washing was 20 cts per cubic yard. Fig. 7. Arrangement of sand washing plant at Lynchburg, VA, in constructing a concrete block dam at Lynchburg, VA. Sand containing from 15 to 30% of loam, clay, and vegetable matter was washed to a cleanliness of 2 to 5% of such matter by the device shown by Fig. 7. A small creek was diverted, as shown, into a wooden flume terminating in 2 sand tanks. By means of the swinging gate, the flow was passed through either tank as desired. The sand was hauled by wagon and shoveled into the upper end of the flume. The current carried it down into one of the tanks, washing the dirt loose and carrying it off with the overflow over the end of the tank while the sand settled in the tank. When one tank was full, the flow was diverted into the other tank, and the sand in the first tank was shoveled out, loaded into wagons, and hauled to the stockpile. As built, this washer handled about 30 cu/ids of sand per 10-hour day, but the tanks were built too small for the flume, which could readily handle 75 cu/ids per day with no larger working force. This force consisted of 3 men at $1.50 per day, making the cost for a 30 cu/yd. Output 15 cts per cu/yd for washing. None of the figures given above includes the cost of handling the sand to and from the washer. When this involves much extra loading and hauling, it amounts to a considerable expense, and in any plan for washing sand, the contractor should figure with exceeding care the extra handling due to the necessity of washing. Aggregates. The aggregates commonly used in making concrete are broken or crushed stone, gravel, slag, and cinders. Slag and cinders make a concrete that weighs considerably less than stone or gravel mixtures, and being the products of combustion are commonly supposed to make a specially fire-resisting concrete. Their use is, therefore, confined very closely to fireproof building work, and in fact to floor construction for such buildings. Slag and cinder concretes are for this reason given minor consideration in this volume. Broken stone. Stone produced by crushing any of the harder and tougher varieties of rock is suitable for concrete. Perhaps the best stone is produced by crushing trap rock. Crushed trap, besides being hard and tough, is angular and has an excellent fracture surface for holding cement. It also withstands heat better than most stone. Next to trap, the hard, tough, crystalline limestones make perhaps the best all-around concrete material. Cement adheres to limestone better than to any other rock. Limestone, however, calcines when subjected to fire and is therefore objected to by many engineers for building construction. The harder and denser sandstones, mica schists, granites, and sienites make good stone for concrete, and occasionally shale and slate may be used. Gravel. Gravel makes one of the best possible aggregates for concrete. The conditions under which gravel is produced by nature make it reasonably certain that only the tougher and harder rocks enter into its composition. The rounded shapes of the component particles permit gravel to be more closely tamped than broken stone, and give less danger of voids from bridging. The mixture is also generally a fairly well-balanced composition of fine and coarse particles. The surfaces of the particles, being generally smooth, give perhaps a poorer bond with the cement than most broken stone. In the matter of strength, the most recent tests show that there is very little choice between gravel and broken stone concrete. Slag and cinders. The slag used for concrete aggregate is iron blast furnace slag crushed to proper size. Cinders for aggregate are steam boiler cinders. They are best with the fine ashes screened out and should not contain more than 15% of unburned coal. Balanced aggregate. With the aggregate, as with the sand for concrete, the best results, other things being equal, will be secured by using a well-balanced mixture of coarse and fine particles. Usually the product of a rock crusher is fairly well balanced except for the very fine material. There is nearly always a deficiency of this, which, as explained in a succeeding section, has to be supplied by adding sand. Usually also, the engineer accepts the crusher product coarser than screenings as being well enough balanced for concrete work. But this is not always the case. Engineers occasionally demand an artificial mixture of varying proportions of different size stones, and may even go so far as to require gravel to be screened and reproportioned. This artificial grading of the aggregate adds to the cost of the concrete in some proportion, which must be determined for each individual case. Size of aggregate. The size of aggregate to be used depends upon the massiveness of the structure, its purpose, and whether or not it is reinforced. It is seldom that aggregate larger than will pass a 3-in. Ring is used, and this only in very massive work. The more usual size is 2½ ins. For reinforced concrete, 1¼ ins is about the maximum size allowed, and in building work 1 in. Aggregate is most commonly used. Same constructors use no aggregate larger than 3/4 in. In reinforced building work, and others require that for that portion of the concrete coming directly in contact with the reinforcement, the aggregate shall not exceed 1/4 to 1/2 in. The great bulk of concrete work is done with aggregates smaller than 2 ins. And as a general thing where the massiveness of the structure will allow of much larger sizes, it will be more economic to use rubble concrete. See Chapter VI, Cost of Aggregate. The locality in which the work is done determines the cost of the aggregate. Concerns producing broken stone or screened and washed gravel for concrete are to be found within shipping distance in most sections of the country, so that these materials may be purchased in any amount desired. The cost will then be the market price of the material FOB. Cars at plant plus the freight rates and the cost of unloading and haulage to the stockpiles. If the contractor uses a local stone or gravel, the aggregate cost will be, for stone, the costs of quarrying and crushing and transportation, and for gravel, the cost of excavation, screening, washing, and transportation. Screened or crusher-run stone for concrete. Formerly, engineers almost universally demanded that broken stone for concrete should have all the finer particles screened out. This practice has been modified to some considerable extent in recent years by using all the crusher product, both coarse and fine, or, as it is commonly expressed, by using run-of-crusher stone. The comparative merits of screened and crusher-run stone for concrete work are questions of comparative economy and convenience. The fine stone dust and chips produced in crushing stone are not, as was once thought, deleterious. They simply take the place of so much of the sand which would, were the stone screened, be required to balance the sand and stone mixture. It is seldom that the proportion of chips and dust produced in crushing stone is large enough to replace the sand constituent entirely. Some sand has nearly always to be added to run-of-crusher stone, and it is in determining the amount of this addition that uncertainty lies. The proportions of dust and chips in crushed stone vary with the kind of stone and with the kind of crusher used. Furthermore, when run-of-crusher stone is chuted from the crusher into a bin or pile, the screenings and the coarse stones segregate. Examination of a crusher-run stone pile will show a cone-shaped heart of fine material enclosed by a shell of coarser stone. Consequently, when this pile of stone is taken from to make concrete, a uniform mixture of fine and coarse particles is not secured. The material taken from the outside of the pile will be mostly coarse, and that from the inside mostly fine. This segregation, combined with the natural variation in the crusher product, makes the task of adding sand and producing a balanced sand and stone mixture one of extreme uncertainty and some difficulty unless considerable expenditure is made in testing and reproportioning. When the product of the crusher is screened, the task of proportioning the sand to the stone is a straightforward operation, and the screened-out chips and dust can be used as a portion of the sand if desired. The only saving, then, in using crusher-run stone direct is the very small one of not having to screen out the fine material. The conclusion must be that the economy of unscreened stone for concrete is a very doubtful quantity, and that the risk of irregularity in unscreened stone mixtures is a serious one. The engineer's specifications will generally determine for the contractor whether he is to use screened or crusher-run stone, but these same specifications will not guarantee the regularity of the resulting concrete mixture. This will be the contractor's burden, and if the engineer's inspection is rigid and the crusher-run product runs uneven for the reasons given above, it will be a burden of considerable expense. The contractor will do well to know his product or to know his man before bidding less or even as little on crusher-run as on screened stone concrete. Cost of quarrying and crushing stone. The following examples of the cost of quarrying and crushing stone are fairly representative of the conditions which would prevail on ordinary contract work. In quarrying and crushing New Jersey, trap rock with gyratory crushers, the following was the cost of producing 200 cu. IDS per day, per cu, YD. 3 drillers at $2, $75 8. 25 $0, 041 3 helpers at $1, 75 5, 25 0, 026 10 men barring out and sledging 15, 0 0 0, 0 75 14 men loading cots 21, 0 0 0, 105 4 cot horses 6, 0 0 0. 032 cot drivers 3, 000, 015 2 men dumping cots and feeding crusher 3, 000, 015 1 fireman for drill boiler 2, 50 0, 013 1 engineman for crusher 3, 000, 015 1 blacksmith 3, 000, 015 1 blacksmith helper 2, 000, 010 1 foreman 5, 000, 025 2 tons coal at $3, 57, 000, 035 150 pounds, 40% dynamite at 15 CTS, 22, 50 0. 113, total $106, $50. 533 The quarry face worked was 12 to 18 ft, and the stone was crushed to 2 in. Size. Owing to the seamy character of the rock, it was broken by blasting into comparatively small pieces requiring very little sledging. The stone was loaded into 1-horse dump carts, the driver taking 1 cart to the crusher while the other was being loaded. The haul was 100 ft. The carts were dumped into an inclined chute leading to a 5 gates crusher. The stone was elevated by a bucket elevator and screened. All stone larger than 2 ins was returned through a chute to a 3 gates crusher for recrushing. The cost given above does not include interest, depreciation, and repairs. These items would add about $8 to $10 more per day or 4 to 5 CTS per cubic yard. In quarrying limestone, where the face of the quarry was only 5 to 6 ft high, and where the amount of stripping was small, 1 steam drill was used. This drill received its steam from the same boiler that supplied the crusher engine. The drill averaged 60 ft of hole drilled per 10 HR day, but was poorly handled and frequently laid off for repairs. The cost of quarrying and crushing was as follows. Quarry, 1 driller $2, 51 helper 1, 51 man stripping 1, 54 men quarrying 6. 001 blacksmith 2, 50-ton coal at $3 1. 00 repairs to drill, 60 hose, drill steel and interest on plant, 90-24 pounds, dynamite 3, 60, total $20. 10 crusher, 1 engineman $2, 52 men feeding crusher 3, 56 men wheeling 9, 001 bin man 1, 51 general foreman 3, 001 third-ton coal at $3 1, 001 gallon oil, 25 repairs to crusher 1, 00 repairs to engine and boiler 1, 00 interest on plant 1, 00 total $23. 75 summary per day, per cu YD, quarrying $20, $10 37 crushing 23, 75 39 total for 60 cu, IDS $43, $85. 76. The 4 men quarrying barred out and sledged the stone to sizes that would enter a 9 times 16 in jaw crusher. The 6 men wheeling delivered the stone in wheelbarrows to the crusher platform, the run plank being never longer than 150 ft. 2 men fed the stone into the crusher, and a bin man helped load the wagons from the bin and kept tally of the loads. The stone was measured loose in the wagons, and it was found that the average load was 1.5 cu. Ids, weighing 2,400 pounds per cu. YD. There were 40 wagon loads or 60 cu. Ids crushed per 10 HR day, although on some days as high as 75 cu. Ids were crushed. The stone was screened through a rotary screen 9 ft long, having 3 sizes of openings, a half in, 1 1/4 in, and 2 1/4 in. The output was 16% of the smallest size, 24% of the middle size, and 60% of the large size. All tailings over 2.5 ins in size were recrushed. It will be noticed that the interest on the plant is quite an important item. This is due to the fact that, year in and year out, a quarrying and crushing plant seldom averages more than 100 days actually worked per year, and the total charge for interest must be distributed over these 100 days, and not over 300 days as is so commonly and erroneously done. The cost of stripping the earth off the rock is often considerably in excess of the above given cost, and each case must be estimated separately. Quarry rental or royalty is usually not in excess of 5 CTS per cu YD, and frequently much less. The dynamite used was 40%, and the cost of electric exploders is included in the cost given. Where a higher quarry face is used, the cost of drilling and the cost of explosives per cu YD is less. Exclusive of quarry rent and heavy stripping costs, a contractor should be able to quarry and crush limestone or sandstone for not more than 75 CTS per cu YD or 62 CTS per ton of 2,000 pounds, wages and conditions being as above given. The labor cost of erecting bins and installing a 9 times 16 jaw crusher, elevator, etc. averages about $75, including hauling the plant 2 or 3 miles and dismantling the plant when work is finished. The following is a record of the cost of crushing stone and cobbles on 4 jobs at Newton, Mass. in 1891. On jobs and B, the stone was quarried and crushed. On jobs C and D, cobblestones were crushed. A 9 times 15 in Farrell Marsondon crusher was used, stone being fed in by 2 laborers. A rotary screen having a half, 1 and 2 a half in. Openings delivered the stone into bins having 4 compartments, the last receiving the tailings which had failed to pass through the screen. The broken stone was measured in carts as they left the bin, but several cart loads were weighed, giving the following weights per cubic foot of broken stone. Size: a half in, 1 in, 2 a half ins, tailings, pounds, 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 greenish trap rock, A95, 884, 388, 391, 0 conglomerate, B, 101, 087, 794, 4 cobblestones, C and D, 102, 598, 099, 6. A 1-horse cart held 26 to 28 cu ft. Average 1 cu YD. Of broken stone, a 2-horse cart 40 to 42 cu ft at the crusher. Job A, B, C, D. Hours run 412, 144, 101, 198 short tons per hour 9. 011, 215, 712, 1 cu. Ids per hour 7, 7, 8. 911, 89, 0% of tailings 31, 829, 317, 520, 5% of 2 a half in, stone 51, 351, 957, 055, 1% of 1 in, stone 10, 2% of a half in, stone or dust 6, 718, 825, 523, 4. Job A, B, C, D. Explosives, coal for drill and repairs $0, 084, $0, 018. Labor steam drilling 0, 092. Labor hand drilling 0, 249. Sharpening tools 0, 069, 023. Sledging stone for crusher 0, 279, 420. Loading carts 0, 098, 127, $0, 144. Carting to crusher 0, 072, 062, $0, 314, 098. Feeding crusher 0, 053, 053, 033, 065. Engineer of crusher 0, 031, 038, 029, 036. Coal for crusher 0, 079, 050, 047, 044. Repairs to crusher 0, 041, 011. Moving portable crusher 0, 023, 019. Watchman $1, 75 a day 0, 053, 022, 030. Total cost per coup YD $0, 898 $1, 116 $0, 445 $0, 447. Total cost per short ton 0, 745 885 330 372. Note: A was trap rock, B was conglomerate rock, C and D were trap and granite cobblestones. Common laborers on jobs A and D were paid $1, 75 per 9/8 Shah day. On jobs B and C, $1, 50 per 9/8 Shah day. 2-horse cart and driver $5 per day. Blacksmith $2, 50. Engineer on crusher $2 on job A, $2, 25 on B, $2, 00 on C, $2, 50 on D. Steam driller received $3 and helper $1, 75 a day. Foreman $3 a day. Coal was $5, 25 per short ton. Forsyth powder 11 1/3 CTS per LB. For full discussion of quarrying and crushing methods and costs, and for descriptions of crushing machinery and plants, the reader is referred to Rock Excavation, Methods and Cost, by Halbert P. Gillette. Screening and washing gravel. Handwork is resorted to in screening gravel only when the amount to be screened is small, and when it is simply required to separate the fine sand without sorting the coarser material into sizes. The gravel is shoveled against a portable inclined screen through which the sand drops, while the pebbles slide down and accumulate at the bottom. The cost of screening by hand is the cost of shoveling the gravel against the screen divided by the number of cubic yards of saved material. In screening gravel for sand, the richer the gravel is in fine material, the cheaper will be the cost per cubic yard for screening. On the contrary, in screening gravel for the pebbles, the less sand there is in the gravel, the cheaper will be the cost per cubic yard for screening. The cost of shoveling divided by the number of cubic yards shoveled is the cost of screening only when both the sand and the coarser material are saved. Tests made in the pit will enable the contractor to estimate how many cubic yards of gravel must be shoveled to get a cubic yard of sand or pebbles. An energetic man will shovel about 25 ids of gravel against a screen per 10-hour day and keep the screened material cleared away, providing no carrying is necessary. A mechanical arrangement capable of handling a considerably larger yardage of material is shown by Fig. 8. 2 men and a team are required. The team is attached to the scraper by means of the rope passing through the pulley at the top of the incline. The scraper is loaded in the usual manner, hauled up the incline until its wheels are stopped by blocks, and then the team is backed up to slacken the rope and permit the scraper to tip and dump its load. The trip holding the scraper while dumping is operated from the ground. The scraper load falls onto an inclined screen which takes out the sand and delivers the pebbles into the wagon. By erecting bins to catch the sand and pebbles, this same arrangement could be made continuous in operation. Fig. 8. Device for excavating and screening gravel and loading wagons. Fig. 9. Gravel washing plant of 120 to 130 ids per hour capacity. In commercial gravel mining, the gravel is usually sorted into several sizes, and generally it is washed as well as screened. Where the pebbles run into larger sizes, a crushing plant is also usually installed to reduce the large stones. Works producing several hundred cubic yards of screened and washed gravel per day require a plant of larger size and greater cost than even a very large piece of concrete work will warrant, so that only general mention will be made here of such plants. The commercial sizes of gravel are usually 2 in, 1 in, a half in, and a quarter in down to sand. No very detailed costs of producing gravel by these commercial plants are available. At the plant of the Lake Shore and Michigan Southern Rye, where gravel is screened and washed for ballast, the gravel is passed over a 2 in, a 3/4 in, a quarter in, and a in screen in turn, and the fine sand is saved. About 2,000 tons are handled per day. The washed gravel 2 in, 2 in sizes represents from 40 to 65% of the raw gravel and costs from 23 to 30 CTS per yd for excavation, screening, and washing. The drawings of Fig. 9 show a gravel washing plant having a capacity of 120 to 130 ids per hour, operated by the Stuart Peck Sand Co. of Kansas City, Mo. Where washing alone is necessary, a plant of 1 or 2 washer units like those here shown could be installed without excessive cost by a contractor at any point where water is available. Each washer unit consists of 2 hexagonal troughs 18 ins in diameter and 18 ft long. A shaft carrying blades set spirally is rotated in each trough to agitate the gravel and force it along. Each trough also has a fall of 6 ins toward its receiving end. The 2 troughs are enclosed in a tank or box, and above and between them is a 5 in pipe having 3/4 in, holes 3 ins. A pot so arranged that the streams are directed into the troughs. The water and dirt pass off at the lower end of the troughs, while the gravel is fed by the screws into a chute discharging into a bucket elevator, which in turn feeds into a storage bin. The gravel to be washed runs from 2 ins, 2 in. In size, it is excavated by steam shovel and loaded into 1/2 yd. Dump cars, 3 of which are hauled by a mule to the washers, where the load is dumped into the troughs. The plant having a capacity of 120 to 130 ids per hour cost $25,000, including pump and an 8-tin pipeline a mile long. A 100 HP engine operates the plant, and 20 men are needed for all purposes. This plant produces washed gravel at a profit for 40 CTS. per cu. YD. Chapter 27. American engineers proportion concrete mixtures by measure. Thus a 1 to 3 to 5 concrete is one composed of 1 volume of cement, 3 volumes of sand, and 5 volumes of aggregate. In continental Europe, concrete is commonly proportioned by weight, and there have been prominent advocates of this practice among American engineers. It is not evident how such a change in prevailing American practice would be of practical advantage, aside from the fact that it is seldom convenient to weigh the ingredients of each batch. Sand, stone, and gravel are by no means constant in specific gravity, so that the greater exactness of proportioning by weight is not apparent. In this volume, only incidental attention is given to gravimetric methods of proportioning concrete. Voids. Both the sand and the aggregates employed for concrete contain voids. The amount of this void space depends upon a number of conditions, as the task of proportioning concrete consists in so proportioning the several materials that all void spaces are filled with finer material. The conditions influencing the proportion of voids in sand and aggregates must be known. Voids in sand. The two conditions exerting the greatest influence on the proportion of voids in sand are the presence of moisture and the size of the grains of which the sand is composed. Table I, showing effect of additions of different percentages of moisture on volume of sand. Percent of water in sand 0, 5 1 2 3 5 10 pounds. Pounds, 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 weight per cu, YD. Of fine sand and water 3,457, 2,206, 2,085, 2,000. In 44, 2,000, in 37, 2,000. In 35, 2,133 weight per cu. YD. Of coarse sand and water 2,551, 2,466, 2,380, 2,122, 2,000, and 58, 2,000, and 72,200. The volume of sand is greatly affected by the presence of varying percentages of moisture in the sand. A dry, loose sand that has 45%. Voids, if mixed with 5%, by weight of water will swell unless tamped to such an extent that its voids may be 57%. The same sand, if saturated with water until it becomes a thin paste, may show only 37.5%. Voids after the sand has settled. Table I shows the results of tests made by Ferret, the French experimenter. 2 kinds of sand were used, a very fine sand and a coarse sand. They were measured in a box that held 2 cu, ft, and was 8 ins deep, the sand being shoveled into the box but not tamped or shaken. After measuring and weighing the dry sand 5%. By weight of water was added, and the sand was mixed and shoveled back into the box again and then weighed. These operations were repeated with varying percentages of water up to 10%. It will be noted that the weight of mixed water and sand is given. To ascertain the exact weight of dry sand in any mixture, divide the weight given in the table by 100%, plus the given tabular percent. Thus, the weight of dry, fine sand in a 5% mixture is 2,035 divided by 1. 5 equals 198 pounds per cu, YD. The voids in the dry sand were 45%, and in the sand with 5%. Moisture, they were 7%. Pouring water onto loose, dry sand compacts it. By mixing fine sand and water to a thin paste and allowing it to settle, it was found that the sand occupied 11%, less space than when measured dry. The voids in fine sand having a specific gravity of 2. 65 were determined by measurement in a quart measure and found to be as follows. Sand not packed %. Voids 40 for a half sand shaken to refusal %. Voids 35. Sand saturated with water %. Voids 37 a half. Another series of tests made by Mr. H.P. Bodman using Chicago sand having 34 to 40%. Voids showed the following results. Water added %. 2, 4, 6, 8, 10 resulting %. Increase 17, 6, 22, 19, 5, 16, 6, 15, 6 Mr. W.M.B. Fuller found by tests that a dry sand having 34%. Voids shrunk 9, 6%. In volume upon thorough tamping until it had 27%. Voids. The same sand moistened with 6%. Water and loose had 44%. Voids, which was reduced to 31% by ramming. The same sand saturated with water had 33%. Voids, and by thorough ramming its volume was reduced 8.5%, until the sand had only 26.25%. Voids. Further experiments might be quoted, and will be found recorded in several general treatises on concrete. But these are enough to demonstrate conclusively that any theory of the quantity of cement in mortar to be correct must take into account the effect of moisture on the voids in sand, the effect of the size and the shape of the component grains on the amount of voids in sand is considerable. Ferret's experiments are conclusive on these points, and they alone will be followed here. Taking for convenience 3 sizes of sand ferret, mixed them in all the varying proportions possible with a total of 10 parts. There were 66 mixtures. The sizes used were large L, sand composed of grains passing a sieve of 5 meshes per linear inch and retained on a sieve of 15 meshes per linear inch. Medium M, sand passing a sieve of 15 meshes and retained on a sieve of 50 meshes per linear inch, and fine F, sand passing a 50 mesh sieve, with a dry sand whose grains have a specific gravity of 2. 65, the weight of a cubic yard of either the fine or the medium or the large size, was 2,190 pounds, which is equivalent to 51%. Voids. The greatest weight of mixture, 2,840 pounds, per cu yd, was an L6M0F4 mixture, that is, one composed of 6 parts large, no parts medium, and 4 parts fine. This mixture was the densest of the 66 mixtures made, having 36%. Voids. It will be noted that the common opinion that the densest mixture is obtained by a mixture of gradually increasing sizes of grains is incorrect. There must be enough difference in the size of the grains to provide voids so large that the smaller grains will enter them and not wedge the larger grains apart. Turning now to the shape of the grains, the tests showed that rounded grains give less voids than angular grains. Using sand having a composition of L5M3F2 ferret got the following results. Percent, voids, kind of grains, shaken, unshaken, natural sand, rounded grains 25, 635, 9 crushed quartzite, angular grains 27, 442, 1 crushed shells, flat grains 31, 844, 3 residue of quartzite, flat grains 34, 647. 5. The sand was shaken until no further settlement occurred. It is plain from these data on the effect of size and shape of grains on voids why it is that discrepancies exist in the published data on voids in dry sand. An idea of the wide variation in the granulometric composition of different sands is given by Table Roman II. Table Roman III shows the voids as determined for sands from different localities in the United States. Table Roman 2. Showing granulometric compositions of different sands, held by a sieve. A BCE no. 1035, 3% no, 2032, 112, 8% for, 2%, 11% no, 3014, 649, 012, 514 no, 40, 44, 4 no, 59, 629, 3, 53 no, 100, 495, 7 no, 202, 023. Voids 33%, 39%, 41, 7%, 31% note. A is a fine gravel containing 8% clay used at Philadelphia. B. Delaware River sand. C. St. Mary's River sand. D. Green River Kai sand, clean and sharp. Table Roman 3. Showing measured voids in sand from different localities. Locality, authority, percent voids. Marks: Ohio River WM, Hall 31 Washed Sandusky, OCE Sherman 40 Lake Franklin Co. OCE Sherman 40 Bank Sandusky Bay OSB Newbury 32, 3 St. Louis Mo. HH Henby 34, 3 Miss River Salt Ste. Marie H. Von Scon 41, 7 River Chicago Ill H.P. Broadman 34 to 40, Philadelphia Pa 39 Del. River Mass. Coast 31 to 34, Boston Mass Geo. Kimball 33 Clean Cow Bay L.I. Myron S. Folk 40 a half. Little Falls NJWB Fuller 45. 6. Canton Ill G.W. Chandler 30 Clean Voids in broken stone and gravel. The percentage of voids in broken stone varies with the nature of the stone, whether it is broken by hand or by crushers, with the kind of crusher used, and upon whether it is screened or crusher-run product. The voids in broken stone seldom exceed 52%, even when the fragments are of uniform size and the stone is shoveled loose into the measuring box. The following records of actual determinations of voids in broken stone cover a sufficiently wide range of conditions to show about the limits of variation. The following are results of tests made by Mr. A. N. Johnson, State Engineer of Illinois, to determine the variation in voids in crushed stone due to variation in size, and to method of loading into the measuring box. The percentage of voids was determined by weighing the amount of water added to fill the box. Size, method of loading. Percent of voids 3 in 20 ft, drop 41, 8 3 in 15 ft, drop 46, 8 3 in 15 ft, drop 47, 2 3 in shovels 48, 7 1/2 in 20 ft, drop 42, 5 1/2 in 15 ft, drop 46, 8 1/2 in 15 ft, drop 46, 8 1/2 in shovels 50, 5 3/4 in 20 ft, drop 39, 4 3/4 in 15 ft, drop 42, 7 3/4 in 15 ft, drop 41, 5 3/4 in 15 ft, drop 41, 8 3/4 in shovels 45, 2 3/4 in shovels 44, 6 in shovels 41, 0 in shovels 46 in shovels 41. 0. The table shows clearly the effect on voids of compacting the stone by dropping it. It also shows for the 3/4 in and the in stone loaded by shovels how uniformly the percentages of voids run for stone of one size only. Dropping the stone 20 ft reduced the voids some 12 to 15%, as compared with shoveling. Table Roman 4. Showing determined percentages of voids in broken stone from various common rocks. Authority, percent voids, remarks, Sabin 49, 0 limestone crusher run after screening out in and under, 44, 0 limestone 1 part screenings mixed with 6 parts broken stone. WMM Black 46, 5 screened and washed 2 ins, and under JJR Crows 47, 5 nice after screening out a quarter in, and under SB Newbury 47, 0 chiefly about egg size. HP Broadman 39 to 42 Chicago Limestone Crusher Run 48 to 52 screened into sizes WM M Hall 48 0 Green River Limestone 2½ ins and smaller dust screened out 50 0 Hudson River Trap 2½ ins and smaller dust screened out WMB Fuller 47 6 New Jersey Trap Crusher Run 1/6 to 2 1 in Geo A Kimball 49 5 Roxbury Conglomerate 1/2 to 2½ ins Myron S Folk 48 0 Limestone 1/2 to 3 ins WH Henby 43 0 2 in size 46 0 1½ in size Ferret 53 4 Stone 1 6 to 2 4 ins 51 7 0 8 to 1 6 in 52 1 0 4 to 0 8 in AW Dow 45 3 Bluestone 89% being 1½ to 2½ ins 45 3 90% being 1/6 to 1½ in Taylor and Thompson 54 5 Trap Hard 1 to 2½ ins 54 5 1/2 to 1 in 45 0 0 to 2½ in 51 2 Soft 3/4 to 2 ins GW Chandler 40 0 Canton Ill Emil Low 39 0 Buffalo Limestone Crusher Run Dust in CM Saville 46 0 Crushed Cobblestone Screened into sizes Table V showing percentages of voids in gravel and broken stone of different granulometric compositions. Percent voids in, passing a ring of 2. 4 1 6 0. 8 round broken held by a ring 1 6 0 8 0. 4 pebbles, stone, parts 1 0 0 40 0 53. 4 0 1 0 38, 851, 7 0 0 1 41, 752, 1 1 1 0 35, 850, 5 1 0 1 35, 647, 1 0 1 1 37, 940, 5 1 1 1 35, 547, 8 4 1 1 34, 549, 2 1 4 1 36, 649, 4 1 1 4 38, 148, 6 8 0 2 34, 1. Table Roman 4 gives the voids in broken stone as determined by various engineers. It requires no explanation. Table V, taken from Ferret's tests, shows the effect of changes in granulometric composition on the amount of voids in both broken stone and gravel. Considering the column giving voids in stone, it is to be noted first how nearly equal the voids are for stone of uniform size, whatever that size be. As was the case with sand, a mixture of coarse and fine particles gives the fewest voids. For stone, an L1M0F1 mixture, and for gravel, an L8M0F2 mixture. Tamping reduces the voids in broken stone. Mr. Geo W. Rafter gives the voids in clean, hand-broken limestone passing a 2½ in, ring as 43%, after being lightly shaken, and 37½ after being rammed. Generally speaking, heavy ramming will reduce the voids in loose stone about 20%. It is rare that gravel has less than 30%, or more than 45%. Voids. If the pebbles vary considerably in size so that the small fit in between the large, the voids may be as low as 30%. But if the pebbles are tolerably uniform in size, the voids will approach 45%. Table V shows the effect of granulometric composition on the voids in gravel as determined by Ferret. Mr. H. von Scon gives the following granulometric analysis of a gravel having 34. 1%. Voids, retained on 1 in. Ring, percent 10, 70 retained on in. Ring, percent 23, 65 retained on no. 4 sieve, percent 8, 70 retained on no. 10 sieve, percent 17, 14 retained on no. 20 sieve, percent 21, 76 retained on no. 30 sieve, percent 6, 49 retained on no. 40 sieve, percent 5, 96 passed a no. 40 sieve, percent 5, 59 passed a 1/2 in ring, percent 100. 0 as mixtures of broken stone and gravel are often used. The following determinations of voids in such mixtures are given. The following determinations were made by Mr. W.M. Hall for mixtures of blue limestone and Ohio River washed gravel. Percent stone, percent gravel, percent voids in mix 100 with 0 48 80, 20 44 70, 30 41 60, 40 38 1/2 50, 50 36 0, 135. The dust was screened from the stone, all of which passed a 2/2 in. Ring, the gravel all passed a 1/2 in. Screen, using the same sizes of gravel and Hudson River trap rock, the results were percent trap, percent gravel, percent voids in mix 100 with 0 50 60, 40 38 1/2 50, 50 36 0, 135. The weight of a cubic foot of loose gravel or stone is not an accurate index of the percentage of voids unless the specific gravity is known. Pure quartz weighs 165 pounds per cu ft, hence broken quartz having 40%. Voids weighs 165 times, 60 equals 99 pounds. Per cu ft, few gravels are entirely quartz, and many contain stone having a greater specific gravity like some traps or a less specific gravity like some shales and sandstone. Tables VI and Roman 7 give the specific gravities of common stones and minerals, and Table Roman 8 gives the weights corresponding to different percentages of voids for different specific gravities. Table VI, specific gravity of stone, condensed from Merrill's Stones for Building. Trap, Boston, Mass. 2, 78 Duluth, Min. 2, 8 to 3. 0 Jersey City, N.J. 303 Staten Island, N.Y. 286 Nice Madison Ave, N.Y. 292 Granite New London Con 266 Greenwich Con 284 Vinalhaven Me 266 Quincy Mass 266 Bar VT 265 Limestone Joliet Ill 256 Quincy Ill 2 51 to 2, 57 Limestone, Ulitic Bedford Ind 2, 25 to 2, 45 Marquette Mitch 2, 34 Glens Falls NY 270 Lake Champlain NY 275 Sandstone Portland Con 2, 64 Haverstraw NY 213 Medina NY 241 Potsdam NY 260 Grit Berea O 2. 12 Table Roman 7, specific gravity of common minerals and rocks. Apatite 2, 92 to 3, 25 Basalt 3, 01 Calcite Caco 32, 5 to 2, 73 Cassiterite SNO 26, 4 to 7, 1 Cerussite PB Co 36, 46 to 6, 48 Chalcopyrite Kufi S24, 1 to 4, 3 Coal Anthracite 1, 3 to 1, 84 Coal Bituminous 1, 2 to 1, 5 Diabase 2, 6 to 3, 03 Diorite 2, 92 Dolomite Car MG Co 322, 8 to 2, 9 Felspar 2, 44 to 2, 78 Felsite 2, 65 Galena PBS 7, 25 to 7, 77 Garnet 3, 15 to 4, 31 nice 2, 62 to 2, 92 granite 2, 55 to 2, 86 gypsum 2, 3 to 3, 28 halite salt Na Cl2, 1 to 2, 56 hematite Fe 2034, 5 to 5, 3 hornblende 3, 0 5 to 3, 47 limonite Fe 3040, 6, 3 6 to 4, 0 limestone 2, 35 to 2, 87 magnetite Fe 3044, 9 to 5, 2 marble 2, 0 8 to 2, 85 mica 2, 75 to 3, 1 mica schist 2, 5 to 2, 9 olivine 3, 33 to 3, 5 porphyry 2, 5 to 2, 6 pyrite Fes24, 83 to 5, 2 quartz CO22, 5 to 2, 8 quartzite 2, 6 to 2, 7 sandstone 2, 0 to 2, 78 medina 2, 4 Ohio 2, 2 slaty 1, 82 shale 2, 4 to 2, 8 slate 2, 5 to 2, 8 sphalerite ZNS3, 9 to 4, 2 stibnite SB2 S3 4, 5 to 4, 6 cyanite 2, 27 to 2, 65 talc 2, 56 to 2, 8 trap 2, 6 to 3, 0 table Roman 8. Showing weight of stone with different percentages of voids for different specific gravities. Weight in pounds per Q YD. When voids are specific gravity, weight in pounds per Q FT, weight in pounds per Q YD. 30%, 35%, 40%, 45%, 50%, 1. 0, 62. 355, 1,684, 1,178, 1,094, 1,010, 926, 842, 2. 0, 124, 7, 3,367, 2,357, 2,187, 2,000, and 21,852, 1,684, 2. 1, 130, 9, 3,536, 2,475, 2,298, 2,121, 1,945, 1,768, 2. 2, 137, 2, 3,704, 2,593, 2,408, 2,222, 2,000, and 37, 1,852, 2. 3, 143, 4, 3,872, 2,711, 2,517, 2,323, 2,130, 1,936, 2. 4, 149, 7, 4,041, 2,008, 128, 2,626, 2,424, 2,222, 2,022. 5, 155, 9, 4,209, 2,946, 2007, 136, 2005, 125, 2003, 115, 2105, 2. 6, 162, 1, 4,377, 3,000, and 64, 2008, 145, 2,626, 2,408, 2,189, 2. 7, 168, 4, 4,546, 3,182, 2,009, 155, 2,727, 2,500, 2,273, 2. 8, 174, 6, 4,714, 3,300, 3,000, in 64 2,828, 2,593, 2,357, 2. 9, 180, 9, 4,882, 3,418, 3,174, 2,009, 129, 2,685, 2,441, 3. 0, 187, 1,551, 3,536, 3,283, 3,000, and 32,778, 2,526, 3. 1, 193, 3, 5,219, 3,653, 3,392, 3,131, 2,871, 2,609, 3. 2, 199, 5, 5,388, 3,771, 3,502, 3,232, 2,963, 2,694, 3. 3, 205, 8, 5,556, 3,889, 3,611, 3,333, 3,056, 2,778, 3. 4, 212, 0, 5,724, 4,000, and 7, 3,721, 3,434, 3,148, 2,862, 3. 5, 218, 3, 5,893, 4,125, 3,008, 133,005, 135, 3,002, 141, 2,947. In buying broken stone by the cubic yard, it should be remembered that hauling in a wagon compacts the stone by shaking it down and reduces the volume. Table Roman 9 shows the results of tests made by the Illinois Highway Commission to determine the settlement of crushed stone in wagon loads for different lengths of haul. The road over which the tests were made was a macadam road, not particularly smooth, but might be considered as an average road surface. The wagon used was one with a dump bottom supported by chains, which were drawn as tight as possible, so as to reduce the sag to a minimum. It will be noticed that about 50% of the settlement occurs within the first 100 ft, and 75% of the settlement in the first 200 ft. Almost all of the settlement occurs during the first half mile, as the tests showed practically no additional settlement for distances beyond. Some of the wagons were loaded from the ground with shovels. Others were loaded from bins, the stone having a 15 ft drop, which compacted the stone a little more than where loaded with shovels, so that there was somewhat less settlement. But at the end of a half mile, the density was practically the same, whatever the method of loading. The density at the beginning and at the end of the haul can be compared by the weight of a given volume of crushed stone. For convenience, the weight of a cubic yard of the material at the beginning of the haul and at the end was computed from the known contents of a wagon. Table Roman 9, showing settlement of broken stone due to different lengths of haul on ordinarily good road in wagons. Percent settlement for hauling, weight per coup, YD, in pounds, size, method of loading, 100, 200, 300, 400, 500, 600, 700, a half mile, 1 mile at start, at finish. Screenings 15 ft, drop 11, 511. 5 2518 2840 screenings 15 FT. Drop 12 612. 6 2518 2886 screenings 15 FT. Drop 7 38 38. 9929 510 110 111 2 2450 2770 screenings 15 FT. Drop 509 610 210 210 410 410 412 4 425 2781 a half-inch 15 FT. Drop 11 511 5C 2305 2601 a half-inch 15 FT. Drop 5 36 27 17 77 98 08 392 2380 2625 1 a half-inch 15 FT. Drop 263 7495 35 35 35 45 4 2450 2601 a half-inch shovels 3 541485 35 35 76 57 25 2270 2445 1 a half-inch shovels 12 612 6 2305 2642 3-inch 15 FT. Drop 10 110 1 2376 2638 3-inch 15 FT. Drop 3 5424 54 85 05 05 06 0 2360 2505 3-inch 15 FT. Drop 0 52 52 54 14 34 34 34 9 2470 2595 3-inch shovels 12 612 6 2270 2601 3-inch shovels 5 0 5 6 6 5 6 5 6 8 6 8 6 8 7 1 2335 2510 C. Same percent of settlement for 2-mile haul. Theory of the quantity of cement in mortar and concrete. All sand contains a large percentage of voids in 1 cu, ft. Of loose sand there is 0, 3 to 0, 5 cu, ft of voids, that is 30 to 50%. Of the sand is voids. In making mortar, the cement is mixed with the sand, and the flour-like particles of the cement fit in between the grains of sand occupying a part or all of the voids. The amount of cement required in a mortar will naturally depend upon the amount of voids in the particular sand with which it is mixed. And since a correct estimate of the number of barrels of cement per cubic yard of mortar is very important, and since it is not always possible to make actual mixtures before bidding, rules based on various theories have been formulated for determining these quantities. In this volume, the rule based on the theory outlined by one of the authors in 1901 will be followed. The following is a discussion of the author's theory. When loose sand is mixed with water, its volume or bulk is increased. Subsequent jarring will decrease its volume but still leave a net gain of about 10%. That is, 1 cu, ft, of dry sand becomes about 1 cu, ft, of damp sand. Not only does this increase in the volume of the sand occur, but instead of increasing the voids that can be filled with cement, there is an absolute loss in the volume of available voids. This is due to the space occupied by the water necessary to bring the sand to the consistency of mortar. Furthermore, there is seldom a perfect mixture of the sand and cement in practice, thus reducing the available voids. It is safe to call this reduction in available voids about 10%. When loose, dry Portland cement is wetted, it shrinks about 15% in volume, behaving differently from the sand, but it never shrinks back to quite as small a volume as it occupies when packed tightly in a barrel. Since barrels of different brands vary widely in size, the careful engineer or contractor will test any brand he intends using in large quantities in order to ascertain exactly how much cement paste can be made. He will find a range of from 3.2 cu ft to 3.8 cu ft per barrel of Portland cement. Obviously, the larger barrel may be cheaper, though its price is higher. Specifications often state the number of cubic feet that will be allowed per barrel in mixing the concrete ingredients, so that any rule or formula to be of practical value must contain a factor to allow for the specified size of the barrel, and another factor to allow for the actual number of cubic feet of paste that a barrel will yield, the two being usually quite different. The deduction of a rational, practical formula for computing the quantity of cement required for a given mixture will now be given, based upon the facts above outlined. Let P equals number of cu ft cement paste per BBL as determined by actual test. N equals number of cu ft of cement per BBL as specified in the specifications. S equals parts of sand by volume to 1 part of cement as specified. G equals parts of gravel or broken stone by volume to 1 part of cement as specified. V equals percentage of voids in the dry sand as determined by test. V equals percentage of voids in the gravel or stone as determined by test. Then, in a mortar of 1 part cement to S parts sand, we have NS equals cu ft of dry sand to 1 BBL of cement. NSV equals voids in the dry sand, 0. 9 NSV equals available voids in the wet sand, 1. 1 NS equals wet sand, P0. 9 NSV equals cement paste in excess of the voids. Therefore, 1 NS plus P0, 9 NSV equals cu ft of mortar per BBL. Therefore, 27 N equals 1 NS plus P0, 9 NSV P plus NS1, 9 VN being the number of barrels of cement per cu YD of mortar. When the mortar is made so lean that there is not enough cement paste to fill the voids in the sand, the formula becomes 27 N equals 1 NS. A similar line of reasoning will give us a rational formula for determining the quantity of cement in concrete. But there is one point of difference between sand and gravel, or broken stone, namely, that the gravel does not swell materially in volume when mixed with water. However, a certain amount of water is required to wet the surface of the pebbles, and this water reduces the available voids, that is, the voids that can be filled by the mortar. With this in mind, the following deduction is clear, using the nomenclature and symbols above given. Ng equals cu ft of dry gravel or stone. Ngv equals voids in dry gravel, 0. 9 Ngv equals available voids in the wet gravel, P plus NS1, 9 V 0. 9 Ngv equals excess of mortar over the available voids in the wet gravel. Ng plus P plus NS1, 9 V 0. 9 Ngv equals cu ft of concrete from 1 BBL cement. 27 N equals P plus NS1, 9 V plus Ng 10. 9 VN being the number of barrels of cement required to make 1 cu YD of concrete. This formula is rational and perfectly general. Other experimenters may find it desirable to use constants slightly different from the 1 and the 0. 9. For fine sands swell more than coarse sands and hold more water. The reader must bear in mind that when the voids in the sand exceed the cement paste, and when the available voids in the gravel or stone exceed the mortar, the formula becomes 27N equals Ng. These formulas give the amounts of cement in mortars and concretes compacted in place. Tables X to Roman 13 are based upon the foregoing theory and will be found to check satisfactorily with actual tests. In using these tables, remember that the proportion of cement to sand is by volume and not by weight. If the specifications state that a barrel of cement shall be considered to hold 4 cu ft, for example, and that the mortar shall be 1 part cement to 2 parts sand, then 2 barrel of cement is mixed with 8 cu ft of sand, regardless of what is the actual size of the barrel and regardless of how much cement paste can be made with a barrel of cement. If the specifications fail to state what the size of a barrel will be, then the contractor is left to guess. Table X. Barrels of Portland cement per cubic yard of mortar. Voids in sand being 35% and 1 bbl. Cement yielding 365 cu ft of cement paste. Proportion of cement to sand 1 to 1, 1 to 1 1/2, 1 to 2, 1 to 2 1/2, 1 to 3, 1 to 4 bbls. BBLS, 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 BBLS. Barrel specified to be 3.5 cu ft. 4. 22.3, 49.2, 97.2, 57.2, 28.1, 76, 3, 8.4093, 33.2, 81.2, 45.2, 16.1, 62, 4.04003, 24.2, 73.2, 36.2, 081, 54, 4.43, 81.3, 072, 57.2, 27.2, 001, 40 cu. IDS sand per cu, YD, mortar 0, 60, 70, 80, 9101, 0 table Roman 11. Barrels of Portland cement per cubic yard of mortar. Voids in sand being 45% and 1 bbl. Cement yielding 3.4 cu ft of cement paste. Proportion of cement to sand 1 to 1, 1 to 1 1/2, 1 to 2, 1 to 2 1/2, 1 to 3, 1 to 4 bbls. BBLS, 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 BBLS. Barrel specified to be 3.5 cu ft. 462 383 25 2 84 2 35 1 76 3 8 4 32 3 61 3 10 2 72 2 16 1 62 4 0 4 19 3 46 3 0 0 2 64 2 0 5 1 54 4 4 3 94 3 34 2 92 57 1 86 1 40 cu. IDS sand per cu YD mortar 0 60 80 91 01 01 0. If the specifications call for proportions by weight, assume a Portland barrel to contain 380 pounds of cement and test the actual weight of a cubic foot of the sand to be used. Sand varies extremely in weight, due both to the variation in the percent of voids and to the variation in the kind of minerals of which the sand is composed. A quartz sand having 35% voids weighs 107 pounds per cu ft, but a quartz sand having 45% voids weighs only 91 pounds per cu ft. If the weight of the sand must be guessed at, assume 100 pounds per cu ft. If the specifications require a mixture of 1 cement to 2 of sand by weight, we will have 380 pounds, or 1 bbl, of cement mixed with 2 times 380 or 760 pounds of sand, and if the sand weighs 90 pounds. Per cu, ft, we shall have 760 divided by 90 or 8, 44 cu, ft, of sand to every barrel of cement. In order to use the tables above given, we may specify our own size of barrel, let us say 4 cu, ft, then 8. 44 divided by 4 gives 2. 11 parts of sand by volume to 1 part of cement. Without material error, we may call this a 1-to-2 mortar and use the tables, remembering that our barrel is now specified to be 4 cu, ft. If we have a brand of cement that yields 4 cu, ft of paste per bbl and sand having 45%, voids, we find that approximately 3 bbls of cement per cu, yd, of mortar will be required. Table Roman 12. Ingredients in 1 cubic yard of concrete. Sand voids 40%, stone voids 45%, Portland cement barrel yielding 65 cu, ft, paste, barrel specified to be 8 cu, ft. 1 2 4 1 2 5 1 2 6 1 2 a half 5 1 2 a half 6 1 3 4 bbls. Cement per cu, yd, concrete 1 46 1 31 18 1 13 1 0 0 1 25 cu, ids, sand 0 41 0 36 0 33 0 40 0 35 0 53 cu, ids, stone 0 82 0 91 0 0 0 80 0 84 0 71 proportions by volume. 1 3 5 1 3 6 1 3 7 1 4 7 1 4 8 1 4 9 bbls. Cement per cu, yd, concrete 1 13 1 0 5 0 96 0 82 0 77 0 73 cu, ids, sand 0 48 0 44 0 40 0 46 0 43 0 41 cu, ids, stone 0 80 0 88 0 93 0 80 0 86 0 92. Note: this table is to be used where cement is measured packed in the barrel, for the ordinary barrel holds 8 cu, ft. It should be evident from the foregoing discussions that no table can be made and no rule can be formulated that will yield accurate results unless the brand of cement is tested and the percentage of voids in the sand determined. This being so, the sensible plan is to use the tables merely as a rough guide, and where the quantity of cement to be used is very large, to make a few batches of mortar using the available brands of cement and sand in the proportions specified. $10 spent in this way may save 1,000, even on a comparatively small job. By showing what cement and sand to select, it will be seen that tables Roman 12 and Roman 13 can be condensed into the following rule. Add together the number of parts and divide this sum into 10. The quotient will be approximately the number of barrels of cement per cubic yard. Table Roman 13. Ingredients in 1 cubic yard of concrete. Sand voids 40%, stone voids 45%, Portland cement barrel yielding 65 cu, ft, of paste. Barrel specified to be 4 cu, ft. Proportions by volume: 1 2 4 1 2 5 1 2 6 1 2 a half 5 1 2 a half 6 1 3 4 bbls. Cement per cu, yd, concrete 1 31 16 1 0 0 1 0 7 0 96 1 0 8 cu, ids, sand 0 42 0 38 0 33 0 44 0 40 0 53 cu, ids, stone 0 84 0 95 1 0 0 0 88 0 95 0 71 proportions by volume. 1351361371471481489 BBLS. Cement per Q, YD, Concrete 0, 96 0, 90 0, 82 0, 75 0, 68 0, 64 Q, IDS, Sand, 0, 47 0, 44 0, 40 0, 49 0, 44 0, 42 Q, IDS, Stone, 0, 78 0, 88 0, 93 0, 86 0, 88 0, 95 Note. This table is to be used when the cement is measured loose after dumping it into a box, for under such conditions a barrel of cement yields 4 Q, FT, of loose cement. Thus for a 1, 2, 5 concrete, the sum of the parts is 1 plus 2 plus 5, which is 8. Then 10 divided by 8 is 1. 25 BBLS, which is approximately equal to the 130 BBLS given in the table. Neither is this rule nor are the tables applicable if a different size of cement barrel is specified, or if the voids in the sand or stone differ materially from 40% to 45%. Respectively. There are such innumerable combinations of varying voids and varying sizes of barrel that the authors do not deem it worth while to give other tables. The following amounts of cement per cubic yard of mortar were determined by test. Authority neat. 1 to 1, 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 7, 1 to 8 BBLS. BBLS, BBLS, BBLS. BBLS, 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 Sabin 7, 44, 17 2, 84 2, 0 6 1, 62 1, 33 1, 14 WB Fuller 8, 024 58 3, 092 31, 81 48 1, 23 1, 11100 H. P. Boardman, 744 53, 182 35. The proportions were by barrels of cement to barrels of sand, and Sabin called a 380 lb. Barrel 3, 65 Q, FT, whereas Fuller called a 380 lb. Barrel 3, 80 Q, FT, and Boardman called a 380 lb. Barrel 3, 5 Q, FT. Sabin used a sand having 38%. Voids. Fuller used a sand having 45%. Voids, and Boardman used a sand having 38%. Voids. It will be seen that the cement used by Sabin yielded 365 Q, FT, of cement paste per BBL. i.e. 27 divided by 7, 4, whereas the Atlas cement used by Fuller yielded 4 Q, FT, of cement paste per BBL. Sabin found that a barrel of cement measured 437 Q, FT when dumped and measured loose. Mr. Boardman states a barrel 380 pounds net of Lehigh Portland cement yields 365 Q, FT, of cement paste, and that a barrel 265 pounds net of Louisville natural cement yields 30 Q, FT, of cement paste. Mr. J. R. Crows M. Amsock, C.E., states that 1 BBL of Rosendale cement and 2 BBL of sand 8 Q, FT. Make 7 Q, FT of mortar, the extreme variations from this average being 7%. Frequently, concrete is made by mixing 1 volume of cement with a given number of volumes of pit gravel, no sand being used other than the sand that is found naturally mixed with the gravel. In such cases, the cement rarely increases the bulk of the gravel. Hence, table Roman 14 will give the approximate amount of cement, assuming 1 Q, YD, of gravel per cubic yard of concrete. Table Roman 14, showing barrels of cement per cubic yard of various mixtures of cement and pit gravel. SPC. Vol. of BBL. Cu, ft, barrels of cement per cubic yard of concrete for mixtures of 1 to 5, 1 to 6, 1 to 7, 1 to 8, 1 to 9, 1 to 10, 1 to 12, 3. 8, 1, 41, 1, 18, 1, 0, 1, 0, 874, 0, 789, 0, 71, 0, 59, 4, 4, 1, 25, 1, 0, 2, 0, 875, 0, 766, 0, 681, 0, 61, 0, 51. Percentage of water in concrete. Tests show that dry mixtures, when carefully deposited and well tamped, produce the stronger concrete. This superiority of dry mixtures, it must be observed, presupposes careful deposition and thorough tamping. And these are tasks which are difficult to have accomplished properly in actual construction work, and which, if accomplished properly, require time and labor. Wet mixtures readily flow into the corners and angles of the forms and between and around the reinforcing bars with only a small amount of puddling and slicing, and are therefore nearly always used because of the time and labor saved in depositing and tamping. The following rule by which to determine the percentage of water by weight for any given mixture of mortar for wet concrete will be found satisfactory. Multiply the parts of sand by 8, add 24 to the product, and divide the total by the sum of the parts of sand and cement. For example, if the percentage of water is required for a 1 to 3 mortar, 3 times 8 plus 24 equals 12. For hence the water should be 12% of the combined weight of cement and sand. For a 1-to-1 mortar, the rule gives 16%. For a 1-to-2 mortar, it gives 13.5%. And for a 1-to-6 mortar, it gives 3%. To calculate the amount of water per cubic yard of 1 to 3 to 6 concrete, for example, the procedure would be as follows. By the above rule, a 1 to 3 mortar requires 3 times 8 plus 24 equals 12% water. For a 1 to 3 to 6 concrete, according to Table Roman 12, contains 1.05 bbls, cement, and 0.44 cu yd, sand. Cement weighs 380 pounds per barrel, hence 1.05 bbls would weigh 380 times 1.05 equals 399 pounds. Sand weighs 2,700 pounds per cu yd, hence 0.44 cu yd. Of sand would weigh 2,700 times 0.44 equals 1,188 pounds. The combined weight of the cement and sand would thus be 399 plus 1,188 equals 1,587 pounds. And 12% of 1,587 pounds is 190 pounds of water. Water weighs 355 pounds per gallon, hence 190 times 355 equals 23 gallons of water per cubic yard of 1 to 3 to 6 concrete. Methods of measuring and weighing. The cement, sand, and aggregate for concrete mixtures are usually measured by hand, the measuring being done either in the charging buckets or in the barrows or other receptacles used to handle the material to the charging buckets. The process is simple in either case, when once the units of measurement are definitely stated. This is not always the case. Some engineers require the contractor to measure the sand and stone in the same sized barrel that the cement comes in which case 1 part of sand or aggregate usually means 3.5 cu ft. Other engineers permit both heads of the barrel to be knocked out for convenience in measuring the sand and stone, in which case a barrel means 3.75 cu ft. Still other engineers permit the cement to be measured loose in a box. Then a barrel usually means from 4 to 4. 5 cu ft. Cement is shipped either in barrels or in bags, and the engineer should specify definitely the volume at which he will allow the original package to be counted. And also, if cement barrels are to be used in measuring the sand and stone, he should specify what a barrel is to be. When the concrete is to be mixed by hand, the better practice is to measure the sand and stone in bottomless boxes of the general type shown by Fig. 10 and of known volume, and then specify that a bag of cement shall be called 1 cu ft, 0, 6 cu ft, or such other fraction of a cubic foot as the engineer may choose. The contractor then has a definite basis on which to estimate the quantity of cement required for any specified mixture. The same is true if the measuring of the sand and stone be done in barrows or in the charging bucket. The volume of the bag or barrel of cement being specified, the contractor has a definite and simple problem to solve in measuring his materials. Fig. 10. Bottomless box for measuring materials in proportioning concrete. To avoid uncertainty and labor in measuring the cement, sand and stone or gravel, various automatic measuring devices have been designed. A continuous mixer with automatic measuring and charging mechanism is described in Chapter Roman 14. Figure 11 shows the Trump automatic measuring device. It consists of a series of revolving cylinders, each opening onto a table, which revolves with the cylinders, and of a set of fixed knives, which, as the tables revolve, scrape off portions of the material discharged from each cylinder onto its table. The illustration shows a set of 2 cylinders. For concrete work, a third cylinder is added. The 3 tables are set one above the other, each with its storage cylinder, and being attached to the same spindle, all revolve together. For each table there is a knife with its own adjusting mechanism. These knives may be adjusted at will to vary the percentage of material scraped off. Fig. 11. Sketch showing Trump automatic measuring device for materials in proportioning concrete. Automatic measuring devices are most used in connection with continuous mixers, but they may be easily adapted to batch mixes if desired. One point to be observed is that all of these automatic devices measure the cement loose, and this must be allowed for in proportioning the mixture. Chapter 28. The making and placing of concrete by hand is divided into the following operations. 1. Loading the barrows, buckets, carts, or cars used to transport the cement, sand, and stone to the mixing board. 2. Transporting and dumping the material. 3. Mixing the material by turning with shovels and hose. 4. Loading the concrete by shovels into barrows, buckets, carts, or cars. 5. Transporting the concrete to place. 6. Dumping and spreading. 7. Ramming. Loading into stockpiles. Stockpiles should always be provided unless there is some very good reason to the contrary. They prevent stoppage of work through irregularities in the delivery of the material, and they save foremen's time in watching that the material is delivered as promptly as needed for the work immediately in hand. The location of the stockpiles should be as close to the work as possible without being in the way of construction. Forethought both in locating the piles and in proportioning their size to the work will save the contractor money. The stone and sand will ordinarily be delivered in wagons or cars. If delivered in cars, effort should be made to secure delivery in flat cars when the unloading is to be done by shoveling. This is more particularly necessary for the broken stone. Stone can be shoveled from hopper-bottom cars only with difficulty as compared with shoveling from flat-bottom cars. The ratio is about 14 ku. Ids, per day per man from hopper-bottom cars as compared with 20 ku. Ids, per day per man from flat-bottom cars. When the cars can be unloaded through a trestle, hopper-bottom cars should by all means be secured for delivering the stone. If the amount of work will justify the expense, a trestle may be built. Often there is a railway embankment which can be dug away for a short distance, and the track carried on stringers to make a dumping place, from which the stone can be shoveled. Sand can be dumped directly on the ground, but broken stone, unless it is very small, 3/4 in, or less, should always be dumped on a well-made plank floor. A good floor is made of 2 in, plank nailed to 4 times 6 in, mud sills spaced 3 ft, apart and well bedded in the ground. Loose plank laid directly on the ground settle unevenly, and thus the smooth shoveling surface which is sought is not obtained. The object of the floor is to provide an even surface, along which a square pointed shovel can be pushed. It is very difficult to force such a shovel into broken stone unless it is very fine. A spading fork is a better tool than a shovel with which to load broken stone from piles. A man can load from 18 to 20 ku. Ids of broken stone into wheelbarrows or carts in 10 hours when shoveling from a good floor, but he can load only 12 to 14 ku. Ids per day when shoveling from a pile without such a floor. It is a common thing to see stone unloaded from cars directly onto the sloping side of a railway embankment. This makes very difficult shoveling and results in a waste of stone. Stone can usually be delivered by a steel-lined chute directly to a flooring located at the foot of the embankment. Coarse broken stone, if given a start when cast from a shovel, will slide on an iron chute having a slope as flat as 3 or 4 to 1. Sand will not slide on a slope of 1/2 to 1. When shooting is not practicable, it will pay often to shovel the stone into buckets handled by a stiff-legged derrick rather than to unload it onto the bank. Stockpiles of ample storage capacity are essential when delivery is by rail, because of the uncertainty of rail shipments. When the contractor is taking the sand and stone direct from pit and quarry by wagon, it is not necessary to have large stockpiles. Loading from stockpiles. In loading sand into wheelbarrows or carts with shovels, a man will load 20 ku. Ids per 10-hour day if he is energetic and is working under a good foreman. Under opposite conditions, 15 ku. Ids per man per day is all that it is safe to count on. A man shoveling from a good floor will load 20 ku. Ids of stone per 10-hour day, this is reduced to 15 ku. Ids per day if the stone is shoveled off the ground, and to 12 ku. Ids per day if in addition the management is poor. There are ordinarily in a cubic yard of concrete about 1 ku. Yd of stone and 0.4 ku. Yd of sand, so that the cost of loading the materials into barrows or carts with wages at 15 cts per hour and assuming 15 ku. Ids to be a day's work would be 1 ku. Yd stone loaded for 10 cts, 0.4 ku. Yd sand loaded for 4 cts. Total 14 cts. To this is to be added the cost of loading the cement. This will cost not over 2 cts per ku. Yd of concrete. The total cost of loading concrete materials into barrows or carts, therefore, does not often exceed 16 cts per ku. Yd of concrete. Transporting materials to mixing boards, carrying the sand and stone from stock piles to mixing board in shovels should never be practiced. It takes from 100 to 150 shovelfuls of stone to make 1 ku. Yd. It therefore costs 50 cts per ku. Yd to carry at 100 ft and return empty-handed, for in walking short distances the men travel very slowly, about 150 ft per minute. It costs more to walk a half-dozen paces with stone carried in shovels than to wheel it in barrows. The most common method of transporting materials from stockpiles to mixing boards is in wheelbarrows. The usual wheelbarrow load on a level plank runway is 3 bags of cement, 300 pounds or 3 ft of sand or stone. If a steep rise must be overcome to reach the mixing platform, the load will be reduced to 2 bags, 200 pounds, of cement or 2 ft of sand or stone. A man wheeling a barrow travels at a rate of 200 ft per minute going and coming and loses 3/4 minute each trip dumping the load, fixing run planks, etc. An active man will do 20 to 25% more work than this, while a very lazy man may do 20% less, with wages at 15 cts per hour. The cost of wheeling materials for 1 yd of concrete may be obtained by the following rule, to a fixed cost of 4 cts. For lost time, add 1 ct for every 20 ft of distance away from the stockpile if there is a steep rise in the runway, but if the runway is level, add 1 ct for every 30 ft distance of haul, since loading the barrows, as given above, was 16 cts per yd. The total fixed cost is 16 plus 4 equals 20 cts per yd, to which is added 1 ct for every 20 or 30 ft haul, depending on the grade of the runway. The preceding figures assume the use of plank runways for the wheelbarrows. These should never be omitted, and the barrows wheeled over the ground. Even a hard, packed earth path in dry weather is inferior to a plank runway, and when the ground is soft or muddy, the loss in efficiency of the men is serious. Where the runway must rise to the mixing board, give it a slope or grade seldom steeper than 1 in 8, and if possible flatter. Make a runway on a trestle at least 18 ins wide, so that men will be in no danger of falling. See to it, also, that the planks are so well supported that they do not spring down when walked over, for a springy plank makes hard wheeling. If the planks are so long between the horses or bents used to support them that they spring badly, it is usually a simple matter to nail a cleat across the underside of the planks and stand an upright strut underneath to support and stiffen the plank. When 2-wheeled carts of the type shown by Fig. 12 are used, the runway requires 2 lines of planks. 2-wheeled carts pushed by hand have been less used for handling concrete materials than for handling concrete, but for distances from 50 to 150 ft. From stockpile to mixing board, such carts are probably cheaper for transporting materials than are wheelbarrows. These carts hold generally 3 wheelbarrow loads, and they are handled by 1 man practically as rapidly and easily as is a wheelbarrow, for all distances over 50 ft. From stockpile to mixing board, it is cheaper to haul materials in 1-horse dump carts than it is in wheelbarrows. A cart should be loaded in 4 minutes and dumped in about 1 minute, making 5 minutes lost time each round trip. It should travel at a speed of not less than 200 ft per minute, although it is not unusual to see variations of 15 or 20%, one way or another from this average, depending upon the management of the work. A 1-horse cart will readily carry enough stone and sand to make a half yd of concrete if the roads are fairly hard and level, and a horse can pull this load up a 10% rise of 1 ft in 10 ft. Planked roadway provided with cleats to give a foothold. If a horse, cart, and driver can be hired for 30 cts per hour, the cost of hauling the materials for 1 YD of concrete is given by the following rule, to a fixed cost of 5 CTS. For lost time at both ends of haul, add 1 CT for every 100 FT of distance from stockpile to mixing board. Fig. 12. Two-wheeled ransom cart for hauling concrete. Where carts are used, it is possible to locate the stockpiles several hundred feet from the mixing boards without adding materially to the cost of the concrete. It is well, however, to have the stockpiles in sight of the foreman at the mixing board, so as to ensure promptness of delivery. Methods and cost of mixing. In mixing concrete by hand, the materials are spread in superimposed layers on a mixing board, and mixed together first dry, and then with water by turning them with shovels or hose. The number of turns, the relative arrangement of the layers, and the sequence of operations vary in practice with the notions of the engineer controlling the work. No one mode of procedure in hand mixing can, therefore, be specified for general application. The following are representative examples of practice in hand mixing. Measure the stone in a bottomless box and spread it until its thickness in inches equals its parts by volume. Measure the sand in a bottomless box set on the stone and spread the sand evenly over the stone layer. Place the cement on the sand and spread evenly. Turn the material twice with a square-pointed shovel, and then turn it a third time while water is gently sprinkled on. A fourth turn is made to mix thoroughly the water, and the concrete is then shoveled into barrows, giving it a fifth turn. Mr. Ernest McCullough, who gives this method, states that it is the cheapest way to mix concrete by hand and still secure a good quality of output. In work done by Mr. H.P. Boardman, the sand is measured in a bottomless box, and over it is spread the cement in an even layer. The cement and sand are mixed dry with hose. The water is added in pailfuls and the whole mixed to a uniform porridge-like consistency. Into this thin mortar all the stone for a batch is dumped. The measuring box is lifted and the mixture turned by shovels. A pair of shovelers, one on each side, is started at one end, turning the material back and working toward the opposite end. A second pair of shovelers takes the turned material and turns it again. The concrete is then shoveled into the barrows by the wheelers themselves as fast as it is turned the second time. By this method, a good gang of 20 to 25 men, using 2 boxes, will, Mr. Boardman states, mix and place 45 to 60 ids of concrete in 10 hours, depending on the wheelbarrow travel necessary. Assuming a gang of 25 men, this is a rate of 1.8 to 2.4 ids per man per 10-hour day concrete mixed and placed. A method somewhat similar to the one just outlined is given by Mr. O. K. Morgan, a mixing board made of matched boards nailed to 2 times 3 in. Sills is used with a mixing box about 8 ft, long 4 ft, wide and 10 to 12 ins deep. This box is set alongside the mixing board, and in it the cement and sand are mixed first dry and then wet. A fairly wet mortar is made. Meanwhile, the stone is spread in an even layer 6 ins, thick on the mixing board and thoroughly drenched with water. The mortar from the mixing box is cast by shovels in a fairly even layer over the stone, and the whole is turned 2 or 3 times with shovels. Generally 2 turns are enough. 6 men are employed, 2 prepare the mortar, while 4 get the stone in readiness, then all hands finish the operation. The following method is given by Mr. E. Sherman Good. Spread the sand in a thin layer on the mixing board, and over it spread the cement. Mix dry with shovels, using 4 men, 1 at each corner, turning outward and then working back again. Over the dry sand and cement mixture spread the broken stone which has been previously wetted, and on top of the stone apply water evenly. The water will thus percolate through the stone without splashing and evenly wet the sand and cement. Finally, turn the whole, using the same number of men and the same mode of procedure as were used in dry mixing the sand and cement. Mr. Good states that by this method the contractor should average 2 ids of mixed concrete per man per 10-hour day. A novel method of hand mixing and an unusual record of output is described by Madge H.M. Chittenden, USA, in connection with the construction of a concrete arch bridge. The mixing was done by hand on a single board 25 ft long and sloping slightly from one end to the other. The materials were dumped together on the upper end of the board. 16 men were stationed along the board, 8 on each side. The first 2 men turned the mixture dry. Next to them stood a man who applied the water after each shovelful. The next mixers kept turning the material along, and another waterman assisted in wetting it further down the board. The men at the end of the board shoveled the concrete into the carts which took it to the work. Each batch contained 18 ft, or 644 yd, and the rate of mixing was 10 ids per hour, or 25 ids per man per 10-hour day. The work of getting the materials properly proportioned to the mixing board is not included in this figure, but the loading of the mixed concrete is included. It is plain from the foregoing that specifications for hand mixing should always state the method to be followed, and particularly the number of turns necessary. If these matters are not specified, the contractor has to guess at the probable requirements of the engineer. The authors have known of inspectors demanding from 6 to 9 turns of the materials when specifications were ambiguous. It should also be made clear whether or not the final shoveling into the barrows or carts constitutes a turn, and whether any subsequent shoveling of the concrete into place constitutes a turn. Inspectors and foremen have frequent disputes over these questions. Estimates of the cost of hand mixing may usually be figured upon the number of times that the materials are to be turned by shovels. A contractor is seldom required to turn the sand and cement more than 3 times dry and 3 times wet, and then turn the mortar and stone 3 times. A willing workman under a good foreman will turn over mortar at the rate of 30 ids in 10 hours, lifting each shovelful and casting it into a pile, with wages at $1. 50 and 6 turns, this means a cost of 5 cts per cubic yard of mortar for each turn, as there is seldom more than 0.4 yd of mortar in a cubic yard of concrete. We have a cost of 2 cts per cubic yard of concrete for each turn that is given the mortar. So if the mortar is given 6 turns before the stone is added, and then the stone and mortar are mixed by 3 turns, we have 2 cts times 6 plus 5 cts times 3 equals 12 plus 15 equals 27 cts per cubic yard for mixing concrete. In pavement foundation work, 2 turns of the mortar followed by 2 turns of the mortar and stone are considered sufficient. The cost of mixing per cubic yard of concrete is then 2 cts times 2 plus 5 cts times 2 equals 4 plus 10 equals 14 cts per cubic yard of concrete. One specification known to the authors requires 6 turns dry and 3 turns wet for the mortar. Under such specifications, the cost of mixing the mortar would be 50%, higher than in the first example assumed. On the other hand, they have seen concrete mixed for street pavement foundation with only 3 turns before shoveling it into place. These costs of mixing apply to work done by diligent men. Easy-going men will make the cost 25 to 50% greater, loading and hauling mixed concrete. Wheelbarrows and carts are employed to haul the mixed concrete to the work. The loading of these with mixed concrete by shoveling costs less than the loading of the materials separately before mixing. While the weight is greater because of the added water, the volume of the concrete is much less than that of the ingredients before mixing. Again, the shoveling is done off a smooth board with the added advantage of having the material lubricated. And finally, the foreman is usually at this point to crowd the work. A good worker will load 12.5 ids of concrete per 10-hour day and with wages at $1.50 per day. This would give a cost of 12 CTS per yd for loading. Practically the same principles govern the transporting of concrete in barrows as govern the handling of the raw materials in them. The cost of wheeling concrete is practically the same as for wheeling the dry ingredients, so that the total cost of loading and wheeling may be estimated by the following rule: to a fixed cost of 16 CTS. For loading and lost time, add 1 CT for every 30 FT of level haul. Within a few years, wheelbarrows have been supplanted to a considerable extent by hand carts of the general type shown by Fig. 12, which illustrates one made by the Ransom Concrete Machinery Co. The bowl of this cart has a capacity of 6 ft water measure. It is hung on a 1/4 steel axle. The wheels are 42 ins in diameter with staggered spokes and 2-in-half oval tires. The top of the bowl is 29.5 ins from the ground. Owing to the large diameter of the wheels and the fact that no weight comes on the wheeler, as with a wheelbarrow, this cart is handled by one man about as rapidly and easily as is a wheelbarrow. It will be noted that the two ends of the bowl differ in shape. The handle is removable and can be attached to either end of the bowl. With the handle attached as shown, the bowl can be inverted for discharging onto a pavement or floor. With the handle transferred to the opposite end, the bowl is fitted for dumping into narrow beam or wall forms. The maximum load of wet concrete for a wheelbarrow is 2 ft, and this is a heavy load and one that is seldom averaged. 1 to 1.5 ft is more nearly the general average. A cart of the above type will, therefore, carry from 3 to 5 wheelbarrow loads, and on good runways, which are essential, may be pushed and dumped about as rapidly as a wheelbarrow. In succeeding pages are given records of actual work with hand carts which should be studied in this connection. Portland cement concrete can be hauled a considerable distance in a dump cart or wagon before it begins to harden. Natural cement sets too quickly to permit of its being hauled far. Portland cement does not begin to set in less than 30 minutes. On a good road with no long, steep hills, a team will haul a loaded wagon at a speed of about 200 ft per minute. It therefore takes 6.5 minutes to travel a quarter of a mile, 13 minutes to travel half a mile, and 26 minutes to travel a mile. Portland cement concrete can, therefore, be hauled a mile before it begins to set. The cost of hauling concrete in carts is about the same as the cost of hauling the raw materials as given in a preceding section. When hand mixing is employed in building piers, abutments, walls, etc., the concrete often has to be hoisted as well as wheeled. A gallows frame or a mast with a pulley block at the top and a team of horses can often be used in such cases as described in Chapter Roman 12 for filling cylinder piers, or in the same chapter for constructing a bridge abutment. It is also possible often to locate the mixing board on high ground, perhaps at some little distance from the forms. If this can be done, The use of derricks may be avoided as above suggested, or by building a light pole trestle from the mixing board to the forms. The concrete can then be wheeled in barrows and dumped into the forms. If the mixing board can be located on ground as high as the top of the concrete structure is to be, obviously a trestle will enable the men to wheel on a level runway. Such a trestle can be built very cheaply, especially where second-hand lumber, or lumber that can be used subsequently for forms, is available. A pole trestle whose bents are made entirely of round sticks cut from the forest is a very cheap structure, if a foreman knows how to throw it together and append the bents after they are made. One of the authors has put up such trestles for 25 CTS per lineal foot of trestle, including all labor of cutting the round timber, erecting it, and placing a plank flooring 4 ft wide on top. The stringers and flooring plank were used later for forms, and their cost is not included. A trestle 100 ft long can thus be built at less cost than hauling, erecting, and taking down a derrick, and once the trestle is up, it saves the cost of operating a derrick. In conclusion, it should be remarked that the comparative economy for concrete work of the different methods of haulage described does not depend wholly on the comparative transportation costs. The effect of the method of haulage on the cost of dumping and spreading costs must be considered. For example, if carts deliver the material in such form that the cost of spreading is greatly increased over what it would be were the concrete delivered in wheelbarrows, the gain made by cart haulage may be easily wiped out, or even turned into loss by the extra spreading charges. These matters are considered more at length in the succeeding section: dumping, spreading, and ramming. The cost of dumping wheelbarrows and carts is included in the rules of cost already given, excepting that in some cases it is necessary to add the wages of a man at the dump who assists the cart drivers or the barrow men. Thus, in dumping concrete from barrows into a deep trench or pit, it is usually advisable to dump into a galvanized iron hopper provided with an iron pipe chute. One man can readily dump all the barrows that can be filled from a concrete mixer in a day, say 150 ids. At this rate of output, the cost of dumping would be only 1 CT per YD. But if one man were required to dump the output of a small gang of men, say 25 ids, the cost of dumping would be 6 CTS per YD. Concrete dumped through a chute requires very little work to spread it in 6 layers, and in fact, concrete that can be dumped from wheelbarrows, which do not all dump in one place, can be spread very cheaply, for not more than half the pile dumped from the barrow needs to be moved, and then moved merely by pushing with a shovel. Since the spreader also rams the concrete, it is difficult to separate these two items. As nearly as the authors have been able to estimate this item of spreading dry concrete dumped from wheelbarrows in street paving work, the cost is 5 CTS per YD. If, on the other hand, nearly all the concrete must be handled by the spreaders, as in spreading concrete dumped from carts, the cost is fully double, or 10 CTS per YD. And if the spreader has to walk even 3 or 4 paces to place the concrete after shoveling it up, the cost of spreading will be 15 CTS per YD. For this reason, it is apparent that carts are not as economical as wheelbarrows for hauling concrete up to about 200 ft, due to the added cost of spreading material delivered by carts. The preceding discussion of spreading is based upon the assumption that the concrete is not so wet that it will run. Obviously, where concrete is made of small stones and contains an excess of water, It will run so readily as to require little or no spreading. The cost of ramming concrete depends almost entirely upon its dryness and upon the number of cubic yards delivered to the rammers. Concrete that is mixed with very little water requires long and hard ramming to flush the water to the surface. The yardage delivered to the rammers is another factor, because if only a few men are engaged in mixing, they will not be able to deliver enough concrete to keep the rammers properly busy. Yet the rammers, by slow, though continuous pounding, may be keeping up an appearance of working. Then again, it has been noticed that the slower the concrete is delivered, the more particular the average inspector becomes. Concrete made sloppy requires no ramming at all and very little spading. The authors have had men do very thorough ramming of moderately dry concrete for 15 CTS per coup, YD, where the rammers had no spreading to do, the material being delivered in shovels. It is rare indeed that spreading and ramming can be made to cost more than 40 CTS per coup, YD. Under the most foolish inspection, yet one instance is recorded which, because of its rarity, is worth noting. Mr. Herman Conroe is the authority for the data. 1 foreman, 9 men mixing, 1 ramming, averaged 15 coup. IDs a day or only 1.5 coup. IDs per man per day when laying wet concrete. When laying dry concrete, the same gang averaged only 8 coup. IDs a day, there being 4 men ramming, with foremen at $2 and laborers at $1. 50 a day, the cost was $2, 12 per coup, YD. For labor on the dry concrete as against $1, 13 per coup, YD. For the wet concrete, 3 turnings of the stone with a wet mortar effected a better mixture than 4 turnings with a dry mortar. The ramming of the wet concrete cost 10 CTS per coup, YD, whereas the ramming of the dry concrete cost 75 CTS per coup, YD. The authors think this is the highest cost on record for ramming. It is evident, however, that the men were under a poor foreman for an output of only 15 coup. IDs per day with 10 men is very low for ordinary conditions. Moreover, the expensive amount of ramming indicates either poor management or the most foolish inspection requirements. In conclusion, it may be noted that if engineers specify a dry concrete and thorough ramming, they would do well also to specify what the word thorough is to mean, using language that can be expressed in cents per cubic yard. It is a common thing, for example, to see a sewer trench specification in which 1 tamper is required for each 2 men shoveling the backfill into the trench, and some such specific requirement should be made in a concrete specification if close estimates from reliable contractors are desired. Surely no engineer will claim that this is too unimportant a matter for consideration when it is known that ramming can easily be made to cost as high as 40 CTS per coup, YD, depending largely upon the whim of the inspector. The cost of superintendence. This item is obviously dependent upon the yardage of concrete handled under 1 foreman and the daily wages of the foreman. If a foreman receives $3 a day and is bossing a job where only 12 coup IDs are placed daily, we have a cost of 25 CTS per coup, YD, for superintendence. If the same foreman is handling a gang of 20 men whose output is 50 coup IDs, the superintendent's item is only 6 CTS per coup, YD. If the same foreman is handling a concrete mixing plant having a daily output of 150 coup IDs, the cost of superintendence is but 2 CTS per coup, YD. These elementary examples have been given simply because figures are more impressive than generalities, and because it is so common a sight to see money wasted by running too small a gang of men under 1 foreman. Of all classes of contract work, none is more readily estimated day by day than concrete work, not only because it is usually built in regular shapes whose volumes are easily ascertained at the end of each day, but because a record of the bags, or barrels, or batches gives a ready method of computing the output of each gang. For this reason, small gangs of concrete workers need no foreman at all, provided one of the workers is given command and required to keep tally of the batches. If the efficiency of a gang of 6 men were to fall off, say 15%, by virtue of having no regular non-working foreman in charge, the loss would be only $1, 35 a day, a loss that would be more than counterbalanced by the saving of a foreman's wages. Indeed, the efficiency of a gang of 6 men would have to fall off 25% or more before it would pay to put a foreman in charge. In many cases, the efficiency will not fall off at all, provided the gang knows that its daily progress is being recorded, and that prompt discharge will follow laziness. Indeed, one of the authors has more than once had the efficiency increased by leaving a small gang to themselves, in command of one of the workers who was required to punch a hole in a card for every batch. To reduce the cost of superintendents, there is no surer method than to work 2 gangs of 18 to 20 men, side by side, each gang under a separate foreman who is striving to make a better showing than his competitor. This is done with marked advantage in street paving, and could be done elsewhere oftener than it is. In addition to the cost of a foreman in direct charge of the laborers, there is always a percentage of the cost of general superintendents and office expenses to be added. In some cases, a general superintendent is put in charge of 1 or 2 foremen, and if he is a high-salaried man, the cost of superintendents becomes a very appreciable item. Summary of costs. Having thus analyzed the costs of making and placing concrete, we can understand why it is that printed records of costs vary so greatly. Moreover, we are enabled to estimate the labor cost with far more accuracy than we can guess it, for by studying the requirements of the specifications and the local conditions governing the placing of stock piles, mixing boards, etc., we can estimate each item with considerable accuracy. The purpose, however, has not been solely to show how to predict the labor cost, but also to indicate to contractors and their foremen some of the many possibilities of reducing the cost of work once the contract has been secured. An analysis of costs, such as above given, is the most effective way of discovering unnecessary leaks and of opening one's eyes to the possibilities of effecting economies in any given case. To indicate the method of summarizing the costs of making concrete by hand, let us assume that the concrete is to be put into a deep foundation requiring wheeling a distance of 30 ft, that the stock piles are on plank 60 ft, distant from the mixing board, that the specifications call for 6 turns of gravel concrete thoroughly rammed in 6-in layers, and that a good-sized gang of, say, 16 men, at $1, 50 a day each, is to work under a foreman receiving $2, 70 a day. We then have the following summary by applying the rules already given, per Q, YD, concrete, loading sand, stone, and cement $, 17 wheeling 60 ft, in barrows 4 + 2 CTS. 06 mixing concrete 6 turns at 5 CTS, 30 wheeling 30 ft, 4 + 1 CT. 05 dumping barrows, 1 man helping barrowman. 05 spreading and heavy ramming. 15 total cost of labor $, 90 foreman at $2, 70 a day. 10 grand total $1.00 to estimate the daily output of this gang of 16 laborers proceed thus. Divide the daily wages of all the 16 men, expressed in cents, by the labor cost of the concrete in cents. The quotient will be the cubic yards output of the gang. Thus, 2,400 divided by 90 is 27 cu. Ids, in this case. In street paving work where no man is needed to help dump the wheelbarrows, and where it is usually possible to shovel concrete direct from the mixing board into place, and where half as much ramming as above assumed is usually satisfactory, we see that the last four labor items, instead of amounting to 12 plus 5 plus 5 plus 15, or 37 CTS, amount only to one half of the last item, one half of 15 CTS, or 7.5 CTS. This makes the total labor cost only 60 CTS, instead of 90 CTS. If we divide 2,400 CTS, the total day's wages of 16 men by 60 CTS, the labor cost per cu, YD, we have 40, which is the cubic yards output of the 16 men. This greater output of the 16 men reduces the cost of superintendents to 7 CTS per cu, YD. Chapter 29. The making and placing of concrete is virtually a manufacturing process. This process as performed by manual labor is discussed in the preceding chapter. It will be discussed here as it is performed by machinery. The objects sought in using machinery for making and placing concrete are 1. The securing of a more perfectly mixed and uniform concrete, and 2. The securing of a cheaper cost of concrete in place. As in every other manufacturing process, both objects cannot be obtained to the highest degree without coordinate and universal efficiency throughout in plant and methods. For example, the substitution of machine mixing for hand mixing will not alone ensure cheaper concrete. If all materials are delivered to the machine in wheelbarrows, and if the concrete is conveyed away in wheelbarrows, the cost of making concrete even with machine mixers is high. On the other hand, where the materials are fed from bins by gravity into the mixer, and when the mixed concrete is hauled away in cars, the cost of making the concrete may be very low. Making and placing concrete by machinery involves not one but several mechanical operations working in conjunction. In a word, a concrete-making plant is required. The mechanical equipment of a concrete-making plant has 4 duties to perform. 1. It has to transport the raw materials from the cars or boats or pits and place them in the stockpiles or storage bins. 2. It has to take the raw materials from stock and charge them to the mixer. 3. It has to mix the raw materials into concrete and discharge the mixture into transportable vehicles. And 4, it has to transport these vehicles from the mixer to the work and discharge them. As all these operations are interrelated component parts of one great process, it is plain why one operation cannot lag without causing all the other operations to slow up. The mechanical devices which may be used for each of these operations are various, and they may be combined in various ways to make the complete train of machinery necessary to the complete process. In this chapter, we shall describe the character and qualities of each type of devices separately. The practicable ways of combining them to form a complete concrete-making plant are best illustrated by descriptions and records of work of actual plants, and such descriptions and records for each class of structure considered in this book are given in the following chapters and may be found by consulting the index. In describing the various machines and devices, we have made one classification for those used in handling raw materials and mixed concrete. for the reason that nearly all of them are suitable for either purpose. Unloading with grab buckets. The orange peel or clamshell bucket is an excellent device for unloading sand or stone from cars or barges. The cost of unloading, including cleaning up the portions not reached by the bucket, is not more than from 2 to 5 CTS per coup, YD. A grab bucket of either of these types can be applied to any derrick. In unloading broken stone from barges at Ossining N.Y., a Haywood clamshell on a stiff-leg derrick unloaded 100 coup, ids, of broken stone per day from barge into wagons with 1 engineman and 1 helper. In addition to the bucket work, there was 24 hours labor cleaning on each 500 coup. YD, barge load, the labor cost of unloading a 500 coup. YD, barge was as follows per coup. YD, 1 engineman at $2.52, 5 CTS, 1 helper at $1.50, 5 CTS. Labor cleaning at $1.50, 7 CTS. Total cost per cubic yard for 7 CTS. Inclines to reach the tops of mixer and storage bins, and the level of concrete work can be operated on about the following grades. For teams hauling wagons or cars, 2% maximum grade. A single heavy team will haul a 5 coup, YD. Car with ordinary bearings, weighing 2.5 tons empty and 12 tons loaded, with ease on a 1.5% grade and with some difficulty on a 2% grade. A locomotive will handle cars on a grade of from 4 to 5%. For team haulage, 20 lb. Rails may be used, and for locomotives, 30 lb. Rails, grades steeper than about 5%, require cable haulage. Trestle and car plants. Trestle and car plants for handling both concrete materials and mixed concrete have a wide range of application, and numerous examples of such plants are described in succeeding chapters and are noted in the index at the end of the book. The following estimates of the cost of a trestle and car plant are given by Mr. W.M. G. Fargo. The work is assumed to cover an area of 100 times 200 ft and to have 3/4 of its bulk below the economical elevation of the mixer, which stands within 50 ft of the near side of the work, if the work is under 3,000 coup, ids, in bulk, and there is a reasonable time limit for completion. 1 mixer of 200 coup, ids. Capacity per 10-hour day is assumed to be sufficient. The items of car plant cost will be about as follows: 150 ft, trestle at $1, $5,225, 5 split switches with spring, bridles at $18.92, iron turntables at $30.63 2/3 coup, YD. Steel cars with roller bearings, $190, total $565. The trestle assumed is double 24 in. Gauge track 6 ft, on centers, stringers 6 times 8 ins, times 22 to 24 ft, ties 2 times 6 ins, 2.5 ft, on centers, running boards 2 times 12 ins, for each track and 12 lb. Rails, trestle legs, average length 30 ft, of green poles at 5 CTS per foot. This outfit, with repairs and renewals amounting to 10%, is considered good for 5 seasons' work, and the timber work for several jobs if not too far apart. The yearly rental on the basis of 5 seasons' work would be $124.30 or $1 per working day for a season of 5 months. 3 cars delivering a half coup, YD. Batches can deliver 200 coup, ids, of concrete, an average of 100 ft, from the mixer in 10 hours. 5 men, including a man tending switches and turntable and 1 man to help dump, can operate the plant. with wages at $1.75 per day. The labor cost of handling 200 ids of concrete would be 4 CTS per YD. Cableways. Cableways arranged to span the work, and if the area is wide, to travel across the work at right angles to the span, will handle concrete materials, forms, steel, and supplies with great economy. They are particularly suitable for bridge and dam work, filter and reservoir work, building foundations and low buildings. The arrangement of a cableway plant for bridge work is described in Chapter 17. A cableway of 800 ft. Clear span on fixed towers 45 ft. High will cost complete from $4,500 to $5,000 and will handle 200 ids of concrete per 10-hour day. To put the cableway on traveling towers will cost about $1,000 more. In constructing the Pittsburgh filtration work, 4 traveling cableways from 250 to 600 ft. span were used. The towers were from 50 to 60 ft. in height and each traveled on a 5-rail track. The cableways were self-propelling. With conditions favorable, each cableway delivered 300 ids of concrete per day. A cableway plant for heavy fortification work is described in Chapter 11. Belt conveyors. Belt conveyors may be used successfully for handling both concrete materials and mixed concrete. For handling wet concrete, the slope must be quite flat, and the belt must be provided with some means of cleaning off the sticky mortar paste. In several cases, rotating brushes stationed at the end of the belt, where it turns over the tail pulley, have worked successfully. These brushes sweep the belt clean. Except for the cleaning device, the ordinary arrangement of belt conveyor for dry materials serves for concrete. In constructing a large gas works at Astoria, Long Island, near New York City, belt conveyors were used to handle both the sand, gravel, and cement bags and the mixed concrete. The belt for handling sand and gravel is shown by Fig. 13. A derrick operating a clamshell unloaded the sand and gravel into a small hopper, discharging into dump cars operated by a dinky up an incline, passing over sand and gravel storage bins. A 20-in belt conveyor ran horizontally 105 ft. under the bins, then up an incline of 4 ft. in 125 ft. to feeding hoppers over the mixes. This conveyor received alternately sand and gravel by chute from the storage bins and bags of cement loaded by hand, and carried them to the feeding bins and mixer platform. The speed of the belt was 350 ft. per minute, and it required 6 HP to operate it when carrying 100 tons per hour. The mixing was done in 2 Smith mixers, which turned out 70 ids or 35 ids each per hour. The mixed concrete was delivered onto a 50 ft. 24-in belt conveyor traveling at a speed of 400 ft. per minute and dumping through a chute into cars. Only 1 HP was required to run the concrete conveyor. A rotating brush was used to keep the belt clean at the dumping end. It will be noted that only a small amount of power is required for operation. Fig. 13. Belt conveyor transporting sand and gravel. Chutes. Chutes of wood or iron are among the simplest and most efficient means of moving the cement, sand, and stone, and the mixed concrete when the ground levels permit such devices. Bags of cement, if given a start in casting, will slide down a steel or very smooth wooden chute with a slope of 1 ft. in 5 or 6 ft. A wooden trough 12 ins, deep and 24 ins. Wide with boards dressed on the inside may be used. When the inclination is steep and the fall is great, some device is necessary to diminish the velocity of descent. The following is an example of such a device which was successfully employed in a chute of the above dimensions: 400 ft, long and having a drop of 110 ft. This chute had a maximum inclination of 45 degrees and its lower end curved to a horizontal tangent running into the storehouse. Near the bottom of the chute, a horizontal strip was nailed across the upper edges, and to it was nailed the upper end of a 20 ft, 1 times 12 in. Board, the lower end of which rested on the bottom of the chute. Several pieces of timber spiked to the upper side loaded the lower end of this board. The cement bag in descending wedged itself into the angle between the chute and the board and lifted the latter, the spring of the board and the weight at the lower end offering enough resistance to cut down the velocity. After the chute had been in use for some time and had worn smooth, it was found necessary to add 2 more brakes to check the bags. Broken stone will slide down a steel or steel-lined chute with a slope of 1 in 3 or 4 ft. If given a start in casting, damp sand will not slide down a chute with a slope of 1/2 in 1. A wet cement grout will flow down a smooth plank chute with a slope of 1 in 4 ft, and wet concrete will move on the same slope. Comparatively dry concrete requires a slope of nearly 1 in 1 or 45 degrees to secure free movement. Mr. W.J. Douglas gives the following examples of conveying concrete by chute, prefaced by the statement that his experience indicates that concrete can thus be conveyed considerable distances without material injury, if proper precautions are taken. In the first case, a semicircular steel trough about 2 ft, wide and 1 ft, deep and 15 ft, long set on a slope of 45 degrees was used. A lift gate of sheet steel was set in the chute about 2 ft from the upper end. The concrete was allowed to accumulate behind this gate until a wheelbarrow load was had, when the batch was let loose by lifting the gate and was discharged into barrows at the bottom. In another case, a vertical chute 15 ft, long, consisting of a 15 in square box with a canvas end was used. The concrete was dumped into the chute in batches of about 8 ft. 2 men at the bottom cut down the pile with hose to keep it from coning and causing separation of the stone. In a third case, a continuous mixer fed into a sheet iron-lined rectangular chute about 2.5 ft, wide and 1 ft, deep, with a vertical drop of 60 ft, on a slope of 1 in 1 or 45 degrees. A gate was fixed in the chute 2 ft. From the top and at the bottom, the chute fed into a pyramidal hopper 3 ft. Square at the top, 1 ft, square at the bottom, and 4.5 ft, deep. This hopper was provided with a bottom gate and was set on legs so that its top was about 10 ft, above ground. As the concrete filled in the hopper was raised and the chute cut off. The hopper was kept full all the time and was discharged by bottom gate and spout into wheelbarrows. In a fourth case, the apparatus shown by the sketch, Fig. 14, was used. The continuous mixer discharged onto an 18 in rubber conveyor belt on conical rollers and 18 ft long. The inner end of the conveyor frame was carried on the ground at the edge of the pit, and the outer end was supported by ropes from the top of a gallows frame standing on the pit bottom. The belt discharged over end into a vertical steel chute 12 ins. In diameter and 8 ft long. This chute was fastened to the conveyor frame, encircling and overlapping the 12 in. The chute was a second, slightly larger chute, suspended by means of 2 ropes from the gallows frame. The bottom of this second chute was kept about 6 ins, below the top edges of a pyramidal hopper like the one described above. In operation, the chutes and the hopper were kept filled with concrete, so that the only drop of the concrete was 3 ft from the conveyor belt into the topmost chute. Fig. 14. Belt, conveyor, and chute for handling concrete. Concrete may be handled in long, flat chutes by stationing men along the chute with shovels which they work like paddles to keep the mixture moving. In one case, concrete was so handled in a chute 200 ft, long having a slope of 1 in 10 ft. The chute was a V-shaped trough made of 1 times 12 in. Boards in sections 16 ft long. The men paddling were stationed 10 ft apart so that with wages at $1.50 per day the cost would be 1.5 CTS per QYD for every 10 ft. The concrete was conveyed. In connection with this particular work, we are informed that a Eureka continuous mixer was used. The gravel was dumped near the mixer, and a team hitched to a drag scraper delivered the gravel alongside the mixer. 4 men shoveled the gravel into the measuring hopper, but only 2 men worked at a time, shoveling for a period of 15 minutes and then resting for a corresponding period while the other 2 men worked. In this manner, the 4 men shoveled enough gravel to make 100 ids of concrete per day. A 5th man opened the cement bags and kept the cement hopper filled. Methods of charging mixers. By charging is meant the process of delivering raw materials from stock into the mixer. Several methods are practiced and will be considered in the following order. 1. By gravity from overhead bins. 2. By wheelbarrow or hand cart. A. To charging chute and B. To elevating charging hoppers. 3. By charging cars operated by cable or other means. 4. By shoveling directly into mixer. 5. By derricks or other hoists. Charging by gravity from overhead bins. Shooting the sand and stone from overhead bins to the charging hopper is a simple, rapid, and economical method of charging mixers. The bottoms of the bins should always be high enough above the charging floor to give ample head room for men to move about erect, and the length of chute may be anything reasonable more than this, that conditions such as the side hill delivery of material may necessitate. When the mixer is located to one side of the bins, the slope of the chute will have to be watched. Broken stone or pebbles will move on a comparatively flat slope, but sand, particularly if damp, requires a steep chute. The measuring hopper is best kept entirely independent of the mixer so that it can be filled with a new charge while the mixer is turning and discharging the preceding batch. 1 man can attend the sand and cement chutes if they be conveniently arranged, and 1 man can open and empty the cement bags if they be stacked close at hand. A 3rd man will level off the sand and stone in the measuring hopper and help in the shooting. A gang of this size will easily measure up a charge every 2 minutes when no delays occur. Fig. 15. Side hill mixing plant. A number of plants charging by gravity from overhead bins are described in succeeding chapters and are referenced in the index. As a general example, a side hill plant of conventional construction is shown by Fig. 15. The trestle work was made of 12 times 12 in timbers and was approximately 40 ft. In height. 3 tracks occupy the top platform. Under each track was a material bin, 1 on each side for gravel and a middle bin for sand. The sand bin was divided by a partition into 2 compartments. These bins discharged into 2 measuring hoppers, 1 gravel bin, and 1 compartment of the sand bin into each hopper. 2 cement chutes from the top platform provided for the delivery of the cement to the mixers, either directly from cars or from the cement storage house. The mixing was done in 2 Smith No. 5 mixers, 1 under each measuring hopper, and these mixers discharged by chutes into buckets on flat cars. Thus, the concrete materials brought directly from a siding in car-load lots to the top of the platform were handled entirely by gravity to the cars delivering the mixed concrete to the work. The gang operating the mixing plant with the wages paid was composed as follows: 1 foreman and engineer at $3 per day, 1 fireman at $2 per day, and 15 laborers at $1.50 per day. With this gang, the two mixers turned out 400 ids of concrete per day and frequently 800 ids in 24 hours. Taking these figures, the labor cost from raw materials in cars on the platform to mixed concrete in cars on the delivery track was as follows: 1 foreman and engineer at $3.03, 1 fireman at $2.02, 15 laborers at $1.50, 50 total labor $27.50, assuming 400 ids. Output. This gives a cost of $27.50 divided by 400 equals 875 CTS per yd. Charging with wheelbarrows. The economics of wheelbarrow haulage are discussed in some detail in Chapter Roman 3. For machine mixer work, the problem of loading, transporting, and dumping is complicated by the greater rapidity with which the mixing is done, and by the necessity, usually, of using inclines to reach the charging hopper level. The incline cuts down the output of the wheelers, or in other words, makes necessary a larger gang to handle the same amount of material. Conditions being the same, the height of the charging chute of the mixer determines the height of incline and the size of the charging gang, so that a mixer with a high charging level costs more to charge with wheelbarrows than does one with a low charging level. Exact figures of the increased cost of a few feet extra elevation of the wheelbarrow incline are not available, but some idea may be had from a brief calculation. The materials for a cubic yard of concrete will weigh about 3,700 pounds, so that to raise the materials for 100 ids of concrete, including weight of barrows, 1 ft, calls for about 400,000 pounds of work. A man will do about 800,000 pounds of useful work in a day, so that each foot of additional height of incline means an additional half-day's work for one man. Wheeling to elevating charging hoppers obviates the use of inclines. Figure 19 shows a mixer equipped with such a hopper, and the arrangement provided for other makes of mixer is much similar. When the hopper is lowered ready to receive its load, its top edge over which the wheelbarrows are dumped is from 12 to 14 inches above ground level. The wheeling is all done on the level. The elevating bucket is operated by the mixer engine and is usually detachable, where mixers have to be moved frequently, requiring the erection and moving of the incline each time. An elevating charging hopper is particularly useful. It can be hoisted clear of the ground and moved with the mixer, so that it is ready to use the moment that the mixer is set at its new station. While the ordinary wheelbarrow is generally used for charging, better work can be done under some conditions by using special charging barrows of larger capacity and dumping from the end and ahead of the wheel. Two forms of charging barrow are shown by Figs 16 and 17. The Acme barrow will hold 4 ft, and the Ransom barrow is made in 3 to 6 ft capacities. Where inclines are necessary, these barrows can often be hauled up the incline by power. A sprocket chain in the plane of the incline and operated by the mixer engine is an excellent arrangement. A prong riveted to the rear face of the barrow and projecting downward is caught into the chain which pulls the barrow to the top, the man following to dump and return for another load. Fig. 16. Forward dump charging barrow, Sterling wheelbarrow co. Fig. 17. Forward dump charging barrow, Ransom concrete machinery co. Charging with cars. Cars moved by cable, team, or hand are a particularly economic charging device when the mixer is located a little distance from the stock piles or bins. Either separate cars for cement, sand, and stone, each holding the proper amount of its material for a batch, can be used, or a single car containing enough of all three materials for a batch. The last arrangement is ordinarily more economical in time and labor, and in plant required. In either case, the car serves as the measuring hopper, there being no further proportioning of the materials after they have been loaded into the car, and it must be arranged for measuring. Usually all that is necessary where one car is used is to mark the levels on the sides to which it is to be filled with sand and then stone. The car is run to the sand stock and filled to the level marked for sand, and then to the stone stock and filled to the level marked for stone. The cement may be added to the charge either before or after it is run to the mixer, as convenience in storing the cement stock dictates. Instead of having marks to show the proper proportions of sand and stone, the car is sometimes divided into two compartments, one for each material, and each holding the proper proportion of its material when level full. This arrangement makes proper proportioning somewhat more certain, since the men charging the car cannot overrun the marks. In case separate cars are used for each material, they are simply filled level full or to mark, and dumped in succession into the feeding hopper. Trestle and car plant construction and costs are given in a preceding section. Charging by shoveling. Charging by shoveling directly into the mixer is seldom practiced except in street work with continuous mixers or in charging gravity mixers of the trough type. Shoveling is not an economic method of handling materials where the work involves carrying in shovels, and it is only in a few classes of concrete work or in isolated, exceptional cases that charging with shovels does not involve carrying. The amount of material that men will load with shovels is given in Chapter Roman 3, and the reader who wishes a full discussion of the subject is referred to Gillette and Howe. Earth excavation and embankments, methods and cost. In charging continuous mixers with shovels, the usual practice for mixers without automatic feed devices is to work from a continuous stockpile of sand, stone, and cement spread in layers in the proper proportions. The shoveling is done in such a manner that each shovelful contains a mixture of cement, sand, and stone, and so that the rate of delivery to the mixer is as uniform as possible. In charging mixers having automatic feed devices, the sand and stone are simply shoveled into the sand and stone hoppers, whence they are fed automatically to the mixer. In charging gravity mixers by shoveling, the method is essentially the same. The cement, sand, and stone, properly proportioned, are spread in layers on the shoveling board at the head of the mixer, and the mixture then shoveled into the mixer. In both of these cases, mixing is performed to a certain extent by the shoveling, and in both the provision of the combination stockpile from which the men work involves labor, which comes within the meaning of the term charging as we have used it here. Examples of street work in which the mixers were charged by shoveling are given in Chapter Roman 14, charging with derricks. When the stockpiles are located close to the mixer and the plant is fixed or is not frequently moved, derricks can be used economically for charging, particularly if the mixer be elevated so that inclines become expensive. The following mode of operation will be found to work well. Set the derrick so that its boom covers the sand and stone piles and the mixer, and provide it with 3 buckets so that there will always be 1 bucket at the stone pile and another at the sand pile while the third is being handled. The derrick swinging from the mixer, where it has discharged a bucket, drops the empty bucket at the stone pile and picks up the bucket standing there, which has received its proper charge of stone, and swings it to the sand pile and drops it to get its charge of sand. Here it picks up the bucket standing at the sand pile and which has its charges of both stone and sand, and swings it to the mixer. By this arrangement, the work of the derrick and of the men filling the buckets is practically continuous. The buckets can be provided with marks on the inside to show the proper points to which to fill the stone, and the sand or a partition may be riveted, in making a compartment for sand and another for stone. A special charging bucket that is arranged with a wheel and detachable handles, which permit it to be handled like a wheelbarrow, is shown by Fig. 18. This bucket can be used to advantage where the stock piles are too far from the mixer for the derrick to reach both, the bucket being loaded and wheeled to within reach of the derrick. Fig. 18. Charging bucket with wheel and detachable handle. Types of mixers. There are 2 types of concrete mixing machines, or concrete mixers as they are more commonly called. 1. Batch mixers and 2. Continuous mixers. In mixers of the first type, a charge of cement, sand, aggregate, and water is put into the machine which mixes and discharges the batch before taking in another charge. Charging, mixing, and discharging is done in batches. In continuous mixers, the cement, sand, stone, and water are charged into the machine in a continuous stream, and the mixed concrete is discharged in another continuous stream. While all concrete mixers are either batch or continuous mixers, it is common practice because of their distinctive character to separate gravity mixers, whether batch or continuous, into a third type. In gravity mixers, the concrete materials are made to mingle by falling through specially constructed troughs, or tubes, or hoppers. We shall describe mixers in this chapter as 1. Batch mixers, 2. Continuous mixers, and 3. Gravity mixers. No attempt will be made, however, to describe all or even all the leading mixers of each type. A representative mixer or 2 of each type will be described, enough to give an indication of the range of practice, and the reader referred to manufacturers' literature for further information. Batch mixers. Batch mixers are made in 2 principal forms which may be designated as tilting and non-tilting mixers. In the first form, the mixer drum is tilted, as one would tilt a bucket of water to discharge the batch. In non-tilting mixers, the mixer drum remains in one position, the batch being discharged by special mechanism which dips it out a portion at a time. In both forms, the charge is put into the mixer as a unit and kept confined as a unit during the time of mixing, which may be any period wished by the operator. Fig. 19. Chicago improved cube concrete mixer with elevating charging hopper. Chicago improved cube tilting mixer. Figure 19 shows the improved cube mixer made by the Municipal Engineering and Contracting Co., Chicago, Ill. The drum consists of a cubical box with rounded corners and edges. This box has hollow gudgeons at 2 diagonally opposite corners, and these gudgeons are open as shown to provide for charging and discharging. The box is rotated by gears meshing with a circumferential rack midway between gudgeons, and another set of gears operate to tilt the mixer. The inside of the box is smooth, there being no deflectors, as its shape is such as to fold the batch repeatedly and thus accomplish the mixing. Fig. 20. Ransom concrete mixer, ransom non-tilting mixer. Figure 20 shows a representative non-tilting mixer made by the Ransom Concrete Machinery Co. Dunellen, N.J. It consists of a cylindrical drum riding on rollers and rotated by a train of gears meshing with circumferential racks on the drum. The drum has a circular opening at each end. A charging chute enters one opening, and a tilting discharge chute may be thrown into or out of the opposite opening. The cylindrical shell of the drum is provided inside with steel plate deflectors, which plow through and pick up and drop the concrete mixture as the drum revolves. The shape and arrangement of the deflectors are such that the batch is shifted back and forth axially across the mixer. To discharge the batch, the discharge chute is tilted so that its end projects into the mixer, in which position the material picked up by the deflectors drops back onto the chute and runs out. The discharge chute being independent of the mixing drum, it can be thrown into and out of discharge position at will without stopping the rotation of the drum, and so can discharge any part or all of the batch at once. The top edge of the charging chute ranges from 30½ to 38 ins, in height above the top of the frame, varying with the size of the mixer. Fig. 21. Smith Concrete Mixer, Smith Tilting Mixer. Figure 21 shows a tilting mixer known as the Smith Mixer made by the Contractors Supply and Equipment Co., Chicago, Ill. The drum consists of two truncated cones with their large ends fastened together, and their small ends open for receiving the charge and discharge of the batch. The drum is operated by a train of gears meshing into a rack at mid-length where the cones join. In addition, there is another set of gears which tilt the drum to make the concrete flow out of the discharge end. The inside of the drum is provided with steel plate deflectors, which plow through and pick and drop the concrete mixture, shifting it back and forth axially in the process. Continuous mixers. Continuous mixers are those in which the cement, sand, and stone are fed to the charging hopper in a continuous stream, and the mixed concrete is discharged in another continuous stream. They are built in two principal forms. In one form, the cement, sand, and stone, properly proportioned, are shoveled directly into the mixing drum. In the other form, these materials are dumped into separate charging hoppers, and are automatically fed into the mixing drum in any relative proportions desired. One form of continuous mixer with automatic feed is described in the succeeding paragraph, and another form is described in Chapter Roman 14. The continuous mixer without automatic feed consists simply of a trough with a rotating paddle shaft and its driving mechanism. The charging, the mixing, and the discharging are done in what is virtually a succession of very small batches. Fig. 22. Eureka Automatic Feed Continuous Mixer. Eureka Automatic Feed Mixer. Figure 22 shows the construction of the continuous mixer built by the Eureka Machine Co., Lansing, Mich. The cement bin and feeder is the small one in the foreground. There is a pocketed cylinder revolving between concave plates, opening into the hopper above, from which the pockets in the feeder are filled, and discharging directly into the mixing trough below. Back of this is shown the feeder for sand or gravel up to 2 in. Screen size. This is a pocketed cylinder similar to that used in the cement feeder, except that it is larger, and instead of being provided on the discharge side with a concave plate, is surmounted by a roller held by springs. This serves to cut off the excessive flow of material, but provides sufficient flexibility to allow the rough coarse material to be fed through the machine without its catching. The feeder for crushed stone is a similar construction on larger lines to handle material up to 3 in. Size. These several feeders can be set to give any desired mixture. On any material fit to be used in concrete, they will measure with an error of less than 5%. An agitator being provided in the sand bin to prevent damp sand from bridging over the feeder and preventing its action. The mixer consists of a trough with a square shaft on which are mounted 37 mixing paddles, which are slipped on in rotation so as to form practically a continuous conveyor, but as each paddle is distinct and is shaped like the mold board of a plow, the material, as it passes from one to the next, is turned over and stirred. Water is sprayed into the mass at the center of the trough. The result is a dry mix followed by a wet mix. The mixing trough is made of heavy gauge steel, well reinforced and practically indestructible. To take care of the discharge of material while changing wheelbarrows, a hood is provided on the discharge end of the machine which can be lowered and will hold about a wheelbarrow load. Gravity mixers. Gravity mixers are constructed in two general forms. The first form is a trough whose bottom or sides or both are provided with pegs, deflectors, or other devices for giving the material a zigzag motion as it flows down the trough. The second form consists of a series of hoppers set one above the other so that the batch is spilled from one into the next and is thus mixed. The chief advantage claimed for gravity mixers is that no power is required to operate them. This is obviously so only in the sense that gravity mixers have no power-operated moving mechanism, and the fact should not be overestimated. The cost of power used in the actual performance of mixing is a very small item. The distance between feed and discharge levels is always greater for gravity mixers than for machine mixers, and the power required to raise the concrete materials, the excess height may easily be greater than the power required to operate a machine mixer. On the other hand, the simplicity of the gravity mixer ensures low maintenance costs. Gillette Trough Mixer. Figure 23 shows the construction of one of the best-known makes of gravity mixers of the trough form. In operation, the cement, sand, and stone in the proper proportions are spread in superimposed layers on a shoveling board at hopper level, and are then shoveled as evenly as possible into the hopper. From the hopper, the materials flow down the trough, receiving the water about halfway down, and are mixed by being cut and turned by the pins and deflectors. The trough of the mixer is about 10 ft. long, Fig. 23. Gillette Gravity Mixer Trough Form, Fig. 24. Haynes Gravity Mixer Fixed Hopper Form, Haynes Gravity Mixer. The form of gravity mixer made by the Haynes Concrete Mixer Co., Washington, D.C., is shown by Figs. 24 and 25. The charge passes through the hoppers in succession, considering first the stationary plant shown by Fig. 24, the four hoppers at the top have a combined capacity of one of the lower hoppers. Each top hopper is charged with cement, sand, and stone in the order named and in the proper proportions. Water is then dashed over the tops of the filled hoppers, and they are dumped simultaneously into the hopper next below. This hopper is then discharged into the next, and so on to the bottom. Meanwhile, the four top hoppers have been charged with materials for another batch. It will be observed that 1. The concrete is mixed in separate batches, and 2. The ingredients making a batch are accurately proportioned and begin to be mixed for the whole batch at once. The best arrangement is to have the top of the hopper tower carry sand and stone bins which shoot directly into the top hoppers. In the telescopic mixer shown by Fig. 25, the purpose has been to provide a mixer which, hung from a derrick or cableway, will receive a charge of raw materials at stockpile and deliver a batch of mixed concrete to the work, the operation of mixing being performed during the hoist to the work. By providing two mixes so that one can be charged while the other is being hoisted, continuous operation is secured. The following are records of operation of stationary gravity mixes of this type. Fig. 25. Haynes Gravity Mixer, Telescoping Hopper Form, in building a dock at Baltimore, MD. A plant consisting of 2 large hoppers and 4 charging hoppers with sand and stone bins above was used. 1 man at each large conical hopper tending the gates and 2 men charging the 4 pyramidal hoppers composed the mixer gang. A scow load of sand and another of stone were moored alongside the work, and a clamshell bucket dredge loaded the material from these barges into the mixer bins. Each batch was 25 ft of 1 to 2 to 5 concrete rammed in place. The men at the upper hoppers would empty a sack of cement in each, and then by opening gates in the bottom of the bins above, allow the necessary amounts of sand and stone to flow in, marks having been previously made on the sides of the hoppers to show the correct proportion of each of the ingredients. The amount of water found by experience to be necessary would then be dashed into the hoppers, and the charges allowed to run into the first cone hopper below. Refilling would begin at the top while the men were caring for the first charge in the lower hoppers. The process was thus continuous. The concrete was chuted directly into place from the bottom hopper. The record of output was 110 batches per 10-hour day. Wages of common labor were $1.50 per day. The labor cost per cubic yard of concrete in place was 35 CTS. In constructing the Cedar Grove Reservoir at Newark, N.J., a Haynes mixer made the following records of output. IDS. Best output per 10-hour day 403 average daily output for best month 302 average daily output for whole job 225. The stone, sand, and cement were all raised by bucket elevators to the top of the high wooden tower that supported the bins and mixer. There were 10 men operating the mixer so that, exclusive of power, interest, and depreciation, the labor cost of mixing averaged only 7 CTS. Per QYD. During 1 month it was as low as 5 CTS. Per QYD. This does not include delivering the materials to the men at the mixer, nor does it include conveying the concrete away and placing it. The work was done by contract. Output of mixers. With a good mixer, the output depends upon the methods of conveying the materials to and from the mixer. Most makers of mixers publish capacities of their machines in batches or cubic yards output per hour. These figures may generally be taken as stating nearly the maximum output possible, considering batch mixers as being the type most commonly used. It may be assumed that where the work is well organized and no delay occurs in delivering the materials to the mixer, that a batch every 2 minutes, or 300 batches in 10 hours, will be averaged, and there are a few records of a batch every 1.5 minutes. To illustrate to how great an extent the output of a mixer depends on the methods adopted in handling the materials to and from the mixer, we compare 2 actual cases that came under the author's observation. The mixers used were of the same size and make. In one case, the stone was shoveled into the charging hopper by 4 men, and the sand and cement were delivered in barrows by 4 other men. 6 men took the concrete away in wheelbarrows. The output of the mixer was 1 batch every 5 minutes, or 120 batches, or 60 IDS, in 10 hours. In the other case, the sand and the stone were chuted directly into the charging hopper from overhead bins, and the mixer discharged into one-batch buckets on cars. The output of the mixer was one batch every 2 minutes, or 300 batches in 10 hours. In the first case, the capacity of the mixer was limited by the ability of a gang of workable size to get the raw materials to and the mixed concrete away from the mixer. In the second case, the capacity was limited only by the amount of mixing deemed necessary. While the necessity of rapid charging of a mixer to secure its best output is generally realized, it is often forgotten that the rapidity of discharge is also a factor of importance. The size of the conveyor by which the concrete is removed affects the time of discharge. By timing a string of wheelbarrows in line, the authors have found that it takes about 7 seconds to fill each barrow. As a rule, slight delays will increase this time to 10 seconds. With a load of 1 cu ft per barrow, it requires 13 barrow loads to take away a half cu yd batch. This makes the time of discharging a batch 130 seconds, or say 2 minutes. The same mixer discharging into a batch-size bucket will discharge in 15 to 20 seconds, saving at least 1.5 minutes in discharging each batch. Mixer efficiency. Various attempts have been made to rate the efficiency of concrete mixers. In all cases, a percentage basis of comparison has been adopted. Arbitrary values are assigned to the several functions of a mixer, such as 40%. For perfect mixing, 10%. For time of mixing, and 25%. For control of water, the total being 100%. And each mixer analyzed and given a rating according as it is considered to approach the full value of any function. Such percentage ratings are unscientific and misleading. They present definite figures for what are mere arbitrary determinations. The values assigned to the several functions are purely arbitrary in the first place, and in the second place, the decision as to how near those values any mixer approaches are matters of personal judgment. The most efficient mixer is the one that gives the maximum product of standard quality at the least cost for production. This rule recognizes the fact that in practical construction, different standards of quality are accepted for different kinds of work. No engineer demands, for example, the same quality of mixture for a pavement base that he does for a reinforced concrete girder. If mixer turns out concrete of a quality suitable for pavement base cheaper than does mixer B, then it is the more efficient mixer for the purpose, even though mixer B will make the superior quality of concrete required for a reinforced girder, while mixer A will not. This method of determining efficiency holds accurate for any standard of quality that may be demanded. Chapter 30. Mixed concrete, if emptied loose and allowed to sink through water, is destroyed. The cement paste is washed away, and the sand and stones settle onto the bottom more or less segregated and practically without cementing value. In fact, if concrete is deposited with the utmost care in closed buckets, and there is any current to speak of, a considerable portion of cement is certain to wash out of the deposited mass. Even in almost still water, some of the cement will rise to the surface and appear as a sort of milky scum, commonly called latents. Placing concrete under water, therefore, involves the distinctive task of providing means to prevent the washing action of the water. It is also distinguished from work done in air by the fact that it cannot be compacted by ramming, but the main problem is that of preventing wash during and after placing. Depositing in closed buckets. Special buckets for depositing concrete under water are made by several manufacturers of concrete buckets. These buckets vary in detail, but are all similar in having doors to close the concrete away from the water, and generally in being bottom dumping. The bucket shown by Fig. 26 was designed by Mr. John F. O'Rourke and is built by the Cockburn Barrow and Machine Co. of Jersey City, N.J. This bucket was used in depositing the concrete for the City Island Bridge foundations described in Chapter Roman 12 and also in a number of other works. It consists of a nearly cubical shell of steel open at top and bottom, and having heavy timbers riveted around the bottom edges. The open top has two flat flap doors. Two similar doors hinged about midway of the sides, close to form a V-shaped hopper bottom inside the shell and serve, when open, to close the openings in the sides of the shell. In loading the bucket, the bottom doors are drawn inward and upward by the chains and held by a temporary key. The loaded bucket is then lifted by the bale and the key removed, since when suspended the pull on the bale holds the chains taut and the doors closed. As soon as the bucket rests on the bottom, the pull of the concrete on the doors slides the bale down and the doors swing downward and back, discharging the concrete. The timbers around the bottom edges keep the bucket from sinking into the deposited concrete, and the doors and shell exclude all water from the batch until it is finally in place. Fig. 26. O'Rourke bucket for depositing concrete under water. The subaqueous concrete bucket shown by Figs. 27 and 28 is made by the Cyclopean Iron Works Co., Jersey City, N.J. Fig. 27 shows the bucket suspended full ready for lowering. The cover is closed and latched, and the bale is held vertical by the tag line catch A. Other points to be noted are the eccentric pivoting of the bale, the latch unlocking lever and roller B and C, and the stop D. In the position shown, the bucket is lowered through the water, and when at the proper depth just above bottom, the tag line is given a sharp pull, uncatching the bale. The body of the bucket turns bottom side up, revolving on the bale pivots, and just as the revolution is completed, the bale engages the roller C on the latch unlocking lever and swings the lever enough to unlatch the top and allow it to swing down as shown by Fig. 28, and release the concrete. The stop D keeps the body of the bucket from swinging beyond the vertical in dumping. Fig. 27. Cyclopean bucket for depositing concrete under water, closed position. Fig. 28. Cyclopean bucket for depositing concrete under water, open position. Figures 29 and 30 show the subaqueous concrete bucket made by the G. L. Stubner Iron Works, Long Island City, NY. Essentially the same bucket, omitting the cover and with a peaked bale, is used for work in air. For subaqueous work, the safety hooks are lifted from the angles B and wired to the bale in the position shown by the dotted lines, and a tag line is attached to the handle bar C. The bucket being filled and the cover placed is lowered through the water to the bottom and then discharged by a pull on the tag line. Depositing in bags. Two methods of depositing concrete in bags are available to the engineer. One method is to employ a bag of heavy, tight woven material, from which the concrete is emptied at the bottom, the bag serving like the buckets previously described simply as means of conveyance. And the other method is to use bags of paper or loose woven gunnysack which are left in the work. The idea being that the paper will soften or the cement will ooze out through the openings in the cloth sufficiently to bond the separate bagfuls into a practically solid mass. Fig. 29. Stubner bucket for depositing concrete under water, closed position. Fig. 30. Stubner bucket for depositing concrete under water, open position. Fig. 31. Bag for depositing concrete under water. Fig. 32. Form for molding footing for block concrete breakwater. The bag shown by Fig. 31 was used to deposit concrete for leveling up a rough rock bottom, and so provide a footing for a concrete block pier constructed in 1902 at Peterhead, N.B. by Mr. William Shield, M. Inst. C. E. Careful longitudinal profiles were taken of the rock bottom, one at each edge of the footing. Side forms were then made in 20 ft. Sections as shown by Fig. 32, the lagging boards being cut to fit the determined profile and the top of the longitudinal piece being flush with the top of the proposed footing. The concrete was filled in between the side forms and leveled off by the T-rail straightedge. In placing the side forms, the longitudinal pieces were placed by divers who were given the proper elevations by level rods having 10 to 15 ft. Extension pieces to raise the targets above the water surface. When leveled, the side pieces were anchor-bolted as shown to the rock, the anchor bolts being wedged into the holes to permit future removal. The concrete was then lowered in the bag shown by Fig. 31, the divers assisting in guiding the bag to position. The mouth of the bag being tied by one turn of a line having loops through which a wooden key is slipped to hold the line tight. A sharp tug on the tripping rope loosens the key and empties the bag. The bags used on this work had a capacity of 2¼ cu. ft. To permit the removal of the side forms after the concrete had hardened, a strip of jute sacking was spread against the lagging boards with a flap extending 15 to 18 ins. Under the concrete, the forms were removed by divers, who loosened the anchor bolt wedges. In placing small amounts of concrete for bridge foundations in Nova Scotia, bags made of rough brown paper were used to hold the concrete. Each bag held about 1 cu. ft. The bags were made up quickly and dropped into the water one after the other so that the following one was deposited before the cement escaped from the former one. The paper was immediately destroyed by submersion and concrete remained. The bags cost $1, 35 per 100 or 35 CTS. Per cu, YD of concrete. Concrete was thus deposited in 18 ft. Of water without a diver. Fig. 33. Steel tremie for depositing concrete under water, depositing through a tremie. A tremie consists of a tube of wood or, better, of sheet metal which reaches from above the surface to the bottom of the water. It is operated by filling the tube with concrete and keeping it full by successive additions, while allowing the concrete to flow out gradually at the bottom by raising the tube slightly to provide the necessary opening. A good example of a sheet steel tremie is shown by Fig. 33. This tremie was used by Mr. W.M. H. Ward in constructing the Harvard Bridge foundations and numerous other subaqueous structures of concrete. In these works, the tube was suspended from a derrick. Wheelbarrows filled the tube and hopper with concrete and kept them full. The derrick raised the tube a few inches and swung it gently so as to move it slowly over the area to be filled. Care being taken to keep the tube at one height, the concrete was readily deposited in even layers. Concrete thus deposited in 18 ft. Of water was found to be level and solid on pumping the pit dry. Fig. 34. Tremie and traveler used at Charlestown, Mass. Bridge. Another method of handling a tremie was employed in constructing the foundations for the Charlestown Bridge at Boston, Mass. Foundation piles were driven and sawed off under water. A frame was built above water and supported by a curbing attached to certain piles in the outer rows of the foundation reserved for this purpose. In this frame, the vertical members were Wakefield sheet piling plank, spaced 6 to 10 ft. apart, and connected by 3 lines of double wailing bolted to the verticals at 3 different heights. This frame was lowered to the bottom so as to enclose the bearing piles. The posts or verticals were then driven, one by one, into the bottom, the frame being flexible enough to permit this. The spaces between the posts or verticals were then filled by sheet piling, and the frame was bolted to the curbing piles. This curbing afterwards supported the traveler used in laying the concrete. Thus a coffer dam was formed to receive the concrete as shown in Fig. 34. The 1 to 2 to 5 concrete was deposited up to within 5½ ft. Of the mean low water level, the last foot being laid after water was pumped out. The tremie used to deposit the concrete was a tube 14 ins. In diameter at the bottom and 11 ins. At the neck with a hopper at the top. It was made in removable sections with outside flanges and was suspended by a differential hoist from a truck moving laterally on a traveler. Fig. 34. The foot of the chute rested on the bottom until filled with concrete. Then the chute was slowly raised and the concrete allowed to run but into a conical heap, more concrete being dumped into the hopper. As the truck moved across the traveler, a ridge of concrete was made. Then the traveler was moved forward and another parallel ridge was made. The best results were obtained when the layers were 2½ ft. Thick, but layers up to 6 ft. Thick were laid. If the layer was too thick, or uneven, or if the chute was moved or raised too quickly, the charge in the tube was lost. This was objectionable because the charging of the chute anew resulted in washing the cement more or less out of the concrete until the chute was again filled. To reduce this objection, the contractor was directed to dump some neat cement into the tube before filling with concrete. A canvas piston was devised which could be pushed ahead of the concrete when filling the chute. It consisted of 2 truncated cones of canvas, one flaring downward to force the water ahead, and the other flaring upward to hold the concrete. The canvas was stiffened and held against the sides of the chute by longitudinal ribs of spring steel wire. The waist was filled by a thick block of wood to which all the springs were attached. And to this block were connected additional steel guides to prevent overturning and a rope to regulate the descent. Very little water forced its way past this piston, and it was a success. But as the cost was considerable and a piston was lost each time, its use was abandoned as the evil to be avoided did not justify the outlay. The chute worked best when the concrete was mixed not quite wet enough to be plastic. If mixed too wet, the charge was liable to be lost, and if dry, it would choke the chute. An excess of gravel permitted water to ascend in the tube, and an excess of sand tended to check the flow of concrete. In constructing the piers for a masonry arch bridge in France in 1888, much the same method was followed, except that a wooden tremie 16 ins. Square made in detachable sections was used. This tremie had a hopper top and was also provided with a removable cap or cover for the bottom end, the latter device being intended to keep the water out of the tube and prevent washing the first charge of concrete. The piers were constructed by first driving piles and sawing them off several feet above the bottom, but below water level, and then filling them nearly to their tops with broken stone. An open box caisson was then sunk onto the stone and embracing the pile tops, and then filled around the outside with more broken stone. The caisson was then filled with concrete through the tremie, which was handled by a traveling crane. The crane was mounted and traveled transversely of the pier on a platform which in turn moved along tracks laid lengthwise of the caisson. The tube was gradually filled with concrete and lowered. The detachable bottom of the tube was then removed, allowing the concrete to run out. The tube was first moved across the caisson and then downstream and back across the caisson, and this operation repeated until a 16-in layer was completed. The tube was then raised 16 ins, and the operations repeated to form another layer. There was almost no latence. From 90 to 100 ids were deposited daily. Still another example of Tremi work is furnished by the task of depositing a large mass of concrete under water in the construction of the Nussdorf lock at Vienna. This lock has a total width of 92 ft overall and is 49, 2 ft, clear inside. The excavation, which was carried to a depth of 26, 24 ft, below water level, was made full width between sheet piling, and the bottom was filled in with rammed sand and gravel, forming a kind of invert with its upper surface horizontal in the middle and sloping upwards a trifle at both sides. A mass of concrete having a total thickness of 13, 12 ft was built on this foundation in the center where the upper surfaces were 13, 12 ft below the water level. Concrete walls were carried up at the sides of the lock to a height of 3, 28 ft. These walls were 8, 2 ft thick. The methods used in placing the concrete were as follows. 3 longitudinal rows of piles were driven on each side of the axis of the lock, these piles supporting a 6-rail track about 7 ft above the water level. 3 carriages spanning the full width of the lock transversely moved on this track. Each carriage had 3 trolleys, one in each of the main panels of the transverse pile bends. These trolleys each carried a vertical telescopic tube, by means of which the concrete was deposited at the bottom of the lock. These tubes or chutes were of different lengths in the 3 carriages. The first ones deposited the concrete up to a level of 23 ft below the surface. The next set deposited the concrete between that level and 19, 7 ft, and the last set completed the subaqueous work up to the final height of 16, 4 ft below the surface. The tops of the tubes were level with a transverse track extending the full length of the carriage. The ends of these tracks just cleared the outside rows of piles, which, on one side of the lock, supported a distribution track parallel to the axis of the lock. Dump cars running on this distribution track delivered the concrete to smaller dump cars on the carriage tracks, and in turn these smaller cars dumped into either of these chutes on each carriage. The carriages were moved from end to end of the lock, the whole area of the lock coming under the 9 chutes, inasmuch as each chute moved 1/3 the length of the carriage. The concrete was deposited in 3 horizontal layers 3, 28 ft thick, the layers being built in comparatively narrow banks, so that the different layers would key together and form a corrugated mass. The chutes were shortened as the concrete was deposited, 3 layers being placed successively. The main body of the bottom and the side walls were built by this method, and then the water was pumped out and a 2, 3 ft layer of concrete rammed over the bottom and completed with a finished surface 9 ft thick. Grouting submerged stone. Masses of gravel, broken, or rubble stone deposited under water may be cemented into virtually a solid concrete by charging the interstices with grout forced through pipes from the surface. Mr. H. F. White gives the following records of grouting submerged gravel. In experiment No. 1, a reservoir 10 ft square was filled to a depth of 18 ins, with clean gravel ballast 1/2 to 2 in, size submerged in water. A 2 in gas pipe rested on the gravel and was surmounted with a funnel. A 1/1 Portland grout was poured in. After 21 days the water was drawn off, and it was found that the grout had permeated the ballast for a space of 8 ft square at the bottom and 6 ft square at the top, leaving a small pile of pure cement mortar 6 ins high about the base of the pipe, 16 ft of cement and 16 ft of sand concreted 100 ids of ballast. In experiment no. 2. Under the same conditions, a grout made of 1 pot lime, 1 pot cirque, puzzolana or trass, and 1 pot sand was found to have spread over the entire bottom 10 ft, square rising 5 ins. On the sides, and making the concreted mass about 3½ ft, square at the top 25 ft. Of the dry materials concreted 100 ft of ballast. In experiment no. 3. The ballast was 2½ ft deep. A grout using 8 ft of each ingredient made as in experiment no. 2. Covered the bottom, rose 14 ins. On the sides and made a top surface 4½ ft, square 32 ft. Of the dry materials grouted 100 ft of ballast. In experiment no. 4. The ballast was of bats and pieces 3 or 4 ins, in size laid 7 ft deep. A grout made as in experiment no. 2. Using 88 ft of each ingredient, concreted the whole mass to a depth of 6 ft. Up the sides and 2½ ft, square at the pipe on the surface of the ballast. Mr. White says that a grout containing more than 1 pot of sand to 1 of Portland cement will not run freely through a 2-in pipe, as the sand settles out and chokes the pipe. Even with one grout, it must be constantly stirred and a steady flow into the pipe maintained. The lime trass grout does not give the same trouble. Mr. W. R. Nipple describes the work of grouting rubble, stone, and gravel for the base of the Hermitage breakwater. This breakwater is 525 ft, long 50 ft, wide at base and 42 ft, wide at top and 68 ft. High. Was built on the island of Jersey, where earth from 0 to 8½ ft. Deep overlaid the granite rock. It was dredged and the trench filled in with rubble, stones, and gravel until a level foundation was secured. Cement grout was then forced into this, filling through pipe placed 8 to 10 ft apart. The grouting was done in sections 12½ ft, long, from 7 to 10 days being taken to complete each. Upon this foundation, concrete blocks, 4 times 4 times 9 to 12 ft, were laid in courses inclined at an angle of 68 degrees. The first 4 courses were laid by divers, the blocks being stacked dry 2 courses high at a time. The joints below water were calked by divers and above water by masons, and a section was then grouted. When 2 courses had been laid and grouted, 2 more courses were laid and grouted in turn, and so on. In places, grouting was done in 50 ft of water. The grout should be a thick paste, a 30 ft. Column of grout will balance a 60 ft. Column of water. Chapter 31. 2 kinds of concrete which vary in composition and character from the common standard mixtures of cement, sand, and broken aggregate are extensively employed in engineering construction. These are rubble concrete and asphaltic concrete. Rubble concrete. In constructing massive walls and slabs, a reduction in cost may often, not always, be obtained by introducing large stones into the concrete. Concrete of this character is called rubble concrete, and the percentage of rubble stone contained varies from a few percent to, in some cases, over half of the volume. The saving effected comes partly from the reduction in the cement required per cubic yard of concrete, and partly from the saving in crushing. The saving in cement may be readily figured if the composition of the concrete and the volume of the added rubble stones be known. A 1 to 2 of 5 concrete requires, according to Table X in Chapter Roman 2:1, 13 bbls of cement per cubic yard, assuming a barrel of cement to make 365 ft of paste. We have 365 times 1, 13 equals 412 ft. of cement paste per cubic yard of 1 to 2 of 5 concrete. This means that about 15% of the volume of the concrete structure is cement, if rubble stone be introduced to 50% of the volume, then the structure has about 7.5% of its volume of cement. It is of interest to note in this connection that rubble masonry composed of 65% stone and 35% of 1 to 2.5 mortar would have some 11.5% of its volume made up of cement. The saving in crushing is not so simple a determination. Generally speaking, the fact that a considerable volume of the concrete is composed of what we will call uncrushed stone means a saving in the stone constituent of one structure amounting to what it would have cost to break up and screen this volume of uncrushed stone. But there are exceptions. For example, the anchorages of the Manhattan Bridge over the East River at New York City were specified to be of rubble concrete, doubtless because the designer believed rubble concrete to be cheaper than plain concrete. In this case, an economic mistake was made, for all the rubble stone used had to be quarried up the Hudson River, loaded onto and shipped by barges to the site, and then unloaded and handled to the work using derricks. Now this repeated handling of large, irregular rubble stones is expensive. Crushed stone, as we have shown in Chapter Roman 4, can be unloaded from boats at a very low cost by means of clamshells. It can be transported on a belt conveyor, elevated by bucket conveyor, mixed with sand and cement, and delivered to the work, all with very little manual labor, when the installation of a very efficient plant is justified by the magnitude of the job. Large rubble stones cannot be handled so cheaply or with so great rapidity as crushed stone. The work may be so expensive, due to repeated handlings, as to offset the cost of crushing as well as the extra cost of cement in plain concrete. On the other hand, the cost of quarrying rock suitable for rubble concrete is no greater than the cost of quarrying it for crushing. It is generally less because the stone does not have to be broken so small, so that when the cost of getting the quarried rock to the crusher and the crushed stone into the concrete comes about the same as getting the quarried stone into the structure, it is absurd practice to require crushing. To go back then to our first thought, the question whether or not saving results from the use of rubble concrete is a separate problem in engineering economics for each structure. In planning rubble concrete work, the form of the rubble stones as they come from the quarry deserves consideration. Stones that have flat beds like many sandstones and limestones can be laid upon layers of dry concrete and have the vertical interstices filled with dry concrete by tamping. It requires a sloppy concrete to thoroughly embed stones which break out irregularly. In the following examples of rubble concrete work, the reader will find structures varying widely enough in character and in the percentages of rubble used to cover most ordinary conditions of such work. Where the rubble stones are very large, it is now customary to use the term cyclopean masonry instead of rubble concrete. Many engineers who have not studied the economics of the subject believe that the use of massive blocks of stone bedded in concrete necessarily gives the cheapest form of masonry. We have already indicated conditions where ordinary concrete is cheaper than rubble concrete. We may add that if the quarry yields a rock that breaks up naturally into small-sized blocks, it is the height of economic folly to specify large-sized cyclopean blocks. Nevertheless, this blunder has been frequently made in the recent past. Fig. 35. Diagram cross-section of rubble concrete dam, Chattahoochee River. Chattahoochee River Dam. The rollway portion 680 ft, long of the dam for the Atlanta Water and Electric Power Co., shown in section by Fig. 35 was built of a hearting of rubble concrete with a fine concrete facing and a rubble rear wall. The facing, 12 ins, thick of 1 to 2 to 4 concrete, gave a smooth surface for the top and face of the dam, while the rubble rear wall enabled back forms to be dispensed with, and it was considered, made a more impervious masonry. The concrete matrix for the core was a 1 to 2 to 5 stone mixture made very wet. The rubble stones, some as large as 4 cu, ids, were bedded in the concrete by dropping them a few yards from a derrick and working them with bars. A well-formed stone was readily settled 6 ins into a 10-in bed of concrete. The volume of rubble was from 33 to 45% of the total volume of the masonry. The 1 to 2 to 4 concrete facing was brought up together with the rubble core, using face forms and templates to get the proper profile. The work was done by contract, and the average was 5,500 cu ids of concrete placed per month. Fig. 36. Cross-section of Barossa Dam of rubble concrete, Barossa Dam, South Australia. The Barossa Dam for the waterworks for Gawler, South Australia, is an arch with a radius of 200 ft and an arc length on top of 422 ft. Its height above the bed of the stream is 95 ft. Figure 36 is a cross-section of the dam at the center. The dam contains 17,975 cu ids of rubble concrete in the proportions of 2,215 cu ids of rubble stone to 15,760 cu ids of concrete, thus about 12.3% of the dam was of rubble. The concrete was mixed by weight of 1 part cement, 1.5 parts sand, and a varying proportion of aggregate composed of 4.5 parts 1/4 to 2 in. Stone, 2 parts 1/2 to 1/4 in. Stone and 1 part to 1/2 in. Stone or screenings. The sand was 1/2 river sand and 1/2 crusher sand. The following shows the amounts by weight of the several materials for each of the several classes of concrete per cubic yard. Stone, class, excess mortar, 1/2, a 1/4. A sand, cement, a 7, 5%, 1,500, 661, 1/2, 333, 1/4, 804, 434, B12, 5, 1,433, 1/3, 637, 318, 858, 1/2, 463, C12, 5, 1,434, 637, 318, 1/2, 859, 474, D15, 1,402, 623, 312, 884, 484, Fig. 37. Apparatus used for weighing concrete materials at Barossa Dam. The average composition of the concrete was 1 to 1/3.5. Its cost per cubic yard in place, including rubble, was 38.9 D per cu. YD, or about $9.30. In proportioning the mixture on the work use was made of the device shown by Fig. 37 to weigh the aggregate. The measuring car is pushed back under the stone hopper chute until the wheels drop into shallow notches in the balance track rails. Stone is then admitted until the lead weight begins to rise, when the car is pushed forward and dumps automatically as indicated. Other rubble concrete dams. Rubble concrete containing from 55 to 60%. Rubble was used in constructing the Boonton Dam at Boonton, N.J. The stones used measured from 1 to 2.5 cu ids each. The concrete was made so wet that when the stones were dropped into it, it flowed into every crevice. The materials were all delivered on cars, from which they were delivered to the dam by derricks provided with bull wheels. On the dam there were 4 laborers and 1 mason to each derrick, and this gang dumped the concrete and joggled the rubble stones into it. Records of 125 ids per 10 hours with 1 derrick were made. With 35 derricks, 20 of which were laying masonry and 15 either passing materials or being moved, as much as 21,000 ids of masonry were laid in 1 month. The amount of cement per cubic yard of masonry is variously stated to have been 0.6 to 0.75 bbl. The stone was granite. The Spear Falls Dam on the upper Hudson River was built of rubble concrete containing about 33% rubble stone. The concrete was a 1:2:5 mixture, and the engineer states that about 1 bbl of cement was used per cubic yard of rubble concrete. This high percentage of cement may be accounted for by the fact that there was a considerable amount of rubble masonry in cement mortar included in the total. The stones and concrete were delivered along the dam by cableways, and stiff-legged derricks set on the downstream sloping face of the dam delivered them from the cableways into place. There were 2 laborers to each mason employed in placing the materials, wages being 15 and 35 CTS per hour, respectively. The labor cost of placing the materials was 60 CTS per cubic yard of masonry. The stone was granite. Granite rubble laid in layers on beds of concrete and filled between with concrete was used in constructing the Hemet Dam in California. The concrete was a 1:3:6 mixture and was thoroughly tamped under and between the stones. For face work, the stones were roughly scabbled to shape and laid in mortar. The stone was taken from the quarry 400 ft away and delivered directly on the dam by cableways. Here 2 derricks handled the stone into place, the dam being only 246 ft. Arc length on top, though it was 122.5 ft high. The cableways would take a 10-ton load. Stones could be taken from the quarry, hoisted 150 ft, and delivered to the work in 40 to 60 seconds. Common labor at $1.75 per day was used for all masonry except facing, where masons at $3.50 were employed. Cement cost delivered $5 per barrel, of which from $1 to $1.50 per barrel was the cost of hauling 23 miles by team over roads having 18% grades in places. Sand was taken from the stream bed and delivered to the work by bucket conveyor. Under favorable conditions, some of the masonry was put in for as low as $4 per yd. There were 31,100 ids of masonry in the dam, which required 20,000 bbls of cement, or 0.64 bbl per cubic yard. The following novel method of making rubble concrete was employed in enlarging 2 old dams and in constructing 2 new dams for a small waterworks. The available time was short. The amount of work was too small and too scattered to justify the installation of a stone crusher, and suitable gravel was not at hand. Sufficient small boulders in old walls and borrow pits and on surface of fields were available, and were used with thin Portland cement mortar. 1 pot of alpha or Lehigh cement and 3 parts sand were mixed dry at first, and then wet with just enough water to make the resulting mortar flow by gravity. This mortar was shoveled into the forms continuously by 1 set of men, while other men were throwing into the mortar in the forms the boulders which were cleaned and broken so as not to be more than 7 inches long. In general, the performance was continuous. 3 mortar beds were placed parallel with and against one side of the forms, with spaces of about 4 ft between the ends of the beds. The boulders were dumped on the opposite side of the forms. 2 men shoveled in all the mortar and did nothing else. While they were emptying one bed, the mortar was being mixed in the preceding bed by 2 other men, and the materials placed in the 3rd bed by still others. Another gang was continually throwing in the boulders and small stones, and still another was breaking stone. 1 man should keep the mortar well stirred while the bed is being emptied. About 20 men were necessary to do all parts of the work. The forms were of 2 in, planed, plank-tongued, and grooved. Especial pains were taken to make the forms tight, and all leaks that appeared were quickly stopped with dry cement. Some pains were taken to prevent a flat side of large stones from coming in direct contact with the forms, but round boulders and small stones needed no care to prevent their showing in the finished work. Fig. 38. Bridge abutment of rubble concrete. In conclusion, it is interesting to note, perhaps, the earliest use of rubble concrete for dam construction in this country, in constructing the Boyd's Corner Dam on the Croton River near New York. This dam was begun in 1867, and for a time rubble concrete was used, but was finally discontinued due to the impression that it might not be watertight. The specifications called for dry concrete to be thoroughly rammed in between the rubble stones, and to give room for this ramming, the contractor was not permitted to lay any 2 stones closer together than 12 ins. As a result, not more than 33% of the concrete was rubble, abutment for railway bridge. Figure 38 shows a bridge abutment built of rubble concrete at a cost of about $4.50 per cu yd. The concrete was a 1:2 or 4½ mixture laid in 4 in layers. On each layer were laid large rubble stones bedded flat and spaced to give 6 in vertical joints. The vertical joints were filled with concrete by ramming, and then another layer of concrete placed, and so on. A force of 28 men and a foreman averaged 40 cu ids of rubble concrete per day. The following is the itemized cost per cubic yard, not including forms, for 278 cu ids item per cu yd 0.82 bbls. Cement at $2, $62, 14 22 cu yd. Sand at $1, 000, 22 52 cu yd. Broken stone at $0, 94 49 38 cu yd. Rubble stone at $0, 63 24 water 007 labor at 15 cts per hour 1, 19 foreman 009, total $4.44. Some English data on rubble concrete. Railway work under Mr. John Strain in Scotland and Spain involved the building of abutments, piers, and arches of rubble concrete. The concrete was made of 1 part cement to 5 parts of ballast, the ballast consisting of broken stone or slag and sand mixed in proportions determined by experiment. The materials were mixed by turning with shovels 4 times dry, then 4 times more during the addition of water through a rose nozzle. A bed of concrete 6 ins thick was first laid, and on this a layer of rubble stones, no 2 stones being nearer together than 3 ins, nor nearer the forms than 3 ins. The stones were rammed and probed around with a trowel to leave no spaces. Over each layer of rubble, concrete was spread to a depth of 6 ins. The forms or molds for piers for a viaduct were simply large open boxes, the 4 sides of which could be taken apart. The depth of the boxes was uniform, and they were numbered from the top down so that, knowing the height of a given pier, the proper box for the base could be selected. As each box was filled, the next one smaller in size was swung into place with a derrick. The following bridge piers for the Tharsis and Kalanas Railway were built. Name: length of bridge, ft height of piers, ft no of spans, ku, ids, in piers, weeks to build. Tamujoso River, 435-28, 12. 1737-14. A half Orak, 423-31. 11 1590-15, Cascablero, 480-30 to 80-10, 2680-21 no. 16 294-28 to 57 1000 and 46-16. A half Taisa, 165-16 to 23-8 424. It is stated that the construction of some of these piers in ordinary masonry would have taken 4 times as long. The rock available for rubble did not yield large blocks. Consequently, the percentage of pure concrete in the piers was large, averaging 70%. In one case, where the stones were smaller than usual, the percentage of concrete was 76.5%. In other work, the percentage has been as low as 55%. And in still other work where a rubble face work was used, the percentage of concrete has been 40%. In these piers, the average quantities of materials per cubic yard of rubble concrete were 448 pounds. 0. 178 cu yd. Cement, 0. 36 cu yd. Sand, 0. 68 cu yd. Broken stone measured loose in piles, 0. 30 cu yd. Rubble measured solid. Several railway bridge piers and abutments in Scotland are cited. In one of these, large rubble stones of irregular size and weighing 2 tons each were set inside the forms 3 ins, away from the plank and 3 ins, from one another. The gang to each derrick was 1 derrick man and 1 boy, 1 mason and 10 laborers, and about 1/4 of the time of 1 carpenter and his helper raising the forms. For bridges of 400 cu ids, the progress was 12 to 15 cu ids a day. The forms were left in place 10 days. To chip off a few inches from the face of a concrete abutment that was too far out required the work of 1 quarryman 5 days per cu yd. Of solid concrete chipped off. Concrete was used for a skew arch over the River Dotshot on the Killin Railway, Scotland. There were 5 arches, each of 30 ft. Span on the square, or 42 ft. On the skew being 45 degrees. The piers were of rubble concrete. The concrete in the arch was wheeled 300 ft. On a trestle and dumped onto the centers. It was rammed in 6 in. Layers which were laid corresponding to the courses of arch stones. As the layers approached the crown of the arch, some difficulty was experienced in keeping the surfaces perpendicular. Each arch was completed in a day. In a paper by John W. Stephen in Proc. Inst. C.E. the following is given: concrete per cu yd. Rubble concrete per cu yd. Percent of rubble in rubble concrete. Ardros and Harbour $6, $005, $0020. 0 Irvine Branch 7, 003. 6863. 6 Kalanas and Tharsis Rye 7, 083. 4330. 3 Mr. Martin Murphy describes some bridge foundations in Nova Scotia. Rubble concrete was used in some of the piers. The rubble concrete consisted of 1 part cement, 2 parts sand, 1 part clean gravel, and 5 parts of large stones weighing 20 pounds, each and upwards. The sand, cement, and gravel were turned 3 times dry and 3 times wet and put into the forms. The rubble stones were bedded in the concrete by hand, being set on end 2 or 3 ins apart. No rubble stones were placed within 6 ins of the forms, thus leaving a face of plain concrete, and the rubble stones were not carried higher than 18 ins. below the top of the pier. 1 cubic yard of this rubble concrete required 0.8 to 0.9 bbl of cement, asphalt concrete. Asphalt or tar concrete in which steam cinders or broken stone or gravel and sand are mixed with asphaltum or tar instead of cement paste are used to some extent in lining reservoirs, constructing mill floors, etc. Such mixtures differ in degree only from the mixtures used for asphalt street paving, for discussion of which the various books on paving and asphalts should be consulted. The 2 examples of asphalt concrete work given here are fairly representative of the mixtures and methods employed for concrete work, as distinguished from asphalt work. Slope paving for earth dam. Mr. Robert B. Stanton describes a small log dam faced upstream with earth, upon which was laid an asphalt concrete lining to make it watertight. The stone was broken to 2 pieces, all the fines being left in and sufficient fine material added to fill the voids. The stone was heated and mixed in pans or kettles from a street paving outfit, and the asphaltum paste, composed of 4 parts California refined asphaltum and 1 part crude petroleum, was boiled in another kettle. The boiling hot paste was poured with ladles over the hot stone, and the whole mixed over the fire with shovels and hose. The asphalt concrete was taken away in hot iron wheelbarrows placed in a 4 layer rammed and ironed with hot irons. The concrete was laid in strips 4 to 6 ft wide, the edges being coated with hot paste. After the whole reservoir was lined, it was painted with the asphalt paste, boiled much longer, until when cold it was hard and stone was broken to 2 pieces, all the fines being left in and sufficient fine material added to fill the voids. The stone was heated and mixed in pans or kettles from a street paving outfit, and the asphaltum paste, composed of 4 parts California refined asphaltum and 1 part crude petroleum, was boiled in another kettle. The boiling hot paste was poured with ladles over the hot stone, and the whole mixed over the fire with shovels and hose. The asphalt concrete was taken away in hot iron wheelbarrows placed in a 4 layer rammed and ironed with hot irons. The concrete was laid in strips 4 to 6 ft wide, the edges being coated with hot paste. After the whole reservoir was lined, it was painted with the asphalt paste, boiled much longer, until when cold it was hard and brittle, breaking like glass under the hammer. This paste was put on very hot and ironed down. It should not be more than thick, or it will creep on slopes of 1/2 to 1. After 2 hot summers and 1 cold winter, there was not a single crack anywhere in the lining. A mixture of sand and asphalt will creep on slopes of 1/2 to 1, but asphalt concrete will not. With asphalt at $20 a ton and labor at $2 a day, the cost was 15 CTS. A SQ/FT for 4 asphalt concrete. On a high slope, Mr. Stanton recommends making slight berms every 6 ft to support the concrete and prevent creeping. Asphalt concrete resists the wear of wind and water that cuts away granite and iron. Base for mill floor. In constructing 17,784 SQ/FT of tar concrete base for a mill floor, Mr. C.H. Chadsey used a sand, broken stone, and tar mixture mixed in a mechanical mixer. The apparatus used and the mode of procedure followed were as follows: 2 parallel 8-in brick walls 26 ft long were built 4 ft apart and 2.5 ft high to form a furnace. On these walls at one end was set a 4 x 6 x 2 ft steel plate tar heating tank, next to this tank for a space of 4 x 8 ft. The walls were spanned between with steel plates. This area was used for heating sand. Another space of 4 times 8 ft was covered with 1/2 in. Steel rods arranged to form a grid. This space was used for heating the broken stones. The grid proved especially efficient, as it permitted the hot air to pass up through the stones, while a small cleaning door at the ground allowed the screenings which dropped through the grid to be raked out and added to the mixture. A fire from barrel staves and refuse wood built under the tank end was sufficient to heat the tar, sand, and stone. For mixing the materials, a ransom mixer was selected for the reason that heat could be supplied to the exterior of the drum by building a wood fire underneath. This fire was maintained to prevent the mixture from adhering to the mixing blades, and it proved quite effective, though occasionally they would have to be cleaned with a chisel bar, particularly when the aggregate was not sufficiently heated before being admitted to the mixer. A little dead oil applied to the discharge chute and to the shovels, wheelbarrows, and other tools effectually prevented the concrete from adhering to them. The method of depositing the concrete was practically the same as that used in laying cement sidewalks. Wood strips attached to stakes driven into the ground provided templates for gauging the thickness of the base and for leveling off the surface. The wood covering consisted of a layer of 2 in planks covered by matched hardwood flooring. In placing the planking, the base was covered with a 1/4 in layer of hot pitch into which the planks were pressed immediately, the last plank laid being toe-nailed to the preceding plank just enough to keep the joint tight. After a few minutes, the planks adhered so firmly to the base that they could be removed only with difficulty. The hardwood surface was put on in the usual manner. The prices of materials and wages for the work were as follows: pitch bulk per lb, $0.0075 gravel per cu, yd, 150 spruce subfloor per m, ft.b, M1500 hardwood surface per m, ft.b, M3300 laborers per 10-hour day, 150 foremen per 10-hour day, 400 carpenters per 10-hour day, 200 at these prices, and not including a small administration cost or the cost of tools and plant, the cost of the floor consisting of 4.5 ins, of concrete 2 ins, of spruce subflooring and in. Hardwood finish was as follows per square foot: pitch $0, 04 gravel 0, 02 spruce for subfloor 0, 03 hardwood for surfacing 0, 035 labor mixing 0, 03 labor laying 0, 015 carpenter work 0, 025 total per square foot $0, 195. Chapter 32. Reinforced concrete work may be done in freezing weather if the end to be gained warrants the extra cost. Laboratory experiments show beyond much doubt that Portland cement concrete, which does not undergo freezing temperatures until final set has taken place, or which, if frozen before it has set, is allowed to complete the setting process after thawing without a second interruption by freezing, does not suffer loss of ultimate strength or durability. These requirements for safety may be satisfied by so treating the materials or compounding the mixture that freezing will not occur at normal freezing temperature, or else will be delayed until the concrete has set. By so housing in the work and artificially treating the enclosed space that its temperature never falls as low as the freezing point, or by letting the concrete freeze if it will, and then by suitable protection, and by artificial heating produce and maintain a thawing temperature until set has taken place, lowering the freezing point of the mixing water. Lowering the freezing point of the mixing water is the simplest and cheapest method by which concrete can be mixed and deposited in freezing weather. The method consists simply in adding some substance to the water, which will produce a brine or emulsion that freezes at some temperature below 32 degrees F, determined by the substance added and the richness of the admixture. A great variety of substances may be added to water to produce low-freezing brines, but in concrete work, only those may be used that do little or no injury to the strength and durability of the concrete. Practice has definitely determined only one of these, namely, sodium chloride or common salt, though some others have been used successfully in isolated cases. A point to be borne in mind is that cold retards the setting of cement, and that the use of anti-freezing mixtures emphasizes this phenomenon and its attendant disadvantages in practical construction. The accompanying diagram, Fig. 39, based on the experiments of Tetmajer, show the effect on the freezing point of water by the admixtures of various substances that have been suggested for reducing the freezing point of mortar and concrete mixtures. Fig. 39. Diagram showing effect on freezing point of water by admixture of various substances. Common salt, sodium chloride. The substance most usually employed to lower the freezing point of water used in concrete is common salt. Laboratory experiments show that the addition of salt retards the setting and probably lowers the strength of cement at short periods, but does not, when not used to excess, injure the ultimate strength. The amount beyond which the addition of salt begins to affect injuriously the strength of cement is stated variously by various authorities. Sutcliffe states that it is not safe to go beyond 7 or 8%. By weight of the water, Sabin places the safe figures at 10%, and the same figure is given by a number of other American experimenters. A number of rules have been formulated for varying the percentage of salt with the temperature of the atmosphere. Prof. Tetmajer's rule as stated by Prof. J. B. Johnson is to add 1% of salt by weight of the water for each degree Fahrenheit below 32 degrees. A rule quoted by many writers is 1 lb of salt to 18 gallons of water for a temperature of 32 degrees F, and an increase of 1 Oz for each degree lower temperature. This rule gives entirely inadequate amounts to be effective, the percentage by weight of the water being about 1%. The familiar rules of enough salt to make a brine that will float an egg or float a potato are likewise untrustworthy. They call respectively, according to actual tests made by Mr. Sanford E. Thompson, for 15% and 11%. Of salt which is too much, according to the authorities quoted above, to be used safely. In practice, an arbitrary quantity of salt per barrel of cement or per 100 pounds of water is usually chosen. Preferably, the amount should be stated in terms of its percentage by weight of the water, since if stated in terms of pounds per barrel of cement, the richness of the brine will vary with the richness of the concrete mixture, its composition, etc. As examples of the percentages used in practice, the following works may be quoted. New York Rapid Transit Railway, 9%. By weight of the water, Foster Armstrong Piano Works, 6%. By weight of the water. In summary, it would seem that if a rule for the use of salt is to be adopted, that of Tetmajer, which is to add 1%, by weight of the water for each degree Fahrenheit below 32 degrees is as logical and accurate as any. It should, however, be accompanied by the proviso that no more than 10% by weight of salt should be considered safe practice, and that if the frost is too keen for this to avail, some other method should be adopted or the work stopped. It may be taken that each unit % of salt added to water reduces the freezing temperature of the brine about 1.08 degrees F. A 10% salt brine will therefore freeze at 32 degrees 11 degrees equals 21 degrees F. The range of efficiency of salt as a preventative of frost in mixing and laying concrete is obviously quite limited. Heating concrete materials. Heating the sand, stone, and mixing water acts both to hasten the setting and to lengthen the time before the mixture becomes cold enough to freeze. At temperatures not greatly below freezing, the combined effects are sufficient to ensure the setting of the concrete before it can freeze. More specific data of efficiency are difficult to arrive at. There are no test data that show how long it takes a concrete mixture at a certain temperature to lose its heat and become cold enough to freeze at any specific temperature of the surrounding air, and a theoretical calculation of this period is so beset with difficulties as to be impracticable. Strength tests of concrete made with heated materials have shown clearly enough that the heating has no effect worth mentioning on either strength or durability. Either the water, the sand, the aggregate, or all three may be heated. Usually the cement is not heated, but it may be if desired. Potable heaters. An ordinary half-cylinder of sheet steel set on the ground like an arch is the simplest form of sand heater. A wood fire is built under the arch, and the sand to be heated is heaped on the top and sides. The efficiency of this device may be improved by closing one end of the arch and adding a short chimney stack, but even the very crude arrangement of sheets of corrugated iron bent to an arc will do good service where the quantities handled are small. This form of heater may be used for stone or gravel in the same manner as for sand. It is inexpensive, simple to operate, and requires only waste wood for fuel. But unless it is fired with exceeding care, the sand in contact with the metal will be burned. The drawings of Fig. 40 show the construction of a portable heater for sand, stone, and water used in constructing concrete culverts on the New York Central and Hudson River Railroad. This device weighs 1,200 pounds and costs about $50. Fig. 40. Portable sand, stone, and water heater, heating in stationary bins. The following arrangement for heating sand and gravel in large quantities in bins was employed in constructing the Foster Armstrong Piano Works at Rochester, NY. The daily consumption of sand and gravel on this work was about 50 cu/ids and 100 cu/ids, respectively. To provide storage for the sand and gravel, a bin 16 ft. square in projected plan was constructed with vertical sides and a sloping bottom as illustrated in Fig. 41. This bin was divided by a vertical partition into a large compartment for gravel and a small compartment for sand, and was provided with 2 grates of boiler tubes arranged as shown. These grates caused V-shaped cavities to be formed beneath in the gravel and sand. Into these cavities penetrated through one end of the bin 6 in pipes from a hot air furnace and 1 in pipes from a steam boiler. The hot air pipes merely pass through the wall, but the steam pipes continue nearly to the opposite side of the bin and are provided with open crosses at intervals along their length. In addition to the conduits described, there is a small pipe for steam located below and near the bottom of the bin. The hot air pipes connected with a small furnace, and air was forced through them by a Sturtevant No. 6 blower. The steam pipes connected with the boiler of a steam heating system installed to keep the buildings warm during construction. Fig. 41. Bin arrangement for heating sand and stone. Other examples of heating materials. In the construction of the power plant of the Billings, Mont. Water Power Co., practically all of the concrete work above the main floor level was put in during weather so cold that it was necessary to heat both the gravel and water used. A sand heater was constructed of 4 15 ft, lengths of 15 in, cast iron pipe, 2 in series, and the 2 sets placed side by side. This gave a total length of 30 ft for heating, making it possible to use the gravel from alternate ends and rendering the heating process continuous. The gravel was dumped directly on the heater, thus avoiding the additional expense of handling it a second time. The heater pipes were laid somewhat slanting, the fire being built in the lower end. A 10 ft flue furnished sufficient draft for all occasions. With this arrangement, it was possible to heat the gravel to a temperature of 80 degrees or 90 degrees F, even during the coldest weather. Steam for heating the water was available from the plant. The temperature at which the concrete was placed in the forms was kept between 65 degrees and 75 degrees F. This was regulated by the man on the mixer platform by varying the temperature of the water to suit the conditions of the gravel. When the ingredients were heated in this manner, it was found advisable to mix the concrete sloppy, using even more water than would be commonly used in the so-called sloppy concrete. No difficulty was experienced with temperature cracks if the concrete, when placed, was not above 75 degrees F. All cracks of this nature which did appear were of no consequence, as they never extended more than a half in, below the surface. The concrete was placed in as large masses as possible. It was covered nights with sacks and canvas, and when the walls were less than 3 ft. In width, the outside of the forms was lagged with tar paper. An air space was always left between the surface of the concrete and the covering. Under these conditions, there was sufficient heat in the mass to prevent its freezing for several days, which was ample time for permanent setting. During the construction in 1902 of the Wachusett Dam at Clinton, Mass., for the Metropolitan Water Works Commission, the following procedures were followed in laying concrete in freezing weather. After November 15, all masonry was laid in Portland cement, and after November 28, the sand and water were heated and salt added in the proportion of 4 pounds per barrel of cement. The sand was heated in a bin, 16 x 15 x 10 ft, deep, provided with about 20 coils of 2 in. Pipe passing around the inside of the bin. The sand, which was dumped in the top of the bin and drawn from the bottom, remained there long enough to become warm. The salt for each batch of mortar was dissolved in the water, which was heated by steam. Steam was also used to thaw ice from the stone masonry. The laying of masonry was not started on mornings when the temperature was lower than 18 degrees F, above zero, and not even with this temperature unless the day was clear and higher temperature expected. At the close of each day, the masonry built was covered with canvas. In the construction of dams for Huron Company's power development in Canada, a large part of the concrete work in dams, and also in powerhouse foundations, was done in winter, with the temperature varying from a few degrees of frost to 15 degrees below zero, and on several occasions much lower. No difficulty was found in securing good concrete work, the only precaution taken being to heat the mixing water by turning a 3/4 in steam pipe into the water barrel supplying the mixer, and during the process of mixing, to use a jet of live steam in the mixer, keeping the cylinder closed by wooden coverings during the process of mixing. No attempt was made to heat sand or stone. In all the winter work, care was taken to use only cement which would attain its initial set in not more than 65 minutes. In constructing a concrete arch bridge at Plano, the sand and gravel were heated previous to mixing, and the mixed concrete after placing was kept from freezing by playing a steam jet from a hose connected with the boiler of the mixer on the surface of the concrete, until it was certain that initial set had taken place. Readings taken with thermometers showed that in no instance did the temperature of the concrete fall below 32 degrees F. Within a period of 10 or 12 hours after placing. From experience gained in doing miscellaneous railway work in cold, whether Mr. L. J. Hotchkiss gives the following. For thin, reinforced walls, it is not safe to rely on heating the water alone or even the water and sand, but the stone also must be heated, and the concrete when it goes into the forms should be steaming hot. For mass walls, the stone need not be heated except in very cold weather. Where concrete is mixed in small quantities, the water can be heated by a wood fire, and if a wood fire be kept burning overnight on top of the piles of stone and sand, a considerable quantity can be heated. The fire can be kept going during the day and moved back on the pile as the heated material is used. This plan requires a quantity of fuel which in most cases is prohibitive and is not sufficient to supply a power mixer. For general use, steam is far better. A convenient method is to build a long wooden box 8 or 10 in, square with numerous holes bored in its sides. This is laid on the ground, connected with a steam pipe and covered with sand, stone, or gravel. The steam escaping through the holes in the box will heat overnight a pile of sand, or sand and gravel 8 or 10 ft. high. Perforated pipes can be substituted for boxes. Material can be heated more rapidly if the steam be allowed to escape in the pile than if it is confined in pipes which are not perforated. Crushed stone requires much more heat than sand or sand and gravel mixed because of the greater volume of air spaces. In many cases, material which has already been unloaded must be heated. The expense of putting steam boxes or pipes under it is considerable. To avoid this, one or more steam jets may be used, the end of the jet pipe being pushed several feet into the pile of material. If the jets are connected up with steam hose, they are easily moved from place to place. It is difficult to heat stone in this way, except in moderate weather. On mass work and at such temperatures as are met within this latitude, Chicago, it is not usually necessary to protect concrete which has been placed hot except in the top of the form. This can be done by covering the top of the form with canvas and running a jet of steam under it. If canvas is not available, boards and straw or manure answer the purpose. If heat is kept on for 36 hours after completion, this is sufficient, except in unusually cold weather. The above treatment is all that is required for reinforced retaining walls of ordinary height. But where box culverts or arches carrying heavy loads must be placed in service as soon as possible, the only safe way is to keep the main part of the structure warm until the concrete is thoroughly hardened. Forms for these structures can be closed at the ends and stoves or salamanders kept going inside, or steam heat may be used. The outside may be covered with canvas or boards, and straw and steam jets run underneath. After the concrete has set enough to permit the removal of the outer forms of box culverts, fires may be built near the side walls and the concrete seasoned rapidly. Where structures need not be loaded until after the arrival of warm weather, heat may be applied for 36 hours, and the centering left in place until the concrete has hardened. Careful inspection of winter concrete should be made before loads are applied. In this connection, it may be noted that concrete which has been partly seasoned and then frozen closely resembles thoroughly seasoned concrete. Pieces broken off with a smooth fracture through all the stones and showing no frost marks when thawed out can be broken with the hands. In building Portland cement concrete foundations for the West End, St. Rye, Boston, and the Brooklyn Heights much of the work was done in winter. A large watertight tank was constructed, of such size that 3 skips or boxes of stone could be lowered into it. The tank was filled with water, and a jet of steam kept the water hot in the coldest weather. The broken stone was heated through to the temperature of the water in a few minutes. One of the stone boxes was then hoisted out and dumped on one side of the mixing machine and then run through the machine with sand, cement, and water. The concrete was wheeled to place without delay and rammed in 12-in layers. The heat was retained until the cement was set. In severely cold weather, the sand was heated and the mixing water also. A covering of hay or gunny sacks may be used, covering and housing the work. Methods of covering concrete to protect it from light frosts, such as may occur overnight, will suggest themselves to all. Sacking, shavings, straw, etc., may all be used. Covering wall forms with tar paper nailed to the studding so as to form with the lagging a cellular covering is an excellent device and will serve in very cold weather if the sand and stone have been heated. From these simple precautions, the methods used may range to the elaborate systems of housing described in the following paragraphs. Method of housing in dam, Chaudière Falls, Quebec. In constructing a dam for the water power plant at Chaudière Falls, PQ, the work was housed in. The wing dam and its end piers aggregated about 250 ft in length by about 20 ft in width. A house 100 ft, long and 24 ft. Wide was constructed in sections about 10 ft. Square connected by cleats with bolts and nuts. This house was put up over the wing dam. It was 20 ft. High to the eaves with a pitched roof, and the ends were closed up. In the roof on the forebay side were hatchways with sliding doors along the whole length. Small entrance doors for the workmen were provided in the ends of the building. The house was heated by a number of cylindrical sheet iron stoves about 18 ins, in diameter by 24 ins. High, burning coke. Thermometers placed at different points in the shed gave warning to stop work when the temperature fell below freezing, which, however, rarely occurred. Mixing boards were located in the shed, and concrete, sand, and broken stone were supplied in skipfuls by guy derricks located in the forebay, which passed the material through the hatchways in the roof, the proper hatchway being opened for the purpose and quickly closed. The mortar was first mixed on a board, and then a skip-load of stone was dumped into the middle of the batch and the whole well mixed. The water was made lukewarm by introducing a steam jet into several casks which were kept full. The sand was heated outside in the forebay on an ordinary sand heater. The broken stone was heated in piles by a steam jet. A pipe line on the ground was made up of short lengths of straight pipe alternating with T-sections, turned up. The stone was piled 3 to 4 ft deep over the pipe, and a little steam turned into the pipe. Several such piles kept going all the time supplied enough stone for the work. The stone was never overheated, and was moist enough not to dry out the mortar when mixed with it. In this manner the concreting was successfully carried on, and the wing dam built high enough to keep high water out of the forebay. Some danger from freezing was also encountered the next season, when the last part of the wing dam was being constructed. This work was done when the temperature was close to freezing, and it became necessary to keep the freshly placed concrete warm overnight. This was done by covering the work loosely with canvas, under which the nozzle of a steam hose was introduced. By keeping a little steam going all night, the concrete was easily kept above freezing temperature. Fig. 42. Canvas curtain for enclosing open walls. Fig. 43. Sketch showing method of applying curtains to open walls. Method of housing in building work. The following method of housing in building work is used by Mr. E. L. Ransom. The feature of the system is that the enclosing structure is made up of a combination of portable units, which can be used over and over again in different jobs. The construction is best explained in connection with sketches. Figure 43 shows a first floor wall column with the wall girder surmounting it and the connecting floor system. It will be seen that the open sides are enclosed by canvas curtains and the floor slab is covered with wood shutters. The curtains are composed of separate pieces so devised that they may be attached to each other by means of snaps and eyes. One of these curtain units is shown by Fig. 42, referring now to Fig. 43. The curtain A is held by the tying rings to a continuous string piece B, the upper portion or flap D being held down by a metal bar or other heavy object, so as to lap over the floor covers E. The lower edge of the curtain is attached to the string piece C. The sketch has been made to show how the curtain adjusts itself to irregular projections, such as the supports for a wall girder form. To prevent the curtain tearing on such projections, it is well to cover or wrap the rough edges with burlap, bagging, or other convenient material. The details of the wooden floor covers are shown by Fig. 44. They are constructed so as to give a hollow space between them and the floor, and holes are left in the floor slab as at H. Fig. 43 to permit the warm air from below to enter this hollow space. This warm air is provided by heating the enclosed story of the building by any convenient adequate means. In constructing factory buildings, 50 times 200 FT, in plan at Rochester, N.Y., Mr. Ransom used a line of 3/4 twin steam pipe located at floor level and running around all 4 sides, and a similar line running lengthwise of the building at the center, these pipes discharging live steam through openings into the enclosed space. In addition to the steam piping, 10 braziers in which coke fires were kept were scattered around the floor. This equipment kept the enclosed story 50 times 100 FT times 13 FT high at a temperature of 80 degrees F and a temperature of about 40 degrees F between the floor top and its board covering. The work was not stopped at any time because of cold, and the temperatures outside ranged from 0 to 10 degrees above. Fig. 44. Portable wooden panels for covering floors. Chapter 33. Good design in concrete as well as in steel, masonry, and wood requires that the structure shall be good to look at. This means that the proportions must be good and that the surface finish must be pleasing. Good proportions are a matter of design, but a pleasing surface finish is a matter of construction. Many, perhaps the majority of concrete structures do not have a pleasing surface finish. The surface is irregular, uneven in texture, and stained or discolored or of lifeless hue. The reasons for these faults and the possible means of remedying them are matters that concern the construction engineer and the contractor. Imperfections in the surface of concrete are due to one or more of the following causes. 1. Imperfectly made forms. 2. Imperfectly mixed concrete. 3. Carelessly placed concrete. 4. Use of forms with dirt or cement adhering to the boards. 5. Efflorescence and discoloration of the surface after the forms are removed. Imperfectly made forms. In well-mixed and placed concrete, the film of cement paste which flushes to the surface will take the impress of every flaw in the surface of the forms. It will even show the grain marks in well-dressed lumber. From this, it will be seen how very difficult it is so to mold concrete that the surface will not bear evidence of the mold used. The task is impracticable of perfect accomplishment, and the degree of perfection to which it can be carried depends upon the workmanship expended in form construction. Forms with a smooth and even surface are difficult and expensive to secure. It is impracticable in the first place to secure lagging boards dressed to exact thickness, and in the second place it is impracticable to secure perfect carpenter work. Joints cannot be got perfectly close, and a nail omitted here, or there leaves a board free to warp. From this point, on the use of imperfectly sized lumber and careless carpentry can go to almost any degree of roughness in the form work. Only approximately smooth and unmarked concrete surfaces can be secured in plain wooden forms, and this only with the very best kind of form construction. So much for the limitations of form work in the matter of securing surface finish. These limitations may be reduced in various ways. Joint marks may be eliminated wholly or partly by pointing the joints with clay or mortar, or by pasting strips of paper or cloth over them, or the whole surface of the lagging can be papered. By the use of oiled paper, there will be little trouble from the paper sticking. Grain marks and surface imperfections can be reduced by oiling the lumber so as to fill the pores, or by first oiling, and then filling the coat of oil with fine sand blown or cast against the boards. The preceding remarks are of course based on the assumption that as nearly as possible a smooth and even surface finish is desired. If something less than this is sufficient, and in many cases it is, form-produced surface defects become negligible in the proportion that they do not exceed the standards of roughness and irregularity considered permissible by the engineer, and these standards are individual with the engineer. What one considers excessive roughness and irregularity, another may consider as amply even and smooth. The point to be kept in mind is that beyond a certain state of evenness and regularity, form-produced surfaces are impracticable to obtain, because to construct forms of the necessary perfection to obtain them costs far more than it does to employ special supplementary finishing processes. Surface blemishes due to dirt or cement adhering to the form boards have no excuse if the engineer or contractor cares to avoid them. It is a simple matter to keep the lagging clean and free from such accumulations. Imperfect mixing and placing. Imperfectly mixed and placed concrete gives irregularly colored, pitted, and honeycombed surfaces with here a patch of smooth mortar and there a patch of exposed stone. Careful mixing and placing will avoid this defect, or all chance of it may be eliminated by using surface coatings of special mixtures. There is no great difficulty, however, in obtaining a reasonably homogeneous surface with concrete. The task merely requires that the mixing shall be reasonably uniform and homogeneous, and that in placing this mixture the spading next to the lagging shall be done in such a way as to pull the coarse stones back and flush the mortar to the surface. Spading forks are excellent for this purpose. A better tool is a special spade made with a perforated blade. This special spade costs $3. Efflorescence. Efflorescence is the term applied to the whitish or yellowish accumulations which often appear on concrete surfaces. Whitewash is another name given to these blotches. Efflorescence is due to certain salts leaching out of the concrete and accumulating into thin layers where the water evaporates on the surface. These salts are most probably sulfates of calcium and magnesium, both of which are contained in many cements and both of which are slightly soluble in water. Efflorescence is very erratic in its appearance. Some concretes never exhibit it. In some it may not appear for several years, and in others it shows soon after construction and may appear in great quantities. The most effective way to prevent efflorescence would naturally be to use cements entirely free from sulfates, chlorides, or whatever other soluble salts are the cause of the phenomenon. But the likelihood of engineers resorting to the trouble of such selection, except in rare instances, is not great, even if they knew what cements to select, so that other means must be sought. The most common place for efflorescence to appear in walls is at the horizontal junction of 2 days' work, or where a coping is placed after the main body of the wall has been completed. The reason of this seems to be that the salt solutions seep down through the concrete until they strike the nearly impervious film of cement that forms on the top surface of the old concrete before the new is added, and then they follow along this impervious film to the face of the wall. The authors have suggested that this cause might be remedied by ending the day's work by a layer whose top has a slight slope down toward the rear of the wall, or perhaps by placing all the concrete in similarly sloping layers. Mr. C. H. Cartledge is authority for the statement that this leaching at joints can be largely done away with by the simple process of washing the top surface of concrete, which has been allowed to set overnight, by scrubbing it with wire brushes in conjunction with thorough flushing with a hose. But efflorescence frequently appears on the faces of walls built without construction joints, and in which a wet concrete is puddled in and not tamped in layers, and here other means are obviously essential. Waterproofing the surface of the wall should be effective so long as the waterproofing lasts. Indeed, one of the claims made for some of these waterproofing compounds is that efflorescence is prevented. The various waterproofing mixtures capable of such use will be found described in Chapter Roman 25. Failing in any or all of these methods of preventing efflorescence, the engineer must resort to remedial measures. The saline coating must be scraped, or chipped, or better, washed away with acids. Efflorescence was removed from a concrete bridge at Washington, D.C., by using hydrochloric, muriatic, acid and common scrubbing brushes, 30 gallons of acid and 36 scrubbing brushes were used to clean 250 ids of concrete. The acid was diluted with 4 or 5 parts water to 1 of acid. Water was constantly played with a hose on the concrete while being cleaned to prevent penetration of the acid. 1 house front cleaner and 5 laborers were employed, and the total cost was $150 or 60 CTS per SQYD. This high cost was due to the difficulty of cleaning the balustrades. It is thought that the cost of cleaning the spandrels and wing walls did not exceed 20 CTS per SQYD. The cleaning was perfectly satisfactory. An experiment was made with wire brushes without acid, but the cost was $2.40 per SQYD. The flour removed by the wire brushes was found by analysis to be silicate of lime. Acetic acid was tried in place of muriatic, but required more scrubbing. spaded and troweled finishes. With wet concrete and ordinarily good form construction, a reasonably good surface appearance can be obtained by spading and troweling. For doing the spading, a common gardener's hoe, straightened out so that the blade is nearly in line with the handle, will do good work. The blade of the tool is pushed down next to the lagging, and the stone pulled back, giving the grout opportunity to flush to the face. Troweling, that is troweling without grout wash, requires, of course, that the concrete be stripped before it has become too hard to be worked. As troweling is seldom required except for tops of copings and corners, it is generally practicable to bare the concrete while it is still fairly green. In this condition, the edges of copings, etc., can be rounded by edging tools such as cement sidewalk workers use. Plaster and stucco finish. The ordinary concrete surface with a film-like cement covering will not hold plaster or stucco. To get proper adhesion, the concrete surface must be scrubbed, treated with acid or tooled before the plaster or stucco is applied. And this makes an expensive finish, since either of the preliminary treatments constitutes a good finish by itself. When a coarse-grained facing is made of very dry mixtures, as described in a succeeding section, it has been made to hold plaster very well on inside work. In general, plaster and stucco finishes can be classed as uncertain even when the concrete surface has been prepared to take them. And when the concrete has not been so prepared, such finishes can be classed as absolutely unreliable. Mortar and cement facing. Where a surface finish of fine texture or of some special color or composition is desired, the concrete is often faced with a coat of mortar or, sometimes, neat cement paste or grout. Mortar facing is laid from 1 to 2 inches, thick, usually 1½ inches. The mortar being a 1-to-1, 1-to-2 or 1-to-3 mixture, and of cement and ordinary sand where no special color or texture is sought. This facing often receives a future special finish as described in succeeding sections, but it is more usually used as left by the forms or at best with only a troweling or brushing with grout. Engineers nearly always require that the mortar facing and the concrete backing shall be constructed simultaneously. This is accomplished by using facing forms, 2 kinds of which are shown by Figs. 45 and 46. In use, the sheet steel plates are placed on edge the proper distance back of the lagging, and the space between them, and the lagging is filled with the facing mortar. The concrete backing is then filled in to the height of the plate, which is then lifted vertically, and the backing and facing thoroughly bonded by tamping them together. The form shown by Fig. 46, though somewhat the more expensive, is the preferable one, since the attached ribs keep the plate its exact distance from the lagging without any watching by the men, while the flare at the top facilitates filling. The facing mortar has to be rather carefully mixed. It must be wet enough to work easily and completely into the narrow space, and yet not be so soft that in tamping the backing the stones are easily forced through it. Also, since the facing cannot proceed faster than the backing, the mortar has to be mixed in small batches so that it is always fresh. A cubic yard of mortar will make 216 SQ, FT, of 1½ in. Facing. Cement facing is seldom made more than 1 in. Thick. If placed as a paste, the process is essentially the same as for placing mortar. When grout is used, a form is not used. Place and tamp the concrete in 6 to 8 in layers, then shove a common gardener's spade down between the concrete and the lagging, and pull back the concrete about 1 inch and pour the opening full of grout and withdraw the spade. If this work is carefully done, There will be very few stones showing when the forms are removed. When stiff pastes or mortars are used, the contractor often places the facing by plastering the lagging just ahead of the concreting. This process requires constant watching to see that the plaster coat does not slough or peel off before it is backed up with concrete. Fig. 45. Form for applying cement facing, Massachusetts Highway Commission. Fig. 46. Form for applying cement facing, Illinois Central Special facing mixtures for minimizing form marks. The ordinary facing mixture of mortar or cement is so fine-grained and plastic that it readily takes the impress of every irregularity in the form lagging. Where a particularly good finish is desired, this makes necessary subsequent finishing treatments. To avoid these subsequent treatments, and at the same time to reduce the form marks, special facing mixtures, which will not take the imprint of and which will minimize rather than exaggerate every imperfection in the forms, have been used with very considerable success in the concrete work done for the various Chicago parks. The mixture used consists usually of 1 part cement, 3 parts fine limestone screenings, and 3 parts 3/4 in crushed limestone. These materials are mixed quite dry so no mortar will flush to the surface when rammed hard. With moderately good form work, the imprint of the joints is hardly noticeable, and grain marks do not show at all. For thin building walls, the special mixture is used throughout the wall, but for more massive structures, it is used only for the facing. Grout washes. Grout finishes serve only to fill the small pits and pores in the surface coating. Cavities or joint lines, if any exist, must be removed by plastering or rubbing before the grout is applied, or else by applying the grout by rubbing. In ordinary work, the grout is applied with a brush after the holes have been plastered and the joint marks rubbed down. The grout to be applied with a brush should be about the consistency of whitewash. A 1 cement 2 sand mixture is a good one. Where a more perfect finish of dark color is desired, the grout of neat cement and lampblack in equal parts may be applied as follows: 2 coats with a brush, the second coat after the first has dried, and 1 coat by sweeping with a small broom. The broom marks give a slightly rough surface. Instead of a liquid grout, a stiff grout or semi-liquid mortar applied with a trowel or float can be used. In this case, the grout should be applied in a very thin coat and troweled or floated, so that only the pores are filled and no body of mortar left on the surface, or else it will scale off. A more expensive but very superior grout finish is obtained by rubbing and scouring the wet grout into the surface with cement mortar bricks, carborundum bricks, or such like abrasive materials. A 1 cement 1 sand mortar brick, with a handle molded into it, and having about the dimensions of an ordinary building brick, makes a good tool for rubbing down joint marks as well as for applying grout. Fig. 47. Concrete baluster finished by scrubbing and washing. Finishing by scrubbing and washing. A successful finish for concrete structures consists in removing the forms while the concrete is green, and then scrubbing the surface with a brush and water until the film of cement is removed and the clean sand or stone left exposed. This method has been chiefly used in concrete work done by the City of Philadelphia, Pa. Mr. Henry M. Quimby, bridge engineer. Figure 47 shows an example of scrubbed finish, but of course the texture or color of the surface will vary with the character of the face mixture and the hue of the sand or chips used. Warm tones can be secured by the use of crushed brick or red gravel. A dark-colored stone with light sand gives a color much resembling granite. Fine gravel or coarse sand gives a texture like sandstone. In much of this work done in Philadelphia, a mixture composed of 1 pot cement, 2 pots bank sand, and 3 pots crushed and cleaned black, slaty shale from 2 1/4 in size has been used with good results both in appearance and in durability. The scrubbing is done with an ordinary house scrubbing brush at the same time, flushing the concrete with water from a sponge or bucket, or, preferably, from a hose. In general, the washing is done on the day following the placing of the concrete, but the proper time depends upon the rapidity with which the concrete sets. In warm weather, 24 hours after placing is generally about right, but in cold weather, 48 hours may be required, and in very cold weather the concrete has been left to set a week, and the scrubbing has been successful. With the concrete in just the proper condition, a few turns of the brush with plenty of water will clean away the cement. But if a little too hard wire brushes must be used, and if still harder a scouring brick or an ordinary brick with sand is necessary to cut the cement film. The process requires that the forms shall be so constructed that the lagging can be removed when the concrete has reached the proper age for treatment. Mr. Quimby sets the studs 8 to 12 ins. From the face and braces, the lagging boards against them by cleats nailed so as to be easily loosened. His practice is to use boards in one width the full depth of the course, and to nail a triangular bead strip to the face at each edge. These bead strips mark the joints between courses as shown by Fig. 48. When a board is taken off, it is cleaned and oiled and reset for a new course by inserting the bottom bead strip in the half indentation left by the top bead in the concrete. This is, of course, for work of such size that 1 course is a day's work of concreting. In such work, 2 carpenters with perhaps 1 helper will remove a course of boards, say 100 ft, long in from 4 to 8 hours. While forms of the kind described cost more to construct, there is a saving by repeated reuse of the lagging boards. The indentations or beads marking the courses serve perfectly to conceal the construction joints. The cost of scrubbing varies with the hardness of the concrete. When in just the right condition for effective work, 1 man can scrub 100 ft in an hour. On the other hand, it has taken 1 man a whole day to scrub and scour the same area when the concrete was allowed to get hard. Fig. 48. Concrete abutment with scrubbed finish and coarse marks. Finishing by etching with acid. The acid-etched or acid wash process of finishing concrete consists in first washing the surface with an acid preparation to remove the surface cement and expose the sand and stone, then with an alkaline solution to remove all free acid, and finally, with clear water in sufficient volume to cleanse and flush the surface thoroughly. The work can be done at any time after the forms are removed and does not require skilled labor. Any man with enough judgment to determine when the etching has progressed far enough can do the work. This process has been very extensively used in Chicago by the South Park Commission, Mr. Lynn White, engineer. In this work, the concrete is faced with a mixture of cement, sand, and stone chips, any stone being used that is not affected by acid. Limestone is excluded. Where some color is desired, the facing can be mixed with mineral pigments or with colored sand or stone chips. This acid wash process has been patented, the patentees being represented by Mr. J. K. Irvine, Sioux City, Iowa, tooling concrete surfaces. Concrete surfaces may be bush-hammered or otherwise tool-finished like natural stone, exactly the same methods and tools being used. Tooling must wait, however, until the concrete has become fairly hard. As the result of his experience in tooling some 43,000 SQ, FT of concrete, Mr. W. J. Douglas states that the concrete should be at least 30 days old and preferably 60 days old if possible when bush-hammered. There is a great variation in the costs given for tooling concrete. Mr. C. R. Neha states that a concrete face can be bush-hammered by an ordinary laborer at the rate of 100 SQ. FT, in 10 hours or at a cost of 1/2 CTS. Per square foot with wages at 15 CTS. Per hour. Mr. E. L. Ransom states that bush hammering costs from 1/2 to 2/2 CTS. Per square foot, wages of common laborers being 15 CTS. Per hour. The walls of the Pacific Borax Co. S factory at Bayonne, NJ, were dressed by hand at the rate of 100 to 200 SQ. FT, per man per day. Using pneumatic hammer, one man was able to dress from 300 to 600 SQ. FT, per day. In constructing the Harvard Stadium, the walls were dressed with pneumatic hammers fitted with a tool with a sawtooth cutting blade like an ice chopper. Men timed by one of the authors on a visit to this work were dressing wall surface at the rate of 50 SQ. FT per hour, but the contractor stated that the average work per man per day was 200 SQ. FT, common laborers were employed. The average cost of bush hammering some 43,000 SQ. FT of plain and ornamental blocks for the Connecticut Avenue Bridge at Washington, D.C. was 26 CTS per square foot. Both pneumatic tools and hand tooling were employed, and the work of both is lumped in the above cost. But hand tooling cost about twice as much as machine tooling. The work was done by high-priced men, foremen stone cutters at $5 per day and stone cutters at $4 per day. Moreover, a grade of work equal to the best bush-hammered stone work was demanded. Full details of the cost of this work are given in Chapter Roman 17. Mr. H. M. Quimby states that the cost of tooling concrete runs from 3 CTS to 12 CTS per square foot, according to the character and extent of the work and the equipment, gravel or pebble surface finish. An effective variation of the ordinary stone concrete surface is secured by using an aggregate of rounded pebbles of nearly uniform size, and by scrubbing or etching remove the cement enough to leave the pebbles about half exposed at the surface. In constructing a bridge at Washington, D.C., the concrete was a 1 to 2 to 5 gravel mixture of 1/2 to 2 in. Pebbles for the spandrels and arch ring face, and of 1 in. Pebbles for the parapet walls. The forms were removed while the concrete was still green, and the cement scrubbed from around the faces and sides of the pebbles using wire brushes and water. Tests showed that at 12 hours age, the concrete was not hard enough to prevent the pebbles from being brushed loose, and that at 36 hours age, it was too hard to permit the mortar to be scrubbed away without excessive labor. The best results were obtained when the concrete was about 24 hours old. Colored facing, where occasion calls for concrete of a color or tint other than is obtained by the use of the ordinary materials, either an aggregate of a color suitable for the purpose may be used, or the mixture may be colored by the addition of some mineral pigment. The first method is by all odds the preferable one. It gives a color which will endure for all time, and it in no way injures the strength or durability of the concrete. Mineral pigments may be secured from any of several well-known firms who make them for coloring concrete, and they may be had in almost every shade. Directions for using these colors can be had from the makers. All but a very few of these mineral colors injure the strength and durability of the concrete if used in amounts sufficient to produce the desired color, and all of them fade in time. The best method of producing a colored mortar or concrete facing is to mix the cement with screenings produced by crushing a natural stone of the desired color. Chapter 34. Concrete, being a plastic material, when deposited, requires molds or forms to give it the shape required and to maintain it in that shape until it has hardened to sufficient strength to require no exterior support. The material used in constructing forms is wood. Beyond the use of metal molds for building blocks for sewer construction and for ornamental and a few architectural shapes, iron and steel are used in form construction only as ties and clamps to hold parts of wood forms together, except in rare instances. A discussion of form construction, therefore, is essentially a discussion of wood forms. Before taking up this discussion, however, attention deserves to be called to the opportunities for the development of metal forms. Lumber is costly and is growing more scarce and costly all the time. A substitute which can be repeatedly used and whose durability and salvage value are great presents itself in steel, if only a system of form units can be devised, which is reasonably adjustable to varying conditions. Cylindrical steel column molds have been used to some extent and are discussed in Chapter Roman 19. In Chapter Roman 16, we describe a steel form for side walls of a tunnel lining. In some building work done in the Northwest, corrugated steel panels or sheets have been used as lagging for floor slab centers. A number of styles of metal forms or centers for sewer and tunnel work have been devised and used and are discussed in Chapter 35. Nothing approaching its general use like wood has been attempted, and the field lies wide open for invention. The economics of form construction deserve the most serious attention of the engineer and contractor. It is seldom that form work, outside of very massive foundation construction, costs less than 50 CTS per cubic yard of concrete in place, and it is not unusual in the more complex structures for it to cost $5 per cubic yard of concrete in place. These costs include the cost of materials and of framing, handling and removing the forms, but they do not embrace extremely high or low costs. It is evident without further demonstration that time spent in planning economic form construction for any considerable job of concrete work is time spent profitably. In the following sections, we review the general considerations which enter into all form work. Specific details of construction and specific costs of form work are given in succeeding chapters, where each class of concrete work is discussed separately. This chapter is intended principally to familiarize the reader with general principles governing form work. Effect of design on form work. The designing engineer can generally aid largely in reducing the cost of form work if he will. This is particularly true in building work in which also form costs run high. By arranging his beam spacing and sizes with a little care, he will enable the contractor to use his forms over and over, and thus greatly reduce the expense for lumber. In the same way, columns may be made of dimensions which will avoid frequent remaking of column forms. Panel recesses in walls may be made the thickness of a board or plank, instead of some odd depth that will require a special thickness of lumber. Or beams may be made of such size that certain dimension widths of lumber can be used without splitting. In general, carpenter work costs more than concrete, and where a little excess concrete may be contributed to save carpenter work, it pays to contribute it. The figures given in Chapter 36. Same material over a second or third time should be studied in this connection. The leading firms of engineering contractors which both design and construct reinforced concrete buildings fully realize these opportunities and take advantage of them. But the general practitioner, particularly if he be an architect, does not do so. The authors have personal knowledge of one building in which a slight change in spacing and dimensions of beams, a change that would have been of no architectural or structural significance, would have reduced the successful contractor's bid for the work by $10,000. The designing engineer should hold it as a cardinal point in design that form work, and we will add here reinforcement also, should so far as possible be made interchangeable from bay to bay and from floor to floor. Kind of lumber. The local market and the character of the work generally determine the kind of lumber to be used for forms. The hardwoods are out of the question for form construction because they cost too much and are too hard to work. Among the soft woods, white pine costs too much for general use, and hemlock is unreliable when exposed to the weather. This reduces the list generally available to spruce, Norway pine, and the southern pines. Neither green nor kiln-dried lumber is so good as partially dry stuff, since the kiln-dried lumber swells and crushes or bulges the joints, and green lumber does not swell enough to close the joints. Forms have to withstand, temporarily, very heavy loads. Therefore, knots, shakes, and rot must be watched after. The choosing of good lumber is a simple process, and the contractor who wants to be able to rely on his forms will look after it carefully, without going to extremes which the work does not warrant. Finish and dimensions of lumber. Dressing the lumber serves 4 important purposes. It permits the forms to be constructed more nearly true to line and surface. It permits tighter joint construction. It gives a smoother surface finish to the concrete, and it facilitates the removal and cleaning of the forms. Undressed lumber may be used for the backs of walls and abutments, for work below ground and wherever a smooth and true surface is unimportant. There are some contractors, however, who prefer lumber dressed on one side even for these purposes because of the smaller cost of cleaning. For floor and wall forms, the lumber should always be dressed on one side. Where the work is very particular, both sides should be dressed, and in special cases, the sides of the joists or studs against which the lagging lies may be dressed. For ordinary work, a square edge finish does well enough, but for fine face work, a tongue and groove or bevel edge finish is preferable. The tongue and groove finish gives a somewhat tighter joint on first laying, but it does not take up swelling or resist wear so well as the bevel edge finish. When ordering new lumber for forms, the contractor will save much future work and waste if he does it from plans. Timber cut to length and width to go directly into the forms reduces both mill and carpenter work on the site, and in many cases it can be so ordered if ordered from plans. Waste is another item that is reduced by ordering from plans. With lumber costing its present prices, crop ends run into money very rapidly. When old lumber from a previous job is to be used, the contractor can only make the best of his stock, but even here form plans will result in saving. Sort and pile the old lumber according to sizes, and make a schedule of the quantity of each size on hand. This schedule in the hands of the man who designs the forms and of the head carpenter will materially reduce waste and carpenter work. It is often possible, especially in making concrete foundations for frame buildings, to use lumber for forms which is subsequently used for floor beams, etc. In the building, contractors differ greatly in their ideas of the proper thickness of lumber to use for various parts of form work. Generally speaking, 1/4 to 2 in. Stuff is used for wall lagging held by studding and 1 in. Stuff when built into panels, for floor lagging 1 in stuff with joists spaced up to 24 ins, or when built into panels, for column lagging 1/4 to 2 in. Stuff, for sides of girders 1, 1/4, 1/2, and 2 in. Stuff are all used, and for bottoms of girders, 1/2 and 2 in. Stuff. These figures are by no means invariable, as a study of the numerous examples of actual form work given throughout this book will show. Computation of forms. If the minimum amount of lumber consistent with a given deflection is to be used in form work, the sizes and spacing of the supporting members must be actually computed for the loading. As a practical matter of fact, the amount of material used and the arrangement of the supports are often subject to requirements of unit construction, clearance, staging, etc., which supersede the matter of economical adaptation of material to loading. The designing of form work is at best, therefore, a compromise between rules of thumb and scientific calculation. In wall work, empirical methods are nearly always followed. In girder and floor slab work, on the other hand, design is commonly based on computation. In the matter of loads, the general practice is to assume the weight of concrete as a liquid at some amount which it is considered will also cover the weight of men, barrows, runways, and current construction materials. The assumed weights vary. One prominent engineering firm assumes the load to be the dead weight of concrete as a liquid, and the load due to placing, and specifies that the forms shall be designed to carry this load without deflection. Mr. W. J. Douglas, engineer of bridges, Washington, D.C., assumes for lateral thrust on wall forms that concrete is a liquid of half its own weight, or 75 pounds. Per coup, Ft. Mr. Sanford E. Thompson, consulting engineer, Newton Highlands, Mass., assumes for dead load, weight of concrete including reinforcement as 154 pounds. Per coup, Ft. and for live load 75 pounds, per SQ Ft. on slabs and 50 pounds, per SQ Ft. in figuring beam and girder forms and struts. The assumed safe stresses in form work may be taken somewhat higher than is usual in timber construction, because of the temporary character of the load. In calculating beams, the safe extreme fiber stress may be assumed at 750 pounds. Per SQ. The safe stress in pounds per square inch for struts or posts is shown by Table Roman 15, compiled by Mr. Sanford E. Thompson. The sizes of struts given are those most commonly used in form work. Table Roman 15. Safe strength of timber struts for frame work. Dimensions of strut. Length strut, 3 times 4 in, 4 times 4 in, 6 times 6 in, 8 times 8 in, feet, pounds, 14. 700, 900, 1,112, 600, 800, 1,000, 1,210, 700, 900, 1,100, 1,208, 850, 1,000, and 50, 1,200, 1,206, 1,000, 1,200, 1,200, 1,200. In using this table, it must be borne in mind that bracing both ways reduces the length of a long strut. For example, if a strut 24 ft. long be divided into 3 panels by bracing, the length of strut so far as the table is concerned is 8 ft. As stated above, wall forms are rarely computed. Experience has shown that the maximum spans of various thicknesses of lagging between supports are 1 in, boards 24 ins, 1/2 in, plank 4 ft. and 2 in, plank 5 ft., Studding will vary in size from 2x4 to 4x6 ins, strutted and braced horizontally to meet conditions. Column forms like wall forms are rarely computed, yokes being spaced 2 ft, apart for 1 1/4 in, lagging up to 3 to 3 1/2 ft, apart for 2 in. Lagging. Floor forms, including girder and slab forms, are computed on the basis of a maximum deflection and not on the basis of strength. Sagging forms are liable to rupture the beam or slab. The amount of deflection considered allowable varies from no deflection up to 2 1/2 in. Assuming the deflection, permissible thickness of the timber necessary to carry the load is determined by the formulas. D equals 5WL3 divided by 384 EI1, and BH3I equals 212. Formula 1 is the familiar one for computing deflection for a beam supported, not fixed at the ends. Mr. Sanford F. Thompson suggests using the constant 3/384, which is an approximate mean between 1/384, that for beams with fixed ends, and 5/384, that for beams with ends supported. Formula 1 then becomes D equals 3WL3 divided by 384 EI, in which, as above, D equals maximum deflection in inches, W equals total load on plank or joist, L equals length between supports in inches, E equals modulus of elasticity of lumber, I equals moment of inertia of cross-section, B equals breadth of lumber, H equals depth of lumber. The deflection, D being assumed formula 1, is solved for I, moment of inertia. Substituting the value of I in formula 2, we can readily estimate the size of joist or thickness of plank to use. For spruce, yellow pine, and the other woods commonly used in form work, E may be taken equal to 1,300,000 pounds. Per SQ. In design and construction, the main points to be kept in mind in the original design and construction of forms are economy in lumber, economy in carpenter work, and economy in taking down, carrying, and re-erecting. Economy in lumber is not merely the matter of using the least amount of lumber that will serve the purpose, considering the form as an isolated structure. It may be possible to build a column form, for example, a very light material which will serve to mold a single column, but it is evident that we could better afford to use twice this amount of lumber if by doing so we obtained a form which could be used over again to mold a second column. No more lumber per column would be used, while the cost of erecting a form already framed is less than the cost of framing a new form. Economy in lumber in form construction involves, therefore, recognition of the economies to be gained by repeated use of the lumber. A certain amount of additional sturdiness is required in the shape of heavier form lumber and stronger framing to provide for the wear and tear of repeated use, and it is always economy to provide it when repeated use is possible. The thing can be overdone, however. There is an economical limit to repeated use, as we demonstrate further on. In the matter of economy in carpenter work, a certain amount of extra work put into framing the forms to withstand the stress of repeated use is economically justifiable. Also, carpenter work put into framing, which substitutes clamps and wedges for nails, is sound economy. Generally speaking, a skillful form carpenter is recognized by the scarcity of nails he uses. The possibility of reducing carpenter work by ordering lumber to length and width from plans has already been mentioned. It is possible often to go a step further by having certain standard panels, boxes, etc., made in regular shops. Piecework is often possible, and will frequently reduce framing costs. In designing for economy in taking down, carrying and re-erecting forms, a cardinal point should be that the work be such that it can be executed by common laborers. This result can be very nearly approached by careful design, even for form work that is quite complex, if a special gang is devoted to the work and trained a little in the various operations. Design the forms so that they come apart in units by simply removing bolts, clamps, and wedges. They can then be taken down, carried and erected by common laborers with a skilled man in charge to meet emergencies and to true and line up the work. In the matter of details, the joints deserve particular attention. In column and girder forms, generally, joints will be square or butt joints, and to get them tight, the lumber must be dressed true to edge. Tight joints are considered essential by many not only to avoid joint marks, but for the more important reason that otherwise, with wet mixtures, a honeycombed concrete is produced by leakage. Where tight joints are desired, tongue and groove stock or stock cut with one edge beveled, and the other square give the best results. The authors believe that the best general satisfaction will be got from the bevel edge stock placed, so that the bevel edge of one board comes against the square edge of the next board. Undue swelling then results in the bevel edge cutting into the adjacent square edge without bulging. Tongues and grooves suffer badly from breakage. As a matter of fact, square-edged stock, if well dressed and sized and well filled with moisture, can be used and is used with entire success in nearly all kinds of work. The leakage will be very slight with ordinarily good butt joints, and so far as surface appearance goes, joint marks are more cheaply and more satisfactorily eliminated by other means than attempting to get cabinet work in form construction. Where girder forms join columns or beams connect with girders, and at the angles of floor slabs with beams the edges or corners of the forms should be rounded. The edges of beams and column corners will appear better if beveled. A triangular strip in the corners of the forms will provide this bevel. Forms and mold construction for ornamental work call for and are given special consideration in Chapter Roman 23. In conclusion, the reader should study the specific examples of form construction for different purposes that are given throughout the book for hints as to special practice and details. Unit construction of forms. Unit construction has a somewhat variable meaning in form work. In wall and tank work and in some other kinds of work, unit construction means the use of form units which are gradually moved ahead or upward as the concreting progresses, or of form units which are used one after another in continuous succession as the concreting progresses. In column, girder, and floor work, unit construction means the division of the form work as a whole, and also of the individual forms into independent structural units. Thus, in forms for a building, the column forms may be independent of the girder forms, and also each column and girder form be made up of several separate units. In all cases, unit construction has for its purpose the use of the same form, or at least the same form lumber over and over for molding purposes. Every time the use of the same form is repeated, the cost of form work per cubic yard of concrete placed is reduced. The theoretical limit of economical repetition is then the limit of endurance of the form. The practical limit, however, is something quite different. Most concrete work varies in form or dimensions often enough to prevent the use of the same forms more than a few times. And even if these variations did not exist, the time element would enter to prevent the same form or form lumber being used more than a certain number of times. Unit construction to give repeated use of forming has, therefore, its economic limits. The significance of this conclusion does not lie in any novelty that it possesses, but in the fact that for any piece of work it determines the labor that may profitably be expended in working out and constructing form units. Lubrication of forms. All forms for concrete require a coating of some lubricant to prevent the concrete from adhering to the wood with which it comes in contact. Incidentally, this coating tends to give a smoother surface to the concrete and to preserve the wood against damage by its alternate wetting and drying. The great value of lubrication is, however, that it reduces the cost of removing forms. The requisite of a good coating material is that it shall be thin enough to spread evenly and to fill the pores and grain of the wood. Crude oil or petroleum makes one of the best coatings, but various other greasy substances will serve. Where the forms are not to be removed until the concrete has set hard, a thorough wetting of the wood just before the concrete is placed is all the coating necessary. Any concrete adhering to forms should be thoroughly cleaned off before they are used again, and the wood underneath given a special heavy coating. False works and bracing. The false works which support the forms proper and stagings for workmen, runways, material hoists, etc., do not call for any striking differences in construction and arrangement from such work elsewhere. For wall forms, inclined props reaching from ground to studding are used for walls of moderate height, such as retaining walls, wing walls, and abutments. For building walls of some height, a gallows frame arrangement or the common braced staging used by masons and carpenters is used. In building construction, however, movable forms are commonly employed for walls more than 1 story high, and should always be employed above 1 story to save staging timber. Column forms are seldom braced, unless erected without connecting girder or floor forms at their tops, and then only by diagonal props to the floor or ground. Girder and floor supports usually consist of uprights set under the girder form at intervals, and occasionally under floor slab forms. The spacing of props and uprights will be regulated by the judgment of the foreman and boss carpenter. No general rule is applicable, except that enough lumber must be used to hold the forms rigid and true to line and level. The various illustrations of actual formwork which follow are the best guides to good practice. Time for and method of removing forms. No exact time schedule for removing forms is wise in concrete work. Concrete which is mixed wet sets slower than dry concrete, and concrete sets slower in cold weather than it does in warm weather. Again, the time of removal is influenced by the risk taken by too early removal, and also by the nature of the stresses in the member to be relieved of support. In all cases, the forms should be removed as soon as possible, so that they can be used over again, and so that the concrete may be exposed to the air to hasten hardening. The following suggestions as to time of removal are general and must be followed with judgment. Using dry concrete in warm weather, the forms for retaining walls, pedestals, isolated pillars, etc., can be removed in 12 hours. Using wet or sloppy concrete, the time will be increased to 24 hours. In cold weather, the setting is further delayed, and inspection is the only safe guide to follow. Very cold weather delays setting indefinitely. Forms for small arch work like sewers and culverts may be removed in 18 to 24 hours if dry concrete is used, and in 24 to 48 hours if wet concrete is used. The time for removing large arch centers should not be less than 14 days for spans up to 50 ft. If the arch is backfilled at once, when the center is not to be used again, it is better to let it stand 28 days. For very large arches, the problem becomes a special one and is considered in Chapter Roman 17. In building construction, the following schedule is a common one. Remove the column forms in 7 days and the sides of the girder forms, and the floor lagging in 14 days, leaving the bottom boards of the girder forms and their supports in place for 21 days. As an example of individual practice, the following requirements of a large firm of concrete contractors are given. Walls in mass work, 1 to 3 days, or until the concrete will bear pressure of the thumb without indentation. Thin walls in summer, 2 days. In cold weather, 5 days. Slabs up to 6 ft. Span in summer, 6 days. In cold weather, 2 weeks. Beams and girders and long span slabs in summer, 10 days or 2 weeks. In cold weather, 3 weeks to 1 month. If shawls are left without disturbing them, the time of removal of the sheeting in summer may be reduced to 1 week. Column forms in summer, 2 days. In cold weather, 4 days, provided girders are shawed to prevent appreciable weight reaching columns. Conduits, 2 or 3 days, provided there is not a heavy fill upon them. Arches of small size, 1 week. For large arches with heavy dead load, 1 month. The method of removing forms will vary in detail with the character of the structure. With proper design and lubrication of forms, they will ordinarily come away from the concrete with a moderate amount of sledge and bar work. If the work will warrant it, have a special gang under a competent foreman for removing forms. The organization of this gang and the procedure it should follow will vary with the nature of the form work, and they are considered in succeeding chapters for each kind of work, estimating and cost of form work. It is common practice to record the cost of forms in cents per cubic yard of concrete, giving separately the cost of lumber and labor. This should be done, but the process of analysis should be carried further. The records should be so kept as to show the first cost per 1,000 ft. B. M. of lumber, the number of times the lumber is used, the labor cost of framing, the labor cost of erecting, and the labor cost of taking down, all expressed in M. Ft. B. M. In this way only is it possible to compare the cost of forms on different kinds of concrete work, and thus only can accurate predictions be made of the cost of forms for concrete work having dimensions differing from work previously done. It is well also to make a note of the number of square feet of exposed concrete surface to which the forms are applied. Some of the items mentioned demand brief explanation. Framing and erecting costs are kept separate for the reason that the framing is done only once, whereas the erecting occurs 2 or more times. The lumber cost, where the material is used more than once, can be computed in 2 ways. An example will illustrate the 2 modes of procedure. In one of the buildings described in Chapter Roman 19, the lumber cost $30 per m, ft. B. m, and was used 3 times, as 34,000 ft. B. m were required to encase the 200 cu. ids. Of concrete in one floor including columns, it would have required 34,000 divided by 200 equals 170 ft. B. m of lumber at $30 per m, per cubic yard of concrete if it had been used only once. But since it was used 3 times, we may call it 170 ft. B. m at $10 per m, per cubic yard of concrete, or we may call it 170 divided by 3 equals 57 ft. B. m at $30 per m, per cubic yard of concrete. The authors prefer the first method due to the fact that it is 170 ft. B. m That is handled and taken down each time, and it is more consistent to have the lumber cost on the same basis. Thus, 170 FT B M of lumber at $10 per M $1. 170 FT B M handled at $2 per M 0. 34 170 FT B M erected at $7 per M 1. 19 total 170 FT B M per coup YD $3. 23. Returning to our main thought, there are three ways of recording the cost of farm work. 1 in cents per cubic yard of concrete, 2 in cents per square foot of concrete face to which forms are applied, and 3 in dollars per 1,000 FT B M of lumber used. In all cases, the cost of materials and of labor should be kept separate. It is well if it can be done to attach a sketch of the forms to the record. So much for the general method of recording costs in farm work. In estimating the probable cost of forms for any job, the following method will be found reliable. Having the total cubic yards of concrete in the work and the time limit within which the work must be completed determine the number of cubic yards that must be placed per day, making liberal allowances for delays. Next, estimate the number of thousands of feet broad measure of forms required to encase the concrete to be placed in a day. This will give the minimum amount of lumber required, for it is seldom permissible to remove the forms until the concrete has hardened overnight. Now we come to the very important and puzzling question of the time element, particularly in work where it is possible to use the same forms or the same form lumber 2 or more times. It has already been pointed out that wet concrete sets more slowly than dry concrete, that all concrete sets more slowly in cold than in warm weather, and that the support of forms is necessary a longer time for pieces subject to bending stress like arches and girders. General suggestions as to specific times for removing forms have also been given. Where the specifications state the time of removal, the contractor has a definite guide, but where they do not, as is most often the case, he must depend very largely on judgment and previous experience. Another matter which deserves consideration is the use of the forms as staging for runways or tracks. Such use may result in forms having to stand on work for sake of their service, as trestles much longer than there is any necessity so far as supporting the concrete is concerned. A derrick or cableway may often prove cheaper than tying up form lumber by trying to make it serve the double purpose of a trestle. The possibilities of repeated use of forms and of unit construction of forms have already been noted. This is the next point to be considered in estimating form lumber. At the expense of a little planning, movable forms can be used to materially reduce the amount of lumber required. The reader is referred particularly to the chapters on retaining wall, conduit, and building work for specific data on movable form work. Having estimated the amount of lumber required and the number of times it can be used, the labor cost of framing, erecting, and taking down can be figured. In ordinary retaining wall work, forms will cost for framing and erection from $6 to $7 per M, FT, B, M. To tear down such forms carefully and to carry the lumber a short distance will cost some $1.50 to $2 per M, FT, B, M. We have then a cost of $7.50 to $9 per M, FT, B, M, for each time the forms are erected and torn down. Where movable panels are used and the forms not ripped apart and put together again each time, there is of course only the cost of moving, which may run as low as 50 CTS per M, FT, B, M. Framing and erecting centers for piers will run about the same as for retaining wall. At this point, it may be noted that in estimating the cost of forms for plain rectangular piers, the following method will give very accurate results. Ascertain the surface area of the four sides of the pier. Multiply this area by 2, and the product will be the number of feet board measure of 2 in. Plank required. Add 40% to this, and the total will be the number of feet board measure of 2 in. Plank and of upright studs 4 times 6, space 2½ ft, centers, sometimes 3 times 6 in. Studs are used and spaced 2 ft, centers, which requires practically the same percentage, 40%, of timber for the studs as where 4 times 6 in. Studs are used and spaced 2½ ft, centers. No allowance is made for timber to brace the studs, since in pier work it is customary to hold the forms together either with bolts or with ordinary 9 telegraph wire, which weighs 0.06 lb per foot. The foregoing data can be condensed into a rule that is easily remembered. Multiply the number of square feet surface area of the sides and ends of a concrete pier by 8, and the product will be the number of feet board measure required for sheet, plank, and studs for the forms. If the form lumber can be used more than once, divide the number of feet board measure by the number of times that it can be used to ascertain the amount to be charged to each pier. Forms can be erected and taken down for $8 per m, carpenters being paid $2.50 and laborers $1.50 a day. Since there are 8 ft/m of forms per square foot of surface area of concrete to be sheeted, it costs 2¼ CTS for the labor of carpenters per square foot of surface area to be sheeted. If lumber is worth $24 per m and is used 3 times, then the lumber itself also costs 2¼ CTS per SQ ft of surface area of concrete. By dividing the total number of cubic yards of concrete into the total number of square feet of area of surface to be sheeted with forms, the area per cubic yard is obtained. Multiply this area by 4½ CTS, and the product is the cost per cubic yard for material in the forms, assumed to be used 3 times, and the labor of erecting it and taking it down. The cost of framing and erection of forms for building work and of centers for large arches is a special problem in each case, and is considered in the chapters devoted to those classes of work. Chapter 37. 2 general methods of concrete pile construction are available for engineering work. By one method, a hole is formed in the ground by driving a steel shell or by other special means, and this hole is filled with concrete. By the other method, the pile is molded in suitable forms, and after becoming hard is driven, as a wood or steel pile is driven. Piles constructed by the first method may be either plain or reinforced, but piles constructed by the second method are always reinforced to strengthen them for handling and driving. Concrete piers for foundation work are simply piles of enlarged diameter. Molding piles in place. Molding piles in place requires the use of special apparatus, and this apparatus is to a very large degree controlled by patents. Pile work of this kind is thus generally done by concerns which control the use of the apparatus employed, and the general contractor can undertake it only by permission of the proprietary companies. The methods of work followed and the cost of work are thus of direct interest only as general information. Method and cost of constructing Raymond piles. The machinery and processes employed in the construction of Raymond concrete piles are patented, and all piling work by this method is controlled by the Raymond Concrete Pile Co. As detailed costs of construction are not given out by the company, the following figures collected by the authors are subject to revision. They are believed to be fairly approximate, having in one case been obtained by personal watch on the work and in the other case from authentic records of the engineers on the work. The pile is made as follows: a collapsible steel core 30 ft, long 20 ins, diameter at the top and 6 ins. Diameter at the bottom, encased in a thin sheet steel shell, is driven into the ground by an ordinary pile driver. When it has reached the proper depth, a wedge is loosened, permitting the two sections of the core to come closer together so that the core can be pulled out of the hole, leaving the steel shell behind as a casing to prevent the sides from caving in. The shell is made of 20-gauge steel, usually in 4 or more sections, which telescope one over the other. A nest of sections is slipped over the lower end of the core as it hangs in the leads. A rope is hitched around the outer section, and the engine hoists away until the sections are untelescoped and drawn snug onto the core. The rope is then unfastened, and the driving begins. Figure 49 shows the usual pile driving rig used. The following are examples of pile construction in actual work. Example I. In this work for building foundation in New York City, the pile driver was mounted on a turntable, the framework of the turntable in turn resting on rollers traveling on timbers laid on the ground. The driver was moved along and rotated when necessary by ropes passing around the winch head of the engine. The driver had 50 ft, leads, and a 3,100 lb. Hammer operated by an ordinary friction clutch hoisting engine. The hammer blow was received by an oak block fitting into a recess at the top of the steel core. This block was so battered by the blows that it had to be renewed about every 5 or 6 piles driven. A 3/4 in, wire rope passing over a 10 in. Sheave lasted for the driving of 130 piles and then broke. When the work was first begun, the crew averaged 10 piles per 10-hour day, but the average for the job was 13 piles per day, and the best day's work was 17 piles. The cost of labor and fuel per pile was as follows. Fig. 49. Pile driver rigged for constructing Raymond concrete piles. 5 men on driver at $1. $75 8. 75 2 men handling shells at $1. 75 3. 51 enginemen 3, 006 men mixing and placing concrete 10, 51 foremen 5, 00 coal and oil 2, 50, total 13 piles at $2, 55 $33, 25 deducting the cost of placing the concrete, we get a cost of $1, 75 for driving the cores. The pile 25 ft, long 6 ins at the point and 18 ins at the head, contains 21¼ cu ft or 0.8 cu yd of concrete and has a surface area of 77 ft. As 20 steel weighs 3 pounds per sq ft. Each shell weighed approximately 100 pounds. The cost per pile may then be summarized as follows. 1. 2 BBLS. Cement in 0.8 cu yd at $1. 75 $2 10 0.8 cu yd. Stone at $1. 25 1 0 1/3 cu yd. Sand at $1. 050 35 100 pounds. Steel in shell at 3½ cts. 3. 50 labor and fuel as above. 2. 55 total per pile. 38 cts per lin ft. $9.50. This cost, it should be carefully noted, does not include cost of moving plant to and from work or general expenses. Example Roman 2. In constructing a building at Salem, Mass., 172 foundation piles, 14 to 37 ft. Long, 6 ins. Diameter at the point and 20 ins. Diameter at the top were constructed by the Raymond process. The general contractor made the necessary excavations and provided clear and level space for the pile driver, braced all trenches and pier holes, set stakes for the piles, and gave all lines and levels. The piles were driven by a No. 2 Vulcan steam hammer with a 3000 lb, plunger having a drop of 3 ft, delivering 60 blows per minute. Figure 49 shows the driver at work. 16 working days were occupied in driving the piles after the driver was in position. The greatest number driven in one day was 20, and the average was 11 piles per day. When in position for driving, the average time required to complete driving was 12 minutes. The total number of blows varied from about 310 to 360, the average being about 350. The piles were driven until the penetration produced by 8 to 10 blows equaled 1 in. When in full operation, a crew of 5 men operated the pile driver. 7 men were engaged in making the concrete and 5 men working upon the metal shells. Assuming the ordinary organization and the wages given below, we have the following labor cost per day. 1 foreman at $5.5. 001 engineman at $3.3. 004 laborers on driver at $1. 75.7. 006 laborers making concrete at $1. 75.10. 55 laborers handling shells at $1. 75.8. 75, total $34. 25, as 172 piles averaging 20 ft. In length were driven in 16 days. The total labor cost of driving given by the figures above is 16 times $34. 25 equals $548, or practically 16 CTS, per lineal foot of pile driven. The concrete used in the piles was a 1 to 3 to 5 Portland cement, sand, and 1/2 in broken stone mixture. A 20 ft. Pile of the section described above contains about 20 ft of concrete, or say 0.75 yd. We can then figure the cost of concrete materials per pile as follows: 0.85 bbl, cement at $1, $61, 36 36 yd, sand at $1, 36 60 yd, stone at $1, 25 75, total per pile $2. 47. The steel shell has an area of about 72 ft, and as No. 20-gauge steel weighs 3 pounds per ft. Its weight for each pile was about 94 pounds, assuming the cost of coal, oil, etc. at $2.50 per day. We have the following summary of costs per lin, ft, of pile. Labor driving and concreting $0. 16 concrete materials 0. 123.94 pounds. Steel shell at 3 CTS, 0. 145 coal, oil, etc. 0. 0.11, total $0. 439. The cost does not include interest on plant, cost of moving plant to and from work, and general expenses. Fig. 50. Sketch showing method of constructing simplex concrete piles. Method of constructing simplex piles. The apparatus employed in driving simplex piles resembles closely the ordinary wooden pile driven, but it is much heavier and is equipped to pull as well as to drive. A 3,300 lb hammer is used, and it strikes on a hickory block set in a steel drive head which rests on the driving form or shell. This form consists of a 3/4 in steel shell 16 ins, in diameter made in a single 40 ft. Length, around the top of the shell a half in. Thick collar or band 18 ins. Deep is riveted by 24 1 in, countersunk rivets. This band serves the double purpose of preventing the shell being upset by the blows of the hammer and of giving a grip for fastening the pulling tackle. The bottom of the form or shell is provided with a point. Two styles of point are employed. One style consists of two segments of a cylinder of the same size as the form, so cut that they close together to form a sort of clam shell point. In driving, the two jaws are held closed by the pressure of the earth, and in pulling they open a part of their own weight to permit the concrete to pass them. This point, known as the alligator point, is pulled with the shell. It is suitable only for driving in firm, compact soil. In loose soil, the pressure inward of the walls keeps the jaws partly closed, and so contracts the diameter of the finished pile. The second style of point is a hollow cast iron point, 10 ins, deep and 16½ ins. In diameter, having a neck over which the driving form slips and an annular shoulder outside the neck to receive the circular edge of the shell. The projected sectional area of this point is 4 sq. ft. It is left in the ground when the form is withdrawn. The form is withdrawn by means of 2 1 in. Cables fasten to a steel collar which engages under the band at the top of the form. The cables pass in the channel leads on each side over the head of the driver and down in back to a pair of 5-fold steel blocks, the lead line from which passes to one of the drums of the engine. In this manner, the power of the drum is increased 10 times, and it is not unusual to break the pulling cables when the forms are in hard ground. The general method of construction is about as shown by Fig. 50, being changed slightly to meet varying conditions. The form resting on a cast iron point is driven to hard ground. A heavy weight is then lowered into the form to make sure the point is loose. While the weight is at the bottom of the form, a target is placed on its line at the top of the form, the purpose of which will be apparent later. The weight is then withdrawn. Given the length of the pile and sectional area, it is an easy matter to determine the volume of concrete necessary to fill the hole. This amount is put into the form by means of a specially designed bottom dump bucket, which permits the concrete to leave it in one mass, reaching its destination with practically no disintegration. It will be noticed that when the full amount of concrete is in the form, its surface is considerably above the surface of the ground. This is due to the fact that the thickness of the form occupies considerable space that is to be occupied by the concrete. The weight is now placed on top of the concrete, and the form is pulled. The target previously mentioned now becomes useful. As the form is withdrawn, the concrete settles down to occupy the space left by the walls of the form. Obviously, this settlement should proceed at a uniform rate, and as it is difficult to watch the weight, the target on its line further up is of considerable help. By watching this target in connection with a scale on the leads of the driver, it can be readily told how the concrete in the form is acting. As another check, the target, just as the bottom of the form is leaving the ground, should be level with the top of the form. This would indicate that the necessary amount of concrete has gone into the ground, and that, other conditions being all right, the pile is a good one. In some grounds where the head of concrete in the form exerts a greater pressure than the back pressure or resistance of the earth, the concrete will be forced out into the sides of the hole, making the pile of increased diameter at that point, and necessitating the use of more concrete to bring the pile up to the required level. Method of constructing piles with enlarged footings. A pile with an enlarged base or footing has been used in several places by Mr. Charles R. Gow of Boston, Mass., who has patented the construction. A single pipe, or a succession of pipes connected as the work proceeds, is driven by hammer to the depths required. The material inside the shell is then washed out by a water jet to the bottom of the shell, and then for a further distance below the shell bottom. An expanding cutter is then lowered to the bottom of the hole and rotated horizontally so as to excavate a conical chamber, the water jet washing the earth out as fast as it is cut away. When the chamber has been excavated, the water is pumped out and the chamber and shell are filled with concrete. The drawings of Fig. 51 show the method of construction clearly. The chambering machine is used only in clay or other soil which does not wash readily. In soil which is readily washed, the chamber can be formed by the jet alone. The practicability of this method of construction is stated by Mr. Gow to be limited to pipe sizes up to about 14 inches in diameter. Fig. 51. Sketch showing method of constructing concrete piles with enlarged footings. Method of constructing piles by the compressor system. The compressor system of concrete pile or pillar construction is a French invention that has been widely used abroad and which is controlled in this country by the Hennebeek Construction Co. of New York, N.Y. The piles are constructed by first ramming a hole in the ground by repeatedly dropping a conical perforator, weighing some 2 tons. This perforator is raised and dropped by a machine resembling an ordinary pile driver. The conical weight gradually sinks the hole deeper and deeper by compacting the earth laterally. This lateral compression is depended upon so to consolidate the walls of the hole that they do not cave before the concrete can be placed. The concrete is deposited loose in the hole and rammed solid by dropping a pear-shaped weight onto it as it is placed. The view Fig. 52 shows the perforator and the tamping apparatus at work. Very successful work has been done abroad by this method. Fig. 52. View of apparatus used in constructing compressor piles. Method of constructing piers in caissons. For piles or pillars of diameters larger than, say, 18 inches, the use of driving shells and cores becomes increasingly impracticable. Concrete pillars of large size are then used. They are constructed by excavating and curbing a well or shaft and filling it with concrete. This construction has been most used in Chicago, for the foundations for heavy buildings, but it is of general application where the subsoil conditions are suitable. The method is not patented or controlled by patents in any particular, except that certain tools and devices which may be used are proprietary. General description. The caisson method of construction is simple in principle. A well is dug by successive excavations of about 5 ft. each. After each excavation of 5 ft. is completed, wood lagging is placed around the sides and supported by internal steel rings, so that the soft ground around the excavation is maintained in its former position. The methods of excavating and removing the soil and of constructing the lagging are considered in detail further on. The caissons vary in diameter according to the load, some as large as 12 ft. In diameter have been sunk, but the usual diameter is 6 ft. A caisson of 3 ft. in diameter is as small as a man can get into and work. When the pier goes to bedrock, the caisson is made of uniform diameter from top to bottom, but where the pier rests on hardpan, the bottom portion of the well is belled out to give greater bearing area. It is customary to load the piers about 20 tons per square foot. Fig. 53. Curbing for concrete piers, usual construction, caisson construction. The caisson construction, or more correctly the form of curbing most commonly used, is that indicated by the sketch, Fig. 53. The lagging is 2 times 6 in, or 3 times 6 in, stuff 5 ft, 4 ins, or 4 ft, long set vertically around the well and held in place by interior wrought iron rings, for a 6 ft. Diameter caisson. These hoops are 3/4 by 3 ins. They are made in 2 parts, which are bolted together as shown by Fig. 53. Generally, there are 2 rings for each length of lagging for 5 ft. Lagging, they are placed about 9 ins from each end. In some cases, however, engineers have specified 3 rings for the upper sections in soft clay and 2 rings for the sections in the hard ground lower down. The lagging used is not cut with radial edges, but is rough, square-cut stuff. The rings, therefore, take the inward pressure altogether. Fig. 54. Curbing for concrete piers, Jackson patent. In some recent work done by the inventor, use has been made of the caisson construction shown by Fig. 54 and patented by Mr. Geo. W. Jackson. In place of the plain rings, a combination of T-beam ribs and jacks is used. This construction is clearly shown by the drawing. The advantages claimed for the construction are that it gives absolute security to the workmen and the work, that the lagging can be jacked tightly against the outer walls of the well, that the braces form a ladder by which the workmen can enter and leave the well, and that the possibility of shifting the bracing easily permits the concrete to be placed to the best advantage. On the other hand, the braces obstruct the clear working space of the caissons. Fig. 55. Layout of plant for concrete pier construction, Cook County Courthouse foundations, excavating and handling material. The excavation of the wells is done by hand using shovels and picks, and in the hardpan special grubs made by A.J. Pement and George Rackey, Chicago blacksmiths. The excavated material is hoisted out of the well in buckets made by the Variety Iron Works of Chicago. For caissons which are not specified to go to rock, it is considered more economical to do the hoisting by windlass derricks operated by hand. These derricks have 4 6 times 6 in legs and a 3 times 6 in top piece. When the caissons go to rock, the hoisting is done by power, so-called cable setups being used in most cases. To illustrate this method, the following account of the foundation work for the Cook County Courthouse is given. The Cook County Courthouse foundations consist of 126 caissons varying from 4 ft to 10.5 ft in diameter and averaging $7.5 ft in diameter. They were sunk to rock at a depth of 115 ft below street level. The work involved 22,000 ids of excavation and the placing in the caissons of 17,000 ids of concrete, over 1,000 piles about 40 ft long that had formed the foundation of the old courthouse built in 1875 were removed. These piles were found to be in good condition. The work was done by the George A. Fuller Co. of Chicago, contractors, with Mr. Edgar S. Belden superintendent in charge. The details which follow have been obtained from Mr. Belden. Fig. 56. Section showing arrangement of hoist for concrete pier construction. The foundation area was 157 times 375 ft and was excavated to a depth of 15 ft below the street surface before the caissons were started. The caissons, of which there were 126, were arranged in rows across the lot, there being from 6 to 8 caissons in a row. The arrangement of the plant for the work is indicated by Fig. 55. One row of caissons formed a unit. A platform or stand was erected over each caisson and carried in its top a tripod fitted with a nigger head operated by a rope sheave. This arrangement is shown by Fig. 56. An engine on the bank operated by a rope drive all the tripod sheaves for a row of 6 or 8 caissons. The arrangement is indicated by Fig. 55. The clay hoisted from the pits was dumped into one coup, YD. Hoppers with which the stands were fitted, as shown by Fig. 56. When a hopper was full, it was dumped into a car running on a 24-in gauge portable track. Side dump Capel cars of one coup, YD. Capacity were used. They dumped their load into an opening connected with the tracks of the Illinois Tunnel Co., where the material passed into tunnel cars and was taken to the lake front about 1 mile away. As soon as one row of caissons was completed, the stands, tripods, etc., which were made portable, were shifted to another row. At times, as many as 5 units were in operation, sinking 40 caissons. Fig. 57. Details of working platform for concrete pier construction. Fig. 56 shows the arrangement in detail at one caisson. In this work, the lagging used was 3 times 6 in. Maple 5 ft, 4 ins long and was supported by 3 times 3 in steel hoops. The lagging was matched and dressed. The nigger head, as will be seen, is operated by a rope sheave on the same axle. As stated above, an endless rope drive operated all the nigger heads on a row of caissons. A 26-in driving sheave was attached to an ordinary hoisting engine equipped with a governor. The driving rope was in steel. It was wrapped twice around the driving sheave and once around the nigger head sheaves. These latter were 18 ins in diameter. For the hoists, 1 in. Manila rope was used. The other details, the bucket, hook, swivel block, etc., are made clear by the drawing. The platforms, tripods, etc., were of the standard dimensions and construction adopted by the contractors of the work. Detailed drawings of the standard platform are given by Fig. 57. One of these platforms contains about 1,000 ft. B.m. of lumber. As will be seen, all connections are bolted, no nails being used anywhere. A platform can thus be taken down and stored or shipped and erected again on another job with very little trouble. The plant described handled some 22,000 ids of excavated material on this work. Work was kept up night and day, working 3 8-hour shifts. It took an average of 35 shifts to excavate one row of caissons. No figures of the working force or the cost of excavation of this work are available. Mixing and placing concrete. The placing of the concrete in the excavated wells is done by means of tremies, or, which is more usual, by simply dumping it in from the top, workmen going down to distribute it. The manner of mixing the concrete and of handling it to the caisson varies, of course, with almost every job. As an example of the better arranged mixing and handling plants, the one used on the Cook County Courthouse work may be described. This plant is shown by the sketch, Fig. 58. Bins for the sand and stone were built at one side of the lot on the sloping bank. Their tops were level with the street surface, and their bottoms were just high enough to permit their contents to be delivered by chutes into one coup. YD. Cars. Wagons dumping through traps in the platform over the bin delivered the sand and stone. The sketches indicate the arrangement of the bins and mixer and the car tracks connecting them. The raw material cars were first run under the stone bin and charged with the required proportion of stone, and then to the sand bin, where the required proportion of sand was chuted on top of the stone. The loaded car was then hauled up the incline and dumped into the hopper, where cement and water were added. A no. 2.5 Smith mixer was used and discharged into cars which delivered their loads on tracks leading to the caissons. The same cars and portable tracks were used as had been used to handle the excavated material. In operation, a batch of raw materials was being prepared in the hopper while the previous batch was being mixed, and while the concrete car was delivering the still previous batch to the caissons. An average of 40 batches an hour mixed and put into the caissons was maintained with a force of 25 men. In all, some 17,000 ids of concrete were mixed and deposited. Fig. 58. Arrangement of concrete making plant, concrete pier construction, cost of caisson work. The following attempt to get at the cost of caisson work is based largely upon information obtained from Mr. John M. Ewan, John M. Ewan Co., Engineers and Builders, Chicago, Ill. Mr. Ewan says, "My experience has taught me that it is almost impossible to determine any definite data of cost for this work. This is due to the fact that no two caisson jobs will average the same cost, notwithstanding the fact that the cost of material used and the labor conditions are exactly the same. This condition is due to the great variety in texture of the soil gone through. For instance, it has come under my experience that in caissons of the same diameter on the same job, it required but 15 8-hour shifts to reach bedrock in some of these, while it required as many as 21 to 25 shifts to reach rock in the others, rock being at the same elevation. In fact, the digging all the way to rock in some was the best that could be wished for, while in the others boulders and quicksand were encountered, and the progress was slower, and the cost consequently greater. Again, we have known it to require 8 hours for 2 men to dig 8 ins. In hardpan in one caisson, while on a job going on at the same time and on the opposite corner of the street 2 men made progress of 2 ft. In 8 hours through apparently the same stuff, the depth of hardpan from grade being 61 ft, 6 ins. In both instances, and the quality of labor exactly the same. There have been more heavy losses among contractors due to the unexpected conditions arising in caisson digging than in any other item of their work. And I predict a loss to some of them that will be serious indeed, if an attempt be made to base future bids for caisson work entirely upon the data kept by them on past work. If a contractor is fortunate enough to find the ordinary conditions existing in his caisson work, and by ordinary conditions I mean few boulders, no quicksand, ordinary hardpan, and no gas, the following items may be considered safe for figuring caisson work. Figure that it will require from 22 to 25 shifts of 8 hours each to strike bedrock, bedrock being from 90 to 95 ft. Below datum, and datum being 15 ft. Below street grade, figure 2 diggers to the shift in all caissons over 5 ft. In diameter, 45 cts. Per hour for each digger, figure 1 top man at 40 cts. Per hour and 1 mucker or common laborer at 30 cts. Per hour for all caissons in which there are 2 diggers and 1 top man less if 1 digger is in the caisson, which condition exists generally in caissons less than 5 ft. In diameter, add the cost of in. Cable, tripods, sheaves, 1 in. Hawser laid line, nigger heads, ball-bearing blocks, etc. for rigging of the job. Lagging, which is 2 times 6 ins and 3 times 6 ins. Hemlock or some hard wood in length of 5 ft, 4 ins, and 4 ft. is priced all the way from $20 to $22, $50 and $21 to $24, 50 per m, ft, b, m, respectively. The price of caisson rings is $2, 40 per 100 pounds. The cost of specially made grubs for digging in hardpan is about $26 per dozen. Shovels are furnished by the diggers themselves in Chicago, Ill. The cost of temporary electric light is $10 per caisson. This includes cost of cable, lamps, guards, etc. Add the cost of or rental of engine or motors for power. Some engineers specify 3 rings to be used to each set of lagging below the top set until hardpan is reached, then 2 rings for each of the remaining sets from hardpan to rock. This is, of course, to ensure against disaster from great pressure of the swelling clay above the hardpan strata and may or may not be necessary. These rings are 3 times 3 ins. Wrought iron. For caissons which are not specified to go to rock, it is not considered economical to rig up cable setups, but rather to use windlass derricks. In this case, 1 in. Hawser-laid line is used as the means of hoisting the buckets of clay out of the caisson, as is the case in cable setups. Hand power being used on the windlass derricks instead of steam or electricity. The windlass derricks are made with 4 legs out of 6 times 6 in. Yellow pine lumber. The top piece is generally a piece of 3 times 6 in. Lagging. The cost of windlass and boxes is about $35 per dozen. Hooks for caisson buckets cost 45 CTS each. Caisson buckets cost $8 each. With the above approximate units as a basis, I have seen unit prices given per lineal foot in caisson work which ranged all the way from $12 to $16. 50 for 6 FT. Diameter caissons, larger and smaller sized caissons being graded in price according to their size. This unit price included rings, lagging, concrete, power, light, labor, etc. From the above data, the following figures of cost can be arrived at, assuming a 6 FT. Caisson, labor, per day. 2 diggers in caisson, at $3. $60 7. 21 top man at $3, 23, 21 mucker at $2, 42, 40, $12. 80 the depth sunk varies from 3.5 to 8 FT. Per 8-hour day depending on the material. Assuming an average of 4 FT, we have then 4 lin. FT of caisson or 2, 8 ku, ids. Excavated at a labor cost of $12. 80, which is at the rate of $3, 20 per lin, FT, or $4.57 per ku, YD. We now get the following per lin FT caisson 40 FT BM, 2 times 6 in, lagging at $25 $1. 00 60 pounds, iron 3 times 3 in, rings at 2.5 C, 150 7 ku, YD. Excavation at $4, 57 3, 20 7 ku, YD. Muck hauled away at $1 70 7 ku, YD. Concrete at $5 350, electric light 10, total $10, 00 if 3 times 6 in. Lagging is used add 50 CTS. Per lin. FT of caisson. Molding piles for driving. Piles for driving are molded like columns in vertical forms or like beams in horizontal forms. European constructors have a strong preference for vertical molding, believing that a pile better able to withstand the strain of driving is so produced. Such lamination as results from tamping and settling is, in vertical molding, in planes normal to the axis of the pile and the line of driving stress. Vertical molding has been rarely employed in America, and then only for molding round piles. The common belief is that horizontal molding is the cheaper method. In the ordinary run of work where comparatively few piles are to be made, it is probably cheaper to use horizontal molds, but where a large number of piles is to be made, the vertical method has certain economic advantages which are worth considering. Fig. 59. Plant for vertical molding of concrete piles. Vertical molding necessitates a tower or staging to support the forms and for handling and placing the concrete. An example of such a staging is shown by Fig. 59. To counterbalance this staging, horizontal molding necessitates a molding platform of very solid and rigid construction if it is to endure continued and repeated use. In the matter of space occupied by molding plant, vertical molding has the advantage. A tower 40 ft square will give ample space around its sides for 80 vertical forms for 12 in. Piles and leaves 1 ft of clear working space between each pair of forms. The ground area occupied by this tower and the forms is 1,764 sq.ft. With the same spacing of molds, a horizontal platform at least 25 times 160 ft equals 4,000 sq.ft would be required for the molds for the same number of piles 25 ft long. For round piles, vertical molding permits the use of sectional steel forms. Horizontal forms for round piles are difficult to manage. For square piles, vertical molding requires forms with 4 sides. Horizontal forms for square piles consist of 2 side pieces only, the molding platform serving as the bottom and no top form being necessary. Thus, for square piles, horizontal molding reduces the quantity of lumber per form by 50%. The side forms for piles molded on their sides can be removed much sooner than can the forms for piles molded on end, so that the form material is more often released for reuse. The labor of assembling and removing forms is somewhat less in horizontal molding than in vertical molding. Removing the piles from molding bed to storage yard for curing requires derricks or locomotive cranes in either case, and as a rule this operation will be about as expensive in plant and labor in one case as in the other. In the ease and certainty of work in placing the reinforcement, horizontal molding presents certain advantages. The placing and working of the concrete around the reinforcement is also easier in horizontal molding. Mixing and transporting the concrete materials, and the concrete is quite as cheap in vertical molding as in horizontal molding. If anything, it is cheaper with vertical molding, since the mixer and material bins can be placed within the tower or close to one side, where a tower derrick can hoist and deposit the concrete directly into the molds. Car tracks, cars, runways, and wheelbarrows are thus done away with in handling the concrete from mixer to molds. Altogether, therefore, the choice of the method of molding is not to be decided offhand. Driving molded piles. Driving molded concrete piles with hammer drivers is an uncertain operation. It has been done successfully even in quite hard soils, and it can be done if time is taken and the proper care is exercised. The conditions of successful hammer driving are perfect alignment of the pile with the line of stroke of the hammer, the use of a cushion cap to prevent shattering of the pile head, and a heavy hammer with a short drop. The pile itself must have become well cured and hardened. At best, hammer driving is uncertain, however. Shattered piles have frequently to be withdrawn, and the builder is never sure that fractures do not exist in the portion of the pile that is underground and hidden. The actual records of concrete pile work given in succeeding sections illustrate successful examples of hammer driving. The plant required need not vary from that ordinarily used for driving wooden piles, except that more power must be provided for handling the heavier concrete pile, and that means must be provided for holding the pile in line and protecting its head. Sinking concrete piles by means of water jets is in all respect a process similar to that of jetting wooden piles. Examples of jetting are given in succeeding section. In rare cases, driving shells or sheaths have been used for driving molded piles. Method and cost of molding and jetting piles for an ocean pier. In reconstructing in reinforced concrete the old steel pier at Atlantic City, N.J., some 116 reinforced concrete piles, 12 ins, in diameter, were molded in air and sunk by jetting. The piles varied in length with the depth of the water, the longest being 34.5 ft. Their construction is shown by Fig. 60, which also shows the floor girders carried by each pair of piles and forming with them a bent, and the struts bracing the bents together. In molding and driving the piles, the old steel pier was used as a working platform. Fig. 60. Concrete pile for pier at Atlantic City, N.J. The forms for the piles were set on end on small pile platforms located close to the positions to be occupied by the piles and were braced to the old pier. The forms were of wood, and the bulb point, the shaft, and the knee braces were molded in one piece. Round iron rods were used for reinforcement. The concrete was composed of 1 part vulcanite Portland cement, 2 parts of fine and coarse sand mixed, and 4 parts of gravel 1 in, and under in size. The mixture was made wet and was puddled into the forms with bamboo fishing rods, which proved very efficient in working the mixture around the reinforcing rods and in getting a good mortar surface. The concrete was placed in small quantities. It was mostly all hand mixed. The forms were removed in from 5 to 7 days, depending on the weather. The piles were planned to be sunk by water jet, and to this end had molded in them a 2-in jet pipe as shown. They were sunk to depths of from 8 ft to 14 ft into the beach sand. Water from the city water mains at a pressure of 65 pounds per SQ in was used for jetting. This water was furnished under special ordinance at a price of $1 per pile, and a record of the amount used per pile was not kept. The piles were swung from the molding platforms and set by derricks and block and fall. The progress of jetting varied greatly owing to obstructions in places in the shape of logs, old iron pipes, etc. In some cases, several days were required to get rid of a single pipe. In clear sand, with no obstruction, a 12-in pile could be jetted down at the rate of about 8 ft per hour, working 1 foreman and 6 men. The following is the itemized actual cost of molding and sinking a 26 ft pile with bulb point and knee braces complete. Forms cost per pile. Lumber 340 ft B.M. at $30, $10. 20. Labor carpenters at $2.50 per day, 12.00. Oil, nails, oakum, bolts, clamps, etc. 1. 20. $23, $40, 3. 90 times used 6. Reinforcement, 275 pounds of plain 3/4 in. Steel rods at 2 CTS per LB, $5.50. Preparing and setting 4/10 CT per LB, 1.10.6. 60 jet pipe, 26.5 ft of 2-in pipe at 10 CTS per FT in place, 2.65. Setting forms 6 men at $2.50 per day equals $15. Set 4 piles, 3.75. Material 90/100 cu. IDS gravel at $1.50 per YD, 135/45/100 cu. IDS sand at $1.50 per YD, 67, 150 BBLS. Cement at $1.62. 44. 42 labor, concrete and labor foreman 3.00. 6 laborers mixing and placing by hand $1.75 each, 10.50. $13.53. 38 average number of piles concreted per day. 4 removing forms. 4 men at $2.50. Remove and clean in half day. 4 columns. 1.25. 1 man at $2.25. Plastering column with cement grout. 4 per day. 56. Jetting 10 ft. Into sand. Foreman $3.00. 4 men $2.25 each, handling hose and traveler $9.00. $12.003. Average number of piles jetted per day. 4. City water pressure used for jetting at $1 per pile. 1.00. Superintendents at $5.00 per day. 1.25 caring for trestle, traveler, material, etc. 4.84 total cost per pile $36.60, the pile being 26 ft. Long, the cost in place was $1.41 per foot, subtracting the cost of sinking amounting to $7.09 per pile. We have the cost of a 26 ft. pile molded and ready to sink coming to about $1.10 per foot. It should be noted that this is the cost for a pile of rather complicated construction. A plain cylindrical pile should be less expensive. Method of molding and jetting square piles for a building foundation. The foundation covered about an acre. The soil was a deposit of semi-fluid mud and quicksand overlying a very irregular rock bottom and encircled by a ledge of rock. The maximum depth of the mud pocket was 40 ft, and interspersed were floating masses of hard pan. Soundings were made at the locations of all piles, or a half-in. Gas pipe was coupled to a hose fed by city pressure and jetted down to rock. The depth was measured, the sounding was numbered, and the pile was molded to length and numbered like the sounding. In all, 414 piles were required, ranging in length from 1.5 to 40 ft. All piles up to 6 ft. were built in place in wooden forms. The piles were 13 ins. Square and were of 1 to 2 of 4 concrete reinforced with welded wire fabric. A tin speaking tube was molded into each pile at the center. This tube was stopped about 10 ins from the head and by means of an elbow and threaded nipple projected through the side of the pile to allow of attaching a pressure hose. The piles were handled to the pile driver, the hose attached and water supplied at 100 pounds. Pressure by a pump, churning the pile up and down, aided the driving. A hammer was used to force the piles through the hard pan layers. A wooden follower was used to protect the pile head. A 2,800 lb. hammer falling 20 ft. did not injure the piles. One pile was given 300 blows with a 2,800 lb. hammer falling 12 ft. and when pulled was unbroken. It was found that 30 ft. piles and under could be picked up safely by one end. Longer piles cracked at the center when so handled. These long piles were successfully handled by a long chain, one end being wrapped around the pile at the center, and the other end similarly wrapped near the head. The hook of the hoisting fall was hooked into the loop of the chain, and as the pile was hoisted, the hook slipped along the chain toward the top, gradually upending the pile. The piles weighed 175 pounds per lin. ft. It was attempted to mold the piles directly on the ground by leveling it off and covering it with tar paper, but the ground settled and the method proved impracticable. Method of molding and jetting piles for building foundations. In a number of foundations, Mr. Frank B. Gilbreth has used a polygonal pile, either octagonal or hexagonal, with the sides corrugated or fluted as indicated in Fig. 61. In longitudinal section, these piles have a uniform taper from butt to point and have flat points. Each pile is cored in the center, the core being 4 ins. in diameter at the top and 2 ends at the bottom end. On each of the octagon or hexagon sides, the pile has a half-round flute, usually from 2½ to 3 ends. In diameter, the principal object of these flutes or corrugations is to give passage for the escape to the surface of the water forced through the center core hole in driving the pile. They are also for the purpose of increasing the perimeter of the pile and thereby gaining greater surface for skin friction. The piles are reinforced longitudinally and transversely. On this particular job, the reinforcement was formed with Clinton electrically welded fabric, the meshes being 3 ends times 12 ends, the longer dimension being lengthwise with the pile and of no 3 wire, the horizontal or transverse reinforcement being of no 10 wire. The meshes being electrically welded together, the reinforcement was got out from a wide sheet taking the form of a cone. No part of the reinforcement was closer than 1 in from the outside of the concrete. In general, only sufficient sectional area of material is put in the reinforcement to take the tensile stresses caused by the bending action when handling the pile preparatory to driving. More reinforcement than this only being necessary when the piles are used for wharves, piers, or other marine structures, where a considerable length of pile is not supported sidewise or when they are subjected to bending stresses. Fig. 61. Cross-section of corrugated reinforced concrete pile. Molding. The forms for molding the piles are made from 2 in stuff, gotten out to the required dimensions, the corrugations being formed by nailing pieces on the inside whose section is the segment of a circle. The sides of the octagon are fastened to the ends through which the core projects some 6 or 8 ends. At times, while the molding of the pile is in progress, the central core is given a partial turn to prevent the setting of the cement holding it fast, and thereby preventing the final removal. The stripping of the forms from the piles is usually done from 24 to 48 hours after molding, and from this time on great care is taken that there is a sufficient amount of moisture in the pile to permit of the proper action for setting of the cement. This is usually accomplished by covering the piles over with burlaps and saturating with water from a hose, the operation of driving the pile not being attempted until the concrete is at least 10 days old. Driving. The operation of driving corrugated concrete piles is somewhat similar to that for driving ordinary wooden piles by water jet, but a much heavier hammer with less drop is used. The jetting is accomplished by inserting a 2 in pipe within the pile. This pipe is tapered at the bottom end to 1 in diameter, forming a nozzle, and the water pressure used is about 120 pounds per SQ. As a rule, this pressure is obtained by the use of a steam pump which may be connected with the boiler which operates the pile driver or with a separate steam supply. At the upper end of this 2 in pipe an elbow is placed and a short length of pipe is connected to this and to the hose from the water supply. Fig. 62. Cushion cap for driving Gillette corrugated pile. As it is not practicable to drop the hammer directly on the head of the concrete piles, the driving is accomplished by the use of a special cap. Fig. 62. This cap is about 3 ft. in height and the bottom end fits over the head of the pile. In one side of this cap is a slot from the outside to the center, which permits the 2 in pipe, which supplies the water jet for driving the pile to project. The outside of this cap is formed with a steel shell. The inside has a compartment filled with rubber packing, and the top has a wooden block which receives a blow from the hammer. In this way, the head of the pile is cushioned, which prevents the blow of the hammer from bruising or breaking the concrete. During the operation of driving, the water from the jet comes up on the outside of the pile and carries with it the material which it displaces in driving. This, with the assistance of the hammer, allows the pile to be driven in place, and contrary to what might be supposed, after the operation of driving when the water has saturated into the ground or been drained away, this operation puddles the earth around the pile, so that after a few hours' time the skin friction is much more than it would be with the pile driven into more compact soil without the use of a jet. Fig. 63. View showing method of fabricating reinforcement for a round pile with flattened sides. Method of molding and driving round piles. In constructing a warehouse at Bristol, England, some 600 spirally reinforced piles of the coignet type were used. Coignet piles are in section circles with 2 longitudinal flat faces to facilitate guiding during driving. This section is the same as would be found by removing 2 thin slabs from opposite sides of a timber pile. The reinforcement consists of longitudinal bars set around the periphery and drawn together to a point at one end, and then inserted into a conical shoe. These longitudinal bars are wound spirally with a quarter-in rod wire tied to the bars at every intersection. This spiral rod has a pitch of only a few inches, but to bind it in place and give rigidity to the skeleton, it is wound by a second spiral with a reverse twist and a pitch of 4 or 5 ft. As thus constructed, the reinforcing frame is sufficiently rigid to bear handling as a unit. The piles used at Bristol were 14 to 15 ins in diameter and 52 ft. long, and weighed about 4 tons gross each. The mixture used was cement, river sand, and crushed granite. Molding. In molding coignet piles, the reinforcement is assembled complete, as shown by Fig. 63, and then suspended as a unit in a horizontal mold constructed as shown by the cross-section Fig. 64. The concrete is deposited in the top opening and rammed and worked into place around the steel, after which the opening is closed by the piece A. After 24 hours, the curved side pieces B and C are removed, and the pile is left on the sill D until hard enough to be shifted. A pile is considered strong enough for driving when about 6 weeks old. Fig. 64. Form for molding round pile with flattened sides. Driving. Coignet piles at the Bristol work were handled by a traveling crane. The material penetrated was river mud, and they were driven with a hammer weighing 2 tons gross. In driving, the pile head was encircled by a metal cylinder into which fitted a wooden plunger or false pile, with a bed of shavings and sawdust between plunger and pile head, molding and driving square piles for a building foundation. The Dittman factory building at Cincinnati, O, is founded on reinforced concrete piles varying from 8 to 22 ft. in length. The piles were square in cross-section with a 2-in. Bevel on the edges, a 16 ft. Pile was 10 ins. Square at the point and 14 ins. Square at the head, shorter or longer piles had the same size of point, but their heads were proportionally smaller or larger, since all piles were cast in the same mold by simply inserting transverse partitions to get the various lengths. Each pile was reinforced by 4 3/4 in. Twisted bars, 1 in each corner, bound together by a quarter-in hoops every 12 ins. The bars were bent in at the point and inserted in a hollow pyramidal cast iron shoe weighing about 50 pounds. The concrete was a 1 to 2 to 4 stone mixture, and the pile was allowed to harden 4 weeks before driving. They were cast horizontally in wooden molds which were removed after 30 hours. Driving, both because of their greater weight and because of the care that had to be taken not to shatter the head, it took longer to adjust and drive one of these concrete piles than it would take with a wooden pile. The arrangement for driving the piles was as follows. A metal cap was set over the head of the pile. On this was set the guide cap having the usual wood deadener, and on this was placed a wood deadener about 1 ft long. The metal cap was filled with wet sand to form a cushion, but as the pile head shattered in driving, the sand cushion was abandoned and pieces of rubber hose were substituted. With this rubber cushion, the driving was accomplished without material damage to the pile head. The hammer used weighed 4,000 pounds, and the drop was from 4 to 6 ft. The blows per pile ranged from 60 up, the average being about 90. In some cases where the driving was hard, it took over 400 blows to drive a 14 ft pile. An attempt to drive one pile with a 16 ft drop resulted in the fracture of the pile. Method of molding and driving octagonal piles. The piles were driven in a sand fill 18 ft deep to form a foundation for a track scales in a railway yard. They were octagonal and 16 ins. Across the top, 16 ft, long and tapered to a diameter of 12 ins. At the bottom, they were also pointed for about a foot. The reinforcement consisted of 4½ in Johnson corrugated bars spaced equally around a circle concentric with the center of the pile, the bars being kept 1½ ins from the surface of the concrete. A No. 11 wire wrapped around the outside of the bars secured the properties of a hooped concrete column. The piles were cast in molds laid on the side. They were made of 1/4½ gravel concrete and were seasoned at least 3 weeks before being driven. An ordinary derrick pile driver with a 2,500 lb hammer falling 18 ft was used in sinking them. A timber follower 6 ft long and banded with iron straps at both ends was placed over the head of the pile to receive directly the hammer blows. The band on the lower end was 10 ins, wide and extended 6 ins, over the end of the follower. In this 6 in space, a thick sheet of heavy rubber was placed, coming between the head of the pile and the follower. Little difficulty was experienced in driving the piles in this manner, although 250 to 300 blows of the hammer were required to sink each pile. The driving being entirely through fine river sand, there is every probability that any kind of piles would have been driven slowly. The heads of the first 4 or 5 piles were battered somewhat, but after the pile driver crew became familiar with the method of driving, no further battering resulted and the heads of most of the piles were practically uninjured. Fig. 65. Cross-section of Chenoweth rolled pile. Fig. 66. Diagram showing method of rolling Chenoweth pile. Method and cost of making reinforced concrete piles by rolling. In molding reinforced concrete piles exceeding 30 or 40 ft in length, the problem of molds or forms becomes a serious one. A pile mold 50 or 60 ft long is not only expensive in first cost, but is costly to maintain because of the difficulty of keeping the long lagging boards from warping. To overcome these difficulties, a method of molding piles without forms has been devised and worked out practically by Mr. A.C. Chenoweth of Brooklyn, N.Y. This method consists in rolling a sheet of concrete and wire netting into a solid cylinder on a mandrel by means of a special machine. Fig. 65 is a sketch showing a cross-section of a finished pile, in which the dotted line shows the wire netting, the hollow circle is the gas pipe mandrel, and the solid circles are the longitudinal reinforcing bars. Fig. 67. Machine for rolling Chenoweth piles. In making the pile, the netting is spread flat, with the reinforcing bars attached as shown at A, Fig. 66, and is then covered with a layer of concrete. One edge of the netting is fastened to the platform, the other edge is attached to the winding mandrel. The winding operation is indicated by sketch B, Fig. 66. Fig. 67 shows the machine for rolling the pile. It consists of a platform and a roll. The platform is mounted on wheels and is so connected up that it moves back under the roll at exactly the circumferential speed of the roll. Thus, the forming pile is under constant heavy pressure between the roll and platform. When the pile has been completely rolled, it is bound at intervals by wire ties. The wire for these ties is carried on spools arranged under the edge of the platform at intervals of 4 ins. For the first 10 ft. From the point, and of 6 ins. For the remainder of the length, the binding is done by giving the pile 2 or 3 extra revolutions, and then cutting and tying the wire. Then by means of a long removable shelf which contains the flushing mortar. As the pile revolves, it becomes coated on the outside with a covering that protects the ties and other surface metal. Finally, the pile is rolled onto a suitable table to harden. An exhibition pile rolled by the process described is 61 ft, long and 13 ins. In diameter, this pile was erected as a pole by hoisting with a tackle attached near one end and dragging the opposite end along the ground exactly as a timber pole would be erected. It was also suspended free by a tackle attached at the center. In this position, the ends deflected 6 ins. Neither of these tests resulted in observable cracks in the pile. The pile contains 8 1-in diameter steel bars 61 ft, long 1 2½ in. Pipe also 61 ft, long 366 sq ft or 46 sq, ids, a ½ in, mesh 14B and S, gauge wire netting and 2 cu ids, loose concrete. Its cost for materials and labor was as follows. Materials, gravel, 28. 8 cu ft at $1 per cu yd. $1. 05 sand 19. 8 cu ft at $1 per cu yd. 73 cement 3 bbls at $1. 60 per bbl. 4. 80 netting 46 sq ids at 17½ cts per sq yd. 7. 10 rods wire etc. 1,826 pounds at 2½ cts per lb. 45 65 total $59. 33 mixing 2 cu ids concrete 4 men 1 hour at 15 cts per hour. $0. 60 placing concrete and netting 4 men 30 mins at 15 cts per hour. 30 winding pile 4 men 20 mins at 15 cts per hour. 20 removing pile 4 men 10 mins at 15 cts per hour. 10. $1. 20 grand total $60. 53. This brings the cost of a pile of the dimensions given to about $1 per lin. Ft. Chapter 38. The construction problem in building concrete structures of massive form and volume is chiefly a problem of plant arrangement and organization of plant operations. In most such work, form construction is simple and of such character that it offers no delay to placing the concrete as rapidly as it can be produced. The same is true of the character of the structure. It is seldom necessary for one part of the work to wait on the setting and hardening of another part. As a rule, there is no reinforcement to fabricate and place, and where there is, it is of such simple character as not to influence the main task of mixing, handling, and placing concrete. Stated broadly, the contractor in such work generally has a certain large amount of concrete to manufacture, transport, and deposit in a certain space, with nothing to limit the rapidity of these operations, except the limitations of plant capacity and management, installation and operation of mixing and conveying plant, then are matters to be considered carefully in heavy concrete work. In the following sections, we have given one or more examples of nearly every kind of heavy concrete work excepting bridge foundations and retaining walls, which are considered in chapters Roman 12 and Roman 13, and except rubble concrete work, which is considered in chapter VI. In each case, so far as the available records made it possible, we have given an account of the plant used and of its operation. Fortification work. Concrete for fortification work consists very largely of heavy platforms and walls for gun foundations and enclosures, and of heavily roofed galleries and chambers for machinery and ammunition. The work is very massive and in the majority of cases of simple form. A large number of data are to be found in the reports of the Chief of Engineers, USA, on all classes of fortification work, but the manner in which they are recorded makes close analysis of relative efficiencies of methods or of relative costs almost impossible. The following data are given, therefore, as examples that may be considered fairly representative of the costs obtained in fortification work done under the direction of Army engineers. These data are not susceptible of close analysis because wages, working force, outputs, etc. are nearly always lacking. Gun emplacements, Staten Island, and Y. The work comprised 5,609 ids of concrete in 212-in gun emplacements and 3,778 ids of concrete in 26-in gun emplacements. Concrete was mixed in a revolving cube mixer with the exception of 809 ids in the 6-in emplacements which were mixed by hand at a cost of 56 CTS, more per cubic yard than machine mixing cost. The body of the concrete was a 1 to 3 to 5 Portland cement, beach sand and broken trap rock mixture. The floors and upper surface of the concrete had a pavement consisting of 6 ins. Of 1 to 3 to 5 concrete surfaced with 2 ins. Of 1 to 3 mortar. Wages are not given, but for the time and place should have been about $1.50 per 8-hour day for common labor. The cost of materials was Alpha Portland cement per BBL, $1.98 broken trap rock per YD, 0, 8112-in, emplacement hauling sand per YD, 0, 175 6-in. Emplacement hauling sand per YD, 0, 20. The cost of the concrete in place was as follows: body concrete, 12-in per YD, 6-in per YD, cement at $1.98 per BBL, $2, 546 $2, 546 broken stone at 81 CTS per YD, 1. 0.41 0.41 sand at 17.5 and 20 CTS per YD, 0 225 0 257 receiving and storing materials at 11 6 CTS per YD and 8 4 CTS per BBL, 0 149 0 180 mixing, placing and ramming, 0 879 110 forms, lumber and labor, 0 477 0 950 superintendents and miscellaneous, 0 190 0 150 total $5 507 $6 234 concrete pavement materials, $2 97 $3 06 labor, 4 63 4 72 total $7 $67 78 fig 68 sketch plans of concrete making plant for mortar battery platform. Mortar Battery Platform, Tampa Bay, Fla. The platform contained 8,994 ids of concrete composed of a mixture of Portland cement, sand, shells, and broken stone. The broken stone and cement were brought in by vessel, and the sand and shells were obtained from the beach nearby. The plant for the work was arranged as shown by the sketch, Fig. 68. Sand, stone, and shells were stored in separate compartments in the storage bins. Box cars divided into compartments of such size that when each was filled with its proper material, the car would contain the proper proportions for one batch of concrete, were pushed by hand under the several compartments of the bin in succession until charged. Then they were hooked to a cable and hauled to the platform over the mixer and dumped. The charge was then turned over with shovels and shoveled into the hopper of a continuous mixer, located beneath. 2 cars were used for charging the mixer, running on separate tracks as shown. The mixer discharged into buckets set on flat cars, which were hauled by mules under the cableway, which then lifted and dumped the bucket and returned it empty to the car. By using 3 bucket cars, one was always ready to receive the mixer discharge as soon as the preceding one had been filled, so that the mixer operated continuously. The cableway had a working span of 270 ft, the cable being carried by traveling towers 69 ft high. The cableway was very easily operated back and forth along the work. The cableway complete with 497 ft of 6-rail track for each tower cost $4,700. The cost of materials and labor for the 8,994 ids of concrete was as follows: per YD 1 BBL, cement at $2, 46 $2, 46 0, 89 YD, stone at $2, 95 2, 622 0, 315 YD, shells at $0, 45 0, 142 0, 51 YD, sand at $0, 12 0, 062 mixing and placing 0, 693 total $5, 979 the above batch tamped in place to 30 ft, or 1:1/9 ids, which gives the cost as follows: per YD, cost of concrete tamped in place $5, 381 cost of form work 0, 370 total cost $5, 751 in the preceding prices of cement and stone 59 CTS and 29 CTS per cubic yard respectively are included for storage. The costs of sand and shells are costs of screening and storing. Rough lumber for forms cost $10, 25 and dressed lumber $12, 75 per m. FTBM. Emplacement for battery, Tampa Bay, Fla. The emplacement contained 6,654 ids of Portland cement, sand, shells, and broken stone concrete. The plant arrangement is shown by Fig. 69. The sand and shells were got near the site, using an inclined cableway running from a 40 ft. Mast near the mixer to a deadman at the shell bank. All the sand for the fill around the emplacement was obtained in the same way. The other materials were brought by vessel to a wharf, loaded by derrick onto cars operated by an endless cable, and taken to the work. The storage bins and mixing plant were operated much like those for the mortar battery work previously described. A cube mixer was used, and the concrete was handled from it to the work by a crane derrick covering a circle of 100 ft in diameter. The cost of materials and concrete was as follows: cement plus 7 CTS. For storage per BBL, $2, 532 stone plus 38 CTS. For storage per YD, 3, 047 shells excavating and storage, 481 sand excavating and storage, 250 lumber rough per m. FTB M 1025 lumber dressed per m. FTB M 1275 Fig 69. Sketch plans of concrete making plant for battery emplacement. A batch made up as follows, tamped in place to a volume of 30 cu ft, or 1:1/9 cu ids, 1 bbl. Cement at $2, $532, $2, 532 315 cu. YD. Shells at $0, 481, 151 51 cu. YD. Sand at $0, 25, 130 89 cu. YD. Stone at $3, 47, 2, 710 mixing and placing, 761, total for 30 cu. FT. $6. 284. This gives a cost per cubic yard of concrete in place as follows. Concrete in place per cu. YD. $5. 655 forms per cu. YD of concrete. 220. Total cost of concrete per cu. YD. $5. 875 United States fortification work. The following methods and cost of mixing and placing concrete by hand and by cubical mixes is given by Mr. L. R. Grabel for U.S. government fortification work done in 1899. Hand mixing and placing. The work was done by contract, using a 1 cement, 2 sand, 2 pebbles and 3 stone mixture turned 4 times. A board large enough for 3 batches at a time was used. 1 batch was being placed, 1 being mixed, and 1 being removed at the same time so that the mixes moved without interval from one to the other. 2 gangs were worked, each mixing 64 batches of 75 cu. YD, or 48 cu. Ids of concrete per day at the following cost. Hand mixing 9,000 cu. Ids per day per cu. YD. 6 men wheeling materials $7, $50. 16 8 men mixing 10, 000. 21 8 men wheeling away 10, 000. 21 6 men placing and ramming 7, 50. 16 1 pump man 1, 25 0, 2 1 water boy 1, 0 2 1 foreman 2, 0 4, totals $39, $25. 82. The entire cost of plant for this work was about $500. Machine mixing and placing. The concrete was mixed in a 4FT cubical mixer operated by a 12 HP engine which also hauled the material cars up the incline to the mixer. These cars passed by double track under the material bins where the compartments of the car body were filled through trap doors. They then passed the cement house where the cement was placed on the load, then up the incline to the mixer and dumped, and then emptied down an opposite incline. 7 turns of the mixer mixed the charge, which was discharged into iron tubs on cars hauled by horses to 2 derricks whose booms covered the work. 1 gang by day labor mixed and placed 168 batches of 7 cu. YD, or 117, 6 cu. Ids per day at the following cost. Machine mixing 4,000 cu. Ids per day per cu. YD. 32 men at $1, $25 $40, $000. 34 1 pumpman 1, 25 0, 1 teamster and horse 2, 000. 022 water boys at $1 2, 000. 021 engineman 1, 70 021 derrickman 1, 50 011 fireman 1, 50 011 Foreman 2, 88003 Fuel cement barrels largely 1, 25001 totals $54, $080. 47 The cost of the plant was about $5,000, Fig. 70. Concrete making plant for constructing Lock Walls, Cascades Canal, Lock Walls, Cascades Canal. 4/5 or 70,000 ids of Lock masonry was concrete, the bulk of which was mixed and deposited by the plant shown by Fig. 70. The concrete was Portland cement, sand, gravel, and broken stone. Cement was brought in barrels by railway, stored and tested. From the storehouse, the barrels were loaded onto cars and taken 250 ft. to a platform onto which the barrels were emptied, and from which the cement was shoveled into the cement hopper and chuted to cars which took it to the charging hopper of the mixer. The stone was crushed from spalls and waste ends from the stone cutting yards, where stone for wall lining and coping and other special parts was prepared. These spalls and ends were brought in cars and dumped into the hopper of a No. 5 gates crusher with a capacity of 30 tons per hour. From the crusher, the stone passed to a 2.5 screen, the pieces passing going to a bin below and the rejections going to a smaller Blake crusher and thence to the bin. The dust and small particles were not screened out. The sand and gravel were obtained by screening and washing pit gravel. The gravel was excavated and brought in cars to the washer. This consisted of a steel cylinder 2 ft, 6.5 ins, in diameter and about 18 ft, long, having an inclination of 1 in per foot. An axial gudgeon supported the cylinder at the lower end, and it rested on rollers at the other end and at an intermediate point. The gravel was fed by hopper and chute into the upper end, and into this same end a 3 in perforated pipe projected and extended to about mid-length of the cylinder. The cylinder shell was solid and provided with internal fins for about half its length from the feed end. For the remainder of its length nearly to the end, the shell was perforated with 2.5 in holes for a length of 4 ft. Beyond midpoint it was encircled by a concentric screen of in holes, and this screen for 3 ft. of its length was encircled by another screen of 30 meshes to the inch. The pit mixture fed into the cylinder was gradually passed along by the combined inclination and rotation, being washed and screened in the process. The sand fell into one bin and the gravel into another, and the waste water was carried away by a flume. The large stones passed out through openings at the lower end of the shell and were chuted into cars. The cars came to the mixer as clearly shown by Fig. 70. The stone and gravel cars were side dump and the cement car was bottom dump. The mixers were of the cube type 4 ft, on each edge and operated by a 7 × 12 in double-cylinder engine at 9 revolutions per minute. The usual charge was 32 ft of the several ingredients, and it was found that 15 revolutions requiring about 1.5 minutes were sufficient for mixing. The average work of one mixer was 17 batches, or about 13 ids per hour, but this could be speeded up to 20 batches per hour when the materials were freely supplied and the output freely removed. 2 cars took the concrete from the mixer to the hopper, from which it was fed to the work by chute. The hopper was mounted on a truck, and the chute was a wrought iron cylinder trussed on 4 sides and having a 45 degrees elbow at the lower end to prevent scattering. The chute fed into a car running along the wall and distributing the material. It was found impracticable to move the chute readily enough to permit of feeding the concrete directly into place. As the concreting progressed upward, the trestle was extended, and the chute shortened. It was found that wear would soon disable a steel chute, so that the main truss cylinder had a smaller, cheaply made cylinder placed inside as a lining to take the wear and be replaced when necessary. The plant described worked very successfully. Records based on 9,614. 4 ids of concrete laid gave the following ids. Concrete mixed by hand 1,777. 0 concrete mixed by machine 7,837. 4 total concrete laid 9,614. 4 concrete placed by derricks 2,372. 0 concrete placed by chute 7,242. 4 concrete 1 to 2 to 4 mixture 156. 0 concrete 1 to 3 to 6 mixture 1,564. 0 concrete 1 to 4 to 8 mixture 6,892. 0 the average mixture was 1 cement 3, 7 sand 4, 8 gravel and 2, 6 broken stone. The average product was 241 ids concrete per barrel of cement and 116 ids of concrete per cubic yard of stone and gravel. The average materials for 1 yd of concrete were cement 0, 805 bbl, sand 0, 456 yd, gravel 0, 579 yd, and stone 0, 317 yd. The cost of these 9,614 4 ids of concrete in place was hand-mixed and placed by derrick per yd. Labor mixing 1,777 ids $1,072 repairs, fuel, etc. 0. 16 total cost mixing $1,088 labor placing 2,372 ids 0. 60-25 fuel, tramways, etc. 0. 1958 total cost placing $0. 79.83 machine mixed and placed by chute. Labor mixing 7,837 ids $0. 388 repairs, fuel, etc. 0. 046 total cost mixing $0. 434 labor placing 7,242 ids 0. 414 fuel, tramways, etc. 0. 045 total cost placing $0. 459 materials and supplies 9,614 ids. Timbering $0. 145 cement 3. 289 sand and gravel 1. 073 broken stone 0. 536 cement testing, repairs, etc. 0. 223 total $5,266 plant and superintendents. 9,614 ids. Engineering, superintendents, repairs, etc. $1,508 20% cost of plant 0. 165 total $1,673. The comparative cost of hand and machine mixing and handling was thus. Item, hand, machine, mixing per yd, $1, $0.88. 434 placing per yd, 0, 798 0, 459 materials, etc. per yd, 5, 466 5, 466 plant, etc. per yd, 1, 673 1, right. Totals $9, $0.25 $8, $0.32. The average total costs of all the concrete placed were mixing per yd, $0, 555 placing per yd, 0, 543 materials per coup, YD. 5. 266 plant, etc. per coup, YD 1. 673, total $8. 037, Locks, Coosa River, Alabama. The following methods and costs are given by Mr. Charles Firth for constructing Loch No. 31 for the Coosa River Canalization, Alabama. This lock is 420 ft, long overall 322 ft, between quoins 52 ft, clear width 14, 7 ft, lift and 8 ft. Depth of water on sills, it contained 20,000 ids of concrete requiring 21,500 bbls. Cement half Alson and half Atlas. Figure 71 shows the concrete mixing plant consisting of two 4x4 ft cube mixer driven by a 10x16 engine. The top floor of the mixer house stored the cement 2,000 bbls. The concrete was a 1 to 3 to 5 a half stone mixture. Each mixer charge consisted of 3 ft. Cement 9 ft, sand and 16, 5 ft, stone. The charge was turned over 4 times before and 6 times after watering at a speed not exceeding 8 revolutions per minute. The average output of the plant was 200 ids per 8-hour day or 100 ids per mixer, but it was limited by the means for placing. Fig. 71. Concrete mixing plant for lock construction, Coosa River, Alabama. The concrete was mixed dry, deposited in 6 to 8 tin layers and rammed with 30 lb. Iron rammers with 6 in. Square faces for all exposed surfaces, a 6 in. Facing of 1 to 3 mortar was placed by setting 2 times 12 in, planks 4 ins. From the laggings being kept to distance by 2 times 4 in. Spacers, placing and ramming the concrete behind them, then withdrawing them, filling the 6 in space with mortar and tamping it to bond with the concrete. The walls were carried up in lifts, each lift being completed entirely around the lock before beginning the next. The first lift was 7 ft. high and the others 6 ft, except the last, which was 5 ft, exclusive of the 18 in coping. The coping was constructed of separately molded blocks 3 ft long, made of 1 to 2 to 3 concrete faced with 1 to 1 mortar and having edges rounded to 3 ins. Radius. In constructing the forms, a row of 6 times 8 tin posts 24 ft long and 5 to 7 ft apart was set up along the inside of each wall, and a similar row of posts 12 ft long was set up along the outside. From the tops of the short posts 6 times 8 tin caps reached across the wall and were bolted to the long posts. These caps carried the stringers for the concrete car tracks. The lagging consisted of 3 times 10 in planks dressed on all sides. The backs of the walls were stepped, and as each step was completed, the rear 12 ft posts were lifted to a footing on its top and carried in the necessary distance. The front posts remained undisturbed until the wall was completed. The lagging was moved up as the filling progressed. As no tie bolts were permitted, these forms required elaborate bracing. From the mixing plant, which was located on the bank above reach of floods, the concrete cars were dropped by elevator to the level of the track over the walls, and then run along the wall and dumped onto platforms inside the forms and just below the track. This arrangement was adopted because it was found that even a small drop separated the stone from the mortar. The concrete was shoveled from the platforms to place and rammed. The cars were bottom dumping with a single door hinged at the side. This door, when swinging back, struck the track stringers and jarred the form so that constant attention was necessary to keep it in line. It would have been much better to have had double doors swinging endwise of the car. Another point noted was that unless the track was high enough to give good head room at the close of a lift, the placing and ramming were not well done. The cost of 8,710 ids of concrete placed during 1895 by day labor employing Negroes at $1 per 8-hour day was as follows per cubic yard. 1 bbl. Cement $2, 48.0, 88 yd. Stone at $0, 76.0, 67.0, 36 yd. Sand at $0, 34.0. 12 mixing, placing, and ramming 0, 88 staging and forms 0, 42 total $4. 57 lock walls, Illinois and Mississippi Canal. The locks and practically all other masonry for the Illinois and Mississippi Canal are of concrete. The following account of the methods and cost of doing this concrete work is taken from information published by Mr. J. W. Wowerman in 1894, and special information furnished by letter. The decision to use concrete was induced by the fact that no suitable stone for masonry was readily available. The local stone was a flinty limestone, usually without bed, or, at best, in thin irregular strata, and cracked in all directions with the cracks filled with fire clay, while good sand and gravel and good stone for crushing were plentifully at hand. The concrete work done in 1893-4 comprised dam abutments, piers for Taintor gates and locks. Dam abutments. 4 dam abutments were constructed, 3 of which were L-shaped with sides next to the river 40 ft. Long and sides extending into the banks 20 ft. Long, the top thickness was 3 ft. The faces were vertical and the backs stepped with treads of 14 to 16 ins. And the width of base was 0, 4 of the height. Each of these abutments was built in 430 yd. Sections, each section being a day's work. The forms consisted of 2 times 8 in. Planks dressed on both sides 2 times 8 in, studs spaced 2 ft on centers and 4 times 6 in. Braces. For the first 2 of the 4 abutments, the forms were erected in sections, the alternate sections being first erected and filled. When these sections had hardened, the forms were shifted to the vacant sections and lined up to and braced against the completed sections. This method did not give well-aligned walls, so in subsequent work, the forms were erected all at once. The concrete was mixed by hand. The sand and cement were mixed dry, being turned 4 times and spread in a lay of pebbles and broken stone previously wetted were spread over the sand and cement, and the whole turned 4 times, the last turn being into wheelbarrows. About 5 common buckets of water were added during the mixing. The mixture sought was one that would ram without quaking. 2 forms of rammers were used. For work next to forms, a 4 times 6 in rammer, and for inside work 6 in diameter circular rammer weighing 20 pounds. The gang mixing and placing concrete consisted usually of item per day per yd 2 handling cement and sand $3 $0 10 3 filling barrows with aggregate 4 50 15 8 mixing concrete 12 0 42 shoveling concrete into barrows 3 0 10 5 wheeling concrete to forms 7 50 25 1 spreading concrete 1 50 0 5 5 tamping concrete 7 50 25 total 26 men $39 $1 30. These cubic yard costs are based on 30 ids of wall completed per 8-hour day. The cost in detail of 2 abutments containing 254 IDS was per cubic yard as follows. Item, per cu YD, 165 BBLS, Portland, Germania, cement $5.60, 5 cu YD, crushed stone 2.070, 24 cu YD, gravel 0.59, 53 cu YD, sand 0, 24 lumber, forms, warehouses, platforms D0, 55 carpenter workey, $9 per m. 1, 10 mixing and placing 1, 47 20%, first cost of plant 0, 31 engineering and miscellanies 0, 31, total $12. 24D charging a quarter of first cost of $18 per m. FTE carpenters $3, 50 laborers $1, 50 per day. There was 1 laborer to 2 carpenters. The large amount of cement 165 BBLS per cubic yard was due to facing the abutments with 8 ins of 1 to 2 mortar. The concrete in the body of the wall was 1 cement, 2 sand, 2 gravel, and 2 broken stone mixture. A dry mixture was used, and this fact is reflected in the cost of ramming, 25 CTS per cu YD. The cost of mixing was also high, Fig. 72. Concrete mixing plant for lock walls, Illinois and Mississippi Canal, piers for Taintor gates. The masonry at this point consisted of 3 piers 6 times 30 FT, and 2 abutments 30 FT, long 6 FT, thick at base and 4 FT, thick at top with wing walls. It amounted to 460 cu IDS. The feet of the inclined braces were set into gains in the horizontal braces and held by an 8-tin lag screw. After the posts were plumbed, a block was lag screwed at the upper end of each brace. These forms proved entirely satisfactory. The cost of the work per cubic yard was as follows. Item, per cu YD, 145 BBLS, Portland cement $4, 330 55 cu YD, crushed stone 0, 604 252 cu YD, pebbles 0, 328 465 cu YD, sand 0, 419 40,000 FT. BM lumber, a quarter cost of $16 per m. 0, 348 carpenter work on forms 0, 780 mixing and placing concrete 1, 909 20%, cost of plant 0, 090 miscellaneous 0, 182, total $8.99. Mixing plant. The concrete for all the lock work of 1893 to 4 was mixed by the plant shown by Figs. 72 and 73. The mixer plant proper consisted of a king truss carried by 2 A-frames of unequal height. Under the higher end of the truss was a frame carrying a 4 FT cubical mixer, and under the lower end a pit for a charging box holding 40 cu FT. This charging box was hoisted by a half-in steel cable running through a pair of double blocks as shown. The slope of the lower chord of the truss was such that the cable hoisted the box and carried it forward without the use of any latching devices. On 2 sides of the pit were tracks from the sand and stone piles, and on the other 2 sides were the cement platform and water tank. The charging box dumped into the hopper above the mixer, and the mixer discharged into cars underneath. A 15 HP engine operated the hoist by 1 pulley and the mixer by the other pulley. 9 revolutions of the mixer made a perfect mixture. The plant as illustrated was slightly changed as the result of experience in constructing the guard lock. The charging hopper was lowered 6 ins, and the space between the mixer and lower platform reduced by 9 ins. Diagonal braces were also inserted under the timbers carrying the mixer axles. This plant cost for framing and erection $300, and for machinery delivered $706. The crushing plant shown by Fig. 73 consisted of a No. 2 gates crusher delivering to a bucket elevator. Fig. 73. Stone crushing plant for lock walls, Illinois and Mississippi Canal. Fig. 74. Forms for guard lock, Illinois and Mississippi Canal. Guard lock. The forms employed in constructing the guard lock are shown by Fig. 74, and in this drawing the trestle and platform for the concrete cars are to be noted. The walls were concreted in sections. A batch of concrete consisted of 1 BBL. Cement, 10 cu, ft, sand and 20 cu, ft, crushed stone. The average run per 8-hour day was 40 batches of facing and 60 batches concrete, representing 100 BBLS. Cement the gang worked was as follows. Duty. No, men, PC, cost. Handling cement 3.5, 26 filling and pushing sand car 5.8, 77 filling and pushing stone car 9.15, 79 measuring water 1.1, 75 dumping bucket on top platform 3.5, 26 opening and closing door of mixer 1.1, 75 operating friction clutch 1.1, 76 attending concrete cars under mixer 1.1, 76 dumping cars at forms 2.3, 51 spreading concrete in forms 3.5, 26 tamping concrete in forms 10.17, 54 mixing, mortar for facing 6.10, 53 finishing top of wall 2.3, 51 hauling concrete cars with 1 horse 1.3, 51 enginemen operating hoist 1.3, 51 enginemen operating engine 1.3, 51 foremen in charge of forms 1.3, 51 general foreman 1.3, 51 total 52,100. 00. The percentages of cost in this statement have been calculated by the authors upon the assumption that each laborer received 1/2 as much wages as each engineman, foreman and horse and driver per 8 hours, which would make the total daily wages equivalent to the wages of 57 men. Wages of common labor were $1.50 per day. Considering the size of the gang, the output of 40 batches of mortar and 60 batches of concrete per day was very small. The total yardage of concrete in the guard lock was 3,762 cu. IDS, 2,212 cu. IDS, in the walls and 1,550 cu. IDS, in foundations, culverts, etc. Its cost per cubic yard was made up as follows. Item, total, per cu, YD, 5,246 BBLS. Portland cement, $15,604, $4. 170,152 BBLS. Natural cement, 84, 2,910 cu. IDS. Stone, 2,901 0. 771 126 cu. IDS. Pebbles, 113 0. 401 1970 cu. IDS. Sand, 1,398 145,000 ft. B. M. Lumber, a quarter th. Cost, 659 0. 175 iron for forms, trestles, etc. 90 0. 024 coal, oil, miscellaneous 327 0. 087 carpenter work 2,726 0. 724 mixing and placing concrete 6,693 1. 780 pumping, engineering, MISC 742 0. 197 20% of plant 550 0. 146. Total $31,887 $8. 475 Fig. 75. Forms for regular lock walls, Illinois and Mississippi Canal, Lock No. 37. The character of the forms used in constructing the lock walls is shown by Fig. 75. The walls were built in sections and work was continuous with 3 8-hour shifts composed about as specified for the guard lock work, except that 1 or 2 men were added in several places, making the total number 58 men. The average output per shift was 65 batches of concrete and 31 batches of facing mortar. The cost of the work, comprising 3,767 IDs, was as follows. Item, total, per YD, 4,564 BBLS. Portland cement, $14,181, $3. 764 2,460 IDs. Crushed stone, 4,521 1. 250 IDs. Pebbles, 325 0. 086 1,750 IDs. Gravel, 2,335 0. 619 450 IDs. Sand, 450 0. 119 180,000 FT. B. M. Lumber, a quarter TH cost, 990 0. 236 fuel, light, repairs, etc. 1,171 0. 311 carpenter work, 2,526 0. 671 pumping, 270 0. 071 mixing and placing concrete, 6,171. 632 20% cost of plant, 730 0. 193 total, $33,669, $8. 902 Lock No. 36. The forms used were of the construction shown by Fig. 75. 3 shifts were worked, each composed as specified for the guard lock, except that the number of tampers and spreaders was doubled, bringing the gang up to 65 men. The average output per gang per shift was 76 batches of concrete and 35 batches of facing mortar. The cost of 2,141 IDs of concrete in this lock was as follows. Item, total, per YD, 3,010 BBLS. Portland cement, $9,057, $4. 23 1,377 IDs. Broken stone, 1,922 0. 9,393 IDs. Pebbles, 354 0. 17,459 IDs. Gravel, 310 0. 15,500 IDs. Sand, 889 0. 42 150,000 FT. B. M. Lumber, a quarter TH cost, 600 0. 28 fuel, light, repairs, etc. 253 0. 68 carpenter work, 1,472 0. 11 mixing and placing concrete, 3,897 1. 82 20% cost of plant, 650 0. 30. Total, $19,404, $9. 06. The preceding data, made public by Mr. Wowerman in 1894, are supplemented by the following information prepared for the authors. If any criticism was to be made of the concrete masonry erected in 1893 and 1894, it would probably be to the effect that it was too expensive. The cost of the masonry erected during those 2 seasons was $8 to $9 per YD. Our records showed that about 45% of this cost was for Portland cement alone, and moreover that 40% of the total cement used at a lock was placed in the 8-in facing and 5-in coping, So in the 7 locks erected in 1895 on the eastern section, the facing was reduced to 3 ins, and the proportions changed from 1 to 2 to 1 to 2.5. In 1898, this cost received another severe cut, and Major Marshall's instructions stated that the facing should not exceed 1.5 ins in thickness nor be less than 3/4 in, while the layer of fine material on top of the coping was to be only sufficient to cover the stone and gravel. The amount of sand was again increased, so that the proportions were 1 to 3. The cost of the Portland cement concrete was likewise cheapened by increasing the amount of aggregates. On the earlier work, the proportions were 1 to 2 to 2 to 3, while on the work in 1898, the proportions were 1 to 4 to 4. The cost of the walls was further cheapened by using Utica cement in the lower steps of the wall, with 2 ft of Portland cement concrete on the face. The proportions used in the Utica cement concrete were 1 to 2 to 2.5. This lower step is 1/3 of the height, or about 7 ft. Fig. 76. Sketch showing method of attaching lagging to studs, Illinois and Mississippi Canal. The forms were of the same character as those used on the first locks, except that for lining the inner face 3 times 10 in. Hard pine planks were substituted for the 4 times 8 in. White pine. The hard pine was damaged less by the continuous handling, and the cost was practically the same. There was also an important change made in the manner of fastening the plank to the 8 times 10 in. Posts. A strip 1/3 ins square was thoroughly nailed to each post once for all with 20D spikes, and the planking was then nailed from the outside, as shown in Fig. 76. This kept the face of the plank in a perfectly smooth condition and prevented the formation of the little knobs on the face of the concrete which represented all the old nail holes. This style of forming was also easier to take apart after the setting of the concrete. Rough pine planks 2 times 12 in were used for the back of the form, the same as before. In order to keep ahead of the concrete force, it was necessary to use 2 gangs of carpenters, erecting the forms for the next 2 locks. Each gang consisted of about 20 carpenters at $2, 25 and 10 helpers at $1.50. But men were transferred from one to the other according to the stage of completion of the 2 locks. In addition to these 2 gangs, 2 carpenters were on duty with each concrete shift to put in the steps in the back of the forms. Sufficient lumber was required for the forms for 3 complete locks, and 14 locks, nos. 8 to 21 were built. The same type of mixer has been used as on the earlier work at Milan, namely a 4 ft. Cubical steel box mounted on corners diagonally opposite. On account of the greater number of locks to be built on the eastern section, however, 2 mixers were found necessary, so that while the concrete force was at work at one lock, the carpenters and helpers were erecting the mixer at the next lock. The facing was mixed by hand. After turning over the dry cement and sand at least twice with shovels, the mixture was then cast through a No. 5 sieve, after which the water was incorporated slowly by the use of a sprinkling can so as to avoid washing. The secret of good concrete after the selection of good materials is thorough mixing and hard tamping. Each batch of concrete consisting of about 1-2 ids in place was turned in the mixer for not less than 2 mins, at the rate of 9 revolutions per minute. The amount of tamping is indicated by the fact that about 16 men out of 72 on each shift did nothing but tamp. The rammers used were 6 ins, square and weighed 33 pounds. The bottom of the rammer consisted of 3 ridges, each 1 in. In height, so as to make more bond between the successive layers. On the eastern section, the top of the lock walls was higher above the ground, as a rule, than at the Milan locks, and the cars were run up an incline with a small hoisting engine. A 15 HP portable engine and boiler operated the bucket hoist from one pulley, the mixer from the other pulley, and also furnished steam for the hoist which pulled the cars up the incline. The incline made an angle of about 30 degrees with the ground. The practice of carrying on two sections at once was continued the same as on the western section. Each main wall was systematically divided into 11 sections, making each section about 20 ft long. The corners of the coping were dressed to a quadrant of about 3 ins, radius with a round trowel like those used on cement walks. In fact, the whole method of finishing the coping was the same as is used on concrete walks. The mortar was put on rather wet and then allowed to stand for about 20 mins. Before finishing, this allowed the water to come to the surface and prevented the formation of the fine water cracks which are sometimes seen on concrete work. After its final set, the coping was covered with several inches of fine gravel which was kept wet for at least a week. The last concrete laid during the season was in November on Loch No. 21 and Aqueducts Nos. 2 and 3. Portions of these structures were built when the temperature was below freezing. The water was warmed to about 60 degrees or 70 degrees F by discharging exhaust steam into the tank. Salt was used only in the facing, simply sufficient to make the water taste saline. The maximum amount used on the coldest night when the temperature was about 20 degrees F was 1.5%. The concrete force on each shift was as follows. Men, filling and pushing stone car 10, filling and pushing gravel car 8, measuring cement 3, measuring water and cleaning bucket 2, dumping bucket on top platform 2, operating mixer 2, loading concrete cars 1, pushing and dumping cars on forms 3, switchmen on forms 2, spreading concrete in forms 12, tamping concrete in forms 16, mixing facing 3, water boys 2. Total laborers 66. Operating hoists 2, finishing coping 2, firemen 1, sub-overseers 2, overseer 1. Total force 74. The cost of material and labor at Loch No. 15, 10 ft. Lift, which contains 2,559 cu. Ids of concrete was as follows. Materials per cu. YD 0. 56 bbl. Portland cement 0. 96 per cu. YD $1.42. 64 bbl. Utica cement 1.58 per cu. YD 30.58 cu. YD. Stone 1.15.60 cu. YD. Gravel 52.14 ft. M. Lumber F at $15 per m. 21.06 lb. Spikes 0.1 coal 10 tons in all at $1.70. 0.10. 35 gal. Kerosene 0.3. Total materials $3.65. Labor erecting forms $7 per m. 45 removing forms $2 per m. 13 erecting and removing mixer $161. 06 loading and unloading materials at yards and lock sites. 23 track laying $86. 03 train service narrow gauge road. 09 delivering materials to mixer. 28 mixing concrete. 11 depositing concrete. 21 tamping concrete. 21 mixing, depositing and tamping 69 cu. Ids. Face mortar $160. 23 general construction $553. 22 total labor $2. 25 F. The lumber was used nearly 5 times, which accounts for its low cost per cu. YD. There were 1,430 ids of Portland cement concrete, 69 ids of Portland cement mortar facing, and 1,059 ids of Utica cement concrete. The Portland concrete cost $6.43 per YD. The Utica concrete, $4.77 per YD. The following is the cost of labor on Lock No. 2011 FT. Lift, 2,750 ids per YD. Erecting forms, $7 per m. $434 removing forms, $1.70 per m. 113 erecting and removing mixer, $151. 058 loading and unloading at yards, lock sites, etc. 614 tracks. 024 train service, narrow gauge. 016 pumping. 114 delivering material to mixer. 288 mixing concrete. 134 depositing concrete. 205 tamping concrete. 192 mixing, depositing, and tamping. 85 ids face mortar. 071 general construction. 246 total $2. 509 cost of hand mixing and placing canal lock foundation. Mr. Geo P. Hawley gives the following record of mixing and placing 4,000 ids of 1 to 4.5 gravel concrete for the foundation of a lock constructed for the Illinois and Mississippi Canal in 1897. The concrete was mixed on 14 times 16 ft. board platforms from which it was shoveled directly into place. The materials were brought to the board in wheelbarrows. 2 boards were used, the usual gang for each being 4 men wheeling gravel, 4 men mixing, 1 man sprinkling, 2 men depositing and leveling, and 2 men tamping. The 2 gangs were worked against each other. 10 hours constituted a day's work, and the average time and cost per cubic yard for mixing and placing were CTS. Foreman 0, 21 HR at 30 CTS 6. 30 laborers 339 HRS at 15 CTS 50, 09 pump runner 0, 129 HR at 20 CTS 3, 58 water boy 0, 087 HR at 7.5 CTS 0, 65 total labor per YD cents, 60, 62 breakwater at Marquette Mitch. The breakwater extends out from the shore and consists of a prism of concrete resting on timber cribs filled with stone. Originally, the cribs carried a timber superstructure. This was removed to give place to the concrete work. A typical cross-section of the concrete prism is shown by Fig. 77. The prism is 23 ft. wide on the base. Farther inshore, the base width was reduced to 20 ft, and in the shore section the prism was changed to a triangular trapezoid by continuing the first slope to the bottom, cutting off the berm and second slope. The wooden structure was removed to a level 1 ft. Below mean low water, and on it a concrete footing approximately 2 ft. Thick was constructed for the prism proper. This footing reached the full width of the crib and was constructed in various ways during the 5 years through which the work continued. At first, the footing concrete was deposited loose under water by means of bottom dumping buckets. Later, the stone filling of the cribs was simply leveled up by depositing concrete in bags, and last toe and heel blocks were molded and set flush with the sides of the crib and filled between. Methods of construction and records of cost are reported for portions only of the work, and these are given here. Fig. 77. Cross-section of Marquette breakwater, footing placed under water with buckets. Besides the material track which was constructed along the old wooden structure, the plant consisted of a mixing scow and a derrick scow, which were moored alongside the work. The sand, stone, and cement were brought out in cars between working hours and stored on the mixing scow, enough for 1 day's work at a time. The derrick handled a 40-cu FT bottom dump bucket, which sat in a well on the mixing scow with its top flush with the deck. The concrete was mixed by hand on the deck and shoveled into the bucket. The bucket was then handled by the derrick to the crib and lowered and dumped under water. The gang consisted of 24 men, 1 foreman, 1 master laborer, 14 men shoveling and mixing, 3 men wheeling materials, 1 derrick man, and 3 men placing and depositing concrete. No record of output of this gang is available. The cost of the concrete in place with wages $1, 25 to $1. 40 per day for common labor is given as follows. Materials per cu, YD, 1, 21 BBLS, 459 pounds. Cement at $2, $22, 657 1 cu, YD. Stone at $1, 58 1, 580 0, 5 cu, YD. Sand at $0, 50 0, 252, 2 pounds. Burlap at $0, 037 0, 075 twine and needles 005. Total materials $4. 567 labor. Loading scow with materials $0. 4114 mixing concrete 0. 8459 depositing concrete 0. 5242 total labor $1. 7815 grand total $6. 348 these figures are based on some 757 cu ids of concrete footing. In explanation of the items of burlap, etc., it should be said that the cribs were carpeted with burlap to prevent waste of concrete into the stone fill. Fig. 78. Cross-section of Marquette breakwater showing manner of constructing footing with bags of concrete, leveling off cribs with concrete in bags. The sketch, Fig. 78, shows the method of leveling off the cribs with concrete in bags. The concrete was mixed by hand on shore and filled into atolls. Burlap bags, 6 ft, long and 80 ins, around, holding 2,000 pounds. The bags were filled while lying in position in a skip holding 1 bag. A skip was lifted by gallows frame and tackle onto a car and run out to the work where the derrick scow handled the skip to the crib, lowered it into the water, and dumped the bag. The cost of making and placing some 375 cu ids of concrete in bags is given as follows. Materials, total, per cu, YD, 453 BBLS, cement at $2, 627 $1,190, $033, 173 375 cu ids, stone at $1, 619 607, 13 619 180 cu ids, sand at $0, 392.70, 56 0, 188 3,220 ids, burlap at $0, 03304 106, 39 0, 283 twine and needles 6, 36 0, 017, total materials $1,980, 47 $5, 280 labor mixing, 108 HRS, master laborer at $0, $21 $23, 42 $0, 062 1,750 HRS, labor at $0, 175 306, 25 0, 816 superintendents 12, 55 0, 033, total labor mixing $342, $22. 911 labor transporting, 306 HRS, labor at $0. 175.53, $55. 142 superintendents 5. 25 0. 014. Total labor transporting, $58, $80. 156 labor depositing, 108 HRS. Engineman at $0, $25, $27, $000, 072 108 HRS. Master laborer at $0, 21 23, 42 0, 062 510 HRS. Labor at $0, 175.89, 25 0, 238 superintendents 13, 25 0, 035. Total labor depositing $152, 92 $0, 407 grand total labor $553, 94 $1, 477 grand total materials and labor $2,534, 41 $6, 757 molding footing blocks. The blocks used at the toe of the prism were of the form and dimensions shown by Fig. 79. They were molded in a temporary shed heated to 50 degrees to 65 degrees F and provided with a 2x8 in. Dressed plank floor on 12x12 in. Sills. The floor formed the bottoms of the block molds. 4 molds were used, each consisting of 4 sides. 3 laborers molded 1 block 22 ids per day, wheeling, mixing, erecting, and removing forms, placing concrete, and doing all other work. The cost of making 40 blocks was recorded as follows. Materials. Total, per YD, 126 BBLS. Cement at $2, 75 $346, $53, 893.88. 9 ids screenings at $1. 1097, 79 1, 098.40, 1 ids sand at $0, 45.18, 040, 203.5 gals, oil at $0, 65.3, 25 0, 036, total materials $465, 58.5, 230 labor, 1,000 HRS. Labor at $0, 125 $125, $001, 404 watchman 29, 15 0, 327 labor cutting wood for fuel 23, 80 0, 267 superintendents 42, 66 0, 480, total labor $220. 61 $2, 478 total labor and materials $686, 19 $7, 708 Fig. 79. Details of toe blocks for footing, marquette breakwater, molding concrete prism in place. The concrete prism was molded in alternate sections 10 ft. long. The form for the isolated sections consisted of 8 pieces so constructed that when assembled in place and secured with bolts and turnbuckles, the form was self-contained as to strength and required no outside support or bracing. The form once in place, all that remained to be done was to fill it, the block with the gallery through it being molded in one operation. The forms for the connecting blocks consisted of 2 slope panels, a panel for the harbor face and the gallery form, the blocks previously molded making the other sides of the form. The concrete was mixed by hand on shore, conveyed to the work in 1 YD, cars and shoveled into the forms where it was rammed with 35 lb. Rammers. The following record covers 1,231 ids of concrete prism. In this concrete, some 214 ids of rubble stone were embedded. The costs given are as follows. Materials total per YD 1,780 BBLS. Natural cement at $1, $0.68 $1,901, $0.41, 545 963 a half ids stone at $1, 619 1,559, 91 267.53 a half ids screenings at $0, 392.20 97 0 017 485 6 ids sand at $0, 392 190 36 0 154 miscellaneous materials 78 15 0 063 totals $3,750 $43 $3 046 labor mixing 254 HRS. Master laborer at $0, $21.55, $56 $0, 045 4,470 HRS. Labor at $0, 175 782, 42 0, 635 superintendents 18, 20 0, 015. Total labor mixing $856, $18 0, 695 labor transporting and placing 35 days overseer at $2, 33 1/3 $81, 67 0, 066 1949 HRS. Labor at $0, 175 342, 070, 277 superintendents 34, 98 0, 028. Total labor transporting and placing $458, 72 0, 371 grand total labor $1,314, 91. 066 total labor and materials $5,065, 33 4. 112 no charge is made under materials for rubble stone, as the only cost for this was cost of handling, and this is included in transporting and placing. Breakwater, Buffalo, N. Y. The following methods and costs of mixing and placing some 2,561 ids of concrete are given by Mr. Emil Lowe for 10 parapet wall sections and 17 parapet deck sections for a breakwater at Buffalo, N. Y. The concrete used was a 1 cement, 1 gravel, 1 sand grit, and 4 unscreened broken stone. 1 bag of cement was assumed to measure 0.9 ft. The voids in the sand, grit, and gravel were 27%, and in the unscreened stone 39%. The hardened concrete weighed 152 pounds per ft. Fig. 80. Sketch plan of concrete mixing plant for Buffalo Breakwater. Figure 80 shows the arrangement of the mixing plant. The mixer was a 5 ft. cube mixer holding 125 ft, mounted on a trestle and operated by a 9 × 12 in. Horizontal engine taking steam from a 4 × 10 ft. Locomotive boiler also supplying steam to 2 derrick engines. The material scow contained 2 pockets for sand, 1 for gravel and 1 housed over for cement. 2 inside cement men passed out the bags in lots of 6 to 1 outside cement man who cut and emptied them into the charging bucket. 3 sand shovelers each loaded a 3.6 ft. barrow and wheeled them tandem to the bucket, and 2 gravel men each loaded a 2.7 ft. barrow and wheeled them tandem to the bucket. The broken stone was loaded by 8 shovelers into another bucket, also containing 21.6 cu ft. The 2 buckets were alternately hoisted and emptied into the mixer hopper, there being a dump man on the mixer who dumped the buckets and attended to the water supply. A charger put the mixer in operation, and when the charge was mixed, the car men dumped it into a skip resting on a small car, which was then run out on the track under the mixer to the derrick which handled the skip to the work. Derrick handled the materials from the scows and derrick handled the mixed concrete. The force on the derricks consisted of 2 enginemen, 4 tagmen, and the firemen. The 10 parapet wall sections containing 841 cu ids were built in 46 hours, making 17 batches of 1.07 cu ids or 18.2 cu ids placed per hour. The 17 parapet deck sections containing 1,720 cu ids were built in 88 hours, making 8 batches of 1.08 cu ids or 19.5 cu ids placed per hour. For the parapet deck work, the force was increased by 2 men handling materials and 1 man on the mixer. The labor cost of mixing and placing the concrete was as follows. Loading gang per day, per cu yd, 1 assistant foreman $2,000, 011 3 cement handlers 525 0, 029 3 sand shovelers 525 0, 029 2 gravel shovelers 350 0, 028 stone shovelers 14 000, 076 1 hooker on 1, 75 0, 010, totals $31, 75 $0, 175 mixer gang 1 dumpman $1, 75 $0, 010 1 charging man 1, 75 0, 010 2 car men 3, 50 0, 022 enginemen at $3, 25 6, 50 0, 035 4 tagmen at $2 8, 000, 044 1 fireman 2, 000, 011, totals $23, 50 $0, 130 wall gang 1 signalman $1, 75 $0, 010 1 dumper 1, 75 0, 010 6 shovelers at $2.12, 000, 065 4 rammers 7, 000, 038 1 foreman 4, 000, 022, totals $26, 50 $0, 145 grand totals $81, 75 $0, 450 fig 81. Concrete blocks for pier at Port Colborne Harbor, fig 82. Forms for molding blocks, Port Colborne Harbor Pier, fig 83. Device for handling blocks, Port Colborne Harbor Pier. Pier construction, Port Colborne, Ont. In constructing the new harbor at Port Colborne, Ont, on Lake Erie, the piers consisted of parallel rows of timber cribs set the width of the pier apart and filled in and between with stone blasted and dredged from the lake bottom in deepening the harbor. The tops of the cribs terminated below water level and were surmounted by concrete walls set on the outer edges. These walls were filled between with stone, and the top of the filling was flawed part way or entirely across, as the case might be, with a thick concrete slab. The footings of the walls to just above the water level were made of concrete blocks 4x4x7 ft, constructed as shown by Fig. 81. The wall above the footing course and the floor slab were of concrete molded in place. The concrete work consisted of molding and setting concrete blocks, and of molding concrete wall and slab in place. The blocks were molded on shore, shipped to the work on scows and set in place by a derrick. Figure 82 shows the construction of the forms for molding the blocks. The bottom tie rods passed through the partitions forming the ends of the molds. The sides were removed in 48 hours and used over again. Figure 83 shows the hooks used for handling the molded blocks. Considerable trouble was had in setting these blocks level and close-jointed, owing to the difficulty of leveling up the stone filling under water. Fig. 84. Scow plant for mixing and placing concrete, Port Colborne Harbor Pier. The mass concrete was mixed and placed by the scow plant, shown by Fig. 84. The scow was loaded with sufficient sand and cement for a day's work and towed to and moored alongside the pier. Forms were set for the wall on top of the block footing. These forms were placed in lengths of 60 to 75 ft. Of wall and resembled the block forms with partitions omitted. The bottoms of the rear uprights were held by being wedged into the grooves in the blocks, and the bottoms of the front uprights were held by bolts resting on top of the blocks. The tops of the uprights were held together across the wall by tie bolts. The forms being placed, the mode of procedure was as follows. The crusher fed directly into a measuring box. After some 6 ins of stone had run into the box, the door of the crusher spout was closed. A wheelbarrow load of sand was spread over the stone in the box, and over this were emptied and spread 2 or 3 bags of cement. Another layer of stone and then of sand and of cement were put in, and these operations repeated until the box was full. The box was then hoisted and dumped into the hopper of a gravity mixer of the trough type, which ran along a track on the scow and fed directly into the forms. The gang worked consisted of 1 foreman, 1 derrickman, and 18 common laborers. This gang placed from 65 to 75 ids of concrete per day at a labor cost of 50 CTS. Per yd. Fig. 85. Cross-section of concrete pier superior wise, concrete block pier superior entry wise. The methods and cost of constructing a concrete pier 3023 ft. Long and of the cross-section shown by Fig. 85 at Superior Entry, Wisconsin, are given in the following paragraphs. Molds and molding. About 80% of the concrete was deposited in molds under water, according to a plan devised by Major D.D. Galliard, Corps of Engineers. In brief, the concrete was built in place in 2 tiers of blocks, the lower tier resting directly on piles and being entirely under water, and the upper tier being almost entirely above water. As shown by Fig. 85, a pile trestle was built on each side of the proposed pier, and a traveler for raising and lowering the molds spanned the space between trestles. The molds were bottomless boxes built in 4 pieces, 2 sides and 2 ends, held together by tie rods. Fig. 86 shows an end and a side of one of the shallow water molds, and Fig. 87 shows in detail the method of fastening the end to the side. It will be seen that the 1/4" turnbuckle rods pass through the ends of beams that bear against the outside of the mold. These tie rods have eyes at each end, in which rods with wedge-shaped ends are inserted. The molds were erected on the trestle by a locomotive crane and were then lifted by the mold traveler, carried and lowered into place. The largest one of these molds, with its iron ballast, weighed 40 tons. To remove a mold after the block had hardened, the nuts on the wedge-ended rods were turned, thus pulling the wedge end from the eye of the tie rod and releasing the sides of the mold from the ends. The locomotive crane then raised the ends and sides, one at a time, and assembled them ready to be lowered again for the next block. The time required to remove one of these 40-ton molds reassemble and set it again rarely exceeded 60 minutes, and was sometimes reduced to 45 minutes. Fig. 86. Mold for concrete block for pier at Superior Wise. The concrete was deposited in alternate blocks, and the molds described were for the first blocks. For the intermediate blocks, molds of two side pieces alone were used, the blocks already in place serving in lieu of end pieces. The two side pieces were bolted together with 3 tie rods at each end. The tie rods were encased in a box of 1 in. Boards 4 times 4 ins. Inside, which served as a strut to prevent the sides from closing together, and as a means of permitting the tie rods to be removed after the concrete had set. The mold was knocked down just as was the full mold described above, and the boxes encasing the tie rods were left in the concrete. Fig. 87. Device for locking end and side of mold for concrete blocks for pier at Superior Wise. An important feature was the device for handling the molds. This, as before stated, was a traveler which straddled the pier site, it having a gauge of 31 ft. It carried a 4-drum engine, the drums of which were actuated, either separately or together, by a worm gear so as to operate positively in lowering as well as in raising. The load was hung from 4 hooks, depending by double blocks and in wire rope from 4 trolleys suspended from the trusses of the traveler. This arrangement allowed a lateral adjustment of the mold. The hoisting speed was 6 ft per minute and the traveling speed 100 ft per minute. The locomotive crane also deserves mention because it was mounted on a gantry high enough to permit material cars to pass under it on the same trestle, thus making it practicable to work 2 cranes. Fig. 88. Bucket for depositing concrete under water for pier at Superior Wise. The concrete was received from the mixer into drop-bottom buckets of the form shown by Fig. 88. The buckets were taken to the work 4 at once on cars, and they're lifted by the locomotive crane and lowered into the mold where they were dumped by tripping a latch connected by rope to the crane. To prevent the concrete from washing, the open tops of the buckets were covered with 3 times 4 ft. Pieces of 12 Oz canvas in which were quilted 110 pieces of 1/16 times 1 times 3 in sheets of lead. 2 covers were used on each bucket and were attached one to each side of the bucket top so as to fold over the top with a lap. This arrangement was entirely successful for its purpose, concrete mixing. The proportions of the subaqueous concrete were 1:2 of 5 by volume, or 1:2, 73:5, 78 by weight, cement being assumed to weigh 100 pounds, per cu ft. The proportions of the superaqueous concrete were 1:3, 12:6, 25 by volume, or 1:3, 41:7, 22 by weight. The dry sand weighed 109, 2 pounds, per cu ft, the voids being 35, 1%. The pebbles weighed 115, 5 pounds, per cu ft, the voids being 31%. The pebbles for the concrete were delivered by contract and were unloaded from scows by clamshell bucket into a hopper. This hopper fed onto an endless belt conveyor which delivered the pebbles to a rotary screen. Inside this screen, water was discharged under a pressure of 60 pounds per SQ in from a 4-in pipe to wash the pebbles. From the screen, the pebbles passed through a chute into 4 cu YD cars which were hauled up an incline to a height of 65 ft by means of a hoisting engine. The cars were dumped automatically, forming a stockpile. Under the stockpile was a double gallery or tunnel provided with 8 chutes through the roof, and from these chutes the cars were loaded and hauled by a hoisting engine up an inclined trestle to the bins above the concrete mixer. The sand was handled from the stockpile in the same manner. The cement was loaded in bags on a car in the warehouse, hauled to the mixer and elevated by a sprocket chain elevator. Chutes from the bins delivered the materials into the concrete mixer, which was of the Chicago improved cube type, revolving on trunnions about an axial line through diagonal corners of the cube. The mixer possessed the advantage of charging and discharging without stopping. It was driven by a 7x10 vertical engine with boiler. The mixer demonstrated its ability to turn out a batch of perfectly mixed concrete every 1/1/3 minutes. It discharged into a hopper provided with a cut-off chute, which discharged into the concrete buckets on the cars. Labor force and costs. In the operation of the plant, 55 men were employed, 43 being engaged on actual concrete work, and 12 building molds and appliances for future work. The work was done by day labor for the government, and the cost of operation was as follows for one typical week, when in 6 days of 8 hours each, the output was 1,383 cu-ids, or an average of 230 cu-ids per day. The output on one day was considerably below the average on account of an accident to the plant, but this may be considered as typical. Pebbles from stockpile to mixer per cu-yd. 4 laborers at $2 $0. 03481 enginemen at $3 0. 0131 coal, oil, and waste at $1. 030. 0043 sand from stockpile to mixer, 5 laborers at $2 $0. 0434 enginemen at $2. 50 0. 0109 coal, oil, and waste at $0. 82 0. 0035 cement from warehouse to mixer, 5 laborers at $2 $0. 0434 mixing concrete, 1 engineman at $2. 50 $0. 0109 1 mechanic at $2. 50 0. 0108 coal, oil, and waste at $1. 29 0. 0056 transporting concrete, 4 laborers at $2 $0. 0348 1 engineman at $3 0. 0130 coal, oil, and waste at $0. 66 0. 0028 depositing concrete in molds, 4 laborers at $2 $0. 0348 1 engineman at $3 0. 0130 1 rigger at $3 0. 0130 coal, oil, and waste at $1. 18 0. 0051 assembling, transporting, setting, and removing molds, 4 laborers at $2 $0. 0347 1 engineman at $3. 25 0. 0141 1 carpenter at $3 0. 0130 1 mechanic at $2. 50 0. 0109 coal, oil, and waste at $1. 39 0. 0060 care of tracks, 1 laborer at $2 $0. 0086 1 mechanic at $2. 50 0. 0109 supplying coal, 3 laborers at $2 $0. 0260 blacksmith work, 1 laborer at $2 $0. 0086 1 blacksmith at $3. 25 0. 01411 1 water boy at $0. 75 0. 0032 total per cubic yard $0. 4473 add 75% of cost of administration 0. 1388 total labor per cu-yd $0. 5861. The total cost of each cubic yard of concrete in place was estimated to be as follows. Per coup, YD, 10/11 coup, YD. Pebbles at $1. $0.85. 9864 10/22 coup, YD. Sand at $0. 000. 0.000126 BBLS. Cement at $1. 77.2. 2302. Labor as above given 0. 5861. Cost of plant distributed over total yardage 0. 8400. Total $4. 6427. It will be noted that the sand cost nothing as it was dredged from the trench in which the pier was built and paid for as dredging. The cost of the plant is distributed over this south pier and over the proposed north pier work on the basis of only 20%. Salvage value after the completion of both piers. It is said, however, that 80% is too high an allowance for the probable depreciation. Dam, Richmond, Indiana. The dam shown in cross-section in Fig. 89 was built at Richmond, Ind. It was 120 ft long and was built between the abutments of a dismantled bridge. The concrete was made in the proportion of 1 BBL, Portland cement to 1 cu, YD. Of gravel, old iron was used for reinforcement. The foundations were put down by means of a cofferdam which was kept dry by pumping. On completion, it was found that there was a tendency to scour in front of the apron, and accordingly piling was driven and the intervening space riprapped with large stone. Labor was paid as follows per day. Foreman, $3, carpenter, $2, 50, cement finisher, $2, laborers, $1, 50. The concrete was mixed by hand and wheeled to place in wheelbarrows. The cost of the work was as follows. Materials per cu, YD, 204 BBLS. Cement at $1, $61. 485 sand and gravel 0. 800 lumber 0. 610 tools, hardware, etc. 0. 445 total materials $3. 34 labor, clearing and excavating $0. 96 setting forms and mixing concrete 1. 01 pumping 0. 27 total labor $2. 24 total materials and labor $5. 58 Fig. 89. Concrete dam at Richmond, Ind. Dam at Rock Island Arsenal, Illinois. The dam was in the shape of an L with one side 192 ft and the other side 208 ft. Long, it consists of a wall 30½ ft. High 3½ ft. Wide at the top and 6½ ft. Wide at the bottom with a counterfort every 16 ft. 26 in all. Each counterfort extended back 16 ft. and was 4 ft. thick for a height of 6 ft, and then 3 ft. thick. There were 3,500 cu, ids, of concrete in the work, which was done by day labor under the direction of the U.S. engineer in charge. The forms consisted of front and back uprights of 8 times 10 in. Stuff 24 ft. High, connected through the wall by 3/4 in, rods which were left in the concrete. The lagging was 2 times 12 in. Plank dressed down 1 3/4 ins, placed inside the uprights. These forms were built full height in 16 ft. Sections with a counterfort coming at the center of each section. Each section contained 95 cu, ids, of concrete and was filled in a day's work. The concrete was a 1:4:7 mixture wet enough to quake when rammed. Run of crusher limestone was used, of which 50%. Pasta 1 in. Sieve 17%. A no, 3 sieve and 9%. A no, 8 sieve. The concrete was mixed in Cockburn Barrow and Machine Co. S screw feed mixer which discharged into 2 in. Plank skips 2 ft. Wide 5 1/3 ft. long and 14 ins, deep, holding a quarter coup, YD. These skips were taken on cars to a derrick crane overhanging the forms and by it hoisted and dumped into the forms. The derrick was moved along a track at the foot of the wall as the work progressed. The concrete was spread and rammed in 6-in layers. The men were paid $1.50 per 8 hours work, and the work cost including footing as follows. Item total per coup YD. Cement $1,500, $000, 429 sand 400, 000. 114 storing and hauling cement 460, 000. 131 taking sand from barge to mixer 96, 000. 027 crushing stone 1,450, 000. 414 mixing concrete 4,825, 001. 378 placing concrete 1,670, 000. 477 lumber for farms, etc. 600, 000. 171 erecting and taking down forms 2,450, 000. 700 totals $13,451, $003. 841 dam at McCall Ferry, PA. The dam was 2,700 ft, long and 48 ft, high of the cross-section shown by Fig. 90 and with its subsidiary works required some 350,000 ids of concrete. The plant for mixing and placing the concrete was notable chiefly for its size and cost. Parallel to the dam, which extended straight across the river, and just below its toe a service bridge consisting of a series of 40 ft. Concrete arch spans was built across the river. This service bridge was 50 ft. wide and carried 4 standard gauge railway tracks besides a traveling crane track of 44 ft. gauge. This very heavy construction of a temporary structure was necessitated by the frequency of floods against which only a solid bridge could stand. It was considered cheaper in the long run to provide a bridge which would certainly last through the work than to chance a structure of less cost which would certainly go out with the floods. The concrete service bridge was designed to be destroyed by blasting when the dam had been completed. The method of construction was to build the dam in alternate 40 ft. sections, mixing the concrete on shore, taking it out along the service bridge in buckets on cars, and handling the buckets from cars to forms by traveling cranes. Fig. 90. Steel forms for McCall Ferry Dam. The concrete mixing plant is shown by Fig. 91. Cars loaded with cement, sand, and stone were brought in over the tracks carried on the wall tops of the bins and were unloaded respectively into bins A, B, and C, of which there were 8 sets. Each set supplied material by means of measuring cars to a 1 coup, YD, Smith mixer. 2 sets of cars were used for each mixer so that one could be loading while the other was charging. The mixers discharged into 1 coup, YD. Buckets set 2 on a car and 8 cars were hauled to the work in train by an 18-ton dinky. At the work, the buckets were picked up by the traveling cranes and the concrete dumped into the forms. Figure 90 shows the construction of the steel forms. 6 sets of forms were used. Each set consisted of 5 frames spaced 10 ft. apart and braced together in the planes parallel to the dam, and each set molded 40 ft. of dam. The lagging consisted of wooden boxes 8.5 ft. wide and 10 ft. long. For the vertical face of the dam, these boxes were attached by bolts to the vertical post. For the curved face, they were bolted to a channel bent to the curve, and held by struts from the inclined post of the steel frame. Fig. 91. Concrete mixing plant from a Call Ferry Dam. In construction, the footing and the body of the dam to an elevation of 5 ft. Above the beginning of the curve were built continuously across the river. Above this elevation, the dam was built in alternate 40 ft. sections. The strut back to the service bridge shown in the lower right-hand corner of Fig. 90 shows the manner of bracing the first 30 ft. section of the inclined post to hold the lagging for the continuous portion. The lagging was added a piece at a time as concreting progressed. The ends of each set of frames for a 40 ft. section were for the isolated sections closed by timber bulkheads carrying box forms to mold grooves into which the concrete of the intermediate sections would bond. Fig. 92. Traveler for concreting dam, Chaudière Falls, Quebec. The concrete used was a 1 to 3 to 5 mixture, the stone ranging in size from 2 to 5 ins. Rubble stone from 1 man's size to a half-ton were bedded in the concrete. The capacity of the concrete plant was 2,000 ids per day, or about 250 ids per mixer per 10-hour day. Dam, Chaudière Falls, Quebec. The dam was 800 ft. long and from 16 to 20 ft. high, constructed of 1 to 2 to 4 concrete with rubble stone embedded. The rubble stones were separated at least 9 ins, horizontally, and 12 ins, vertically, and were kept 20 ins, from faces. At one point the rubble amounted to 40% of the volume, but the average for the dam was 25 to 30%. The stone was broken at the work, some by hand but most by machine, all to pass a 2-in ring. Hand-broken stone ran very uniform in size and high in voids, often up to 50%. Stone broken by crusher with jaws 2 ins. A pot would run 20 to 30%, over 2 ins, in size and give about 45%. Voids with crusher jaws 1.5 ins. A pot from 98 to 100%, was under 2 ins, in size and contained about 42%. Of voids, it was found that if the crushers were kept full all the time, the product was much smaller, particularly with Gates' gyratory crusher, though a little more than rated power was required when the crusher was thus kept full. This practice secured increased economy in both quantity and quality of product. The concrete was made and placed by means of a movable traveler shown by Fig. 92. Concrete materials were supplied to the charging platform of the traveler by means of a traveling derrick moving on a parallel track. In placing the concrete on the rock bottom, it was found necessary, in order to secure good bond, to scrub the rock with water and brooms and cover it with a bed of 2 ins of 1 to 2 mortar. The method of concreting in freezing weather is described in Chapter 7. Chapter 39. The construction of piers and abutments for bridges is best explained by describing individual examples of such work. So far in America, bridge piers have been nearly always of plain concrete, and of form and section differing little from masonry piers. Where reinforcement has been used at all, it has consisted of a surface network of bars introduced chiefly to ensure monolithic action of the pier under lateral stresses. In Europe, cellular piers of reinforced concrete have been much used. Plain concrete abutments differ little in form and volume from masonry abutments. Reinforced concrete abutments are usually of L section, with counterforts bracing the upright slab and bridge seat to the base slab. Form work for reinforced abutments is somewhat complex. That for plain abutments and piers is of simple character. The only variations from plain stud and sheathing construction being in the forms for moldings and coping, and for cut waters. For piers of moderate height, the form is commonly framed complete for the whole pier, but for high piers it is built up as the work progresses by removing the bottom boards and placing them at the top. Opposite forms are held together by wire ties through the concrete. Movable panel forms have been successfully employed, but they rarely cheapen the cost much. Sectional forms, which can be shifted from pier to pier where a number of piers of identical size are to be built, may frequently be used to advantage. An example of such use is given in this chapter. Derricks are the recognized appliances for hoisting and placing the concrete in pier work. They are the only practicable appliance where the pier is high and particularly where it stands in water and mixing barges are employed. For abutment work and land piers of moderate height, derricks and wheelbarrow or cart inclines are both available, and where much shifting of the derricks is involved, the apparently more crude method compares favorably in cost. The methods of placing concrete under water for pier foundations are described in Chapter V, and the use of rubble concrete for pier construction is illustrated by several examples in Chapter VI. The following examples of pier and abutment construction cover both large and small work and give a clear idea of current practice. Fig. 93. Pier and cofferdam for a railway bridge. Cost of constructing rectangular pier for a railway bridge. This pier, Fig. 93, was built in water averaging 5 ft deep. The cofferdam consisted of triple lap sheet piling of the Wakefield pattern, the planks being 2 ins thick and spiked together so as to give a cofferdam wall 6 ins thick. The cofferdam enclosed an area 14 times 20 ft, giving a clearance of 1 ft all around the base of the concrete pier and a clearance of 2 ft between the cofferdam and the outer edge of the nearest pile. The cofferdam sheet piles were 18 ft long, driven 11 ft deep into sand and projecting 2 ft above the surface of the water. The concrete base resting on the foundation piles was 12 times 18 ft. The concrete pier resting on this base was 7 times 13 ft at the bottom and 5 times 11 ft at the top. The pier supported deck plate girders. There were 100 ids of concrete in the pier and base. The cost of this pier, which is typical of a large class of concrete pier work, has been obtained in such detail that we analyze it in detail, giving the costs of cofferdam construction and excavation as well as of mixing and placing the concrete, setting up and taking down derrick and platform, 4 days foreman at $5, $00.20. 00 3/4 days engineman at $3, 002, 25 3/4 days blacksmith at $3, 002, 25 3/4 days blacksmith helper at $2, 001, 50 22 days laborers at $2, 0044, 00, total $70, 00 cofferdam, 7 days foreman at $5, 00.35, 00 4 days engineman at $3, 0012, 00 38 days laborers at $2, 0076, 00 1 ton coal at $3, 003, 00 total labor on 7,900 ft. B.M. at $16, 00 $126, 00 7,900 ft. B.M. at $20, 00 158, 00 total for 58 ids. Excavation $284, $0 wet excavation. 1. 8 days foreman at $5. $0 $9. 001. 5 days engineman at $3. $0 59 days. Laborers at $2. $0 18. $0 a half-ton coal at $3. $0 50. Total labor on 58 coup. IDS at 57 C. $33. $0 foundation piles 960 Lin. FT at 10 C. $96. $0 4 days setting up driver and driving 24 piles at $20 per day for labor and fuel 80. $0 total $176. $0 concrete 100 coup IDS stone at $1. $0 $100. $0 40 coup IDS sand at $0 50 20. $0 100 BBLS cement at $2. $0 200. $0 5 days foreman at $5. $0 25. $0 50 days laborers at $2. $0 100. $0 5 days engineman at $3. $0 15. $0 2 tons coal at $3. $0 6. $0 total 100 coup IDS at $4. 66 $466. $0 8 days carpenters at $3. $0 24. $0 2,400 FT. B. M. 2 in. Plank at $25. $0 60. $0 1,000 FT. B. M. 4 times 6 in. Studs at $20. $0 20. $0 nails, wire, etc. 2. $0 total forms for 100 coup IDS at $1. $0 $106. $0 summary setting up derrick, etc. $70. $0 cofferdam 7,900 FT. B. M. 284. $0 wet excavation 58 coup IDS 33. $0 foundation piles 24 176. $0 concrete 100 coup IDS 466. $0 forms 3,400 FT. B. M. 106. $0 total $1,135. $0 transporting plant 20. $0 20 days rental of plant at $5. $0 100. $0 total cost of pier $1,252. $0 regarding the item of plant rental, it should be said that the plant consisted of a pile driver, a derrick, a hoisting engine, and sundry timbers for platforms. There was no concrete mixer. Hence, an allowance $5 per day for use of plant is sufficient. It will be noted that no salvage has been allowed on the lumber for forms. As a matter of fact, all this lumber was recovered and was used again in similar work. Referring to the cost of cofferdam work, we see that, in order to excavate the 58 coup IDS, inside the cofferdam it was necessary to spend $284 or nearly $5 per coup YD before the actual excavation was begun. The work of excavating cost only 57 CTS per coup YD. But this does not include the cost of erecting the derrick, which was used in raising the loaded buckets of earth, as well as in subsequently placing the concrete. The sheet piles were not pulled in this instance, but a contractor who understands the art of pile pulling would certainly not leave the piles in the ground. A hand pump served to keep the cofferdam dry enough for excavating, but in more open material a power pump is usually required. The above costs are the actual costs, and do not include the contractor's profits. His bid on the work was as follows. Piles delivered 12 CTS per FT. Piles driven $5 each, cofferdam $37 per m. Wet excavation $1, 00 per cu, YD. Concrete $8, 00 per cu, YD. In order to ascertain whether or not these prices yielded a fair profit, it is necessary to distribute the cost of the plant transportation and rental over the various items. We have allowed $120 for plant transportation and rental, and $70 for setting up and taking down the plant, or $190 in all. The working time of the plant was as follows: days, percent of time, prorated plant cost. Cofferdam $739.74 excavation, $211.21 foundation piles, $422.42 concrete, $528.53. Totals $1,190 as above given. The labor on the 7,900 FT. B. M. In the cofferdam cost $126 or $16 per m. But this additional $74 of prorated plant costs adds another $9 per m, bringing the total labor and plant to $25 per m, to which must be added the $20 per m, paid for the timber in the cofferdam, making a grand total of $45 per m. This shows that the contractor's bid of $37 per m was much too low. The labor on the excavation cost 57 CTS per cu, YD, to which must be added the prorated plant cost of $21 distributed over the 58 cu. IDs, or 36 CTS per cu, YD, making a total of 93 CTS per cu, YD. This shows that the bid of $1 per cu, YD, was hardly high enough. The labor on the 24 foundation piles cost $80 or $3.33 each. The prorated plant cost is $42 or $1.75 per pile, which, added to $3.33, makes a total of $5.08. This shows that the bid of $5 per pile for driving was too low. However, there was a profit of 2 CTS per FT, or 80 CTS per pile on the cost of piles delivered. The concrete amounted to 100 cu, IDs, hence the prorated plant cost of $53 is equivalent to 53 CTS per cu, YD. Hence, the total cost of the concrete was, per cu, YD. Cement, sand, and stone $3. 20 foremen at $5.00. 25 labor at $2.01. 00 enginemen at $3.00. 15 coal at $3.00. 06 carpenters at $3.00. 24 forms at $23. 50 used once 0, 80 wire nails, etc. 0. 02 prorated plant cost 0. 53 total $6. 25 since the contract price for concrete was $8 per cu. YD. There was a good profit in this item. Backing for bridge piers and abutments. 6 piers and 2 abutments of the City Island Bridge were constructed in 1906 at New York City, of masonry backed with 1 to 2 to 4 concrete below and 1 to 3 to 5 concrete above high water. The piers and abutments were all sunk to rock or hard material by means of timber cofferdams. Table Roman 16 gives the labor cost of mixing and placing the concrete backing for 1 abutment and 3 piers, after the materials were delivered on the scows. The concrete was mixed by a rectangular horizontal machine mixer and deposited by 2 cu. YD. Bottom dump buckets handled by derrick scows and stiff-leg derricks. The high cost of concreting on Pier 2 was due to the fact that the concrete was improperly deposited and had to be removed and the higher cost in abutment 1 was probably due to the fact that the abutment was so long and narrow that it was difficult to handle the bucket. Table Roman 16. Cost of concrete, backing for masonry piers. Abutment No. 1, Pier No. 2, Pier No. 3, Pier No. 4. Summary wages per hour No. HRS total cost per QYD 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 total HRS total cost AV per QYD. Superintendent $70.24 $16 $80 $03.47 $32 $90 $09.72 $50 $40 $05.16 $11 $20 $03 $159 $111 $30 $05 Foreman 35 $160 $56 000 09 $128 $44 80 13 $324 $113 40 12 $54 $18 90 06 $666 $233 10 11 laborers 15 to 2025 55 383 25 65 2038 313 60 92 35 13 526 95 56 940 141 000 44 90 46 13 64 90 62 Engineman 30 365 109 50 19 196 58 50 19 244 73 20 08 60 18 000 06 865 259 50 12 Timekeeper 40 86 34 40 06 46 18 40 06 81 32 40 04 10 4 000 01 223 89 20 04 Pneumatic Caissons Williamsburg Bridge. Mr. Francis L. Prine, a sock, M. Sock, C.E., gives the following costs of concreting the pneumatic caissons for the Brooklyn Tower of the Williamsburg Bridge at New York City. The work comprised the mixing and placing of some 13,637 ids of concrete in 2 caissons. Table Roman 17 shows the itemized costs for 1 caisson, and Table Roman 18 shows them for the other caisson. The methods of work were as follows. After each caisson was built, it was towed to its proper site, where it was held in place by temporary pile dock built completely around it. On these docks the concrete was placed, a 2 YD, cubical mixer of the usual pattern being used for mixing. The concrete materials, consisting of sand, stone, and cement, was handled direct from barges alongside into the mixer. The concrete was placed by a derrick located in the center of the caisson, which was a bad feature as the caisson was usually out of level and considerable difficulty was experienced in swinging the derrick. On the south caisson 3/4 YD, bottom dump buckets were used in placing the concrete. On the north caisson, the size of these was increased to 1/2 YD, which reduced the cost of placing 15 CTS per YD. There were placed in the south caisson 3,827 ids, in 32 days of actual working time, 120 ids per day of 10 HRS. The gross time was 2 months. On the north caisson 5,693 Ids were placed in 46 days worked, 124 ids per day. The gross time was 4 months. The rates of labor were as follows per 10-hour day. Foreman $5, 00 assistant foreman 2, 50 hoisters 2, 50 firemen 1, 60 laborer 1, 50 proportions concrete were 1, 2, 5, 6. The low price of sand in the North Cason was brought about by the finding of good building sand in the excavation for the anchorage, which work was done by the same contractor. When the caissons had been sealed, the iron material shafts were removed. This left holes 5 ft times 6 ft, extending from the roof of the caisson up to mean HW, which were filled with concrete. These shaft holes were 80 ft deep on the south caisson and 100 ft deep on the north caisson. They were partially filled with water, and the concrete had to be placed with considerable care. Wooden chutes were used on the south caisson. They rested on the caisson roof, were filled with concrete, and then raised, allowing concrete to flow out at the bottom. The shaft holes were 2 deep on the north caisson for chutes, and 20 ft bottom dump buckets were used. They had to be lowered to bottom of shaft each trip before dumping, a slow operation, which greatly added to the cost. Proportion for concrete 1 to 2, 5 to 6. The proportion for concrete in working chamber was the same as for all other concrete. The specifications called for 6 in of mortar, of 1 part of cement to 2½ parts of sand between the concrete and all bearing areas. That is, under the cutting edge and directly under the roof of the working chamber. The concrete was mixed in the cubical mixer and dumped on the bottom door of the material lock. The top door of the lock was then closed. The bottom door opened and the concrete fell through the shaft to the working chamber. It was then shoveled by the sand hogs into place. A 6 in space was left below all bearing surfaces into which damp mortar was tightly rammed. Concreting the south caisson took 10¼ working days of 24 hours, the gangs working night and day in 12 2-hour shifts, 1,566 ids of concrete and mortar were placed, or at the rate of 140 ids per 24 hours. The gross time, including Sundays, was 14½ days. The sand hogs worked in shifts of 2 hours each and received $3.50 for the 2 hours' work. The 12 foremen received $1 more. The average gang consisted of 12 sand hogs. On the North Caisson, the organization was much better, owing to the experience gained on the first caisson, and in spite of the fact that the sand hogs, on account of the increased depth, received $4.00 for 1½ hour's work, or an increase of $22.00 per man per 24 HRS. Over that on the South Caisson, the work was done for less money. There were placed 1,566 ids of concrete in 7 working days of 24 HRS, or at the rate of 224 ids per day. The gross time was 11½ days, including Sundays. The average number of men in the sand hog gangs was 18, with 1 foreman who received $5 for 1½ hour's work. Table Roman 17. Itemized cost of concreting South Caisson for Brooklyn Tower of the Williamsburg Bridge. Cost of concreting caissons above roof. South Caisson, 3,827 ids. Materials, quantity, rate, amount. Cement 4,480 BBLS, $1, 57 $7,034, 00 sand 1,288 ids, 6,773, 00 broken stone 3,421 ids, 1, 55,132, 00 water 36, 00 total 3,827 Ku, IDS $3, 39 $12,975, 00 labor, mixing and placing 3,827 Ku, IDS $0, $93,432, 00 plant charges 2,280, 00 plant labor 742, 00 total plant 3,827 Ku, IDS $0, 79 $3,022, 00 total cost 3,827 Ku, IDS $5, 08 $19,429, 00 general expenses 10% 3,827 Ku, IDS 51 $1,943, 00 grand total 3,827 Ku, IDS $5, 59 $21,372, 00 cost of concreting shafts, South Cason, materials, quantity, rate, amount, concrete 612 a half BBLS, $1, 57 $962, 00 sand 193 Ku, IDS 4077, 00 stone 493 Ku, IDS 1 10 542, 00 total 541 Ku, IDS $2, 92 $1,581, 00 labor, handling, mixing, and placing 541 Ku, IDS $0, 96 $519, 00 plant charges, etc. 541 Ku, IDS 1, 06 576, 00 total 541 Ku, IDS $4, 94 $2,676, 00 general expenses 10% 541 Ku, IDS 49 $267, 00 grand total 541 Ku, IDS $5, 43 $2,943, 00 cost of concrete in working chambers, South Cason, 1,435 Ku, IDS materials, quantity, rate, amount, cement for concrete 1,666 BBLS, $1, 57 $2,615, 00 cement for mortar 459 BBLS, 1, 57 $720, 00 sand for both 670 Ku, IDS 40 $268, 00 broken stone 1,181 Ku, IDS 1 10 $1,299, 00 total materials 1,435 Ku, IDS $3, 42 $4,902, 00 labor, top labor, mixing and placing 1,435 Ku, IDS $1, 09 $1,575, 00 pneumatic labor 1,435 Ku, IDS 4 93 $7,117, 00 compressor house labor 1,435 Ku, IDS 19,275, 00 total labor 1,435 Ku, IDS $6, 21 $8,967, 00 plant, coal at $2, 40 per ton 1,435 Ku, IDS 10 $140, 00 concrete plant 1,435 Ku, IDS 79 1145, 00 Pneumatic Plant 1, 435 Ku, IDS 1, 05 1522, 00 Total Plant 1435 Ku, IDS $1, 94 $2,807, 00 Totals 1435 Ku, IDS $11, 57 $16,676, 00 General Expenses 10% 1435 Ku, IDS 1, 16 $1,667, 00 Grand Total 1435 Ku, IDS $12, 73 $18,343, 00 Table Roman 18. Itemized cost of concreting North Caisson for Brooklyn Tower of the Williamsburg Bridge. Cost of concreting caisson above roof, 5,692 Ku. IDS. Materials, quantity, rate, amount. Cement 6,707 a half BBLS, $1. 57 $10,531, 00 Sand 2,133 Ku. IDS 4,845, 00 Broken Stone 4,938 Ku. IDS 1, 10 5,432, 00 Water 51, 00 Total 5,692 Ku. IDS $2, 96 $16,859, 00 Labor. Mixing and placing 5,692 Ku. IDS $0, 73 $4,159, 00 Plant charges 2,952, 00 Plant labor 517. 00 Total 5,692 Ku. IDS $0, 61 $3,469, 00 Total cost 5,692 Ku. IDS $4, 30 $24,487, 00 General Expenses 10% 5,692 Ku. IDS 43 $2,448, 00 Grand Total 5,692 Ku. IDS $4, 73 $26,935, 00 Cost of concreting shafts, materials, quantity, rate, amount. Cement 614 a half BBLS, $1, 57 $965, 00 Sand 204 Ku. IDS 4082, 00 Stone 521 Ku. IDS 1, 10 574, 00 Total 576 Ku. IDS $2, 82 $1,621, 00 Labor. Mixing and placing 576 Ku. IDS 1, 7,982, 00 Plant charges, etc. 576 Ku. IDS 1, 36 $795, 00 Total 576 Ku. IDS $5, 88 $3,398, 00 General Expenses 10% 576 Ku. IDS 59 $339, 00 Grand Total 576 Ku. IDS $6, 47 $3,737, 00 Cost of concreting working chambers 1,566 Ku. IDS Materials, quantity, rate, amount. Cement for concrete 1,559 BBLS, $1, 51 $2,446, 00 cement for mortar 442 BBLS. 51,694. 00 sand for both 630 Ku. IDS 4,252. 00 broken stone 1,380 Ku. IDS 1, 10 1,518. 00 total 1, 566 Ku. IDS $3. 14 $4,910. 00 labor. Top labor mixing and placing 1,566 Ku. IDS $0. 78 $1,198. 00 pneumatic labor 1,566 Ku. IDS 4. 91 $7,694. 00 compressor house labor 1,566 Ku. IDS 11 $180. 00 total labor 1,566 Ku. IDS $5. 89,072. 00 plant coal at $2. 40 per ton 1,566 Ku. IDS 0687. 00 concrete plant 1,566 Ku. IDS 86 1,352. 00 pneumatic plant 1,566 Ku. IDS 81 1,272. 00 total plant 1,566 Ku. IDS $1. 73 $2,711. 00 totals 1,566 Ku. IDS $10. 67 $16,693. 00 general expenses 10% 1,566 Ku. IDS 1, 06 1,669. 00 grand total 1,566 Ku. IDS $11. 73 $18,362. 00 cost of filling pier cylinders. The following costs were obtained in mixing and placing concrete in steel cylinder piers. The sand and gravel were wheeled 100 ft. to the mixing board at the foot of the cylinder, mixed and shoveled into wooden skips hoisted 20 ft. by horsepower and dumped into the cylinder. The foreman worked on the mixing board and the men worked with great energy. The costs were as follows: item per day, per Ku, YD. 6 men wheeling materials and mixing at 15 CTS per hour 9,000. 45 2 men dumping skips and ramming at 15 CTS per hour 3,000. 15 1 team and driver at 40 CTS per hour 4,000. 21 foreman at 30 CTS per hour 3,000. 15 totals $19. 000. 95 piers Calf Killer River Bridge. The following methods and costs of building 2 new piers and extending 3 old piers with concrete are given by Mr. J. Guy Huff. The work was done by the railway company's masonry gangs. Figure 94 shows the arrangement of the several piers and the character of the work on each and Fig. 95 gives the detailed dimensions of the 3 main piers. The sand and aggregate consisting of blast furnace slag were unloaded from cars to platforms on a level with the top of rail, placed about 100 ft. south from the south end of the bridge. A cubicle 1/6 Ku, YD, mixer was used. This was operated by a gasoline engine and was located on a platform about 50 ft. south of the south end pier. A tank near the mixer to supply water was elevated enough to get the desired head, and was kept filled by a pump run by another gasoline engine located down by the river bank. The cement house was located between the mixer platform and slag pile. Fig. 94. Diagram arrangement of piers, Calf Killer River Bridge. Fig. 95. Details of pier for Calf Killer Elva Bridge. Slag and sand were delivered to the mixer by means of wheelbarrows. The mixer was so placed that it would dump onto a platform, and the concrete could then be shoveled into a specially designed narrow-gauge car. This car ran on one rail of the main track and an extra rail outside. A turnout for clearing passing trains was provided at both ends of the bridge. The track over the bridge from the mixer had a descending grade of about 1%, so that with a little start, the concrete car would roll alone down to the required points on the bridge. Only in returning the empty cars to the mixer was it necessary to push them by hand, and then only for a distance of never more than 400 ft. Over the piers on the bridge in the center of the concrete car track openings were sawed to let the concrete pass to the forms below. To get the concrete into the forms, there were used zigzag chutes with arms about 10 ft long, which sections were removed as the concrete in the forms was increased. These chutes were a convenience by their ends alternating from one side to the other as the arms were removed in coming up. The cost of the concrete work was as follows: unloading material, rate per day, total days worked, total per coup, YD, concrete, foreman $3, 45 $17, $000, 0411 laborers 1, 368/105271, 14. 15. Total for unloading material $0. 19. Building forms, bins, etc. Foreman $3, 40 18 $61, $20 $0. 14. 9. Carpenters 2, 25 166 373, 50. 81. New lumber 23, 7 m. FT at $17, 8421, 86. 92. Old lumber 6 m. FT at $8, 3349, 98. 11. Total for building forms, bins, etc. $1. 98. Cofferdam excavation 45 coup, IDS. Foreman $3, 48 $27, $20 $069 laborers 1, 156/1074 a half 86. 12. 19. Total for cofferdam excavation $0. 25. Cofferdam concrete 37 coup, IDS. Foreman $3, 48 $27, $20 $0611 laborers 1, 363/1079 107, 68. 23. Cofferdam lumber 2, 25 m. FT at $20, 0045 0009. Total for cofferdam concrete $0. 38. Concrete mixing and placing. Foreman $3, 40 30 $102, $000, 22 9 laborers 1, 156/10 282 325, 99. 71. Cement 452 BBLS at $1. 55 701, 001. 52. Slag 437 coup, IDS at $0, 2087, 40. 19. Sand 220 coup, IDS at $0, 3066, 00. 14. Total for mixing and placing $2. 78. Taking down forms and clearing up. Foreman $3, 40 13 $44, $20 $0911 laborers 1, 17 1. 43 107 31 36. Total for taking down forms, etc. $200. $000. 45 engineering and supervision. 43. Grand total 460 ku. IDS concrete $6. 46. The wages given are the average wages. The men worked a 10-hour day. The concrete was a 1 to 3 to 6 mixture. The cofferdam work was done in connection with the construction of the fourth pier, this pier being the only one coming in the bed of the river to be built entirely new. The work on this was started in water about 6 ft. deep. The 37 ku IDS of concrete is included in the total of 460 ku IDS in the above tabulation. By itself, the cost of the cofferdam work, not including cost of cement, sand, and slag, was as follows. Total, per ku YD, concrete, lumber $45, $001, 21 labor, excavating 113, 32 3, 06 labor, concrete 134, 88 3, 64, total 37 ku. IDS, concrete $7, 91 fig, 96. Details of piers for K, C, M, and O, Rye, bridge. Method and cost of constructing 21 bridge piers. The following account of the methods and cost of constructing 21 concrete piers for a railway bridge consisting of 2050 ft. Plate girder spans has been compiled from records kept by Mr. W. W. Colpitts, Assistant Chief Engineer, Kansas City, Mexico, and Orient Rye. The shape and dimensions of the piers are shown by Fig. 96 and Fig. 97 shows the construction of the forms. Sheet pile cofferdams to solid rock were used for constructing the foundations. Fig. 97. Forms for piers for K, C, M, and O, Rye. Bridge. The 1 to 3 to 5 concrete was mixed in a Smith mixer having a batch capacity of 9 ku. ft. The mixer was located on the slope of the embankment approach, with the main track at its rear and facing a temporary material track. This temporary track turned out from the main track about 500 ft. Beyond the mixer and extended diagonally down the embankment approach on a 3%. Grade and across the river bottom alongside the pier sites. The portion of the track in the river bottom was supported on bents of spliced ties, jetted to the rock, and wired to the cofferdam to avoid the danger of loss in case of high water. The sand and crushed rock were delivered by cars from the main line track, immediately above the mixer, and the cement was stored in a shanty at one side of the mixer. The concrete materials and machinery were, in this manner, very conveniently located for rapid work and well above the high water line. The concrete was transported to the pier sites in improvised dump boxes, set on push cars. These dump boxes were hinged longitudinally and discharged directly into the cofferdams. The grade of the temporary track carried the push cars by gravity to the cofferdams, and they were returned by teams, for which purpose a straw and brush road had been built paralleling the track. As the work progressed farther into the stream, more cars were added properly to balance the work. While the concrete in the base was still fresh, a number of steel reinforcing bars, 8 ft. in length, were set in place along each end to ensure a good bond between the base and shaft. In general, the work of putting in the bases was organized so that about the same time was required in filling a cofferdam with concrete, in excavating the sand from the next, and in driving the sheet piling for the third. These three operations were thus carried on simultaneously, and although interruptions in one part of the work or the other occurred frequently, the gangs were interchangeable, and no appreciable loss was suffered, except in time, because of such delays. In piers 19 and 20, where the rock was from 17 to 19 ft, Below the surface, some difficulty was encountered due to the presence of fissures in the rock, from which it was necessary to remove the sand to fill with concrete. In such cases, the larger leaks were stopped as much as possible by driving sheet piles against the outside face of the cofferdam and into the fissures, and the smaller leaks by manure in canvas bags rammed into the openings. Upon the completion of all the bases, the forms for several shafts were set in position, and the work of filling with concrete proceeded as in the case of the bases, except that a derrick erected on a flat car and stationed at the pier was utilized to raise the dump boxes in depositing the concrete in the forms. As soon as the concrete in one shaft had set sufficiently to permit of it, the forms were removed and placed on the pier ahead. 4 sets of forms were used for the shafts. The following are the average prices paid for materials and labor. Materials: lumber for forms, etc., $16, 50 per m, FT, m. Cement, Kansas, Portland, $1.50 per BBL. Broken limestone, 45 C per cu, YD. Sand, Arkansas River, 15 C per ton. Labor: general foreman, $110 per month. Assistant foreman, $75 per month. Timekeeper, $60 per month. Riveters, 35 C per hour. Blacksmith, 30 C per hour. Blacksmith assistant, 20 C per hour. Carpenters, 22.5 C and 25 C per hour. Enginemen, 25 C per hour. Firemen, 20 C per hour. Night watchmen, 20 C per hour. Laborers, 17.5 C and 20 C per hour. Team, including driver, 40 C per hour. The prices quoted for lumber, cement, limestone, and sand are prices F. O. B. Louisiana, Iola, can. El Dorado, can. And Wichita, can. The total and unit cost of constructing the concrete piers and abutments and of erecting the steel superstructure are given in the following tabulation. Altogether, there was about 2,300 cu. ids of concrete in the substructure, most of which, as stated above, was a 1 to 3 to 5 mixture. Machinery and supplies: concrete mixer, 20% of cost, $152. 10 supplies, freight, hauling, setting up, $505. 04 total, $657. 14 centrifugal sand pump, 20% of cost, $27. 00 supplies, freight, hauling, setting up, $277. 50 rent of traction engine to operate, $83. 25 total, $387. 75 water pump and pipe, 20% of cost, $29. 00 supplies, freight, hauling, setting up, $177. 32 total, $206. 32 pile driver engine, 20% of cost, $100. 00 supplies, freight, hauling, setting up, $243. 65 total, $343. 65 grand total, $1,594. 86 cofferdams. Materials, lumber and nails, $1,285. 26 freight and train haul, $306. 33 labor making piles, $696. 82 labor driving piles, $1,384. 05 total, $3,672. 46 the sheet piling took 63,500 FT. B. M of lumber, the cost per 1,000 FT. B. M. for the sheet piling was then materials, lumber, and nails, $20. 08 freight and haulage, 4. 82 labor making piles, 10. 97 labor driving piles, 21. 80 total, $57. 67 forms, platforms, and runways, lumber, hardware, etc., $224. 59 freight and train haul, 40. 20 labor making, removing, and placing, $556, 51, total $821, 30 concrete materials. Cement, freight, unloading, and storing, $4,617. 48 sand, freight, unloading, etc. 1,336. 05 broken stone, freight, unloading, etc. 2,026. 92, total $7,980. 45. This gives us for 2,300 ids of concrete a cost of $3. 47 per yd. For materials, including freight, storage, and unloading charges of all kinds. A line on the proportion of the cost contributed by these latter items may be got by taking the prices of the materials F, O, B at the places of production and assuming the proportions for a 1 to 3 to 5 concrete. According to tables in Chapter Roman 2, a 1 to 3 to 5 broken stone concrete requires per cubic yard 1, 13 BBLS. Cement 0, 48 yd, sand and 0, 80 yd, broken stone, we have then 1, 13 BBLS. Cement at $1, $51, 69 0, 48 yd, sand at 20 C, 10 0, 80 yd, stone at 45 C, 36, total $2. 15. This leaves a charge of $1. 32 per cubic yard of concrete for freight and handling materials. The cost of mixing concrete and placing it in the forms was $3,490. 87 or $1, 52 per yd. We have then cost of concrete materials per yd, $3, 47 cost of mixing and placing concrete, 152 total, $4. 99 the miscellaneous expenses of the work comprised. Watchman, tools, telephone, etc. $722. 48 shanties, furnishings, supplies, etc. $829. 04 total, $1,551. 52 to this has to be added $1,134. 28 the cost of excavating the cofferdams. The total and unit costs of the different items of the concrete substructure work can now be summarized as follows. Item. Total, per yd, machinery and supplies $1,594, $86. 69 cofferdams $3,672. 49 1, 60 forms, etc. $821. 30. 36 concrete materials $7,980. 45 3. 47 mixing and placing concrete $3,490. 87 1. 53 excavating cofferdams $1,134. 28. 49 miscellaneous $1,551. 52. 67. Total $20,245. 74 $8. 81 cost of permanent way structures Kansas City outer belt and electric rye. The following cost of concrete work including retaining walls, abutments, and box culverts for the permanent way of the Kansas City outer belt and electric rye is given by Mr. W. W. Colpitts. These figures are of particular interest for the variation in prices of materials during the 2-year period while work was in progress, and as giving the average cost of the work on the whole line as well as for individual structures. The culverts were all box culverts with wing walls, and the abutments were for girder bridges. Walls and abutments were of L section with triangular or trapezoidal counterforts at the back between base slab and coping. The form work was thus rather complex. All work was reinforced concrete and was done by contract under the following conditions. The work of preparing foundations, including excavation, pile driving, diversions of streams, etc., was done by the railroad company, which also bore one-half the cost of keeping foundations dry while forms were being built and concrete placed. The railroad company also furnished the reinforcing bars at the site of each opening. The concrete work was let at $9 per coup, YD, which figure covered all the labor and materials necessary to complete the work other than the exceptions mentioned. The concrete proportions were 1:3:5. The cement used was Iola Portland and Atlas Portland. The sand was obtained from the bed of the Kansas River in Kansas City. The rock used was crushed limestone passing a 2-in ring and freed from dust by screening. Corrugated reinforcing bars, having an elastic limit of from 50,000 to 60,000 pounds per SQ, manufactured by the Expanded Metal and Corrugated Bar Co. of St. Louis, Mo., were used exclusively. The concrete in the smaller structures was mixed by hand, in the larger by a No. 1 Smith mixer. In the first structures built 2-in. Form lumber was used with 2x6-in. Studs placed 3 ft on centers. This was abandoned later for 1-in. Lumber with 2x6-in. Studs 12-ins on centers and was found to be more satisfactory in producing a better face. The structures were built in the period from April 1905 to May 1907. The cost of materials and the wages paid labor were as follows. Cement per barrel at structure, April 1905, $1. 25 per barrel at structure, April 1907, 1. 92 average cost per barrel at mill, 1. 42 freight per barrel, 0. 21 hauling 1.5 miles and storage, 0. 12 average cost at structure, 1. 75 average cost per coup, YD, concrete, 1 BBLS. 193 sand per coup, YD. At structure, April 1905, $0. 625 per coup, YD. At structure, April 1907, 0. 75 average cost per coup, YD. Riverbank, 0. 30 freight per coup, YD, 0. 22 hauling 1.5 miles, 0. 20 average cost at structure, 0. 72 average cost per coup, YD, concrete a half coup, YD. 0. 36 stone per coup, YD. At structure, April 1905, $1. 10 per coup, YD. At structure, April 1907, 1. 75 average cost per coup, YD. Crusher, 0. 65 hauling 4 miles, 0. 84 average cost at structure, 1. 49 average cost per coup, YD. Concrete, 0. 9 coup, YD. 1. 34 lumber per MFT. At structure, April 1905, $15. 00 per M. FT at structure, April 1907, 22. 50 average cost per M at structure, 19. 00 average cost per coup, YD, concrete, 0. 49 labor max, min, common labor, CTS. Per hour 2017 carpenters, CTS. Per hour 40-30 with these prices and wages. The average cost of concrete work for the whole line was: item, per coup, YD. Form building and removing, $1. 98 mixing and placing concrete, 0. 74 placing reinforcement, 0. 10 wire, nails, water, etc., 0. 21 1 BBLS, cement at $1. 75 1 93 a half coup, YD. Sand at $0. 72 0. 36 0. 9 coup, YD. Stone at $1. 49 1. 34 lumber for forms, 0. 49 total, $7. 14 The following are the costs of specific structures built at different times. Example I. Indian Creek Culvert, 14 times 15 ft, 250 long, completed November 1905 per QYD. Cement $1, 37 sand, 34 stone 1, 10 labor 2, 48 lumber, 76 miscellaneous, 18 total $6, 23 example Roman 2. 3rd Street abutments and retaining wall, completed November 1906 per QYD. Cement $1, 78 sand, 35 stone 1, 35 lumber, 74 labor 2, 75 miscellaneous, 16, total $7. 13. Example Roman 3. Abutments overhead crossing with Union Pacific and Rock Island, completed May 1907 per QYD. Cement $1, 92 sand, 32 stone 1, 74 lumber, 98 labor 2, 96 miscellaneous, 16, total $8. 08 cost of plate girder bridge abutments. The following record of the construction of 20 abutments for 10 four-track plate girder bridges over streets in Chicago, Ill. are given by Mr. W.A. Rogers. The work was done between May 1 and Oct. 1, 1898, in which time 8,400 ids of concrete were placed, all the work being done by company labor. The forms were made of 2 in plank and 6 times 6 in posts bolted together at the top and bottom with 3/4 in rods. The lumber was used over and over again. When the dressed plank became too poor for the face, it was used for the back. The concrete was 1 Portland cement, 3 gravel, and 4 to 4.5 limestone crusher run up to 3 in size. A mortar face 1.5 ins thick was built up with the rest of the concrete. The concrete was made quite wet, and each man ramming averaged 18 ids a day rammed. The concrete was mixed by a machine of the Ransom type, operated by a 12 HP portable gasoline engine. The load was very light for the engine, and 8 HP would have been sufficient. The engine made 235 revolutions per minute, and the pulley wheels were proportioned so that the mixer made 12 revs per minute. 1 gallon of gasoline was used per hour, and the mixing was carried on day and night so as not to give the concrete time to set. The time required for each batch was 2 to 3 mins, and about a half YD of concrete was delivered per batch. The average output was 70 ids per 10 HR shift with a crew of 28 men, but as high as 96 ids were mixed in 10 HRS. The concrete was far superior to hand-mixed concrete. The water for the concrete was measured in an upright tank and discharged by a pipe into the mixer. The sand and stone were delivered to the mixer in wheelbarrows, and the concrete was taken away in wheelbarrows. No derricks were used at all. Each wheelbarrow of concrete was raised by a rope passing over a pulley at the top of a gallows frame, 1 horse and a driver serving for this raising. A small gasoline hoisting engine would have been more satisfactory than the horse, which was worked to its full capacity. After the barrows were raised, 12 ft, they were wheeled to the abutment forms and dumped. The empty wheelbarrows were lowered by hand, by means of a rope passing over a sheave and provided with a counterweight to check the descent of the barrow. The cost of the concrete built by company labor was as follows per QYD. Cement, gravel, and stone delivered $3. 28 material in forms used many time. 11 carpenters building and taking down forms. 34 labor 1. 18 total per QYD $4. 91 The labor cost includes moving plant from one bridge to the next, building runways, gasoline for engine, oil for lights at night, and unloading materials, as well as mixing, transporting, and placing concrete. Wages were $1.75 per 10-hour day for laborers and $2. $50 for carpenters. Cost of abutments and piers, Lonesome Valley Viaduct. Mr. Gustave R. Tusker gives the following on the concrete substructure of the Lonesome Valley Viaduct, near Knoxville, 10. There were 2 U-shaped abutments and 36 concrete piers made of a light limestone that deteriorates rapidly when used for masonry. Derricks were not needed as would have been the case with masonry piers, and colored labor at $1 for 11 HRS could be used. The piers were made 4 FT, square on top from 5 to 16 FT, high and with a batter of 1 in to the foot. The abutments averaged 26 FT, high 26 FT, long on the face with wing walls 27 FT, long the wall at the bridge seat is 5 FT, thick and the wing walls are 3.5 FT, wide on top, batters are 1 in, to the foot. The forms were made of 2 in, tongued and grooved plank, braced by posts of 2 times 10 in. Plank placed 3 FT, C to C, for the abutments and at each corner for the piers. At the corners, one side was dapped into the other so as to prevent leakage of cement. The posts were braced by batter posts from the earth. For the piers, a square frame was dropped over the forms and spiked to the posts. The abutment forms were built up as the concreting progressed. The north abutment forms were made in sections 6 FT, high held by 3/4 in, bolts buried in the concrete. The lower sections were removed and used again on the upper part of the work, thus saving plank. The inside of forms was painted with a thin coat of crude black oil. The same form was used for several piers. The concrete was 1 to 2 to 5, the barrel being the unit of measure, making about 3/4 cu. YD of concrete per batch. The mortar was mixed with hose, but shovels were used to mix in the stone. By passing the blade of a shovel between the form and the concrete, the stone was forced back and a smooth mortar face was secured. Rammers weighing 30 to 40 pounds were used for tamping. 2 days after the completion of a pier, the forms were removed. The concrete was protected from the sun by twigs and was watered twice a day for a week. It was found by actual measurement that 1 cu. YD of concrete 1 to 2 to 5, the ingredients being measured in barrels consisted of 1/4 BBLS. Of Atlas cement 10 cu. FT of sand and 26.5 cu. FT of stone. The total amount of concrete was 926 cu. IDs, of which 2/3 was in the 2 abutments. The work was done in 1894 by contract for $7 per cu. YD, cement costing $2.80 per BBL, sand 30 CTS per cu. YD, and wages $1 a day. A slight profit was made at this price. A gang of 15 men and a foreman would mix and lay about 40 cu. IDs in 11 HRS were not delayed by lack of materials. The cost of making the concrete with wages at $1 a day was CTS per cu. YD, 1 man filling sand barrels and handling water 2, 7 2 men filling rock barrels 5, 4 men mixing sand and cement 10, 6 4 men mixing stone and mortar 10, 6 2 men wheeling concrete 5, 3 1 man spreading concrete 2, 7 1 man tamping 2, 7 1 foreman 5, 0 total labor 45, 0 cost of hand mixing and wheelbarrow work for 4 bridge piers. The following figures of the cost of hand-mixed concrete for bridge piers and abutments are given by Mr. Fred R. Charles of Richmond, Ind. The figures cover 3 jobs. All concrete was mixed by hand, and with one exception noted below was moved to place in wheelbarrows. The concrete was a 1 to 2 of 5.5 mixture. In this connection, it is well to note that in 1 or 2 of the jobs where the proportion of the aggregate seems too small for the yardage of concrete, The difference is accounted for by the fact that large stones were placed in the foundations, these stone being on the ground and costing nothing but the labor to throw them in. Job I. The first job consisted of the construction of one abutment and 6 piers for a bridge over the Miami River at Fernald, O. The stone was procured on the site and crushed by a portable crusher run by a traction engine. The rough stone cost 10 CTS a cubic yard, and this, with the cost of handling, fuel, and hire of engine and crusher, made the cost of crushed stone about $1 per cu. YD. Sand was obtained close to the work, but the cement had to be teamed 10 miles. Labor was paid $1.75 per day. The cost of materials and labor per cubic yard of concrete in place was as follows. Item, per cu, YD, 1.16 BBLS. Cement at $2, 10 $1. 58 sand 0. 35 stone 0. 75 lumber 0. 64 tools, hardware, etc. 0. 20 labor including 15 CTS per cu YD for pumping 2. 78 total materials and labor $6. 30 job Roman 2. The second job was the construction of 2 abutments containing 434 cu ids of concrete for a viaduct at Ernst Street, Cincinnati, O. The abutments were constructed at the street and the excavation was clay and shale. Labor received $1.75 per day. The cost of materials and labor per cubic yard of concrete in place was as follows. Materials per cu YD, 376 BBLS. Cement at $1, $71, 48 224 cu ids. Sand at $1, 20, 64 255 cu ids. Stone at $1, 55 100 lumber 0. 40 tools, hardware, etc. 0. 06 total materials $3. 58 labor, clearing and excavating $1. 12 mixing and placing concrete 1. 13 building forms, etc. 0. 25 total labor $2. 50 total labor and materials $6. 08 job Roman 3. This job consisted in placing 570 cu ids of concrete in the pedestals for a viaduct at Quebec Avenue, Cincinnati, O. The pedestals were 5 ft square on top and from 8 to 20 ft high. The location of the work was very inconvenient for the delivery of materials, all materials having to be teamed or wheeled. Labor was paid $1.75 per day. The cost of labor and materials per cubic yard of concrete in place was as follows. Item, per cu YD, 500 BBLS. Cement at $1, $61, 40 239 cu ids. Sand at $1, 25 53 560 cu ids. Stone at $1, 88 84 lumber 0. 38 tools, hardware, etc. 0. 05 labor 2. 96 total labor and materials $7. 16 job Roman 4. This job consisted in placing 2,111 cu ids of concrete in a railway viaduct at Cincinnati, O. For 1 pier 56 ft high, the concrete was raised to place by a derrick. For the remainder of the work, it was wheeled or teamed to place. Labor was paid $1.75 per day. The cost of labor and materials per cubic yard of concrete in place was as follows. Item, per cu YD, 1908 BBLS. Cement at $1, $61, 44 1105 cu ids. Sand at $1, 95 51,468 cu ids. Stone at $1, 48 03 lumber 0. 54 tools, hardware, etc. 0. 25 water 0. 03 labor 3, 44 total labor and materials $7. 23. Chapter 40. Concrete retaining walls may for construction purposes be divided into two classes: plain concrete walls of gravity section and reinforced concrete walls consisting of a thin slab taking the thrust of the earth as a cantilever anchored to a base slab, or as a flat beam between counterforts. The reinforced wall requires much less concrete for a given height than does the plain gravity wall, but the concrete is more expensive owing to the reinforcement and to the more complex form of construction, and in some measure to the greater cost of placing the mixture in narrow forms and around reinforcement. It is common, too, to require a richer concrete for the reinforced than for the plain wall. Fig. 98. Comparison of plain and reinforced sections for retaining walls. C.E. Graph. Comparative economy of plain and reinforced concrete walls, prior to the construction of some 2,000 ft, of retaining wall ranging in height from 2 ft to 38 ft at Seattle, Wash. The calculation was made by the engineers of the Great Northern Rye to determine the comparative economy of plain concrete and reinforced concrete sections. The sections assumed were those shown by Fig. 98, and comparisons were made at heights of 10, 20, 30, and 40 ft, with the following results: height in plain, reinforced, percent, feet, cu ids per ft, cu ids per ft, saving, 10-1, 63-1, 29-20, 424, 082, 5936, 438, 44, 73, 43, 340, 14, 78, 0745, 0. The saving in concrete increased as the height of the wall increased. For a 40 ft wall reinforced concrete at nearly double the cost per cubic yard in place would be as cheap as plain concrete. Fig. 99. Comparison of plain and reinforced sections for retaining wall F sinks, taking substantially the section of reinforced wall being used on the Chicago track elevation work of the Chicago, Burlington, and Quincy R.R., and comparing it with a plain wall as shown by Fig. 99. Mr. F. Sinks obtain the following results. Plain wall cost per lineal foot, 8 cu ids, concrete at $4.19, 2,115 ft bm of forms at $31.356, total for 8 cu ids at $4. $74.22, reinforced wall cost per lineal foot, 346 cu ids, concrete at $4, $10.14, 1,815 ft b.m. of forms at $31.356, 109 pounds, reinforcing steel at 3/4 cts. 3. 54 34 cu ids, extra fill at 20 cts. 0. 27 32 cu yd, extra excavation at 20 cts. 0. 06 total 346 cu ids, concrete at $6, $25, $21, 61. The saving in this case was $1. 15 per lineal foot of wall, with the unit cost of reinforced concrete in place 24%, greater than the unit cost of plain concrete. It will be noted that there is some 28% less concrete per lineal foot of wall in the reinforced section, and also that this section is so designed that the form work is about as simple for one section as for the other. Another point to be noticed is that there is no saving in excavation by using a reinforced section instead of a gravity section. In fact, the excavation runs slightly more for the reinforced section. Fig. 100. Forms for retaining wall work, NYC, and HRRR form construction. Retaining wall work often affords an opportunity for constructing the forms in panels, and this opportunity should be taken advantage of when possible. Several of the walls described later give examples of form work that may be studied with profit in this respect. Figure 100 shows a panel form construction employed on the New York Central and Hudson River the 3x8 Studs are erected, care being taken to get them in proper line and to true batter, and also to brace them rigidly by diagonal props. Generally, the studding is erected for a section of wall 50 ft, long at one time, the lagging made in panels 2½ ft, wide and 10 ft, long by nailing 2 in. Plank to 2x4 in. Cleats is attached to the studding a panel at a time and beginning at the bottom by means of the straps, wedges, and blocks shown. 5 bottom panels making a form 2½ ft, high and 50 ft, long are placed first. When the concrete has been brought up nearly to the top of these panels, a second row of panels is placed on top of the first. When it is judged that the concrete is hard enough, the lowermost panels are loosened and made free by removing the wedges, blocks, and straps, and the panels are drawn out endwise from behind the studding and used over again for one of the upper courses. The small size of the panels makes it practicable to lay bare the concrete while it is yet soft enough to work with a float or to finish by scrubbing as described in Chapter Roman 8. In cases where this object is not sought, panels of much larger size may be used. Working with panels 2x12½ ft of 2 in. Plank, it was found that each panel could be used 16 times before becoming unfit for further use, but as, owing to the nicety of molded surface demanded, panels were discarded when showing comparatively small blemishes, this record cannot be taken as a true indication of the life of such forms. These panel forms are used by the railway named for long abutments and piers as well as for retaining walls. A different type of sectional form construction is illustrated by Figs 101 and 102. It has been extensively used for retaining wall work by the Chicago, Burlington, and Quincy The studding and wailing are framed in units as shown. The lagging is framed in panels for the rear of the wall, for the face of the coping, and for the inclined toe of the wall, and is ordinary sheathing boards for the main face of the wall. The makeup of the several panels is shown by the drawings. The reason for using ordinary sheathing instead of panels for the face of the wall is stated by Mr. L.J. Hotchkiss, Assistant Bridge Engineer, to be that the sections become battered and warped with use, do not fit closely together, and leave the wall rough when they are removed. The manner of bracing the form and of anchoring it down against the upthrust of the wet concrete is shown by Fig 102. 2 other examples of sectional form construction are given in the succeeding descriptions of work for the Grand Central Station Terminal in New York City and for the Chicago Drainage Canal. In the former work, it is notable that panels 51x20 ft were used, being handled by locomotive crane. The panels used on the drainage canal work and in the forms previously described are of sizes that can be taken down and erected by hand, and the means of handling them should always be given consideration in deciding on the sizes to be adopted for form panels not only in wall construction, but in any other class of work where sectional forms may be used. Wet spruce or yellow pine will weigh 4½ pounds per ft/m, so that a panel 10x2½ ft made of 2 in, plank and 3 2x4 in, Battens will weigh some 225 pounds. In form work where the panels are removed and re-erected in succession facility in handling is an important matter when one figures that he may handle both the concrete and the form panels with it. A cableway or a locomotive crane becomes a tool well worth considering in heavy wall work. Fig. 101. Forms for retaining wall work C, B, and Q are three details in retaining wall form work that are often sources of annoyance out of proportion to their magnitude are alignment, coping, construction, and wall ties. Small variations from line in the face of the wall are seldom noticeable, but a wavy coping shows at a glance. For this reason, it is often wise to build the coping after the main body of the wall has been stripped, or if both are built together to provide in the forms some independent means of lining up the coping molds. In the form shown by Fig. 101, the latter is done by bracing the coping panel so as to permit it to be set and lined up independently of the main form. A separate form for molding the coping after the main body of the wall is completed may be constructed as shown by Fig. 103. Bolts at B and C permit the yokes to be collapsed and the form to be shifted ahead as the work advances. This mold provides for beveling the top edges of the coping and also the edge of the overhang, and the beveling or rounding of these edges should never be omitted where a neat appearance is desired. It is not essential, however, that this finishing be done in the molds. By stripping the concrete, while it is still pliable, the edges can be worked down by the ordinary cement sidewalk edger. Fig. 102. Sketch showing method of bracing form shown by Fig. 101. Fig. 103. Sectional form for constructing coping. Wall ties are commonly used to hold the face and back forms to proper spacing, but occasionally they are not permitted. In the latter case, the bracing must be arranged to hold the forms from tipping inward as well as from being thrust outward. A good arrangement is that shown by Fig. 102. In fastening the forms with ties, the choice is usually between long bolts which are removed when the molds are taken down and wire ties which are left embedded in the concrete. The selection to be made depends upon the character of the work. When sectional forms are used like the one shown by Fig. 101, for long stretches of wall of nearly uniform cross-section, bolts are generally more economical and always more secure. If the bolts are sleeved with scrap gas pipe, having the ends caulked with waste, the bolts can be removed ordinarily without difficulty. To make the pipe sleeve serve also as a spacer, the end next the face may be capped with a wooden washer which is removed, and the whole plastered when the forms are taken down. With bolt ties, the forms can be filled to a depth of 15 to 20 ft with sloppy concrete. This is hardly safe with wire ties unless more wire and better tying are employed than is usual. It takes 4 strands of no. 10 to give the same working stress as a half-in. Threaded rod and the tying in of 4 strands of wire so that they will be without slack and give is a task requiring some skill. Bolts are much more easily placed and made tight. In the matter of cost of metal left in the wall, the question is between the cost of scrap gas pipe and of wire. The pound price of the wire is greater, but fewer pounds are used, and the metal is in more convenient shape to cut to length and to handle. This convenience in shaping the tie to the work gives the advantage to wire ties for isolated jobs or jobs which involve a continual change in the length and spacing of the ties. In general, the contractor will find bolts preferable where sectional forms are used, and wire ties preferable when using continuous forms. One objection urged against the use of wire ties is that the metal is exposed at the face of the work when they are clipped off unless the concrete is chipped and the cavity plastered. To obviate this objection, various forms of removable heads have been devised. Two such devices are shown by Figs, 104 and 105. In both, the bolt is unscrewed, leaving the heads embedded. The head shown by Fig 104 has the advantage that it can be made by any blacksmith, while the head shown by Fig 105 is a special casting. Fig 104, tie for wall forms. Fig 105, tie for wall forms, mixing and placing concrete. Where a long stretch of wall is to be built, the system of mixing and handling the concrete must be capable of being shifted along the work. For isolated walls of short length, this problem is a simpler one. Where the mixer can be installed on the bank above, wheeling to chutes reaching down to the work is the best solution. As shown in Chapter 4, concrete can be successfully and economically chuted to place to a greater extent than most contractors realize. Where the mixer has to be installed at the foot of the wall wheelbarrow inclines, derricks, gallows frames, etc., suggest themselves as means of handling the concrete. It is not this class of work, however, but the long stretches of heavy section walls, such as occur in depressed or elevated railway work in cities, that call for thought in the arrangement and selection of mixing and handling plant. In building the many miles of retaining wall in the work of doing away with grade crossings in Chicago, trains made up of a mixer car and several material cars have been used. The mixer is mounted on a flat car set at the head of the train and is covered by a decking carrying two charging hoppers set above the mixer. The material cars are arranged behind, the sand and stone or gravel being in gondola cars. Portable brackets hooked to the sides of the gondola cars carry runways for wheelbarrows. Sand and stone or gravel are wheeled to the charging hoppers, the work being continuous since one hopper is being filled while the other is being discharged into the mixer. The mixer discharges either into a chute, wheelbarrows, or buckets. The foregoing is the general arrangement. It is modified in special instances, as is mentioned further on. The chief objection to the method is the difficulty of loading the wheelbarrows standing on runways level with the tops of the gondola sides. The lift from the bottom of the car is excessive, and as pointed out previously, shoveling stone or gravel by digging into it from the top is a difficult task. The delivery of the concrete into the forms was accomplished by chute where possible, otherwise by wheelbarrows or cranes, and in one case by belt conveyor. In the last instance, the mixer car was equipped with a Drake continuous mixer and was set in front. Behind it came 3 or 4 gondola cars of sand and stone, and at the rear end a box car of cement. All material was wheeled on side runways to 2 charging hoppers over the mixer. The mixer discharged onto a belt conveyor carried by a 25 FT. Boom guide to an A-frame on the car and pivoted at the car end to swing 180 degrees by means of a tag line. The outer end of the conveyor was swung over the forms. A 3/4 in. Wire rope wrapped 8 times around 2 drums on the mixer car and passing through slots in the floor to anchors placed 1/500 FT. In front, and 1/500 FT to the rear enabled the train to be moved back and forth along the work. This scheme of self-propulsion saved the hire of a locomotive. In another case, the mixer was discharged into buckets which were handled by a crane traveling back and forth along a track laid on 2 flat cars. Fig 106. Side elevation of traveling mixer plant, Galveston sea wall. Another type of movable mixer plant used in constructing a seawall some 3.5 miles long at Galveston, Tex, is shown by Figs. 106 and 107. Two of these machines mixed and placed some 127,000 ids of concrete in 1 yd batches, 212 HP. Engines operated the derricks and 116 HP. Engine operated the Smith mixer. All engines took steam from a 50 HP boiler. The rated capacity of each machine was 300 to 350 ids per day. The method of operation is clearly indicated by the drawings. Fig. 107. End elevation of traveling mixer, Galveston sea wall. Placing the concrete in the forms is generally required to be done in layers. With wet mixtures, this means little more than distributing the concrete somewhat evenly along the wall and slicing, and puddling it to get rid of air and prevent segregation. Where mortar facing is required, the face form described in Chapter Roman 8 may be used. A reasonably good surface can be secured without mortar facing by spading the face. With dry concrete, placing and ramming in layers calls for such care as is necessary in dry concrete work everywhere. Where new concrete has to be placed on concrete placed the day before, good bond may be secured, and the chance of efflorescence be reduced by the methods described in Chapter 41, Walls in Trench. In canal excavation, in subway work in cities, and the like, it is often necessary to dig trenches and build retaining walls in them before excavating the core of earth between the walls. The following examples of such work are taken from personal records. Example I. A Smith mixer was used, the concrete being delivered where wanted by a Lambert cableway of 400 ft. Span. The broken stone and sand were delivered near the work in hopper-bottom cars which were dumped through a trestle onto a plank floor. Men loaded the material into one-horse dump carts which hauled it 900 ft to the mixer platform. This platform was 24 times 24 ft, square and 5 ft, high with a planked approach 40 ft, long and contained 7,300 ft, b.m. The stone and sand were dumped at the mouth of the mixer and shoveled in by 4 men. 8 men, working in pairs, loaded the broken stone into the carts, and 2 men loaded the sand. Each cart was loaded with about 70 shovelfuls of stone, on top of which 35 shovelfuls of sand were thrown. It took 3 to 5 minutes to load on the stone and 1 minute to load the sand. The carts traveled very slowly, about 150 ft. A minute, in fact, all the men on the job, including the cart drivers, were slow. After mixing, the concrete was dumped into iron buckets holding 14 ft. Water measure making about a half yd in a batch. The buckets were hooked onto the cableway and conveyed where wanted in the wall. Steam for running the mixer was taken from the same boiler that supplied the cableway engine. The average output of this plant was 100 ids of concrete per 10-hour day, although on many days the output was 125 ids, or 250 batches. The cost of mixing and placing was as follows on a basis of 100 ids per day per yd. 8 men loading stone into carts, $12. 12 2 men loading sand into carts, $3. 1 cart hauling cement, $3. 3 8 carts hauling stone and sand, $24. 24 4 men loading mixer, $6. 6 1 man dumping mixer, $1. 50. 012 men handling buckets at Mixer 3, 036 men dumping buckets and ramming 9, 0912 men making forms at $2, 5030, 31 cable engine MN 3, 031 fireman 2, 021 foreman 6, 06061 waterboy 1, 00011 ton coal for cableway and Mixer 4, 0004, total $107, $51, 07 in addition to this cost of $1, 07 per coup, YD. There was the cost of moving the whole plant for every 350 FT of wall. This required 2 days at a cost of $100, and as there were about 1,000 ids of concrete in 350 FT, of wall 16 FT high, the cost of moving the plant was 10 CTS per YD of concrete, bringing the total cost of mixing and placing up to $1, 17 per YD. As above stated, the whole gang was slow. The labor cost of making the forms was high for such simple and heavy work, costing $10 per m of lumber placed each day. The forms were 2 in. Sheeting plank held by 4 times 6 in. Upright studs 2½ FT apart, which were braced against the sides of the trench. The face of the forms was dressed lumber, and all cracks were carefully putted and sandpapered. The above costs relate only to the massive part of the wall and not the cost of putting in the facing mortar, which was excessively high. The face mortar was 2 ins, thick and about 3½ ids. Of it were placed each day with a force of 8 men. 2 of these men mixed the mortar, 2 men wheeled it in barrows to the wall, 2 men lowered it in buckets, and 2 men put it in place on the face of the wall. If we distribute this labor cost on the face mortar over the 100 ids of concrete laid each day, we have another 12 CTS per YD. But a better way is to regard this work as a separate item and estimate it as square feet of facing work. In that case, these 8 men did 500 FT of facing work per day at a cost of nearly 2 a CTS per FT for labor. Example Roman 2. The building of a wall similar to the one just described was done by another gang as follows. The stone and sand were delivered in flat cars provided with side boards. In a stone car, 5 men were kept busy shoveling stone into iron dump buckets having a capacity of 20 FT. Water measure. Each bucket was filled about 2/3 full of stone. Then it was picked up by a derrick and swung over to the next car, which contained sand, where 2 men filled the remaining third of the bucket with sand. The bucket was then lifted and swung by the derrick over to the platform of the mixer, where it was dumped, and its contents shoveled by 4 men into the mixer, cement being added by these men. The mixer was dumped by 2 men, loading iron buckets holding about a ½ YD of concrete each, which was the size of each batch. A second derrick picked up the concrete bucket and swung it over to a platform where it was dumped by 1 man. Then 10 men loaded the concrete into wheelbarrows and wheeled it along a runway to the wall. 1 man assisted each barrow in dumping into a hopper on the top of a sheet iron pipe, which delivered the concrete. The 2 derricks were stiff-legged derricks with 40 FT. Booms provided with bull wheels and operated by double cylinder, 7 times 10 in. Engines of 18 HP each. About 1 ton of coal was burned daily under the boiler supplying steam to these 2 hoisting engines. The output of this plant was 200 batches or 100 ids of concrete per 10 HR. day when materials were promptly supplied by the railroad, but delays in delivering cars ran the average output down to 80 ids per day, on the basis of 100 ids. Daily output, the cost of mixing and placing the concrete was as follows per day per yd. 5 men loading stone $7, $50, 0.7 2 men loading sand 3, 0.0 4 men charging mixer 6, 0.0 2 men loading concrete into buckets 3, 0.0 1 man dumping concrete from buckets 50, 0.1 10 men loading and wheeling concrete 0.0 1 man dumping wheelbarrows 1, 50, 0.1 3 men spreading and ramming 4, 50, 0.4 2 enginemen 5, 0.0 1 fireman 2, 0.0 2 1 waterboy 1, 0.0 1 foreman 6, 0.0 6 10 men making forms 25, 0.0 25 1-ton coal 4, 0.0 4, total 85, 0.0 85. In addition, there were 8 men engaged in mixing and placing the 2 in facing of mortar as stated above. Chicago Drainage Canal. The method and cost of constructing some 20,000 ft. of concrete wall by contract in building the Chicago Drainage Canal is compiled from records kept by Mr. James W. Beardsley. The work was done on 2 separate sections, Section 14 and Section 15. In both cases, a 1-to-1 of 4 natural cement concrete was used with a 3-in facing and a 3-in coping of 1-to-3 Portland cement mortar. Section 14. The average height of the wall was 10 ft, and the thickness at base was 1/2 the height. The stone for the concrete was obtained from the spoil bank of the canal, loaded into wheelbarrows and wheeled about 100 ft. to the crusher. Some was hauled in wagons. An Austin jaw crusher was used, and it discharged the stone into bins from which it was fed into a Suismith mixer. The crusher and the mixer were mounted on a flat car. Bucket elevators were used to raise the stone, sand, and cement from their bins to the mixer. The buckets were made of such size as to give the proper proportions of ingredients, as they all traveled at the same speed. Only 2 laborers were required to look after the elevators. The sand and cement were hauled by teams and dumped into the receiving bins. There were 23,568 ids on Section 14, and the cost was as follows. Typical force. Wages per 10 HRS. Cost per yd. General force superintendent 1, $0.5, $0.00, $0.26 blacksmith 1, 1.2, 75 0, 16 timekeeper 0, 5.2, 50 0, 007 watchman 0, 6.2, 000, 007 waterboys 3, 9.1, 000. 0.22 wall force foreman 0, 9.2, 50 0, 0.13 laborers 8, 6.1, 50 0, 0.73 tampers 2, 3.1, 75 0, 0.22 mixer force foreman 1, 2.2, 50 0, 0.17 engineman 1, 8.2, 50 0, 0.25 laborers 6, 7.1, 50 0, 0.57 pump runner 1, 0.2, 0.00, 0.10 mixing machines 1, 7.1, 25 0, 0.12 timber force foreman 0, 6.2, 50 0, 0.08 carpenters 4, 7.2, 50 0, 0.57 laborers 1, 2.1, 50 0, 0.10 helpers 5, 3.2, 50 0, 075 hauling force, laborers 2, 61, 75 0, 026 teams 6, 33, 25 0. 116 crushing force, foreman 0, 52, 50 0, 007 engineman 1, 72, 50 0, 023 laborers 3, 51, 50 0, 032 Austin crushers 1, 7 1, 20 0, 011 loading stone, foreman 1, 7 2, 50 0, 023 laborers 32, 9 1, 50 0, 280, total for crushing, mixing, and placing $0. 975, the daily costs charged to the mixers and crushers include the cost of coal at $2 a ton and the cost of oil. The gang loading stone apparently did a good deal of sledging of large stones, and they also wheeled a large part of it in barrows to the crusher. The plant cost $9,600, distributed as follows: 2 jaw crushers $3,000, 2 mixers $3,000, track 1,260, lumber 500, pipe 840, sheds 400, pumps 600. Total $9,600 if this first cost of the plant were distributed over the 23,568 ids. Of concrete, it would amount to 41 CTS per YD. The cost of the concrete was as follows: per YD, Utica cement at $0, 65 per BBL, $0, 863 Portland cement at $2, 25 per BBL, 0, 305 sand at $1, 35 per YD, 0, 465 stone and labor as above given, 0, 975 total $2. 608 first cost of plant $0, 407. Section 15. The conditions on this section were much the same as on section 14 just described, except that the limestone was quarried from the bed of the canal and was crushed in a stationary crusher, 7 gates. The stone was hauled 1,000 ft to the crusher on cars drawn by a cable from a hoisting engine. The output of this crusher averaged 210 ids per day of 10 HRS. The crushed stone was hauled in dump cars, drawn by a locomotive to the mixers. Spiral screw mixers mounted on flat cars were used, and they delivered the concrete to belt conveyors which delivered the concrete into the forms. The forms on Section 15, and on Section 14 as well, consisted of upright posts set 8 ft apart and 9 ins. In front of the wall, held at the toe by iron dowels driven into holes in the rock, and held to the rear posts by tie rods. The plank sheeting was made up in panels 2 ft wide and 16 ft long, and was held up temporarily by loose rings which passed around the posts, which were gripped by the friction of the rings. These panels were brought to proper line and held in place by wooden wedges. After the concrete had set 24 HRS, the wedges were struck, the panels removed and scraped clean, ready to be used again. The cost of quarrying and crushing the stone and mixing the concrete on Section 15 was as follows: typical force. Wages per 10 HRS. Cost per YD. General force, Superintendent 1, $0.05, $0.00, $0.24, blacksmith 0, 92, 75, 0, 0.11 teams 1, 73, 0, 0, 0, 0.25 waterboy 4, 51, 0, 0, 0, 0.22 wall force foreman 1, 12, 50, 0, 0.10 laborers 14, 41, 50 0, 105 Tampa's 0, 11, 75 0, 001 mixer force foreman 2, 12, 50 0, 026 engineman 2, 12, 50 0, 22 laborers 23, 50 180 mixing machines 2, 25 22 timber force carpenters 83 13 laborers 50 5 helpers 10, 50 125 hauling force foreman 50 009 enginemen 50 19 firemen 75 003 brakemen 18 teams 43 25 007 laborers 50 10 locomotives 25 15 crushing force foreman 50 14 enginemen 50 14 laborers 11 50 81 firemen 75 008 gyratory crusher 25 011 quarry force foreman 50 12 laborers 19 50 140 drillers 82 17 drill helpers 81 50 13 machine drills 81 25 11 total $0. 993. The first cost of the plant for this work on Section 15 was $25,420, distributed as follows. 1 crusher, no. 7 gates, $12,000, use of locomotive, 2,200 car. And track, 5,303 mixers, 3,000 lumber, 1,200 pipe, 720 small tools, 1,000. Total, $25,420. This $25,420 distributed over the 44,800